Welcome to the CCNP Voice C-Voice exam video certification series. This is Module 1, and we're going to be going through a course introduction and a lab topology overview. Let me introduce myself. My name is Josh Kittle, or you may know me from Twitter as Cisco Voice Dude. I've been working with Cisco Unified Communications pretty much since the beginning, the Call Manager 3.x days, and I'm currently employed by a Cisco partner working in the delivery side of the house, so I install and build and upgrade and patch and maintain these types of systems pretty much every day. I got my CCNA in 2002, and I'm currently a CCNP voice, and I'm in process of studying for my CCIE collaboration. We're just waiting on November to come around when the tests become available. So I've got a little bit of a background in this stuff, and I've kind of been there, done that, seen lots of different things, but what's cool to me is, every new day, every new version of software, is a new feature, is a new opportunity to learn, and that's really why I kind of do the voice thing. But anyway, enough about me. We're going to go through the video course here, and if you haven't seen videos that I've done in the past, my style may be a bit new to you. But, there's going to be some lecture, there's going to be some presentation, but there's going to be a lot of interactivity going on. I'm going to be asking questions, telling stories, and demonstrating things. So hopefully the style is something that you find useful. I'll certainly do my best to give you the best training experience possible. If you're watching this video, you're doing it probably for one reason. You're going to go after the Cisco CCNP Voice certification. And this is one of the videos, or I'm sorry, one of the courses that people tend to start with and do first. It's a good foundational concepts type of exam. First things first, cisco.com/go/certification is going to be a resource that you're going to find useful, and even if you don't find it useful, you're going to find yourself going there anyway and utilizing it as a reference point throughout your certification process. When looking at the Cisco CCNP Voice, and really what Cisco wants you to take away from the certification, or kind of their synopsis, if you will, of the certification, is that it's going to validate that you have the advanced knowledge and the necessary skills required to integrate unified communications solutions into underlying network architectures. Now, those might be new architectures, or they might be existing architectures that you're going to then, voice or collaboration enable. They want to make sure that you're capable to implement, operate, configure, and troubleshoot a converged unified communications network. And we've gone through different explanations or different buzzwords, if you will, over the last decade and a half for what we're now calling unified communications environments. Cisco had the phrase AVID, and then we've called things voice over IP, but really unified communications or unified collaboration is kind of where we are today in things. So we want to make sure you're able to deal with these technologies. And the certification focuses on Cisco Unified Communications Manager. It's going to focus on knowledge of IP quality of service on the infrastructure. It's going to focus on gateway configuration, gatekeepers to some extent, IP phones, voice applications, and utilities on Cisco routers and switches. And really it's bigger than that. We're going to get into the servers that run the stuff and everything else. But soup to nuts, Cisco Unified Communications, that's kind of what the CCNP Voice is all about. You've seen the certification triangle before. Everybody has their own twist on things, so here is mine. When you're going after the CCNP Voice, you're likely going to be starting with the C-Voice video, and we're going to assume that you've got some background. And let's take a step back for a moment and talk about what that background expectation is, and really the course that you need to follow, or the sequence that you need to follow in order to obtain your CCNP Voice. So it all starts with the CCENT, and CCENT is what we kind of think of as the foundation of everything. The CCENT is Cisco's entry-level exam. It's even a precursor, or what do you want to call it? A prerequisite for obtaining the Cisco CCNA certification. Now, keep in mind, to get the CCNA voice certification, which comes next, you don't have to have a CCNA, and that's something that's changed. Originally you did. What's required now, or these days, is you require your CCENT. Now, I'm going to assume that you're going to go after your CCNA. I'm going to recommend that you go after your CCNA because it's going to give you valuable foundation knowledge that is going to truly help you as you proceed in your career and with your studies. So, we've got the first tier out of the way. Now you're into CCNA Voice, and we're talking the ICOM 8.0 exam. If you haven't already watched it, we've put together a nice video series on that. And I think we did a pretty good job of preparing you for the exam with that, and hopefully can live up to that with this series as well. Once you're into the CCNP voice arena, you've got 5 exams that are going to be necessary to pass to wrap up your certification. C-Voice, which is, Unified Communications Fundamentals, Gateways, Quality of Service, etc., which is this series here, is 642-437 as of this recording. You'll go into CIPT1 and CIPT2. Those 2 exams cover Unified Communications Manager. CIPT1 is more call manager fundamentals and core concepts in a single-site environment. And then CIPT2 gets into multi-site stuff, gets into more advanced security stuff, etc. T-Voice is a troubleshooting class. It's going to test your ability to really focus on and resolve problems as they occur in the voice network. So you're going to learn to read debugs and things like that, and understand how to break apart various problems and locate the faults and cause them, and resolve them. CAPS is voice over IP or Unified Communications Applications. So we're going to get into more advanced features and functionality and pieces and parts, and we'll cross that bridge when we get there. But this is kind of the certification lineup. And if you're going for your CCNP voice, you can see the exams that you're going to need to pass in order to achieve that. And this is always a moving target, so by the time you see this, it may have changed or been revised. And so again, cisco.com/go/certification is something you're going to want to check out. This exam, 642-437, or C-Voice, or Cisco Voice over IP, is going to focus on teaching you about voice gateways, call legs, and dial plans. So these are all core gateway concepts. We're going to go through a basic implementation of Cisco Unified Communications Manager Express, or CME. CME is an iOS-based PBX, and it'll run on a Cisco router, and it will provide for call control and call routing capabilities for IP phones. More about CME as we get into it. We'll talk about Cisco Unified Border Element, or Cube, in its role as a gateway, and really, as a session border controller, what can Cube do for you? How does it work? We'll talk about voice-related QoS techniques and mechanisms for implementing these types of things. So, we talked in the beginning that this is focused on preparing you to interact with those underlying networks. So we're going to talk about what you need to know and how those underlying networks need to be configured to support the unified communications. If we look at the exam blueprint for C-Voice, Cisco wants you to go through these following key items. They want you to be able to describe a dial plan, describe the basic operation of a voice over IP call, implement Unified Communications Manager Express to support phone registration using the command line interface. We're going to describe the components of a voice gateway, and we'll talk a little bit about voice gateway implementation. We're going to talk about Cube, or the Cisco Unified Border Element, as a session border controller. And you're going to be able to describe and implement QoS using a DiffServ or a DSCP methodology. So again, this is just kind of more summary of what we've talked about already. But this is what the exam blueprint identifies that you need to be able to do in preparation for passing and taking and passing your C-Voice exam. Let's talk about strategies for success. And if you've watched my videos before, you'll understand that this is something that doesn't change, and I'm going to talk about it quite a bit. I believe that you're the master of your own destiny, and you can do this. In the beginning, when you get into intranetworking technologies and when you start looking at collaboration and voice and video, etc., it can really be a lot to kind of swallow all at once. We go broad and we go deep, and we do both at the same time. So my best recommendation to you is, first off, believe in yourself. If I can do this stuff, anybody can do this stuff. And it's my goal within this video series to help break down the things that are complicated, because let's face it, these aren't trivial tasks. But let's break down the things that are complicated into more simple, concise, and to the point facts and bits of information so that you can digest it and deal with it in a more manageable way. I'm going to do this by giving you lots and lots of video content, and a lot of that's going to be in the form of lecture. We're going to do video labs or demonstrations, if you will, where I will walk you through configuring something or setting something up or troubleshooting something or whatever. And I would encourage you to follow along with these videos. We'll talk about labs here in a minute, but be prepared to do what I do yourself in your own environment. I encourage you to do independent labs. So take my examples, change them up a bit, and do it for yourself. By customizing these labs and these demonstrations, you're going to create problems. You're going to break things, and by breaking things, you're going to introduce the opportunity to troubleshoot and truly learn how to resolve the issues. So you got to play with the stuff. You've got to have hands-on. And really, are you seeing a pattern here? It's repetition, repetition, repetition. You got to get in there, and you got to do the stuff, and it's going to kind of grow on you. Once you get to this point and you've done the labs and you're starting to really become familiar with the ins and outs of how we get things done within the voice world, you're going to go through your final review. You're going to go and you want to participate in some exam simulations. There's lots of great resources out on the internet for that, so I'm not going to pitch anything in particular. I would encourage you to stay away from the brain dump sites that just try to get you to memorize content. You really can't pass a Cisco exam, and you really can't be a good engineer for that matter, by studying brain dumps. Now, on the other side of the coin, it doesn't hurt for you to become familiar with the types of topics that are being seen in the current exam cycles. So you can't memorize questions and answers, you're going to fail. But if you can become more familiar with what to expect and then polish up your skills in those areas, you're just going to have an advantage when taking the test. So I don't encourage brain dumps, but I do encourage you doing some research, finding out, hey, what's happening in the current exam series? What are the things I really need to focus on? And then, spit and polish your skills accordingly. And finally, take the exam. It's not a big deal if you don't pass the Cisco certification exam the first time around. Trust me, I've failed plenty of them, and I probably will continue to do so throughout my career. Exams are just a measurement. They're a benchmark. They're gauging where you are. Unfortunately, the first time you go in, you're probably not where you think you are. But use that as an opportunity to identify the areas that you're still a little weak in, take the chance to immediately go fill in those holes in your knowledge, and then go take an immediate attempt. I am a huge, huge, huge advocate, and I really can't stress this enough, of taking a retake of the exam immediately upon failing it. So there's something like a 5-day grace period that Cisco is going to make you wait between failing a test and taking it again. Take your next attempt on day 6 or whatever. Don't go longer than like 10 days or you're going to start losing the edge. So get in a rhythm, bang this stuff out, and you can do this. You will need access to real equipment, and whether that's rack rental or whether that's equipment that you have access to in your own lab or someone else's, that's fine, but you're going to need to lay your hands on stuff, and we'll talk more about rack rental, etc. here in just a moment. In my opinion, rack rental can suffice, but it is really best to build a lab. It's just more flexible that way, but I'm not gonna dog rack rental. It definitely has its place. Why do I need a lab? Well, voice technologies, they're interactive. We're not dealing with things that can simply be simulated on paper. We really need to touch and feel things. Studying for voice is not the same as studying for a data or a routing or a switching exam. We're dealing with interactive technologies here. We have telephones. We have experiences that take place over these things. And it's important that you can lay your hands on it, set it up, and really make it work and really see what happens. So that's kind of my approach on the thing. And a real-world environment means real problems. And basically what I mean by that is you're going to screw things up. I do all the time. And that's the opportunity for you to troubleshoot. And troubleshooting something is when the learning happens. When it's broken, you're going to figure out how to fix it, and then you're going to commit that to memory. If it just works the first time around, you're never going to remember how to do it. So embrace those challenges, and when things don't quite go as planned, they really can help through the study process and help you learn the technology. So a little bit more on rack rental. Can I use rack rental time? Absolutely. Just keep in mind that the environment that the rack rental provider has set up for you may not exactly match the labs that I'm presenting here in this video. They may not exactly meet your needs, but they'll probably get you pretty close. So keep in mind that labs are kind of a personal thing, and everybody's is a little bit different. So should you use rack rental? It's really up to you. I prefer real gear, but that doesn't mean that I'm opposed to rack rental. Now let's talk about a lab topology, and this is an example topology that I'm going to refer to throughout this video course, and really throughout this whole video series, although I may vary it just a little bit as necessary. This is an example of the current state of my lab here, and it's always in a state of flux, so don't get fixated on, oh, that's a Cisco 3750 switch instead of a 3560 switch, or don't worry that, oh, that's a 2811 instead of a 30, whatever. Don't worry about model numbers quite that deep. Understand the fundamental concepts. And really what I'm going to talk about with the topology is what you see on the screen here. This is similar to my lab. Yours can and may vary, and that's perfectly fine. That's okay. Don't worry about making things exact. Understand what we're trying to demonstrate, understand what the necessary components are, and mock it up accordingly. So, this is not an eBay shopping list, although these are some fairly good choices of equipment to get your hands on if you'd like to use it as such. But this is a good reference example of what we're going to use here through this video series. That really kind of sums it up right now, and that's the intro video for the course here. We're going to start with some of the fundamental concepts and, talk about gateways and talk about, Cisco UC in general, and then we'll get into demonstrations of how to do things. So thanks for watching. I'm really looking forward to going through this video course with you. And for those of you who are returning after successfully completing your CCNA voice, welcome and thank you. And I hope I can live up to your expectations throughout this track on the C-Voice exam. Thanks, guys, and I will talk to you soon. Have good studying, and I'll see you later. Welcome to Module 2 in this CCNP Voice C-Voice exam video series. In this video, we're going to be talking about the role of a voice gateway and how it plays into your unified communications environments. When we talk about the traditional PSTN, and really to understand the role of a voice gateway, it's important to understand PSTN fundamentals. So I'm going to take a second here and sketch out to you what the PSTN typically looks like. So if I were to go ahead and say that this circle represents the public switched telephone network, the PSTN is comprised of a bunch of various central offices, and these central offices are interconnected, and we call these central offices COs. They're interconnected and signaled with something we call SS7, and we don't have to worry about that too much from the end user perspective, but that's the magic that kind of makes the PSTN happen. Now, when you have a location or business, and we'll go ahead and we'll draw a couple of them here on the screen, and we have a PBX, we'll go ahead and show our PBX, we have a connection to the central office, PBX, and this connection to the central office is carried over what we call a local loop. And typically this is, an ISDN PRI, this could be a POTS line, this could be a BRI, it could be a SIP trunk, in modern times anyway. But, we've got these local loops. Go ahead and use ISDN or T1 as the example here. And, when your call is placed from your PBX, and in fact on the back of this PBX, we've got our traditional handsets hanging off of the end of it. So when a call is placed from one handset to another, so let's say, handset A here wants to call handset B, the call is going to go through the PBX, out to the PSTN, across these various CO interconnections, and these CO trunks as they call them, and ultimately work its way to our site, to the PBX, and ring the phone that we've dialed. Now, there's a concept of interconnecting traditional PBXs, and we called those tie lines or tie trunks. And really, what it is it's just another circuit going into a CO. We'll draw a couple different ones here. I'll just call it a tie line. And really think of this as, for example, a point-to-point T1, where PBX at site A is connected to the PBX at site B. So they act as though they're within the same premise, or certainly anyway, they're reachable from premise to premise, but all that signaling is going through the PSTN. Now, things are a little bit different with voice gateways, and really, I'll go ahead and I'll just draw another site here that is a unified communications enabled location, and we're still going to have that CO trunk, and it still might be an ISDN PRI. However, it's going to enter our premise and terminate to a device called a voice gateway. Now, the voice gateway is going to be on our LAN, and we're going to have other things on our LAN, such as our call manager, such as our IP phones, etc. So it's a little bit different architecture-wise than what we've done traditionally, but the same kind of concepts apply, relative to the PSTN. When we talk about call signaling, voice gateways are signaled or have call signaling occurring with one of a number of different protocols. The 4 protocols that you're going to primarily deal with are shown here on the screen. We have SCCP, which is the skinny call control protocol. We have MGCP, the Media Gateway Control Protocol. We have the standard H.323, and we have the other standard SIP. So lots of choices here. It's one of those things that you'll have to kind of analyze, what is my use case, and ultimately you'll make a decision of in a given instance, am I using skinny or am I using SIP, or what makes sense for this implementation or this client. So these are the 4 common call signaling protocols that you're going to run into, and here in the next couple of slides we're going to talk about what each of these call signaling protocols has in common, and then not so in common with the others. So that'll kind of be the basis for understanding how you make those choices. Skinny, or SCCP, the Skinny Call Control Protocol. Skinny is a Cisco proprietary call control protocol, and it's primarily used as a protocol for signaling events between unified communication endpoints like IP phones and a PBX, Cisco Unified Communications Manager or Call Manager Express, if you're a CME on a router. It is a client-server protocol, and really, the thing I want you to take away from Skinny, at the high level here, is that because it's a client-server protocol, it's not real intelligent. Most of the intelligence is at the head end. The device is just kind of sending messages back to that call manager, and call manager is doing the intelligent decision-making. Without the call manager, the phone running Skinny doesn't have the capability to set up and tear down calls on its own. So when I pick up the handset and I go off hook, it's going to send an event message over to call manager. When I press keys on the keypad, it's going to send messages to call manager. When it's time for my phone to ring, call manager is going to signal my phone, hey, play the WAV file and send your ringer. So all of these different things, because it's client server, really the head of the snake is the call agent or the call processing system like Call Manager or Call Manager Express. So that's Skinny, the Skinny Call Control Protocol. And once again, most of the time you're going to see Skinny in use for controlling telephone endpoints. However, you can also control things such as FXS ports, the analog ports that we can connect station devices to on a voice gateway. And more about those ports and that interconnection method later. The next protocol we want to talk about is MGCP, or the Media Gateway Control Protocol. MGCP is standards-based. A lot of people seem to think that MGCP is a Cisco proprietary protocol. That's not entirely true. In fact, it's not true. Cisco was a key player, in fact, probably the key player in the development of MGCP, but they didn't do it alone. MGCP is defined currently, anyway, in the latest iteration of the standards, in RFC 3435. Previously you could look at like RFC 2705 and get information about MGCP as well. But MGCP really, in a nutshell, it's the successor to the SGCP, the Simple Gateway Control Protocol. And with MGCP, the gateway devices that you're communicating with using MGCP, they're controlled by what we call a call agent. And that would be your call manager, your Unified Communications Manager, or your Unified Communications Manager Express, your CME. MGCP is also a client-server protocol, so there's a lot of chatting going on between the endpoints and the call agent. One of the major benefits for MGCP, and one of the reasons a lot of people have kind of fallen in love with it, is that it offers you the opportunity for centralized gateway. And what I mean by that is centralized dial plane administration. So if I'm in an enterprise and I've got 27, 28 gateways spread throughout my organization, and I'm running MGCP, all of that dial plane logic, every little last bit of it, is managed from the call manager. It's not something that I have to manage individually from gateway to gateway. Now, I'm not saying that that's always the best the best thing, but it is attractive to some people. Another interesting capability, and really I don't even want to call it a capability, one characteristic or behavior, if you will, of MGCP is that it performs something we call Q.931 layer 3 backhaul. So let's say I've got a PRI, and I've connected that PRI to a voice gateway, and that voice gateway is running MGCP. Well, let's say it was an H.323 gateway, which we'll talk about in another slide, that D channel, that signaling channel on that PRI would be under the control of the gateway it's terminated on, i.e. the voice gateway, the router. With MGCP, however, that Q931 signaling is tunneled all the way, or backhauled all the way back to the call agent, back to the call manager, back to the call manager express. So it's a little bit different. It's got some pros and cons. We'll learn more about MGCP as we go, but it's kind of interesting to understand how that Q931 PRI backhaul actually works. H.323, this is kind of the good old standby. It's been around for a really, really long time. H.323 is standards-based by the ITU-T, and it's probably, if not the most, it's certainly one of the most widely deployed protocols for voice over IP type of applications, and we're talking, well beyond just Cisco here. H.323, again, it's been around a long time. It includes a couple of other protocols in the family. We've got H.225 call control. We've got H.225 what we call RAS, which is registration, admission, and status. We've got H.245 control signaling, and this is also a peer-to-peer protocol. And when I talk about a peer-to-peer protocol as opposed to a client-server protocol, if you remember when I was talking about MGCP or Skinny, those are client-server protocols, and really the endpoint is pretty dumb. There's not a lot of intelligence in the endpoint. If you want to if you want to really do anything, you got to talk to the call manager. Well, with H.323, that's not the case. Being that it's a peer-to-peer protocol, the H.323 device, the gateway in this case, can control or can have control over its own dial plan, all by itself. You can create call routing rules within the H.323 gateway that have nothing to do with the dial plan and call manager. And it's kind of different in that way. And, the next protocol we're going to talk about, SIP, has a lot of similarities to H.323, as you're going to see in the next slide. SIP, the Session Initiation Protocol. SIP is also standards-based, just like H.323 is. However, whereas H.323 was a standard created by the ITU-T, SIP is an IETF standard. And, I'm going to just call it a standard. You'll get people arguing with me about draft standard status and all this stuff. It's so... changing so fast, I'm just not even going to go there. But SIP is a standards-based protocol. It's also widely deployed. SIP is everywhere. When we start talking multi-vendor stuff especially, SIP is kind of becoming the de facto go-to method of integrating System A and System B. SIP uses the concept of a user agent, or a SIP UA. With SIP, user agents initiate sessions, and we'll get into all the user agent stuff later in the video series, but I just want to kind of give you a high level here. One of the cool things about SIP is that the signaling communications is formatted as ASCII human-readable text messages, and that goes to my next bullet here, is that we have the capability to do plain text debugging. I don't have to sit here, run a debug, capture tons of data, throw it into a text editor, and then take my highlighter out and go find the pieces of data that are important to me. I can simply sit there and read it off the screen and see what's going on. It's very intuitive to troubleshoot. And that's one of the things that I certainly like with the SIP protocol. And SIP, just like H.223, is also a peer-to-peer protocol. So, lots of call routing intelligence native on the SIP gateway. And SIP's one of those protocols. I'm talking about it in kind of a gateway context here, but it can be used for so many more things. SIP can be used as a phone signaling protocol. And in fact, when you do that, the phone itself has the capability or the intelligence to be able to do call setup and teardown on its own. So I'm kind of digging deeper than we need to right now, but SIP is the last protocol that I really wanted to talk to you about in this introduction to the role of voice gateways. So this kind of wraps it up for this quick little video. I just wanted to talk about gateways, what they are, what they do, and what protocols are at play. We're going to have videos coming up next, and we're going to go over some of the specific hardware models of voice gateways. We'll talk about the kinds of modules that will go in them, and you'll get a whole lot more understanding about how voice gateways work. And ultimately, we'll go through some pretty significant configuration exercises. So for now, this is your primer on voice gateways and the role of voice gateways. And I want to thank you for watching, and I will see you in the next video. Good studying. Welcome to Module 3, and we're going to be discussing UC deployment models. And more specifically, or I should say, for the most part, this conversation centers around Cisco Unified Communications Manager. We are going to mention Call Manager Express and even third-party PBXs in this a little bit, but by and large, this is a Call Manager conversation. And again, this is part of the C-Voice exam series. Right now, the exam is 642-437. But let's jump right into this and talk about UC deployment models. Now, there are 3 models that you're going to run into. In fact, two out of the 3, really most of the time. The third is kind of an exception to the rule. But when deploying Call Manager, you've got the single site deployment model, the multi-site centralized call processing deployment model, and the multi-site distributed call processing deployment model. Single site works great, scales well. Some of the multi-site stuff also can kind of incredibly scale if you really need to get into these huge, 100,000 phone count kind of things. But, we'll jump right into that. So keep in mind there's 3: single site, multi-site centralized call processing, and multi-site with distributed call processing. Let's talk about the single site deployment model. So when we're talking about a single site, we're talking about one building, local area network only, no WAN, and we're talking about a single CUCM cluster. Now, a single CUCM cluster, from a test perspective, I want you to think the number 30,000, but understand that this has grown, in the 9.x version. Now it's 40,000 SIP or skinny endpoints. So this is IP phones. We can support up to 2,100 H.323 devices, so those could be H.323 endpoints or, gateways running the H.323 protocol. And everything that leaves the site is going to use the PSTN because there is no connectivity to any other sites. There's no WAN. There are no other sites as far as that's concerned, so everything's going to the PSTN. Some of the benefits of the single site deployment model, obviously it's simple. So ease of deployment. You've got one call manager cluster, phones, gateways, you're done. We've got a common infrastructure for our voice and our data traffic. So, and I'm kind of mentioning, routing and switching here. We're using that same enterprise infrastructure. Because everything's going to the PSTN and not to other sites, we've got a simplified dial plan. And again, because there are no other sites, we're using one codec. So we don't require transcoding. What are some of the design considerations for a single site? And really, this is what are some of the design considerations for a call manager cluster. And this will scale to, multi-site as well. You need to provide a fault-tolerant underlying network infrastructure. So I'm talking routing, I'm talking switching here. You need to analyze your dial plan and your calling needs. How many digits do I want to have in my extensions? What are my gateways and PSTN paths? We're going to talk about codec use. And with a single site, you're typically going to be using a high bitrate codec, such as G711 or more recently, G722. We're going to need to evaluate high availability requirements for the telephony environment. Do I need multiple call processing nodes? Do I need subscribers? If so, how many? Do I need multiple voice gateways? If so, how many? Do I need multiple paths to the PSTN, i.e. circuits? If so, how many? So all of these things are going to come into play, even with a single site, and then obviously we'll think about them in multi-site environments as well. When we look at the multi-site centralized model, we've got a single call manager cluster still. This is really just building on that single site environment. And we've got support for the same number of endpoints, 30 to 40,000 endpoints, 2,100 H.323 devices. But here's where it starts to differ. We're going to talk about a maximum of 100 locations. We're going to start using multiple codecs because obviously our WAN links are going to be lower bandwidth than the LAN. So we're going to need things like transcoding services, and we'll use DSPs to do that. We'll talk about redundancy options relative to site survivability and what I'm going to call SRST. You know, how do I deal with WAN failures? And I'll draw you a sketch here in a minute to demonstrate some of these things. We're going to have calls going across the WAN, so obviously there'll be cost savings. You know, why are calls going across the WAN? Because they can. You know, why would I send a call from phone A to phone B in 2 different locations across the PSTN and pay for it if I can send it across my data network for free? And the same goes, you know, with toll bypass. If I can send a long distance call, you know, out a gateway, so it's not a long distance call anymore, I bet that call is going to be cheaper. So let's leverage the WAN to do that. Now, when we talk about these multi-site models, and in fact, a centralized call processing model, let's look at it this way. Let's say that I've got, you know, a headquarters location, HQ, and I've got, you know, multiple nodes in my call manager cluster, and phones are registered, etc. You know, I may have a voice gateway with PSTN connectivity, you know, let's draw a little LAN here, and I may have a WAN router, you know, out to some kind of IP WAN. This could be point-to-point links, this could be an MPLS cloud, this could be DMVPN, this could be any number of different things. And, you know, I'm going to have, you know, a branch location, we'll call it branch A, and we'll have, you know, a LAN and, you know, some kind of router or terminating equipment for, you know, whatever that connectivity is. You know, and I'm going to have IP phones out here. Now, I'm not going to have a call manager cluster. Centralized call processing means everything happens in a central location. So in this example, it's happening out here at HQ. Now, when we look at the branch, you know, I mentioned WAN failure. Let's say this IP WAN goes down. What am I going to do? Well, this gateway right here is going to need the ability or need the capability to handle local call processing. So this phone can register to the gateway, which has, you know, its PSTN pathway, you know, maybe it's a PRI, maybe it's a POTS line, whatever. But, you know, in the event of that WAN failure, the phones can swing over to the gateway, and the gateway can provide for services until the call manager is restored. Let's talk about the multi-site centralized deployment benefits. You know, it's just like having a single cluster, but we're serving multiple sites. Or I'm sorry, it's just like having a single site, but we're serving multiple sites. It's still a single cluster. We're going to have reduced infrastructure over what would be required if we had a cluster in each location, which is what we're going to talk about in the multi-site distributed architecture. We're going to have a centralized dial plan. You know, because there's one cluster, all the dial plan logic is all in one place. And we're going to start having, you know, survivability capabilities for these remote locations should that, you know, the primary call processing node or cluster become unreachable. So that's SRST. What are some of the design considerations for the multi-site centralized environment? Obviously, we've got to consider WAN latency and bandwidth and quality of service and fault tolerance of the WAN. You know, we want to make sure that that WAN, you know, is less than 80 milliseconds round trip, or, you know, we're going to have some issues. We're going to think about using different codecs for calls across the WAN versus locally. You know, if I've got a switched environment and I've got bandwidth to spare, or, you know, unlimited bandwidth, if you even want to think about it that way, at my disposal, the choice of codec that I'm going to use isn't going to be such a big deal. But if I'm going to go across a low bandwidth WAN link, like maybe a fractional T1, I'm going to start to care about those things. So we'll talk about using low bitrate codecs. Again, we're going to evaluate our survivability needs for SRST. Do these phones need to be able to register and have PSTN access in the event of a WAN failure? And we're going to start thinking about call emission control. Again, this is a bandwidth discussion. You know, when we talk about CAC, let's say my WAN is big enough to support 10 calls, period. If that 11th call is allowed to happen, guess what happens to all 11 calls? They all start to suck because every one of them, they're all going to be competing for bandwidth, and there's not enough bandwidth for all of them. So QoS can't solve this problem. I can't prioritize traffic when the bandwidth exceeds, or the bandwidth demand exceeds the available bandwidth. So call emission control can help to route calls, you know, either reject calls or, you know, using alternate routing, you know, AAR stuff, we can send it up to the PSTN and route around the WAN. So we'll talk about that stuff in other videos, but you know, we'll start to think about CAC in the multi-site centralized design. When we start scaling that even farther and going into this distributed call processing model for multi-site, we're going to deal with multiple CUCM clusters. And let me draw you a picture here. So, you know, HQ right here, you know, maybe this is a large branch, or maybe this is some kind of a campus environment. You know, maybe it's college, and I have, you know, regional locations or whatever. You know, and I've got this big monster IP WAN in the middle, and I've got this call manager cluster, you know, out here, and he handles his local phones, and I've got this call manager cluster out here, and he handles his local phone. So that's a multi-site distributed call processing environment. Again, 30,000 to 40,000 endpoints per cluster. Same kind of counts on H.323 devices as you've seen before. But as we start doing this multi-site environment, we're going to evaluate the use of things like gatekeepers and deal with ways of distributing dial plan. We're also going to continue to think about things like PSTN toll bypass. So lots of stuff come into play here. What are some of the benefits of the multi-site distributed environments? Obviously, we're still using the IP-WAN for enterprise calls, so we're not sending things to the PSTN, unless they need to go to the PSTN. We've got toll bypass capabilities still. We're maximizing your bandwidth utilization still, because we've got voice and data running one common network. We're gonna, have benefits of, high availability and call processing survivability. We're going to have lots and lots of scalability because obviously if I can get 30, 40,000 endpoints per cluster, I can put the things all over the place. I don't care if there's 10 or 100 locations or even more. Just keep spinning these things up and keep having more and more capabilities. What are some of the design considerations for the multi-site distributed model? Well, you're going to start thinking about, and I mentioned it before, but you're going to start thinking about things like gatekeepers and SIP proxies to deal with distributing your dial plan. You're going to have to think about trunks between systems. Obviously, if you've got multiple clusters, you got to have ways for calls to flow between those clusters. Those are going to be SIP trunks or intercluster trunks. You're going to want to think about things like using HSRP for gatekeeper pairs to give you some redundancy and access to those gatekeepers. You're going to be limiting the WAN to one type of audio codec. Again, this is gatekeeper stuff, and we'll get into that a little bit more as we go on. But lots of things go into these multi-site distributed environments. When we start talking about these distributed environments, and really this is more it's kind of a blend. It's not a single site call processing model. It's not really distributed, but let me just draw you a picture. Let's say we're in an enterprise and we have two data centers. And these two data centers are kind of the center of our universe, DC1 and DC2. I may have a call manager pub and sub in this primary data center, and I've got this IP-WAN out here, and I may have another sub at data center 2, and maybe all my branch locations are connected, let's call this a branch router, maybe they're all connected via multiple WAN links, one to each data center, and I've got IP phones out here, like that, etc. So I've got to think about what's the delay across this WAN? Because I've got nodes here that need to be synchronized with each other. So what is the delay of this WAN? And like I'm showing you here, it needs to be less than 80 milliseconds. You start creeping above those numbers, you're going to have problems. We're going to start thinking about QoS-enabled WAN links. And really, we're not just going to start thinking about it. These things are going to be critical. We need to make sure this communication is happening in a timely fashion. We need to make sure that we're minimizing jitter. We need to make sure we have sufficient bandwidth. And we need to manage packet loss and errors. If this WAN is lossy and dropping 10% of the data, you can bet that you're going to notice it. And I mean, that's just all there is to it. You're going to notice it. It's going to be a problem. So you really have to handle your network and make sure things are in order to do this clustering across the WAN. But this is kind of a hybrid. It's multi-site, and it's still kind of distributed call processing, but it's still just one cluster. So cool stuff here. I'm seeing a lot of this. So clustering across the WAN, definitely something you're going to run into out there in the enterprise. When we talk about these, multi-site environments, especially the distributed call processing environments, we may not just be talking about call manager here. We may be talking about CUCM, call manager, in one location. We may be talking about CME or a small location somewhere else with a SIP trunk to call manager. We may be talking about a traditional or legacy PBX with a voice gateway running SIP to bring it into the thing. And, these things could look like lots of different things. I could have, HQ out here. He could have call manager, and so CM. We could have another location out here with a CME running on an iOS device. We could have, a voice gateway at another branch connecting to a traditional PBX. So lots of different models here and lots of ways these things can all connect together. I know you've been drinking from the fire hose through this video, and I both apologize for that and also say you're welcome because, this is really kind of where the rubber meets the road here on call manager design. You need to understand the multi-site, distributed and centralized model. You need to understand the single site model and, how all these things kind of tie together. So I'm going to call that good for this video. And in the next video, we're going to start talking about some of the specific hardware and jump kind of back into the gateway conversation and talk about makes and models of hardware, types of interfaces, and what's typical. What are things you may see out there in the field? What are the things you're going to need to know for the exam? And, really continue the gateway conversation. So thanks for watching. I really appreciate it. I hope that this has been informative to you and good studying. I'll see you in the next video. Welcome to Module 4. This is going to be a really quick review or overview of common voice gateway hardware that you may run into in unified communications environments. We're going to talk about the modern stuff as well as some of the more traditional pieces of equipment that you're likely to run into in the field. Common PSTN gateways, we've got all kinds of gear here that we can be talking about. Lots of routers, lots of purpose-built devices, etc. But let's talk about the more common things. When I show over here on the left, modern equipment, we're talking about Generation 2 integrated service router. So ISRG2 hardware. So, the X9 series of things. So the 2900s, the 3900s, etc. One of the cool things about this, the router-based voice gateway services is you can provision the hardware however you want. You can put FXO modules or FXS modules in it, or you can put an E&M module or a T1 PRI module, or, if you need to do, something other than that. You've got choices here as far as quantities of ports and densities and exact configurations. So ISRG2, very popular choice here. And you can scale this from a single POTS line clear up to multiple PRIs. Taking a step back, one generation, we're going to be looking at the original integrated services routers, so your 2800s, your 3800s, etc. Very similar in functionality to the more modern, ISRG2 hardware. Many similar cards. We're going to have the same type of flexibility and configuration where we're dealing with, FXOs and FXSs and E&Ms and PRI, etc. So these are the two, tried and true, very popular, widely deployed types of equipment you're going to deal with, the ISRG1s, G2s. I've done a lot of work with gateways even older than this, Cisco 3700s. If you even want to go back farther, the 3600s, 3660 made a great voice gateway with, ISDN PRI or T1 CAS circuits in it. And, same goes for, an old device we called the VG200. It was a very small 1U voice gateway that was used in a lot of entry-level deployments or, small density deployments. But let's move on to the next slide, and we're going to talk about some of the special purpose gateways that you're going to run into. These are more purpose-built devices. The ATA 187s or ATA 186s, those are the analog telephone adapters. Now, the ATA, whether you're talking the original 186s, 188s, or the more modern replacement, the 187, they serve generally one purpose, and that's to provide an analog station connection to your IP PBX. A lot of times you'll see these servicing fax machines or servicing, an analog phone on the wall for, maybe it's in a warehouse and it's just a common area phone, things along those lines, where, perhaps the distance limitation of Ethernet is an issue, but you can still swing a POTS line out there. So analog telephone adapters, the biggest difference between the ATA 187 and the more legacy 186s, 188s, the ATA 187 is SIP-based, and the 186s were skinny. So a little bit different, but, serve a similar purpose. If you want to kind of kick it up a notch to an ATA on steroids, or, and really it's a small miniature voice gateway, it'd be something like the VG202 or 204. Get a couple of ports of FXS connectivity. Now, these are iOS-based devices, whereas the smaller, ATA 186, 187s, those are kind of purpose-built devices, and they really don't have, an iOS-like interface that you're used to on a router. But, you get into the VG202s, etc., and they're going to be. Another voice gateway for high-density analog connections was the VG224, or more historically, the VG248. Now, it might sound like the 248's bigger. Well, it was bigger, but it was older. The 248 was a Cisco acquisition, early, first, second-gen product, whereas the VG224 is an iOS-based platform. So two very, different pieces of gear. The VG248, that could run skinny. The VG224s, those are going to support multiple protocols. You can, MGCP, SIP, H.323, we can keep going on. But those are your analog services gateways. Now, you can still put a couple of analog ports, or, a lot of analog ports if you want, into one of those ISRG2s or ISRG1s, but it's not real common. So for density, you're going to end up in something like a VG224 more often than not these days. Now, universal gateways, we just call them universal gateways because they can be configured to do lots of other things. And really, so could the ISRs. But these are more service provider-centric or more specific purpose-built devices. The AS5350s or AS5400XMs, those were, I'll call them carrier-grade equipment. They're built a little bit differently than gear that you're targeting for an enterprise. Cisco 7200s, especially things like 7206 VXRs, those were not real popular. I've maybe seen like one, maybe, in the field, but people just didn't use them for voice. Excellent WAN routers, excellent edge devices, just not real popular for voice. But, certainly there were some capabilities there. As we get into talking about different routers and programming things, you're going to likely kind of adopt a favorite device that you use. Mine is the ISR, ISR G1 and G2. Those things are just amazing. You can provision them however you want. But this was really meant to just be a quick tease of what's out there and give you an idea of the types of hardware you're going to run into. There's not a whole lot that we're going to dig into great detail on there. But one more thing I want to hit in this video: session border controllers. It's another type of gateway. And you're going to hear me refer to these things as cubes or Cisco Unified Border Elements more often than not. But a session border controller is a type of gateway that really, I want you to think of it as an IP to IP gateway. In fact, early on, that's what Cisco called it. They called it IP gateway as a feature set in one of the, the iOS feature packs. So session border controller is used to terminate media sessions and signaling, and there's different ways to configure these things with media flow around, flow through, and we're not going to get into all this in this video, but they're often installed as an edge device. So let's say I want to have a SIP trunk to my carrier. I'll have them bring in an IP connection to my edge, and they'll plug it into my queue or my border element, my session border controller, and then I'll have a SIP trunk from that device over to my call manager, and it sits there at the edge of the network. Providing that point of demarcation. These things are providing for SIP to SIP, H.323 to SIP, or H.323 to H.323 connectivity. So again, it's an IP to IP gateway. And one of the biggest differences is when you look at a traditional voice gateway, and we'll cover a lot of this when we start talking about dial peers and programming those things, but you're going to have a PSTN leg or a PSTN interface and associated dial peer, what we call a POTS dial peer. And you're going to have a IP-facing interface, whether that's a SIP trunk or H.323 or whatever. And you're going to have, the associated VoIP dial peers. But the session border controllers, it's IP on both sides. So SIP to SIP, H.323 to SIP, etc. So that's really it for talking about, types of hardware gateways that we're going to get into. Really, you're going to be touching and feeling these things and getting your arms around them. So there's not a real need to go a lot deeper than that. But I just wanted to give you a quick little Nichols tour of the types of hardware that's out there, which you're likely going to run into in both new and existing installations. So thanks for watching, guys. As we get into the next series of videos, we're going to be talking about voice call legs and going through basic dial peer configuration and some not so basic dial peer configuration, and really start talking about how to make the calls flow through these devices. So thanks for watching. Good luck with your studying, and I will see you soon. In this video, we're going to talk about call legs and dial peer fundamentals. I want you to understand the concept of how calls route their way through a voice gateway, and that's all about dial pairs. So let's just jump straight into this. I think that a picture is worth 1,000 words as far as this subject goes, and I think we're going to help paint you that picture as we go through this video. Now, when you're dealing with a voice gateway, I want you to understand that every call into and out of a voice gateway requires a dial pair to be routed. And we're going to make decisions on routing based on calls coming into us, or what we call an incoming call leg. We'll go ahead and draw you one here. And calls going out of us, and what we're going to call an outgoing call leg. Now, inbound, outbound, etc. So a voice gateway is going to make decisions that will influence how it routes a call when the call enters it through the incoming dial pair, and as the call leaves it on the outgoing dial pair or call leg. And really, call legs and dial pairs are not synonymous to each other, but they go hand in hand from a functionality perspective. So if you've got multiple hops in your voice network, where you're jumping from voice gateway to voice gateway to voice gateway, perhaps you've got SIP trunks or H.323 trunks between them, you're going to have dial pairs at each point, and you're going to have call legs at each point. So let's just jump right into this here and talk about types of dial pairs. There are 3 types of dial pairs I want you to be concerned with: POTS dial pairs, VoIP dial pairs, and multimedia over IP dial pairs. In fact, the first 2 you're going to use day in and day out, and on occasion you may use an MMOIP dial pair. So first and foremost, POTS dial pairs. POTS dial pairs are used whenever we are going to route a call in or out a physical interface that is either analog or TDM. So FXO and FXS ports, a T1 CAS interface, or an ISDN PRI interface. VoIP dial pairs, we're going to use these when we're routing a call to another IP peer. So that could be router to router. It could be an H.323 connection to another voice gateway. It could be a SIP trunk to a call manager, etc. Multimedia over IP dial pairs we're going to use when we're doing store and forward fax, and they are going to point to an email destination. And more about these types as we go through the various videos in this course. But I just want to jump right into it, and we're going to show you what dial pairs look like and how they work. So keep in mind, and in fact this is a good analogy to build, is that together dial pairs build a dial plan. So if you want to think of this similar to routing, I want you to say routes build a routing table. So dial pairs are really similar to routes, and the dial plan is really very similar to the routing table. Now I've got a voice gateway here in the lab that I'm going to go ahead and show you some dial pairs on. This is a Cisco router with a analog FXO module in it. Actually, it's a 2-port FXO module. And I use this as a connection to a PSTN interface for the lab here. I happen to use 9 as an outside access code. So whenever I pick up my IP phone, I press a 9 and I dial the numbers I want to dial. Well, what happens in my call manager is I send the calls to the voice gateway, and once I hit the voice gateway, it's going to evaluate its dial pairs and look at an incoming called leg. And what it's going to do is it's actually going to match based on some values in the gateway for an incoming call leg and make some routing decisions. And then it's going to look at what number I'm trying to dial and try to find an egress path, and it's going to match another dial pair. And I want to show you here on the inbound dial pair. This is coming from call manager. So I've got an IP phone with an IP connection to call manager. So the incoming call leg is actually going to match this dial pair voice 100 VoIP, and it's just going to match it. I'm not doing anything with it, but it's going to know that it came from this, the source address, etc. I've got my incoming figured out. I need to pick a next hop. I need to go to the PSTN. My call is 9. Let's say I dialed a toll-free number. Maybe I dialed, like a 9. Whoops, let me draw it here. 9 1, 513 555 1000 or whatever. Maybe that's the number I dialed. My router or my voice gateway is going to need to analyze the number I dialed and figure out where to send me. Now this dial pair voice 12 POTS that you see here, it says destination pattern 9 1 and then digits 2 through 9 and then X number of more digits. So basically I'm going to match that pattern like I would a route. So I'm going to match that dial pair, and then it says port 100. Well, that happens to be an FXO port where I've got a POTS line connected. And as simple as that, the call is made, the routing takes place, and, I'm talking on the phone. So dial pairs really don't have to be crazy complicated, although they can be. There's lots and lots of things you can do with dial pairs. Tons of different ways you can match on things coming in and out, and there's orders of priority, and what do I look at first, and we're going to get into all of those things. But at a high level, I want you to understand dial pairs are like routing statements. We're going to match one as we come into a device. We're going to match one as we leave a device. And, really high level, that's it. You've got it. So as we go into more explanation of dial pairs, just keep that in mind. There's incoming call legs and outgoing call legs. Each call leg is going to be associated with an incoming dial pair and an outgoing dial pair. With that, we're going to say thanks for watching, and we're going to move into the next set of videos, and we're going to really dive into dial pair configuration in a lot greater detail. This was really just a skim of the surface. So I'll see you in the next video. Good studying, and we'll talk to you soon. Thanks, guys. In this video, we're going to talk about dial pair matching and call routing decisions as they're made within the voice gateway. Now, previously we talked about the structure of dial pairs and how they relate to, call legs. In fact, here's a review of the call leg concept, where I've got a voice gateway and I've got an incoming call leg, and then I've got an outgoing call leg or an outbound call leg. And we talked about how we would match a dial pair for the incoming leg, and we'd match a dial pair for the outgoing leg, and that's how we decide how to make our routing decisions. And we talked about how together, all of these dial pairs, like routing statements, would create a dial plan, or effectively a routing table. So that's all the same, and we're going to kind of zoom in on it a little bit granular, a little more granular detail in this video. Now, I told some fibs about how things were actually working in the last video for the purpose of keeping things simple. I didn't want you to focus on the exact specifics of why I'd matched this peer or that peer, or the details of what came first or any of that. I wanted you to focus simply on the fact of understanding incoming call legs, or inbound call legs, whatever term you want to use, and outbound or outgoing call legs. And I wanted you to understand that we would evaluate dial pairs and match them to make routing decisions. Beyond that, the rest of it is for this video and, stuff that's going to follow. I want to go a little deeper, and I want to talk about the specifics of what we match, why we match, how we match, the order in which we match, and all the various considerations that come into play with that. So let's now zoom in on dial pairs and talk about the meat and potatoes of it, if you will. And I've got a good example for you here of POTS dial pairs. This is a fictitious network here. We're going to, go ahead and put some extensions, 1001 and 2001, on these phones. And I'm going to walk you through some dial pairs that would be on the voice gateways shown here on the page. So let's say extension 1001 wants to call extension 2001. So that's the call we're going to create. Well, what's going to happen is extension 1001 is hooked up to an FXS port on the router. And let's assume that the router is connected to the PSTN via a PRI, and that the router at the other end is also connected via a PRI. And we've got another FXS port. So let's walk through the flow. So guy at extension 1001 picks up the handset, gets a dial tone, makes a call. He dials 2001. So here's what's going to happen. And obviously these patterns wouldn't work on the real PSTN, but we're just mocking this up as an example here. So we're going to match an inbound dial pair. Well, I want to show you dial pair voice 20 POTS down here. I've got a command here, incoming called dot. That command is going to match any dialed number coming in
So I'm going to see that in the dial peer, and I'm going to match that. So I'm going to match an incoming dial peer. So I've matched 20. Now that I've matched an incoming dial peer, I have the ability to evaluate the dial plan, think of it as a routing table, and look for my next hop. Well, I've dialed 1001. Well, guess what? I'm going to use the same dial peer as an outbound dial peer in this example. Maybe I shouldn't have done that for the example, but it'll work just fine. Because my destination pattern is 1001. So, I'm sorry, I'm lying to you. Let me back up for a second. My destination pattern is actually 2001. I'm going to match this dial pair. I was looking at my drawing backwards. So I'm going to match 20 for an inbound dial pair. I'm going to match 10 for an outbound dial pair. So I've matched 10 for a destination pattern of 2001. It has port 200 configured. That's this interface right here. So we're going to send the call at that port to the PSTN. So we're going to have a call come in. The magic of the PSTN is going to route it to me. And we're going to match, another incoming call leg. Now, if you'll see dial peer voice 10 pots, again, incoming call dot. That's a beautiful match for an incoming dial peer. I'm going to match the dial number. So, now that I've matched an inbound dial peer, number 10, let's match an outbound dial peer. Well, you know that I dialed 2001. So, since I dialed 2001, again, this command down here, destination pattern 2001, port 100, we're going to send the call out port 100, and we're going to ring the phone. Extension 2001 is going to answer, and our call is connected. So we've actually, in this scenario, evaluated 4 dial pairs. We had the inbound call leg to the gateway, the outbound call leg from the gateway to the PSTN, the inbound call leg from the PSTN to the gateway, and the outbound call leg from the gateway to extension 2001. So we've walked you through the whole cycle, and that's how the call was made. I've thrown a lot of different options at you here. I've introduced you to incoming call dot. We'll talk more later about this direct inward dial command that has to do with, one stage versus 2-stage dialing. But really, what I want you to take away from this is, again, understand you're matching incoming dial pairs and you're matching outbound dial pairs. Understand some of the options under the dial pair, like port. Understand forward digits. I'm telling it in this case to forward digits all. So all the digits I dialed, continue to forward them. And, really that's a good textbook example. Now, let's talk about the matching, because I've showed you that we matched, but I didn't really explain why. There are a few things you can match on. First, DNIS, the dialed number information service. That's the number that was called. And you saw I used incoming called number as the command. I can match on Annie, which is my caller ID, using answer address. I can match on Annie using destination pattern. I can match based on the voice port. And if I don't match anything else, I'm going to match dial peer 0. And dial peer 0 is our default dial peer. So let's talk about dial peer 0. Dial peer 0 is not a dial peer you program. It exists by default within the iOS. What does dial peer 0 support? Well, it's G729 or G711 only. Any packets that match dial peer 0 are going to have an IP precedence of 0. Not great. That, or voice activity detection, is enabled on dial peer 0. There's no support for the RSVP QoS mechanisms when using dial peer 0. And it does not support direct inward dial. And that's a big deal. We'll talk about 1-stage versus 2-stage dialing throughout the course. Let's suffice it to say that if you call a gateway and your inbound call leg matches the default dial peer 0, instead of your call routing to the number you dialed, we call that 1-stage dialing, you'll be greeted with the dial tone, which is, you then have to type in the number, and then it's going to evaluate the route plan and find a dial pair and route your call. That's not good. We used to do that back before direct number dial was available, and we did two-stage dialing. So the PBX would answer, give you a second dial tone, you'd dial the destination. But nowadays, we don't do that anymore. Now, we allow the PSTN to pass the DNS to the PBX, and we use one-stage dialing. Now, I want to show you an example of a real voice gateway. This is a gateway that I use here in my lab, but it's not lab gear. This is actually production gear. Show dial peer voice summary. Good command to use. We'll go ahead and blow this up a little bit bigger. And I'm going to show you, let me run that again, that screen's a little wider. I'm going to show you the dial peers I have configured in this gateway. I've got 3 POTS dial peers, a 10, an 11, and a 12. And I have 2 VoIP dial peers, a 100 and a 200. You can see the patterns that I'm using. They're a bit more specific than those vague patterns I was showing you in previous videos. And this is actually a gateway I used for PSTN connections. So if I match 9 plus a number, a second digit beginning with 2 through 9, and 6 more digits, so I'm dialing a 7-digit number, then route it out port 100. That happens to be an FXO port going to an analog phone line here. The next pattern, that's a 10-digit match. And these still aren't perfect patterns for a production system. Your patterns are going to be a lot more specific than this, and that's okay. I'm just trying to demonstrate some basics here. For inbound calls, that dial peer 100 you see, if a call comes in and presents a DNS of, 1 through 2, ... so 1,000 numbers or 2,000 numbers, then it's going to send it to an IPv4 target. It's going to send it to a call manager. So check this out. I'm going to show you a little more detail of what's running in these dial peers. Show run pipe section dial peer voice. So I have got, actually here, dial peer voice 10 POTS. Destination pattern, 9 plus 7 digits. I point it to my analog port, and I say forward digit 7. So I'm telling it to strip the 9, because obviously that's an 8-digit pattern, and I only want to match a 7-digit number. The number 11, that's a 10-digit number. So you're seeing forward digits 10, plus the 9, of course. But we don't want to pass the 9 to the PSTN. You'll see my VoIP dial peer, which is a SIP dial peer in this example. I can do SIP or H323, and within VoIP dial peers, this one happens to be a SIP dial peer. So I'm creating effectively a SIP trunk to my call manager. You're going to see I've made a codec selection in there, G711 ULA. And then I've got dial peer voice 12 POTS. That's a long distance number, a 9 plus 1 plus 10. And that's going out my analog port, and you'll see forward digits 11. And then you'll see my incoming dial peer. That's 200. Incoming call number dot. Now, I want to tell you, you can use the same dial peer or dial peers as incoming and outgoing dial peers. There's no reason I couldn't have gone to dial peer voice 100 VoIP and said incoming call dot and not had to have 200. But I broke it out simply to make it a little easier to understand. So that's a good example of a production gateway. And actually, let me show you something pretty cool here. Let's do a debug. In fact, I may already have it enabled. Show debug. I do already have it enabled. Term mon. This debug is going to illustrate dial peer matching as I make a call to the PSTN. So I'm picking up a phone connected to this gateway, and I'm going to dial 9. And you see, called number equals 9. I'm going to say 1 614 555 1212. So you're actually seeing my dial peer evaluation process as it occurs as I try to decide which dial peers to match. And I did that slowly so you could see how the digit matching process works. On a voice gateway, digit matching and dial peer analysis happens as each digit is dialed. So the first match I find, I will take. I will use it. It is not the best match. It is not the most specific match. It is the first match. So keep that in mind. And you'll find that that's the opposite of how Call Manager does it. In Call Manager, we're looking for the best match. So, some differences there. We'll close the session here and show you one more example. This is a little different. This is a voice gateway with a PSTN connection on one side and a PBX on the other, a Call Manager. So we're going to have, again, let's assume PRI, and let's assume this is an H.323 connection. Call comes in from the PSTN over the PRI, and presents a a 4-digit DNIS. I dialed 2001. So what I'm not showing you here is this is a LAN, and out here off this switch there's a phone with extension 2001. I'm going to match this incoming call number dot, and I support direct inward dial. So the DNIS that was dialed, from out here on the PSTN, you had a guy with a phone, and he dialed 2001, presumably, routed across PSTN, hit my incoming call leg, matched this dial pair voice 1 POTS. And I support direct inward dial. So we're going to support single stage dialing. Next, I'm going to evaluate my dial pairs. So the number dialed was 2001. I see a match. Destination pattern 2001. That's a VoIP dial pair. You'll see it here. And the session target 10.1.1.5. That's the PBX out here, 10.1.1.5. So I've matched the incoming and the outgoing dial pair, and I connect the call. If the PBX wanted to make a call, he has his own dial plan that will send the call to me, and I'll match on an incoming dial pair. In fact, I'm going to match the same one because incoming call number dot. I'm then going to evaluate to make an outbound call. Now he had a 9 that he dialed as a prefix code for an external call. And actually, this is a really, really good destination pattern to use. This is more of a production quality pattern. 9, and then a digit of 2 through 9, and then 2 more digits, and then a digit of 2 through 9, and 3 more digits. So it's a 7-digit number, following the rules of the North American numbering plan. And it's porting to port 200 with a forward digits of 7. So we're going to strip that 9. So call's going to go out to the PSTN as 5551212. So there you have it. There's an example of a POTS dial pair and a VoIP dial pair on a voice gateway. So we've talked about a lot. We've gotten into a little bit more detail on dial pair configuration. You've seen some commands to show dial pair voice summary and the debug dial pair stuff that we can do. Again, essential tools in your toolbox when dealing with dial pairs and call routing within a voice gateway. In the next couple of videos, we're going to talk about some of these interfaces a little more specifically, some of the analog, FXO and FXS interfaces, and we'll talk about, some analog signaling techniques, and really start introducing, things like ENM to you, and, some more specific configuration related to these ports. So again, we're starting at the 1,000-foot view, and we're zooming in a little bit at a time. So with that, I'm going to say thanks for watching, and good luck with your studying. I hope that this has been informative to you, and I'll see you in the next video. Thanks, guys. Talk to you later. Welcome to the module on configuring basic ISDN PRI services. Thanks for hanging in there. I know we've done a lot of slide content through the last, 6 or so videos. We're hitting a lot of theory information, but we're going to change it up a little bit in this module, and we're going to get practical. We are going to configure ISDN PRI on a Cisco router or a voice gateway, And I'm going to walk you through various configuration steps to setting this up. We're going to actually place a call from an IP phone on a call manager and send it out a gateway and across the PRI and bring things into service. I'm going to show you some useful debugs and give you the all-around Nichols tour the ISDN PRI. Now, this is important both from a practical perspective as a voice engineer, but also for the certification exam. So Cisco's going to want you to know this really, really well, and you're going to use this day in and day out. So let's talk about ISDN PRI. So Integrated Services Digital Network is ISDN. ISDN's been around for decades, and primary rate ISDN is 23 bearer channels or B channels and 1 delta channel. And we use the B channels for supporting up to 23 simultaneous calls. The signaling for those calls occurs in the delta channel, and the audio is going to ride on the bearer channel. So we're talking standard, Nyquist theorem here. 8K times 8-bit sample rate equals 64K call. It's a physical T1. That's important to understand. The ISDN PRI is just a T1, and it's got an ISDN switch connected at one end and a PBX connected at the other. So physical T1 services. 24 time slots, 1 for call signaling and 23 for bearing the audio. And, that's kind of the high level. Now I'm talking domestic ISDN PRI here for United States. If you're in a country that uses E1 services, you're going to do ISDN PRI E1. And, pretty much the same thing. You've got additional time slots. But if you're living in the E1 world, you understand those things already. So no need to readdress it here. So let's jump in a little bit here and talk about the scenario we're going to mock up. Like I said before, I've got a Cisco phone. In fact, let me draw a switch out here. Here's a switch, and I've got a Cisco 8945 phone, and he's extension, 2001. And he's going to make a call to the PSTN. I've got my PBX configured with some dial plan logic so that we'll use 8 as an outside access code, and then we're going to dial, a 7-digit number. So, whatever route plan entry you want to use to do that. And I'm not going to go through that because it's a call manager thing. We'll talk about that in CIPT1. But we're going to send the call to the voice gateway. We're going to match an inbound dial peer. We're going to select an outbound dial peer that we're actually going to build on this video. It's going to be dial peer 500. Dial-peer 500 POTS. And we'll walk through that configuration. And it's going to send the call out this ISDN PRI circuit. And I happen to, this evening, have a ISDN or a PRI test set connected to my voice gateway. But if you're using an AdTrain Atlas 550 or a Cisco router as a PSTN simulator, or maybe you're lucky enough to have a real ISDN PRI at your disposal, those things will work identical to this. So, pick your tool of choice. I'm just using the test set tonight because it was within arm's reach of me. And so there you go. So here's what we're going to build. We're going to walk through this soup to nuts. I'm going to show you some debugs. I'm going to show you how to validate ISDN's working. And it should leave you prepared to support ISDN in your environment and be ready for the test. So let me pull down a putty session here. And we're going to take a look at this router I've got. This is my real PSTN gateway. This is what I'm using in my lab for access to the PSTN. And tonight it's going to be a simulated PSTN across this ISDN PRI circuit. If we do a show controller T120, I want to show you we've got a T1 and physical layers in service. We're not taking any errors. The circuit's clean, but it's just a plain old data T1 at this point. In fact, if I do a show run, you're not going to see anything PRI related. You can look at the T1. It's configured with B8ZS ESF for its framing and line coding, standard T1 stuff there. But let's go ahead and make this T1 an ISDN PRI. Now, the first thing we have to do on our voice gateway is define globally an ISDN switch type. And I'm going to say ISDN switch type ? And I want to show you a few options. Primary, 4 and 5 ESS, DMS 100, primary NI for national ISDN. These are choices that are common here in the United States. If you're, in the UK, you may be using a Net 5, etc. So lots of options here. We're going to go ahead and use primary-NI for ours. Now, depending what version of iOS and model of hardware you're using, you may also be able to set these there's been some changes over time. Some places you could send them both globally and in the serial interfaces. Some didn't quite have the same level of support. I'm going to set it globally because I only have one circuit connected here. If for some reason you have multiple PRIs from multiple providers, and I'm not going to get into all the other things you're going to think about relative to T1 timing and all those sorts of things, but if you have that, you may have different switch types to play with. So set one global, and then for the oddball, set it on the port. But I'm going to set it global, and it's going to meet the leads for this exercise. So we've set the ISDN switch type. Now we're going to go to controller T120, and I'm going to say PRI group time slots 1 through 6. I don't have enough DSPs to really bring a whole PRI up. Maybe I do, but I don't need to. So I'm just going to pick 6 of them on this device and hit enter. And that right there has defined an ISDN PRI on that controller. Now check this out. If I do a show run, I'm going to navigate down to a bit of code here that has just been created. You'll see this interface serial 20:23. Again, we've got ISDN switch type primary NI, ISDN incoming voice. That is a virtual interface that was created for our D channel, or our signaling channel for ISDN on this T1. And that's kind of what we're going to point at with our dial pair. So we've got ISDN. It's actually in service now. So if I want to do a show ISDN status, this is a great command just to give you a high-level view of how ISDN is doing on your router. So we're going to see ISDN serial 20:23. We're going to see the interface. ISDN switch type is primary NI. Layer 1 is active because the T1's up and in service. You'll see the state of layer 2 is multiple frame established. If you see multiple frame established on an ISDN PRI, you are golden. That means that the D channel has negotiated with your hardware, and the circuit is up and in service and ready to place and receive calls. Layer 3 status, we've got 0 active calls. Obviously, I'm not on the phone right now because I'm talking to you guys. But, that's pretty much the what's going on. Now, if for some reason this circuit were down, in fact, I'll go ahead and simulate that by unplugging my test set right now. If I run a show ISDN status, you're going to see, in this case, the T1 is down, so layer 1 status is deactivated, and layer 2 status is TEI assigned. So you're going to know something's up. I'll go ahead and plug it back in here, and awaiting establishment, and run it again, multiple frame established. So PRI is good and ready to go. Now, we don't have any dial plan right now in the voice gateway to support this PRI. So here's what I'm going to do. We're going to go config T, and I'm going to say dial peer voice 500 pots, and I'm going to say destination pattern 8 ... So 7 digits, and that's not an overlapping pattern in my dial plan, so I can get away with a simple dial peer like that. And we're going to say port 20, and I think I need to go :23. There we go. So we've pointed it at our D channel, and really that's enough for an outbound call to take place. So check this out. ISDN has 2 useful debugs. Show ISDN, debug ISDN question mark, Q921 and Q931. If I do a Q921 debug and go turn them on, you're going to see layer 2 messages for the ISDN circuit as they occur. And, a lot of this is going to happen, when I bring the thing into service. But, we're going to see some, transmit, receive data here, etc. Good indication of what's happening at layer 2. I'm going to go ahead and turn that off and show you a debug that is much more frequently used for me anyway, and that is debug ISDN Q931. Now Q931, this is my layer 3 debug. This is going to show me what's happening. It's going to show me the call setup, the messages, the who's calling, where am I calling, all the good stuff. So let's sit back and let's make a call from my call manager. It's going to hit the gateway. It's going to match that outbound dial pair. Obviously, it's going to match an inbound dial pair, but that's beyond this video. We're going to match that outbound dial pair that we just created, and it's going to ring the phone. And you should hear it ringing here on the desk. So I'm going to pick up my phone, and I'm going to say 8555123 And you can hear it ringing. You can hear my test set here ringing in the background. I'm going to go ahead and answer that call. It's going to take me just a second here and hit answer. And answer speech. Here we go. that call is now connected. In fact, if I get a little closer to my phone, you may hear a slight echo in my voice. So the call's connected. In fact, you can see a connected state on the screen. And in fact, I'm going to go ahead and hang it up here in a second because I'm going to get a heterodyte if I don't. But, you know, right there, that's basic ISDN PRI. We placed a call. So calling party number 2001, that's the extension on my IP phone. Numbering, plane, and type and use is unknown, unknown. So that's correct. That's what's showing up here. We're going to see the called party number of 5551234. That's the digits that my dial peer passed to the PSTN. And, you know, that's exactly what I wanted as well. In fact, that's a good example. You'll notice my dial peer said 8 ... Why didn't I pass the 8? I didn't pass the 8 because I automatically strip the specific digits when doing a wildcard match. So only the dots got passed, which is exactly what I wanted. So that is a perfect example of an ISDN PRI call that was successful. In fact, you'll take a look down at the bottom here. You're going to see the disconnect cause, normal call clearing. So, you know, that is fantastic. Call lasted 15 seconds. We've got a lot of good information here. We brought up an ISDN call. Now, let me show you a few other things about ISDN. You know, we've shown you how to take a look at the ISDN status. I want to show you a show ISDN service command. Show ISDN service. This shows you the state of the individual bearer channels. Now remember, I only programmed 6 of them because of, you know, limitations of DSP resources on this hardware. You'll see that the channel state and the service state for those 6 B channels is reflected. You know, the channel state is idle, and the service state is in service. Idle and in service, that's a great indicator. If you look at the channel state on the ones I didn't program, it says reserved, and the service state is out of service. So that's, you know, that's perfect. It matches up great. Now, normally on a full PRI where you're using all the time slots, you know, those will all be zeros across the bottom, which is what you want. Now, if I make a call, check this out. I'm going to go ahead and make that call again. I'm going to say 85551234. We're going to let it ring. It's going to take me a second to answer it here. Answer speech. All right, the call is up. I'm going to run that same command, show ISDN service. And, you know, again, everything looks good. No problems. We're connected. And, you know, it gives you a good idea of what is happening. Now, take a look at channel 6. We've got a 2 instead of a 0. So let me hang this call up and we'll get rid of the heterodyne. The 2 says busy. So it shows you that it's on a call. So that's awesome. So we've got show commands for ISDN. We've got debug commands for ISDN. You've seen the both of them. Let's see, what other things do you need to understand about ISDN PRI? I mean, really, that's the high level right there. You know, MGCP, if you're doing MGCP as a gateway protocol, and we'll cover this more later when we get into Call Manager, but understand that your PRI D channel is actually going to backhaul all the way to Call Manager. And I'm actually using a SIP trunk to my Call Manager from this gateway, so I don't have to worry about that. Oh, I know what I wanted to show you. There's a cool command when you're testing out a voice gateway, and it's called CSIM. This is one of those famous yet undocumented commands from Cisco. CSIM is a call simulator. I'm going to actually type CSIM start, and I'm going to type the number 85551000, and I'm going to hit enter. Did you hear that? And you see the debug. I've actually told my gateway to make a call. Now I can answer it on my test set there. It's connected. Obviously, there's no audio stream coming because there's no other endpoint, but I forced the gateway to make a call all by itself. And in fact, I'll go ahead and I will hang that call up here. But it's a useful command, and really that's all there is to it. You know, use it and enjoy it. So we've hit the high level here. This is a very practical example of ISDN PRI on a Cisco voice gateway. Yeah, really, that's it. I'm going to go ahead and stop there because there's no reason to hit anything else. So we're assuming in this video that you have basic T1 fundamentals down. You know, we talked about a lot of those concepts and time division multiplexing and all that good stuff in the CCNA voice. So, you know, I think you've got a good handle on what Cisco is going to expect you to be able to handle. Obviously, there's more advanced topics, and there's other things you can do with ISDN. You know, there's something called NFAS, or non-facility associated signaling. And what NFAS is is it's a method that's going to allow you to share 1D channel among multiple ISDN PRI circuits, and just kind of squeak a little additional capacity out there. So really, that's what you need to know, and we're going to stop it right here. I'm going to say thanks for watching. Good luck with your studying, and I will see you in the next video. All right, we've made it to the analog part of the lecture here, and we live in an analog world, and there's a lot of what we do with telephony that is because of the way things have always been done. And as we talk about analog services, we're going to talk about some of these fundamental techniques that we've been using kind of since the beginning of time, and they're going to be a major part of the foundation. You're going to need to understand how these environments work. So I'm kind of rambling here. This is going to be long enough that I know even right now, before I've even recorded the other parts, this is going to be a multi-part video. I'm thinking 2 or 3 parts, so we'll see how it lands when I get through it. But this is part 1 in configuring basic analog voice services. Now, when we talk about analog services, there's really 3 categories of analog services, or 3 types of analog services you're going to run into: FXO, FXS, and ENM. Now, let me draw a couple of pictures here. FXO and FXS can be described, if I draw a voice gateway, and I take one analog line, a POTS line, to the PSTN. This interface right here is called an FXO interface, Foreign Exchange Office. On an FXO interface, voltage is provided to the equipment by the line. So the PSTN, or the central office, is providing me voltage to the voice gateway's interface port. FXS, or foreign exchange station, if I were to take an analog phone and connect it to this voice gateway, this port is an FXS port, or a foreign exchange station port. The voice gateway is providing voltage to my station equipment, or my analog phone. Now, ENM, this isn't so much, a phone to PSTN kind of thing as much as it is, but when you start dealing with PBXs, so I could have a PBX, and I could have the PBX either connected to the PSTN, or one PBX connected to another PBX. These are the types of places where I would likely run into ENM signaling. And ENM, either ear and mouth, earth and magneto, you may have heard some variations on the phrase there. But FXO and FXS is pretty much where we're going to spend our time here, but you do need to understand the existence of ENM and a little bit about it. So we'll dive into this as we go. And I'm going to step back here in a moment, and we're going to take a CCNA voice look at analog signaling and analog circuits and how it all works. And if you took my CCNA voice course, you'll recognize some of these slides. And then we're going to deep dive a little bit. So when we talk about analog signaling, we've got 3 types of signaling. We've got supervisory signaling, which is responsible for telling us, hey, something has changed. Like, hey, guess what? The line went off hook. Somebody wants to place a call. Or hey, we hung up. That's a disconnect. So those are supervisory signaling. Addressing, this is about passing digits. Where do I want to call to? And then informational signaling, this is, I'm notifying the user of some status. So I place a call, I get a busy signal. That, or I get a reorder tone, or, something like that. That's an informational signaling message. So 3 types of signaling, and when we deal with supervisory signaling, you're going to see 2 types mentioned. You're going to see loop start, and you're going to see ground start. And with this, let's take a step back to the CCNA voice content that we went through and talk about. In the beginning, there was analog. I love saying it that way. So analog waveforms, or the stuff coming out of my mouth when I talk, it's rippling through the air and being captured by my microphone as an electrical signal. I'm then going to send that electrical signal over the PSTN, a pair of wires, and it's going to get where it's going. Now, fundamental concept here for analog circuits is the concept of tip and ring. Tip and ring dates back to manual switchboards when the PSTN was in its infancy, and we have used a lot of stuff hasn't changed really. It's kind of sad to say, but we've used this technology for some time now. And the way tip and ring works is we use these two lines to carry our audio conversation as well as to deal with some signaling. So normally a tip of the plug is going to be at ground potential and the ring is going to be at a negative 48 volt DC nominal potential when you're in an on-hook state. And you can hit the Wikipedia link there at the bottom for some additional information on tip and ring if you'd like. When we talk about loop start signaling happens when a handset is lifted and the circuit is closed. So closing a circuit means completing a circuit. So normally when I'm just sitting there with a phone and I haven't made a call, I haven't picked up the handset, the circuit is open and it is not closed, which means it is not connected. Basic electrical theory there. When I lift the handset, the circuit is closed, making a complete circuit or completing the circuit. And what happens, in fact, we'll dive into that here in a second. I'm not going to get into what happens yet. Loop start signaling is the most commonly used signaling method for dealing with standard analog phone lines. So when I say standard analog phone lines, I'm referring to things like residential service or, hey, I got a really small business, can I have 3 POTS lines? So this is loop start connections. One of the problems, in fact, the most significant problem with loop start signaling is that you can run into a scenario called glare. And if you think back to glare, you'll remember that glare is an event that occurs when an inbound call and an outbound call try to seize the analog line at the same point in time. So when the CO tries to send me a call at the same time I'm trying to place a call, and I pick up the handset and I'm not getting dial tone, but I hear someone going, hello, hello, and we're connected, but my phone never rang, and I didn't know they called me, and they're not sure what's going on either. That's glare. Because of the low volume of calls on an analog or a residential analog circuit, glare is not a huge problem. It happens once in a while, big deal. Do we really need to do anything about it? Yeah, not really. So, low volume calls, loop start signaling certainly can work. Business phone systems where call volume is higher are much more susceptible to the effects, and the negative effects anyway, of glare. So what do we do about it? In fact, let's not say what we do about it yet. Let's get into a little more detail. So let's talk loop start. And I have to give credit to some others out there. I've seen this drawing done a few different ways in the past. In fact, as it was explained to me in the beginning, how loop start signaling really works. So let's draw this as we represent a phone, and we'll call this the calling party. I like that phrase. And then we will draw a CO switch. And really, this isn't necessarily representative of just a switch, but the PSTN as a whole. And then the called party. So, party, another phone. And if you remember, we talked about tip and ring. Tip and ring. So we've got 2 phones. We've got a line from each phone to the central office. How does loop start signaling work? So let's start with both phones on hook. With both phones on hook, the circuit is open. You'll notice that tip and ring are, they're just kind of floating out there. They're not connected. When you pick up a handset, the phone is going to close the circuit or complete the connection, and it's completing the connection with your audio, your microphone. There's other electronics here at play, but your audio insertion, you're becoming the thing that makes that connection. So this is where we're going to obviously send our audio down the PSTN, but we're going to close the circuit. Now, when we close the circuit, you'll remember that with FXO connections, which is what this is, the PSTN is providing loop current. Now,
what's going to happen is the CO switch, as we draw, let's draw current, C-U-R-R-E-N-T. As we draw electrical current, the CO switch is going to recognize, hey, he's drawing current. That means he went off hook, and he's going to assume that I've gone off hook and I want to dial a number. So he's going to play dial tone to me. So that's how dial tone works. Now, I'm going to respond to that dial tone by punching in digits and DTMF tones, and those tones are going to be sent to the CO switch, so DTMF, and he's going to parse them, figure out where I'm going, route my call, and ultimately at the other end, he is then going to send a ringing voltage to the destination phone. So he's going to send ringing voltage on the tip, so we'll just say ring, to this phone. Phone's going to ring. When it goes off hook, we're going to close the circuit again, and our call is connected. So that's pretty much, the call setup process with loop start signaling. Now what you'll see here, and this is where the glare issue comes from, is there's no way for me as the calling party to tell the CO switch that I'm ready to make a call. Is it okay if I do so? Or in other words, are you getting ready to send a call to me, or is it okay if I use this line? So that's the what's missing. That's the glare component of things. So loop start signaling, it's not going away, has some limitations. Glare is one of them. Disconnect supervision, knowledge of when the phone has hung up can be another issue. If the far end, the called party hangs up, there's no way for the CO switch to signal my phone that I've had the other guy hung up, so so that I know to hang up. But I know because he said goodbye. But anyway, that's loop start signaling. Ground start signaling, which came about with payphones, etc., is a way that we deal with the problem of glare. So when we utilize ground start, we have a little different kind of signaling occurring here. We actually do grounding of tip, grounding of the ring, etc., to inform the other guy what's happening. And we'll do a sketch here in a minute. Ground start circuits are not susceptible to the same glare problem that loop start circuits are, because we have this way of signaling the CO switch, I'm ready to make a call, and it has a way of signaling me, I'm going to send you a call. So we deal with that problem. So ground start signal, and let's see if we can do this justice with a photo here. So ground start's typically going to be between a PBX and the central office. It's not going to be just a standalone phone. So we'll draw a little bigger here. We'll say PBX, and then we'll say CO. So again, we've got this tip and ring going on here. We'll say tip and ring. So when I want to make a call from my PBX, my PBX is going to signal the PSTN that I want to make a call. And I'm going to do that by grounding my ring line. So what's going to happen is I'm going to ground the ring like that, connected to ground potential, 0 volts. The CO is going to detect that I have grounded my ringing line, and he is going to respond by grounding his tip. Boom, ground. So we have a handshaking that occurs, and I actually drew that backwards. You see the monitoring of it. So I observe that ring was grounded, and I observe that tip was grounded. So we've got a signaling here that a call setup is wanting to take place. And obviously when when the call actually takes place, then we close this loop again, or close the circuit, just like we would, electrically it's the same thing happening, but we've got a little bit of a handshaking process here with ground start signaling. So ground start solves the glare problem. Ground start gives us a way of doing disconnect supervision, so I know when the other guy hung up because my status is going to go back to the way it was before I had a call. And that's really it for part 1 of the video here. We're going to, in the next section, we'll talk about DTMF a little bit. We'll talk about call progress tones. We'll touch on ENM briefly. ENM, we've got immediate start, wink start, etc. So we'll hit on it briefly. And in the third part, we're going to actually do a little bit of configuration on FXO and FXS interfaces and give you an idea what that's like and what's necessary to make the stuff actually work. So with that, we're going to stop in on part 1 here of the analog stuff. Let's call it the analog stuff video. And I'll see you in the next video. And thanks for watching. Good luck with your studying, and I'll see you soon. All right, welcome to part 2 of configuring basic analog voice services. And in the first section, or the first part of this module, we talked about fundamental concepts relative to FXO and FXS and ENM. And we really dived in pretty deep into the FXO, FXS, but we didn't touch on the ENM stuff as much as we need to. So we're going to talk about ENM in this video and get through the theory part of it. Really, there's not a whole lot to worry about, but I do want you to have a good understanding of this for when the time comes that you're taking your exam. And then finally, in part 3, we're going to get into some configuration demonstration and lab it up and show you exactly what it takes to configure these voice ports. So on to part 2 of analog. We talked about supervisory signaling in the first section. And now, as I mentioned before, there's 2 other types of signaling on an analog circuit. We've got address signaling and informational signaling. So let's talk about address signaling. The first type of address signaling that we had was what we called rotary or pulse dialing. And basically what you had is you had a phone with a wheel. In fact, you've seen these before. And you'd spin the wheel, and it would go click, 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 and it would count the pulses, and the switch would ratchet your car. Well, that's long gone. Thankfully, that is done and over with, and we're living in a DTMF or a tone-based dialing world. Now, DTMF, dual tone multiple frequency, is a audio signaling mechanism that uses, just like it sounds, dual tones. And I'm going to show you a chart here of all of the buttons on a DTMF keypad. 1, 2, 3, 4, 5, 6, 7, 8, 9, asterisk 0 pound, or the hash symbol if you're in the UK. But anyway, what happens when you press O1 is we play the 697 hertz tone and the 1209 hertz tone simultaneously. And that's why the tones sound kind of weird, when you play them. It's not just one noise. It's like there's a couple of noises happening, because there are. In fact, DTMF5, for another example, is 770 hertz and 1336 hertz playing at the same time. So this is a way for us to send a representation of a key. In this case, we've got 12 of them. In fact, there's some other keys that we don't commonly use, and I'm not going to get into those crazy. There's like an A and a B, etc. But DTMF. So that's address signaling. When we talk about informational signaling, we're going to talk about CP tones, or call progress tones. Now, call progress tones are used to provide some feedback to you, the caller, on how a call is progressing. It sounds straightforward enough. And again, we're going to show you a chart. And this is different from country to country, so I want you to consider that. This chart is the North American CP tones. Consult your local chart, based on the country you're in. So when I pick up the phone and I hear a dial tone, I'm actually hearing a DTMF, combination of audio. I'm getting a 350 hertz and a 440 hertz tone. Now, it's continuous, so you'll see off time and on time, is listed as continuous, because we just get the, and in fact, let me see if I can get one near a microphone here.
There we go. So that's the DTMF for a dial tone. Now, if I place a call and the called party is busy, I'm going to get a busy signal. Let's see, 480 hertz and 620 hertz frequency. Now, it's going to be an alternating series of on, off, on, off, on, off. So the time between tones is going to be a half a second, and the time that a tone plays is going to be half a second. So that's a busy. Now, if you go down to the reorder tone, you'll see 480 and 620 again, same tones, but the tone time is 0.3 seconds, and the time between tones is 0.2 seconds. So that's the fast busy signal we're used to. So you've got the busy and the reorder tone, which we call the fast busy. You've got a ring back, you've got the receiver off hook. You know, the receiver off hook, have you ever walked away from the phone, set it down, and you hear it going, eh, 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 eh? That's a really bad impersonation, but you know exactly what I'm talking about if you've ever experienced it. It's a really annoying, shrill kind of tone. So we've actually got 4 different frequencies playing at you, in very fast, fast repetition. So 0.1 seconds of on and off time. So those are CP tones, or call progress tones. Now, when you're configuring voice ports on a Cisco voice gateway, let's say I'm configuring an FXS port, I'm going to configure it to mimic the CP tones for the country that I'm in. So I'm in North America, I'm in the United States, so those are the CP tones that I'll use. But I can actually change the CP tone country and use somebody else's CP tone. So if I want my dial tone to sound like a United Kingdom dial tone, then I can do that by setting the CP tone. And we'll get into that as we get into demonstrations in lab work of configuring the FXS ports on the Cisco gateway. But this is called progress tones. I want you to understand what they're for and understand that they're using DTMF. All right, so E&M. You're not going to run into a tremendous amount of E&M signaling in the wild. That doesn't mean it's not there. It just isn't as popular these days as it was historically with traditional PBXs. So E&M signaling, ear and mouth, earth and magneto, etc., depending on which version of the description you subscribe to, is most often used from PBX to PBX, or a PBX to an ACD, or a PBX to an IVR, something where it's system to system. There are different types of E&M signaling. The most common type of E&M signaling in North America is E&M type 1, while the most common type outside of North America is type 5. And different E&M physical interface types utilize either 2 or 4 wires for the signaling behavior. So on an E&M type 1, I've got 2 wires for audio and 2 wires for signaling. So I've got the audio path, which is a pair, and then I've got an E wire, and I've got an M wire. Now on E&M type 2, I've got an E lead, an M lead, and then I've got an SG lead, which is signal ground, and an SB lead, which is signal battery. And you'll see different variations on the theme here. So when I say 2 wire, it's 2 wires for the signaling. So it's, an E&M type 1 is actually 4 physical wires, 2 for the audio path, 2 for the signaling. So you've got 4 wire and 6 wire connections here, but we refer to it as a 2 wire or 4 wire. So how's that for confusing you? Again, there's some other signaling types out there. It's important to make note that E&M type 4 is not supported by Cisco gateways, and they're very very vocal about that. I, in the wild, have very infrequently run into E&M and as a physical interface in modern systems. We use E&M type signaling on T1 CAS a bit, and we're basically taking the analog representation and doing it in a digital way. And you'll learn more about that as you get into CAD stuff. But at a high level, understand this chart. Understand E&M type 1, most commonly used in North America, and E&M type 5 is most common outside of North America. And know the other types. With E&M signaling, we have 3 different what I'll call start types. And the start types have to do with the the address signaling. So immediate start, this is very similar to loop start. And basically what happens is with immediate start, the calling party is going to seize the line. They're going to go off hook by bringing the e-lead off hook. And then they're going to wait for a period of time. Now that period of time, at least for where I'm at, is 150 milliseconds. So they're going to wait 150 milliseconds, and then they're going to do their thing and use the line. So really there's no handshaking taking place. It's more of a, okay, here I go type of behavior. So that's immediate start. Now, just like loop start, there was really no handshaking taking place. So guess what I'm susceptible to? Yes, I am susceptible to glare. E&M wink start is by far the most common E&M address signaling method used. And wink start basically is going to give you a handshaking capability. So the calling party is going to go off hook on the e-lead, and then it's going to wait for a wink or a temporary pulse sent from the other end on its M lead before sending the DTMF digits. So it's kind of a, are you ready? Yes, go type of a signaling. So wink start, the most common. Now there's one more, and that is delay start. Delay start is used mostly for tie trunks, and the calling station is going to go off hook on the e-lead, and then after a period of time, the calling side is going to look at the status of the called side and then make a decision for routing based on whether the called side is on hook or not. So tie trunks for that. That's the foundation you're going to need to understand for E&M for the C-Voice exam. Nothing too crazy here. We didn't get into anything kind of at the electrical signaling level all that much. We did talk about SG and SB and E&M lines and those types of things. But Cisco's, they understand, they realize that this is legacy and not prevalent anymore. But there's E&M. So this is it for video 2 or part 2 of module 8. So we've covered FXO and FXS and signaling types, and we've covered E&M. And in video 3, we're going to go through and do some configuration of some FXO and FXS ports, and we'll show you how to program CP tones and how to do some basic dial peer configuration to use an FXO or FXS line. So with that, I'm going to say thank you for watching. Good luck with your studying process. I really appreciate you tuning in there and hanging in there with us as we go through these modules. I know this is a lot of information to kind of take in at once, but you're well on your way to preparing for the Cisco C-Voice exam. So I'll see you in the next video in part 3. All right, part 3 of configuring basic analog voice services. We've made it, and I'm just going to jump straight into it here and give you guys kind of the what is. So we've talked about basic FXO and FXS logic and theory. Now it's time to do some programming. So my lab is always changing, and I'm always adding a piece of hardware, removing a piece of hardware, etc. And, I'm not even sure which gateway I'm on right now. Chauver. We are on a 3725. You'll see that I've got 2 voice FXO interfaces and 2 voice FXS interfaces installed. In fact, we'll highlight them right here. So we're going to demonstrate provisioning of both. So I've got an analog phone, an FXS interface here. And I'm going to try to kick my gain up just a little bit so that you can hear the sound it makes when I'm holding it up to the microphone. It's a little tough to capture. But let's go ahead and configure a FXS port on a Cisco router. Now, the first thing you're going to find out is there's very little to configure for basic FXS functionality. I'm going to do a show run here. I'm kind of show you what's going on. This is actually my PSTN gateway that I'm using, and I've actually got an FXO port in it connected to what do you call it? A Magic Jack Plus, and I'm using that as a it's a SIP trunk basically, and I get PSTN access from it for crazy little money. Comes in great for lab purposes. But I've also got a POTS phone connected here to port 110, and you'll see voice port 110, and it's got absolutely nothing configured. And really, if I pick the thing up, in fact, let me do a debug here. Term mod debug. Oh, which one do I want to use? VPM all. I'm going to take it off hook, and you're going to see the results of me taking it off hook. And I'll go ahead and put it back on hook, and you'll get a little debug output there. So I've got a phone hooked up. In fact, if I want to make a call, I can. In fact, let me kick this gain up here just a little bit, and we'll make a call. And you can see exactly what happens. And actually, for whatever reason, that call wasn't routable. But you kind of get the point here. That I've got an FXS line connected to an analog phone. And I attempt to make a call, and I match dial pairs, and everything that's supposed to happen happens. So yeah, that's just really simple. Now let's talk about the unique stuff on an FXS port. We talked earlier about CP tones. Let's do this. Let's go to the voice port. Config T. Voice port. What did I say it was? 110. CP tone question mark. I've got a list of locales, and I can select the locale for wherever I want this to seem like it is. Let's go ahead and pick let's see here, I'm looking through the list here. How about the United Kingdom? CP tone GB. Now, when I take the phone off hook, let's listen to it. Here goes. Actually, that sounds like the US. Let me find one that's kind of weird. Now, I should have done this ahead of time to see what I like, but here we go. It's kind of a weird one. A little different off-hook tone there. Let's see what the Pakistan CP tone sounds like. Here we go. Ready? A little different. There's got to be a really, really goofy one in here. I wonder what Zimbabwe sounds like. Whoops. Config T. Voice port. CP tone ZW. Let's see what Zimbabwe sounds like. Another hum. Once you've heard one hum, you've kind of heard them all, I guess. But anyway, I'm changing the call progress tones by using the CP tone command. We'll go ahead and set it back to US because that's where I'm at. And by changing the call progress tones, we're going to change the DTMF behavior that occurs. Other things I can do is I can manipulate ring cadence using the ring cadence command, and you can see patterns 1 through 12. 2 seconds on, 4 seconds off, or 1 second on, 5 seconds off, or 1.5 seconds on, and 3 seconds off. So we can change how this FXS interface rings. In fact, now I'm going to stop there. I don't want to go too far off track. So that's a couple of cool things you can do on an FXS port. Let me show you a few other things that you can do on an FXS port. We can configure comfort noise. And we can turn that on or off. No comfort noise. We can mess with, what's a good one here? I'm just staring at it. Let's see what jumps out at me. Yeah, there's not anything really jumping out at me. I mean, the FXS ports aren't all that exciting. The FXO ports are where we can really do some cool stuff. But let's see here. Here we go. I know one thing I should show you. Signal. This is where I would specify loop start or ground start. So on this FXS port, if I wanted to behave in a ground start fashion, I could do that, or obviously the default is loop start. Let me show you what we've got going on here. Show voice port 110. Again, this is that FXS line. You can see that I'm FXS 110. You can see that we're in the up state. You can see that our, let's find it here. Here we go. Our signal type is loop start. You can see that our ring cadence is currently defined by the CP tone selection. So a lot of useful information here. Again, like I said before, it's FXS. There's not a whole lot to get excited with. Now, FXO, a lot of cool stuff you can do with FXO lines. So I mentioned before that I've got an FXO line connected to a Magic Jack Plus. So basically, I get a what would be a POTS line, like I ordered a phone line from the telco, and I plug it in to my Cisco router on the FXO port. And if I do a show run, we'll show you it's going to be this voice port 100. And voice port 100 is configured with something we call PLAR, Private Line Automatic Ring Down. And what PLAR does is when someone calls me on this line and it rings, the line will automatically answer on the gateway. It'll go off hook in response to that incoming ring. And it will then place the next leg of the call to a destination of 2001. Now that's going to have to evaluate my dial plan. Show dial peer, no, not show dial plan, show dial peer voice summary. Good command for that. You can see all my patterns, and I've got a 4-digit pattern pointing to my call manager, which then rings my phone. So if I actually were to, in fact I will do that here in just a second, call, I'm not going to say this out loud because everybody will be calling me here in the lab, 614, I'm going to hit the call button, and you should hear my phone ring. And the reason for that is because of PLAR. Actually, I'm sorry, it rang through the voicemail, but no worries there. But anyway, I've got inbound calling, outbound calling on this FXO port. Now, this particular FXO port is a loop start connection, but just like the FXS port, voice port, I always forget whether there's a dash or not, 100, question mark, a lot of the same settings. We would go to, let's see here, signal, and I could, again, ground start, loop start, pick whatever I wanted. And, pretty straightforward stuff. We've got dial peers that will send calls to a given port. In fact, it'll take me a second to mock this up, but I should probably do it for you. Let's see here. Show dial peer voice summary. Let's find a good one. How about 300? Dial peer voice 300 POTS. And we're going to say destination pattern 5000. Okay? And then I'm going to say port 110. This is my FXS port. So, if I were to place a call to port 5000 or extension 5000, I would evaluate and match a dial pair, and you can now hear the phone ringing here in the background because I made that call. We'll go ahead and answer it and hang it up, and that'll finish up the call simulation there. But that's how I point a call to a voice port. So if I've got a fax machine, and I want to point a DNS to the port where the fax machine's plugged in, I can do that. If I want to have a PLAR connection, maybe I want a phone to be a hotline phone, a hot button phone.
I can go to an FXS phone voice port. In fact, I'll do it just for the heck of it. Voice port 110 connection plar, and we will say, what's a good number to use? How about 2001? I will pick the phone up, and I didn't dial anything. I just picked it up, and now you can hear in the background an IP phone ringing. So I basically made that a hotline phone or a bat phone, so that if you pick it up, it automatically makes a phone call. Whoops, config T, voice port 110. Let's turn plar off, and now it's back to a normal phone again. There's really not anything else I need to show you about FXO and FXS ports. They really are that straightforward, and you're going to use a lot of these. You're going to find that hanging fax machines off of a router is very convenient, and you're going to find that in a warehouse you may have a run for a phone that's in excess of the 328 feet or 100 meters of Ethernet, and you're like, yeah, let's just run a twisted pair out there, Cat3 for a phone, and put an analog phone out there, run it to a gateway. All of these things are very much things we do day in and day out in production environments. So configuring FXS and FXO, at least basic configuration, is something you definitely want to be familiar with. And I showed you a good debug, the debug VPM. Let me show you a couple options there. Debug VPM ? We've got all, or we can look at DSP information, or we can narrow it down to a specific port. Very, very useful commands. So I'm going to stop there. This was meant to be a really short and sweet lab on FXO and FXS. And hopefully that is giving you a little bit of an understanding of how to configure FXO and FXS. If you've got access to some E&M interfaces, you're going to notice that the configuration is pretty much the same. You're going to specify a type. So whether type 1 or type 5, and you're going to tell it whether it's 2-wire or 4-wire, etc. But other than that, configuring these things is pretty much exactly the same. So with that, I think we're pretty much wrapping up with analog services. There's a couple of other analog things out there you may run into. There's these things we call camera trunks, which are used for 911. But again, they're configured exactly the same. You may find that there's a bit of anti-mapping that you do. Some unique stuff for camera trunks. Where I'm from, I don't run into camera trunks really. For the most part, we send our emergency calls just down a PRI or a POTS line. So it's one of those things that kind of varies from region to region. You may find yourself using what we call a DID trunk, or a direct inward dial trunk. Now, we've already talked about configuring PRIs, and you understand how DNIS is presented. You can have multiple numbers point to a single physical circuit, etc. Analog DID trunks kind of smell like a PRI in fact that you can have multiple numbers writing or using the same physical facilities. But one thing that's kind of backwards about an analog DID trunk is, unlike an FXO line where the CO switch provides the ring voltage or the line voltage, on an a DID analog line, it's actually backwards. It's more of like a PBX functionality where your Cisco router is going to provide the power. So kind of a weird service. I've seen it used for fax in the past, but it's one of those things I've only run into a time or two in the last decade. So we're not going to dig crazy deep into it because you'll probably never see one. And if you do, have fun. It's really not all that different from everything else that we're doing. So we're going to talk a little bit about T1 CAS and how CAS works in the next video. And we've already talked about PRI, so I think we've got that covered pretty well. We'll go ahead and get into some additional debug commands and troubleshooting commands that may be useful with you. We'll talk a little bit about cross-connecting DS0s, which is kind of cool, being able to use some of the multiflex trunk cards. And Beyond that, we're ready to start talking about digital signal processors. So with that, I'm going to leave you to your labs. Please take the time, set some of this up. Do like I do. Get into it and just poke around. Make a phone ring. Implement, one feature, then turn around and, rip it out and do something different. Play with the CP tones and see what, Uzbekistan sounds like when you call there. See what, New Zealand sounds like, or, China, or, any of these other locations. But have fun with it. It's important that you play with the stuff. Listening to me lecture is going to only take you so far. Reading the book is only going to take you so far. Watching my videos is only going to take you so far. You really need to get into the gear, get your hands dirty, and play with it. So with that, I'm going to leave you to it. Thanks for tuning in, and good luck with your studying, and I will see you in the next video. All right. So, Module 9, Understanding and Configuring T1 CAS Services. This is kind of a little bonus that I want to make sure we cover as part of the C-Voice curriculum. Now, obviously, Cisco wants you to know T1 CAS, but, in all of the CCNP voice material I've seen, time and again, I really don't think that justice has been done to describing T1 CAS, and at least not in the video world. I think Cisco Press has done a pretty good job with it in some of their publications, but I want to walk you through it. I want to show you how it works, and we're actually going to place some calls using T1 CAS and really kind of bring things full circle. So let's talk about T1 CAS. Channel Associated Signaling, or CAS, it's a data T1 with 24 DSOs for voice, but unlike a PRI where the signaling is handled in a channel of its own, or what we call common channel signaling, CAS is channel associated signaling, which means robbed bit signaling. In fact, you'll hear the phrase robbed bit signaling, or RBS. And what's happening, and I'll show you visually here in another slide, but what's happening is we're actually stealing some space or some data from frames that would otherwise be used, and we're putting our signaling information inside them. But we'll show you a visual. It'll make a lot more sense. Now, keep in mind, this is a digital circuit. However, it's using analog signaling methods. So you can use loop start or ground start or ENM. In fact, the example I show you, we're going to be using ENM Wink. Now, there are 3 signaling types that are common. Obviously, there's others. You get into loop start, ground start, etc. But when you start talking about the ENM signaling types, which is what you're most often going to see on a T1 CAS, you're going to be looking at things like ENM feature group B, or feature group D, or the ENM version of feature group D. And what I want you to see, and really you don't need to memorize this chart, but understand that different ENM feature groups offer different capabilities relative to Annie and DNS, and we show some of the differences here within the slide. So when we talk about T1 CAS framing, or ESF, the extended super frame, I wanted to break it down for you and show you what's really happening. So with an ISDN PRI, we've got 23 voice paths and 1 delta channel that's used for signaling. So in CAS, we're doing things differently. So you already know that a T1 has 24 time slots. And you probably already know that each time slot is 8 bits of data. What you probably don't know, or what you may not know, is that with T1 CAS, or with robbed bit signaling, every 6th frame is, or every 6th, we'll call it that, every 6th frame is being subject to borrowing a bit for framing. So frame number 6, 12, 18, and 24. Or really, I can say data for time slot 6, 12, 18, and 24 is going to be just a little bit different. So a standard time slot, and we showed time slot 11 there. There are 8 bits for voice in that time slot. Now, 6, 12, 18, and 24 are a little bit different. We actually drop the least significant bit, or we steal it, we rob it, for signaling only leaving 7 bits for voice transport. So RBS, hopefully this visual helps you a little bit. Very common, not as prevalent as it used to be. If you're ordering new service from the PSTN, from your carrier, you're not going to be ordering T1 CAS. You're going to be likely ordering either ISDN PRI or, even more modern, some kind of a SIP trunk. But you're going to use T1 CAS for interconnections between PBXs and other PBXs and ACD systems and IVRs. So CAS is important to understand. I want to demonstrate to you, in fact, let me pull it down here from my PSTN gateway, the configuration of a T1 CAS circuit. And it's really quite straightforward. It's actually a little bit easier than setting up a PRI. The debugging is not as intuitive, but you can certainly handle this. So if we do a show controller T1, you're going to see T120 is up. And actually, yeah, everything's, I'm taking some slips, but we're not going to let that really bother us here. I'm going to go config T and say controller T120. And I'm going to say DS0 group, and I can give it a number. We'll call it group 0. Time slots 1 through 24. And I can specify the signaling type. Now, you can see here we've got that FXO and FXS loop start and ground start and a bunch of ENM variants. More often than not, including my example, you're going to be using ENM wink start. So we've configured ENM wink start. And you'll see as I do that the E and M, in fact, you'll see receive and transmit. You see how they're doing the E and the M there? I know I talked earlier about ear and mouth and earth and magneto. You see there, receive and transmit. So thank you, Cisco. We brought those time slots into service. Now, we're going to, let's see here, clear counters. Let's see if that thing stops slipping. There we go. Show controller T120. Yeah, we're still slipping, but I'm not going to spend a whole lot of time worrying about timing on this. It's not going to cause us any problems here in my little limited lab scenario. Debug command you're going to use for CAS, probably the most significant debug command, debug voice, CCAPI, in out. Obviously, other debugs are out there. This is the one that's going to give you the magic juice. So I've actually got a test set connected to my router. It's a TTC Tberg 2209, and I'm going to use it to place a call down this CAS circuit, and then we're going to, you're going to hear it ring a phone. In fact, let me turn the ringer up on a phone here nearby that it is going to ring. All right, hopefully that's loud enough you can hear it. But I'm going to go and I'm going to say, what's the extension on this phone? 2001. I'm going to say 2001, and I'm going to go off hook. Actually, I did that in the wrong order. Off hook 2001. There we go. Wait for it. It should be ringing here. Why did that not ring? Let me try that again. On hook, off hook. I may have forgot to build the dial pair. 2001. Nope, there it goes. I just had an error in my dialing. So you can hear my phone ringing in the background. You can see the debug here. In fact, if you look at the called number right here, called number equals 2001. We've got a ringing phone. In fact, oops, I missed it. I wasn't fast enough to answer it. Let me call it back again, and I'll actually answer it, and let's just see some debugs as things get in service. So off hook. Oops, hang on hook. Let me hang it up. Off hook. 2001. There it goes. There it's ringing in. We will pick it up. Hello, hello, hello. We are now on a phone call, and I'm going to hang it up now. You're going to see the debugs proceed. You're going to see the disconnect and the cause, and everything you would expect there. We'll go ahead and go on hook with the test set. And there you go. We've got T1 CAS up and in service and working. I mean, really, it's not that much difficult, or that much more difficult to configure anyway than ISDN PRI, but just a little bit different twist on things. So there you go. That's what you need to understand about T1 CAS. So I think we've really covered most of the voice interfaces that you're going to deal with in a Cisco UC environment, or at least the ones you're going to deal with most often. We've talked about analog, FXO and FXS. We've talked about E&M interfaces. We've talked about ISDN, PRI, and now we've talked about T1 CAS. So with that, I think I'm going to leave it, kind of stop right here. There's some other things you can do. I can go into these controllers, and I can actually create some cross connects if I want, and do drop and insert, and all kinds of things I can do, in the TDM world that you can play with. But actually, you know what? One more thing before I end this up. Let me talk to you about a couple of other debug commands that are useful here. Show voice port summary. Very useful to see your voice port and kind of what's going on. You can see this 200. That's the T1 CAS we've got. It's configured E&M wink. It's up. In fact, let me make a call and I'll run that command again to show you what it looks like when there's a call in progress. Off hook 2001 and answering. So now let me just run that command again. So you're going to see channel 1 is seized. So call's in progress. And we go ahead and hang that up again and hang it up on the test set. There we go. Other debugs or other show commands that are useful. So we did a show voice port summary. We can do just a show voice port. And we're going to get a little more detailed information. So there's my FXO port. We'll bang through these and get down to the CAS interface. Where is it at here? I'm looking for it. There it is. Slot 2, subunit 0, port 0, receive and transmit. So E&M, type of voice interface is E&M. It's dormant, etc. And you can get lots of information about echo cancellation and etc. I'm not going to dig too deep on that. We can take a look, and you've seen me using this one quite a bit, but show controller. And I've been going detailed, for like show controller T1. In fact, I'm going to do that. Show controller T1. We can see, physical interface statistics. Yes, I'm still slipping. Don't worry about that. It's a lab. I haven't defined a proper clock source. Show voice DSP. And we'll talk more about DSPs in another video, but show voice DSP. Also useful to see how your DSPs are allocated and what they're available to be used for. Show voice call summary. Very, very helpful. In fact, I'm going to do that call one more time. Maybe one more time. Hell, maybe I'll do it twice or 3 more times. Yeah, we'll just do it as many times as it's useful for us. And I want to show you the show voice call summary here. Off hook 2001. There we go. It's ringing. Show voice call summary. You'll see that we have a call E&M connect. So useful there. We can do a show call active voice. Show call active voice. And get information. Setup time, connection IDs, codec information, lots of debug related stuff. Packet counts and number of. I scrolled by it here already. Let me find it here. Where is it at? There we go. Transmit, receive bytes and packets. Lots of different information about the call and the call legs. And one more here. Show call history voice. Show call history voice. And get, again, detailed information about the call that was set up. And a lot of these, you can go ahead and show you like brief, get some summary information. So play with it a little bit. Play with some CAS. It's good to go router to router with CAS. So if you want to set that up, just remember clock source internal on one side, clock source line on the other, and you should be good to go. And that pretty much wraps up our lectures and our videos and our demonstrations on configuring voice services. So with that, I'm going to say thanks for watching. Sorry I've been kind of dragging it on here in this video and getting a little chatty, but I think we've hit the high points, and I think you're ready to go as far as the key competencies that Cisco wants you to have. So we'll see you in the next video. Good studying, and thanks for watching. All right, we've made it to Module 10, and we're going to kind of wrap up, actually, in this video, I think, this section of the course where we're talking about, fundamental concepts. And we're going to wrap it up by talking about DSPs, digital signal processors. Now, DSPs do a lot of different things for us. There are actually digital signal processors in many components of a Cisco Unified Communications environment. But the DSPs we're going to focus on within this module are the DSPs that get installed in your voice gateway or in your router. So let's talk about the different roles of a digital signal processor. One of the key functions or responsibilities of a DSP is transcoding. And transcoding is direct conversion from one audio codec to another. So let's say, for example, that I am on a phone that is only capable of supporting G.711. And the person I want to call is on a phone that is only capable of supporting G.729. For us to be able to communicate with each other, our call is going to have to utilize the services of a transcoder to convert one codec to another. Another role of a DSP within a Cisco router is voice termination, and this really is coming into play when you have TDM, or I'm even going to say analog, and IP call legs. So when you've got interfaces from the PSTN, and you're going to have a call leg going to an IP destination. So it's the packetization of voice. So obviously PRI cards require DSPs, T1 CAS circuits require DSPs, etc. Conferencing services, both for audio and for video, require the use of DSP resources. And when we start talking about video capabilities in DSPs, this is something fairly new to the PVDM3s, and we'll talk about PVDM3, boy, that's a tongue twister, here in just a moment. And obviously media termination points. Now this is kind of sort of like a transcoder, except no change of codec is taking place. So it's still this termination point where two audio streams are terminating, but it's simply for the purpose of having two audio streams terminate to a device so they can be bridged together. And there's lots of things you can use media termination points for, and you'll learn more about those as you explore Cisco Call Manager within some of the other videos in this series. We've got some photos, and we've got a table here I'm going to show you. Up in the upper right-hand corner, that is actually a PVDM module. In fact, I think that's a PVDM3. That's a DSP module. Now, the actual DSP is one of the chips on the module, but we call the module as a whole, a DSP. So it's not technically true. It's a collection of DSPs, or it's a DSP module, but you get the point. Now, the PVDM2 is a legacy DSP module, and it was supported on the Cisco 2800 series and 3800 series of integrated services routers. Now, we call it legacy, but it's still supported and can be used on the 2900s and 3900 series ISRs, but you require an adapter, and that's actually what I've got in the photo on the bottom right-hand corner. It shows you the adapter. So you take a PVDM2, put it in the module, and you can put it in a PVDM3 slot. So thank you, Cisco, for form factor changes. With PVDM2s, you had a couple of different models that were available. You had, as small as the PVDM2-8, which would give you 8 DSP resources to use, and as high as the PVDM2-64, which was, I'll let you guess, yes, 64 DSP resources. And to put it quite simply, if I am doing, let's use media conversion or audio termination as the example here. Say I got a PRI coming in and I've got 23 time slots. I need 23 DSP resources to be able to terminate those 23 time slots of audio on the PRI. So it's real easy to read these model numbers. We'll get into the Cisco DSP calculator here in another slide or two. The capability of the PVDM2 was it would do voice, and it would also support some fax capabilities for Cisco Fax Relay. I'm not going to talk about that in depth, but I do want you to know the PVDM3 has video capabilities, and you can actually take a router and do ad hoc video bridging or ad hoc video conferencing, multi-party conferencing, using a PVDM3 in a router. So PVDM3s, we've got bigger steps between the model numbers, but still, useful types of quantities. PVDM 3-16 up through the 256. Now, how many DSP resources do I need is a question that you're going to ask yourself until the end of time. It's always changing, and it really varies based on the situation you're in and based on the environment that you are working in. Cisco has an application they call the DSP calculator. In fact, I'm going to pull it down here and show you the DSP calculator so you have kind of an idea what's going on. Within the DSP calculator, and again, we show you the URL here that you can use to access it. Within the DSP calculator, I'm going to select the model of hardware I'm using. So I'm going to go ahead and say 3945 ISR. And we're going to tell it what iOS I'm using. Let's say that I'm on 1514M. And it's going to ask me what cards are in your router. So we're going to go ahead and say that in slot 1 of my router, I have a VWIC3 2MFT T1E1. And it tells me the maximum number of voice channels that are supported on that card. Now, what I need to do is tell the calculator how many sessions of a given codec do I want to use. In fact, you can look here down at the bottom, and Cisco lists low, medium, and high complexity codecs. And I'm going to have some notes in the next slide. It's actually a recycle from my CCNA voice certification class video where I tell you a little bit more about this. But, simply, the DSP calculator is going to ask me how many streams of a given complexity type do I want, and it's going to ask me, am I using DSP sharing? Am I talking PVDM2s or PVDM3s? I can hit next, fill out, exactly what I want to be able to do, and, the system will then give me the results. We'll say next. It's going to tell me exactly what I need. So it's going to say DSP modules required. It tells me I need one PVDM3-64 for the requirements that I fed into the calculator. So a very useful tool. Definitely something you're going to spend some time with if you're working with Cisco voice gateways for any period of time. And I don't know why my web browser won't scroll out. There we go. So that's the DSP calculator. Now, codec complexity. We skipped over it real fast there, and I want to zoom in on it just a little bit more and talk about what is codec complexity. So Cisco classifies codecs based on what they call a complexity. And really the complexity is how much horsepower, what kind of resources does it take for me to process and do what I do utilizing streams that are using a given codec. So Cisco says that G711, G729 ALAW, etc., are medium complexity codecs. And Cisco says that G7, what do I want to use? G723 or ILBC are high complexity codecs. And back when I was first doing voice, we didn't have a category called low complexity. And depending on the revision of the test you're in and what you see and what kind of documentation you're reading, you need to keep that in mind. So the DSP calculator, in fact, I've still got it open. Let me pull it down here and show you a little footnote at the bottom here. So the DSP calculator is considering G711 as a low complexity codec. That wasn't always the case. We used to consider G711 a medium complexity codec. So keep in mind that that there have been some changes over time. So when you're asked a question about low and medium complexity codecs, think about how the question is structured, so you know whether if it's talking about G711, is it medium or low. So we're going to stop there and pause for a break, and I'm going to pull up a router, and we're going to go through the process of configuring some DSP resources both on a Cisco router or a voice gateway, as well as within Cisco Unified Communications Manager or Call Manager. DSPs are accessed on a router using the skinny call control protocol. So we'll go through some skinny setup. We'll build a DSP farm in the router and show you how to allocate resources for both conferencing and transcoding purposes. So we'll be right back and give you a walkthrough of how to do those various tasks, and then that'll be it for this video as we talk about digital signal processors. All right, so we're going to go through a demonstration of some DSP configuration, and I want to first start start talking about codec complexity. So if you need to configure a DSP to support different kinds of codec complexity, you're able to do that. And you've got different types of complexities that are supported. And in fact, I'm just going to jump right into this. We're going to go config T. And I'm actually on a 2800 series ISR here, and I've got a PVDM 216. In fact, watch this. Show diag pipe begin PVDM. Let's see if that's useful. Yeah, PVDM slot 0. I have a 16 channel PVDM 2. So PVDM 216. So what I'm going to do, config T, is I'm going to say, actually, I'm going to show you the state before I do it. I'm going to say show voice DSP, and then I'm going to say detailed. And what I want to show you here is that currently we have, I showed you 16 channels. So here are the 16 channels. The DSPs in use are the 5510s, and you're seeing all 16 of them. This is what we call flex complexity. If I need to be able to support medium, I'm going to start the other end, high complexity codecs, which lets me do high complexity or a combination of high and lower complexity, I'll go voice card 0, and I'll say codec complexity and then question mark, and I've got high, medium, secure, and flex. So I'm going to say high. Now that same command that I just ran that previously showed me 16 resources available now is only going to show me 6. And you can see that we're configured in high complexity mode here, obviously by the count, the number we've got. If I want to change that, voice card 0, codec complexity medium, and show voice DSP detailed, whoops, get rid of that. Now I'm up to 8. And if you're curious, medium complexity codecs support medium or combination of things lower than medium, so medium and low. Basically, it's half the available resources if you were running in flex mode. I can go back to flex mode, config T, voice card 0, and codec complexity flex, and then show voice DSP detail, and now I'm back to 16 channels. So it's a matter of how many DSP channels or resources do I allocate to a given voice port. Now, you're not often going to have to mess with this. In fact, I can't think of a time where I've really had to mess with this, and as far back as I can remember, because typically we're running G711 to the gateway, and I'm not doing G729 stuff here. If I'm doing G729, it's between phones across the WAN. It's not to a voice gateway, so you probably won't have to monkey with that too often, but certainly the possibility is there. All right, now that we've configured basic codec complexity within DSPs and allocated the proper parameters there, the next thing you're going to do with a DSP farm, or with DSPs, is configure a DSP farm. And the reason you're going to do this is to either support conferencing services, transcoding services, or both. Now, the way you configure conferencing and transcoding is pretty much the same. So I'm going to walk you through configuring conferencing, and then I'll let you know what the differences are if you were going to do transcoding. So it all starts out with a DSP farm profile. So we're going to go ahead and say config T. We're going to say DSP farm profile 1, and we're going to actually say whether it's conference or transcoding. So this is one of the differences, obviously. I'm then going to specify the codecs that I'm going to want to support. So we're going to say codec G711 EULA codec. We'll keep this one really simple. G729 RH. Okay, so I'm going to support those two codecs. I'm going to define the number of sessions. So we can have maximum sessions, and I'm going to say 2. I'm going to support up to 2 conferences. Now I'm going to say associate application skinny, and I'm going to say no shutdown. that's going to bring this DSP farm profile into service. So if I want to go out here, I can say show DSP farm profile 1, and you'll see that it's a conferencing profile. I've got that right here. And you'll see that I've got 2 resources configured, 2 are available, and it tells me the maximum number of conference participants are 8. So if you stop and think for a second, I can have 8 participants in 2 conferences, which equals 16 resources. So no shutdown. Now we're going to go ahead and configure Skinny. We're going to say Skinny local fast Ethernet 00.30. And I'm going to say Skinny CCM. I'm going to put the IP of my call manager 10.10.210.10. Identifier 1, which is my call manager 1. And then I'm going to say priority 1 version, and I'm going to give you a question mark here. Depending what version of call manager you're using, you'll need to specify that so that you're running the right version of Skinny. So I'm going to say 7. Hopefully everybody here is on 7 or newer. And then I'm going to go Skinny and turn Skinny on. Now I'm going to associate some things together here. I'm going to say Skinny CCM group 1 bind interface FA0 0.30. And we're going to say associate CCM1 priority 1 associate profile, and I'm going to give it a name. I'm going to call it one register conference is what we're going to call it. So if I do a show CCM, not CCM, show SCCP, you're going to see that we're configured. Skinny is up. You can see the addresses and port numbers. And you can see that we are active and in progress, and our cause code is not registered with Call Manager. So what do I need to do? I need to go to Call Manager. So here's Call Manager, and we're in Media Resources Conference Bridge, and I'm going to hit Find, and you'll see the Software Conference Bridge that is default there. It's running on the server. But I'm going to go ahead and add a hardware bridge, and because this is a PVDM2, it is an iOS Enhanced Conference Bridge. Now I'm going to give it a conference bridge name, and that needs to match what I put out here in this associate profile 1 line. So we called it conference there. So conference. I'm going to put it in the default device pool and tell it it's a non-secure conference bridge and hit save. Now check this out. We're going to go back and hit find, and you'll see that after a moment it registered with the call manager. So if I do a show Skinny, now you'll see our status is active and we are registered with the call manager. So call manager is able to, using Skinny, access these conferencing resources on this endpoint. So there you go. And if I wanted to do transcoding, it's the same kind of thing, but on call manager I would be adding a transcoder instead of a conference bridge. And again, different models of DSPs and different chips are going to support different total numbers of conferences, numbers of participants per conference, etc. And it's just something you're going to have to do a little bit of planning on and look up and do the math. But that's pretty much it for configuring conferencing transcoding services on the DSPs on a Cisco ISR. So I think that wraps up our module here on DSPs and gives you the core competencies that you're going to need to have to pass the exam and to be comfortable working with these things in the field. So a lot of other things you can do. You could dive into tweaking and tuning echo cancelers on voice interfaces, which is another DSP function. You could talk about go way deeper into this whole codec complexity thing if you wanted to. But just the facts and just the important stuff here for this pass through. So we'll talk more about this stuff later as we go. But this is a great stopping point for this video. As we get into the next area here, we're going to get out of this basic, voice gateway introduction type of topics, and we're going to get into some of the basic voice over IP configuration tasks. So you're going to learn about SIP, and you're going to learn about MGCP and H323, and learn about just all kinds of practical on the gateway type of stuff. So until then, or until next time, I'll say see ya, good luck, good studying, and thanks for watching. In this module, we're going to talk about the packetizing and transportation of voice. We finally made it into the next section within your C-Voice curriculum. You know, we talked a lot about hardware and routers and WANs and call legs and a lot of fundamental concepts, but we haven't really gotten into the how does voice over IP actually work? How do we manage taking this audio and sending it across the network? Well, we're going to cover just that in this video and talk about packetizing and transportation of voice. So I want to talk to you about the 5 steps of packetizing voice and getting it on the network and to where it's going. We have sampling, quantization, encoding, compression, and encapsulation. And I know I buzzed through those kind of fast. We're going to spend a little bit of time talking about each of them here. So when we talk about sampling, we're talking about Nyquist's theorem. Harry Nyquist was a mathematician who came up or postulated that you would be able to reproduce a signal by sampling at twice the frequency rate of the transmitter. So basically, if I take an audio sample at twice the frequency, I'll be able to recreate that signal at the far end. So as this pertains to the telephone network, the telephone channel range is roughly 300 to 4,000 hertz. So that is a very good subset of the human, speech range. Obviously, it's not CD quality fidelity if we're only sampling 4,000 hertz, or I should say if we're only able to reproduce 4,000 hertz, but it does suffice, and it's what we call toll quality audio. So if you take 4,000 hertz and multiply it by 2, we're going to sample at 8,000 hertz, or 8,000 samples per second. And we're using a process called pulse amplitude modulation. Now, what's happening with pulse amplitude modulation is essentially we're taking a snapshot of a signal level at a point in time over the entire analog waveform that we're sampling. Once we've sampled the audio, we're going to go into a process called quantization. And really, we're going to take that analog waveform and turn it into a true digital signal. So we took the sample, and the values of the sample are then scaled. We're quantizing them. We are taking a value or taking a sample and putting a numerical representation to that particular sound. And this value that we use is going to define the amplitude of the signal. Once we have quantized the signal, we're going to then encode the signal. So we take these PAM samples, these pulse amplitude modulation samples, and we encode them using PCM audio, or pulse code modulation. Now PCM, and in fact we'll talk about PCM just a little bit here, but let's talk about the encoding process. Just a little bit of history here. 1 byte of data is 8 bits. And when we're talking, in a digital world here, we're typically using values of 0 through 255 to represent, these individual bits of data. So let's take the waveform that we've sampled and let's divide, 255 divided by 2. Let's divide that high-end binary value by 2. And, when we get basically a range that we can represent the audio signal as. It is a PCM value of negative 127 through positive 127. So obviously, if you're looking at a sine wave, you've got the portion of the wave that dips below the 0 reference, and the portion of wave that dips or that goes above the 0 reference line. So that's where your negative 127 through positive 127 value comes up. So, kind of the short and sweet, if you want to really think of it that way, is 127 plus 0, as a position plus 127. So lots of different values that we can assign to these samples. An example of how this is represented within those 8 bits is we use the first bit as a sine value. A 0 is going to indicate a negative value follows, and a 1 is going to indicate that a positive value follows. We're then going to take the segment and interval for the remaining 7 bits, and that's going to present the 8-bit data. So I've got 2 examples here. So a 0 with 7 ones is going to be a value of negative 127. And a value of 1 with 7 ones is going to be a value of positive 127. The process of compression is the next step in packetizing this voice stream. Depending what audio codec you're using, you're going to require a different, or occupy, I should say, a different amount of bandwidth on the network for each conversation that is taking place. Utilizing the G711 codec, we get 64 KB a second, and that's plain old uncompressed audio. That's Nyquist theorem math. So if we take 8,000 hertz samples, so 4,000 hertz times 2 equals 8,000, and we multiply that by 8 bits, we then get 64 kilobits per second. So that is a single T1 DS0 worth of bandwidth. Now, we may choose to use a different codec within our network. Perhaps we have congested wide area network links, and we want to use a lower bitrate codec across those wide area links. Well, G729 or one of its variants are certainly a popular choice for doing that because we only use roughly 8 kilobits per second of bandwidth. GSM, just for a reference point here, uses 13 KB a second. And then if you really want to get small, G723 R53 is 5.3 KB per second. So lots of different choices available to you as a telephony engineer as far as what codecs you want to use to transport voice across the data network. Finally, we get to encapsulation, and let's talk about packetization rates. There are two different sample sizes, or I should say durations, of audio that we're going to packetize. And typically it's either 20 milliseconds or 30 milliseconds. And I've got two examples here. I've got a G711 example and a G729 example. So we're trying to show you the total bandwidth utilized. So at 20 milliseconds, we are using an uncompressed bandwidth of about 80 KB a second for G711. And if we use 30 millisecond samples, it's slightly less. If we're doing G729, that 20 millisecond sample reduces down to 24 KB a second. And if you want to see the formula to actually work all this out, you take, bandwidth's what we're solving for. So bandwidth equals the voice payload plus the layer 3 overhead, so the IP overhead, plus the layer 2 overhead. And we multiply that by the packets per second times 8 bits per byte. So keep in mind, depending what layer 2 network technology you're using, perhaps it's Ethernet, perhaps it's not, your layer 2 overhead number may vary. But, basically, voice payload plus layer 3 overhead plus layer 2 overhead times packets per second times 8 bits per byte. Let's talk about transmission protocols that are used for moving these newly created packets around the data network. First and foremost, the star of the show is RTP. RTP is the real-time transport protocol. RTP works in conjunction with a protocol called RTCP, which is the real-time transport control protocol. You may have even heard me refer to it. I know I've heard others call it the RTP transport control protocol, because essentially that's what it's doing. We have CRTP, which is compressed RTP, and we have SRTP, which is secure RTP. And we'll talk about all of these in greater detail in the following slides. RTP was created and standardized in the publication RFC 3550. And RTP defines a packet format, or protocol, for audio and video transport over an IP network. Now, RTP rides on top of UDP, and it has dynamic port assignment. So it frequently uses ports anywhere in the range of 16384 through 32767. Now, because of this dynamic port range, RTP can be somewhat challenging to traverse firewalls. And you'll see that firewalls such as the Cisco ASA, etc., have developed special techniques to analyze the protocol and poke holes accordingly, if I can be so blunt. But so that's RTP. dynamic port range, and 16384 through 32767. Now, one of the cool things with RTP is that both unicast and multicast network types are supported. So if I'm on a phone call from phone A to phone B, the RTP stream between us is going to be unicast. However, if I am leveraging a solution to send audio to a building full of IP speakers, perhaps in a paging application, I can still use RTP to do it, but I'm going to utilize multicast. RTP adds timestamps and sequence numbers, I should say, so that out-of-order packets can be reordered inside of the djitter buffer, and it makes sure that playback speeds are managed. Being that RTP travels over UDP, we want to make sure that if we've lost data, we just skip over it. We don't want to have replays and data out of order, etc. So sequence numbers and timestamps help us deal with these out-of-order packets, assuming they arrive quickly enough that they can land in our djitter buffer to be dealt with. I'm going to show you two different, I'll just call them, I don't know how to describe it. Frame formats is a great word to describe it. We've got the RTP packet on the left-hand side, and we've got the RTP header on the other side. So you'll see that the RTP packet includes the layer 2 header, the IP header, so presumably layer 2 header is your Ethernet header, layer 3 header, which is the IP header, the UDP header, the RTP header, which we detail on the right, and then finally the voice payload. The RTP header itself contains the various fields for flags, payload type, sequence number, timestamp, and options. So we've got, again, on the left, the RTP packet framing format, and the RTP header format on the right. RTCP, the partner to RTP, also defined in RFC 3550, provides for out-of-band control information relative or pertaining to the flow of an RTP session. And its primary role in practical use is to provide feedback related to quality of service. Again, RTCP, both unicast and multicast are supported. And some of the values that RTCP provides to us is bytes or packets sent, round-trip delay, packet loss, and jitter. And RTCP packets are sent at least every 5 seconds. So RTCP, the little brother to RTP. Now, compressed RTP, or CRTP, is defined in RFCs 2508, 2509, and 3545. And the whole point of CRTP is to decrease the size of RTP, UDP, and IP headers. So when you're sending voice across the network, it's not unusual for the overhead to exceed the amount of data that you're trying to move. Now, on a LAN, we don't really care because there's bandwidth to spare, and it's just not a problem. But when we deal with slow links, it's something that we want to consider. So what can compressed RTP give us? Well, it can compress and decrease the size of these headers to 2 bytes without checksum or 4 bytes with checksum. So RTP header compression is going to be used not so much on the LAN, but on point-to-point interfaces. And you do need to explicitly configure this on both sides of these links. So whether this is a PPP link or an HDLC link, you've got to configure it at both ends. This is recommended for use. In fact, it's a best practice to utilize this on slow links. So when you have a network that has links slower than 768K, go ahead and turn on compressed RTP for those links. And keep in mind, though, with the bandwidth savings comes a increase in CPU load. So make sure that your CPU budget accounts for the overhead that's going to be created by compressing these RTP headers. SRTP, or Secure RTP, was defined in RFC 3711 and provides for encryption, message authentication and integrity, and replay protection for RTP packets. So SRTP is going to use AES for its encryption type. We're going to use HMAC SHA-1 for message authentication, and we're going to use sequencing as a technique to prevent the replay of packets. One more thing I want to talk about, since we're talking about moving data around the network or moving voice around the network, is VAD, and that's voice activity detection. And this is kind of the opposite of moving stuff around the network. This is not moving stuff around the network. Voice activity detection classifies VoIP traffic as one of three types. You have speech, you have silence, and you have unknown. A maximum of 35% bandwidth savings can be realized when leveraging voice activity detection on a network averaging more than 24 calls. So what's VAD really do? Well, if a voice packet is classified as speech or as unknown, it will be sent across the network. If it's classified as silence, it will not be sent. So by reducing the sending of packets that simply contain silence, you can save some bandwidth. Now, VAD is enabled by default when you're using a codec that supports it. However, we can disable this within a dial peer. And frequently, in fact, I would say almost always, I disable VAD within my dial peers because I may be transporting things, other than just voice that have problems with that, or perhaps my users just are uncomfortable by hearing the very crisp silence that occurs when VAD is at play on a network. That's all we've got for this video. We've talked about how do we packetize voice for transport across an IP network, and we've talked a little bit about the transmission itself and RTCP, RTP, compressed RTP, and secure RTP, as well as voice activity detection. Thanks for watching. I'll see you in the next video, and we're going to continue talking fundamentals of voice over IP. And I thank you for watching, and I hope to see you soon. Good studying. In this video, we're going to talk about the first of our gateway protocols. And it's really one of the more popular gateway protocols. In fact, it's probably, I don't even say probably, it's the first protocol I ever saw on a Cisco Voice gateway, way back when in Call Manager 3 days. And it is H.323. So we're going to go through some H.323 fundamentals within this video, and we're going to walk through basic configuration steps for an H.323 gateway. When we talk about H.323 architecture, I want you to understand that it's an ITU standard, and really it governs everything multimedia over a LAN. So we can be talking about voice, we can be talking about video, or we can be talking about collaboration. It's a mature protocol, and it is vendor neutral. In fact, it's one of the more vendor neutral protocols out there relative to voice. It is a peer-to-peer protocol, and when I say that it's a peer-to-peer protocol, I want you to understand that a voice gateway first off, doesn't rely on Call Manager. There doesn't have to be a Call Manager to have an H.323 gateway, as the gateway maintains its own self-sufficient dial plan. So if you've got a network and a Call Manager and a half a dozen sites, and each site has a voice gateway, and they're H.323 gateways, each gateway will have its own unique dial plan that is controlled by the device itself. One of the advantages of H.323 is it allows for very specific call routing rules, even more so than within Call Manager itself. Within an H.323 gateway, we can make routing decisions based on both the called and calling number, so very flexible. If you're doing SRST or survivable remote site telephony, H.323 is a great option for you because the dial peers you use during the course of normal business will be the same dial peers that you're using during a survivability scenario. Like I said before, there's no dependency on Cisco Unified Communications Manager. I could certainly have a voice gateway running H.323 and another voice gateway running H.323, build a dial plan to allow calls to route between them, and be done without a Call Manager. One of the features that is supported on H.323 but not on some of the other protocols is ISDN NFAS, or Non-Facility Associated Signaling. NFAS is a methodology where you have multiple ISDN PRI circuits and you share a single D channel or delta channel for a combination of multiple, and in fact I think it's like up to 6 different PRIs. So you can buy yourself a couple of extra time slots for voice by not allocating a time slot for signaling. So MGCP, which we'll talk about later, does not support NFAS. H.323 does. H.323, again, very feature-rich, has T.38 support for fax, and T38 is a fax over IP implementation that's very popular. And H.323 has the advantage of supporting enhanced call preservation. So, for example, let's say that I have a voice call in progress between a Cisco IP phone and an H.323 gateway, out to a PSTN caller. If the call manager were to experience a failure, the call would actually remain in progress because the H.323 device is not reliant on the call manager to maintain the call. So we've got enhanced call preservation. Let's talk about H.323 network elements for a moment. We have terminals. We have devices called multi-point control units, or MCUs, and an MCU is nothing more than a conference bridge for audio or video. We have gateways, and we have gatekeepers. So a terminal, that's an endpoint. That could be a video endpoint, a voice endpoint, it could be a computer, running, video conferencing software, etc. We talked about MCUs. Those can be devices that facilitate for audio and video multiplexing for conferences. Gateways are just what they sound. They're where we connect things like PSTN interfaces. Gatekeepers are kind of unique. A gatekeeper allows you to distribute dial plan elements or distribute logic and knowledge of a dial plan throughout an H.323 network. And we'll talk more about gatekeepers in some of the next couple of slides. With H.323, gatekeepers, which are optional devices, I want to stress that gatekeepers are not mandatory within H.323. They can be used for H.323 dial plan management. Gatekeepers perform a number of functions, including address translation, admission control, bandwidth control, zone management, call authorization, bandwidth management, call management. And the endpoints themselves are going to register with the gatekeeper when you turn them on and boot them up. Endpoints are going to request permission, or what we call admission, from the gatekeeper in order to place a call. So as we talk about the components of H.323, I want to mention that H.323 is what we refer to as an umbrella protocol. And what that really means is that there are a number of other protocols underneath H.323 that make up the entire communication flow. H.225 is one of those protocols. In fact, we're talking here on this slide about H.225 RAS, which is registration, authorization, and status. So when H.323 endpoints are using a gatekeeper, they're going to use the H.225 RAS protocol to communicate with the gatekeeper. Gatekeepers have lots and lots of different message types, and I'm going to go through some of those message types pretty quickly here. And depending on your experience with gatekeepers, you may want to study this for the test. I remember when I was going through the CCNP voice curriculum for my C-Voice exam, they drilled me pretty heavy on this stuff. So take your time to understand this. We have gatekeeper requests, rejects, and confirms. Those are the GRX messages. We have registration request, reject, confirms. We have unregister request, reject, confirm. We have administration request, reject, confirm. We have bandwidth request, reject, confirm. You seeing a pattern here? We have disengage request, reject, confirm. Location request, reject, confirm. We have information requests, acknowledgments, non-acknowledgments, and responses. We have non-standard messages, unknown message responses, request in progress. the resource availability indication and confirm, the service control indication and response, and finally the admission confirm sequence. H.225, as we talk about H.225, when endpoint communication begins and we resolve the endpoint address and we try to set up a call, the next thing that happens is that H.225 messages are used to establish communications with the remote endpoint. You've got a setup and setup acknowledge message, a call proceeding message, a connect message, alerting, information, release complete, facility in progress. Now, one thing you may recognize here is this is very similar to the Q.931 protocol we use for ISDN. And that's because H.225 was based off of Q931. I'm sorry, and I skipped one. We've got status and status inquiry and notify messages. Actually, I skipped two. H.245 call control takes place once a call is initiated. So H.225 comes first. Next is H.245 call control. So we're going to use 245 call signaling to do things like capabilities negotiations for video and audio. We're going to use it for opening and closing of logical channels for video, audio, collaboration. We're going to use it for flow control and conference control. And I found a resource on the web. I don't like reinventing the wheel here. I found a resource on the web with Wikipedia that gives just a phenomenal breakdown of the H.323 protocol, and I've got that URL shown here. So please take a moment, go to Wikipedia, view the H.323 page, and I think you're going to find a lot of value add in that link. We're going to go through some basic H.323 gateway configurations within this video, and I want to walk you through what is involved in setting up a 323 gateway. Alright, in this example, we're going to walk you through basic configuration of an H.323 gateway. We've got a Cisco 2811 router here, HQ router. You've seen me use this device a number of times before, and I want to show you just how dead stupid simple H.323 is to configure. We're going to go config T, and in fact, before I do that, do show IP int brief. You'll see that I've got just a couple of IP addresses, router on a stick going on. We've got loopback 0 in use, and in fact, I'm going to use the loopback interface here for a moment. I'm going to say interface loopback 0, and I'm going to say H.323 gateway VoIP bind source address 10.150.1.1. What I've done there is I've enabled H.323 on that interface. And this is the address we're going to use as the source IP address for all of our outgoing H.323 traffic. So H.225, H.245, and RAS signaling. So it's all going to originate from that loopback interface. Again, depending on your network layout, your choice of interface may very well be a physical interface. We've talked about dial peers before, and it's necessary to configure a dial peer to make a gateway in H.323 gateway. In fact, specifically is a VoIP dial peer. So we're going to say dial peer voice 100 VoIP. And we're going to say destination pattern, I'm just going to make it, 8 ... And then we're going to say session target IPv4 10.10.2.10.10. So that's my call manager. And guess what? That's an H.323 gateway. I mean, as simple as that. I've got a dial peer. In fact, I'll do a show run, pipe include, or pipe begin, dial peer voice. We'll see that dial peer that I just built up here. This dial peer, whoops, scroll by it here. Dial peer voice 100 VoIP. If I had an incoming call leg hit the gateway and look to select an outgoing call leg, that is an H.323 gateway configuration. In fact, by default, a VoIP dial peer is an H.323 dial peer. Now, when we get into SIP gateways, you're going to see that it's configured almost the same, except we're going to specify a session protocol. And that's fine too. But, really, turning up an H.323 gateway is one of the most simple things that you're going to do. Now, if I wanted to turn off capabilities for H.323, they're on by default, voice service VoIP, but I can do a shutdown and turn them off. Now, You're not going to do that if you're programming a voice gateway, but you could. Other things you might want to do with H323 is configure whether or not the session transport is TCP or UDP. The default for H323 is TCP, but one of the advantages of using UDP, obviously your application and the endpoints have to support it, but if I'm using UDP, I'm going to get a slightly faster call setup. So if that matters to you, you might consider this. But basically what we'll do, we're already under the voice service VoIP menu, and I'm going to go ahead and say, let's see here, H323, whoops, got to get on the keyboard, right? And then let me show you here, we've got session, transport, TCP, or UDP. So I could go UDP and tell it to use UDP for H323, but I'm going to go back to TCP, which is the default. I've never changed it in production, but you certainly can. If I want to monkey with the H225 timers, I've got an idle call connection timer. So we're going to be, actually I'm in the right place right now. I can say H225 question mark. I want to show you all the things we've got going on here. The one I'm going to mess with is timeout. And I'm going to mess with the TCP call idle. And then I can set a value here, or I can say never. So if I wanted to change the timeout, I could do that. The default is going to be 10 seconds, but play with that as necessary. You can do a lot of different tuning with H225. You've got, in a voice class, if I want to configure a voice class, let me get out of here. I'll show you that. We'll say voice class, and then I'm going to say H323, and then let's give it a tag. We'll just call it Josh. Can I do that? Hang on. Oh, it's a numeric tag. Okay, we'll say 1. Sorry about that. We will say H225 timeout, TCP establish, and then we can put a value. I can say, 5 seconds if I want. I can mess with the H225 timeout setup by going H225 timeout setup, question mark. Again, I've got some timers here, 4 seconds, whatever. And you would then associate the voice class with a dial peer or a series of dial peers if you wanted to use it. And we're getting into some of the granular stuff here, but what was that dial peer I had? Show, run, pipe, begin, dial, peer, voice. We called it 100. Okay, so config T, dial peer voice 100 VoIP, and I would say voice class. I'm sorry. I would actually say voice dash class. I always forget hyphens. Voice class, and then I'm just going to say H323, and then that tag I used, so 1. I wish Cisco was a little more consistent in tags of numeric versus alphanumeric, but we'll take a numeric tag there. So anyway, the timers and the parameters that I tweaked there would be available to you. Now, if I want to verify the configuration of my gateway, show gateway, kind of a real easy command. We can show H323 ITUT version 4.0, H323 stack version 0.1. The H323 service is up. It shows us that the gateway is not registered to any gatekeeper. And in fact, I have not seen a gatekeeper in use in a network in I don't even know how long. They've fallen out of popularity because, quite frankly, there are better ways to manage dial plan than using H323 gateways and gatekeepers. That said, they do exist and you may run into them from time to time. Now, how do I debug an H323 gateway? I'm going to show you a command you've seen before. It's a debug you're going to love to hate or hate to love, one or the other. Debug voice CCAPI in out. If I've got an H323 gateway and I'm sending calls to and from call manager and I want to know what's going on, that bad boy is the debug we're going to use. So with that, I think we've covered fundamentals of H.323, and I think you're ready to move on to the next section. We're going to talk about SIP, we're going to talk about MGCP, and get into some of the other gateway protocols, and kind of dig into the how and the why and the where and how to debug, etc. And I think that's enough to move you on to the next video. So thanks for watching, guys. Have a great evening, and good studying. I'll talk to you soon. In this module, we're going to talk about one of my favorite protocols, and that is SIP. Now, I have to admit that in the beginning, when I first began working with Cisco Unified Communications, I was a H.323 and MGCP fan, and those were the protocols I used, and I would never touch SIP. Part of that was because of where it was as a protocol in maturing. Part of it was because I didn't know how it worked, and part of it was because other people told me not to. They said 323 and MGCP, and these are the things you need to be using. Well, 10 years later, here we are, and let me tell you, my opinion has changed, or I should say, my opinion has evolved. Just as the SIP protocol has evolved, widespread adoption or adoption of it in general has evolved, and I think you'll find that it is absolutely a contender technology for voice gateways today. So let's get into talking about SIP and understanding SIP architecture. So, like H.323, SIP is a protocol created by a standards body. H.323 was an ITU standard, and SIP is an IETF standard. So we've got two competing, kind of sort of, governing bodies and their individual protocols. And it was developed as an alternative to H.323. A lot of the things you're going to see me say about SIP are the same things that I said about H.323. They're both mature and vendor neutral. SIP, also a peer-to-peer protocol, and each gateway is going to maintain its own dial plan logic. There's no extra configuration that needs to be done if you're using SRST. The same dial pairs you're using for call routing can be used for survivability features. It's got no dependency on call manager. Again, you can do ISDN fast, and you can do T38 support for faxing. Now, keep in mind, if you're doing T38 for faxing, that is supported with SIP UDP only, not with SIP TCP. But that's a little bit beyond the scope of the C-Voice exam, so don't stress that too much. But if you're doing fax over IP, you'll know exactly what I'm talking about. Let's talk about SIP network elements. There are two types of network elements I want you to understand. And in SIP, we call these user agents, the SIP UA. There are SIP UA clients, or what we call a UAC. And those include endpoints such as phone, video conferencing, codecs, voice gateways. And then there are endpoints, or I should say, there are user agents we call servers, or UAS, which includes SIP registrars and proxies and redirect servers and location servers. Let's walk through a basic SIP call flow. You'll understand, once we get through this, how simple SIP really is and how a call flow works. So let's take a network example here. We've got a phone and a voice gateway, an IP WAN, another voice gateway, and a phone. So you'll notice there's no call manager here. And let's walk through the SIP setup. So step one, the phone initiates the call, and the voice gateway sends a SIP invite message to the other voice gateway across the IP network. Step 3, we get a 100 trying response. Step 4, we're going to ring the called party. Step 5, we're going to send a 180 ringing message from the destination voice gateway to the originating voice gateway. We're going to play ringback to the phone in step 6. When the called party answers, we're then going to send a 200 OK message back to the originating voice gateway. We're going to receive an acknowledgement, and the RTP stream will be set up end to end. So that is a SIP call setup. Now, let's say this session runs for a few minutes and it's ready to shut down. One party hangs up, the gateway sends a bye, the other gateway sends a 200 OK to acknowledge it, and we're done. That is the basic SIP call flow. When we talk about SIP addressing is based on internet URLs. So the typical format you're going to see is user at domain. And just like other protocols, we have a URL type, and our URL type is SIP colon. So just like you've got HTTP colon, FTP colon, etc., we're going to use SIP colon. Here are some examples of SIP address types. We've got fully qualified domain names, SIP colon josh@howtonetwork.com. We've got E164 address variants, SIP colon and the number at howtonetwork.com. We've got some additional information in there as well. And then we've got some mixed mode examples. So SIP addressing can either be learned through DNS, or it can be the responsibility of the proxy server if you're registered to a SIP proxy. to resolve the address for you. Now, I want you to understand that SIP is going to leverage SDP, or the Session Discovery Protocol. I'm sorry, not the Session Discovery Protocol. Hang on, let me tell you exactly what that one stands for. I don't want to lie. Session Description Protocol. The Session Description Protocol is utilizing offer and answer messages. And what you'll see, there we go, got my head around order there a little bit. What you'll see is we've got a number of fields here. Version, origin, session time, times, connection data, media, and AVP codecs. And all of these values are going to be populated into the SDP message. So inside of the SIP packet, you're going to see this SDP message and this negotiation taking place. Here I'm showing you an example of what an SDP message might look like. Version 0, origin is Josh. We've got some additional information in there, network type, address, address. We got a session equals, and I've got a session name called my session. We've got a start and end time of 0. We've got connection data, including our network type and address type and our connection address. We've got our media negotiation, where here we're trying to negotiate a list of 3 codecs. In fact, I'm going to circle them here for you. We say first G711 ULAW, G729, and then GSM. So a couple of different negotiation options taking place there. Let's talk for a second about delayed offer versus early offer. And this is really about SDP. SDP, like I just showed you, is used for capabilities negotiation, media negotiation, codec negotiation, etc. There are 2 modes that you're going to run into of SDP message exchange. There's delayed offer and there's early offer. I'm going to show you the same network example here, a little bit smaller, and we're going to compare delayed offer to early offer. So in a delayed offer call, step 1, we're going to pick up the handset and initiate the call and send the invite. We're going to do the 100 trying. We're going to ring the calling party. We're going to play back the 180 ringing, give the ringback tone to the calling phone, and wait for the party to answer. Once the answer has occurred, here is our SDP media offer. So the person we called is going to begin negotiating the capabilities. And we tell him, here's what I can do. We acknowledge having negotiated a set of parameters to use, and this is our media answer. We have our RTP stream set up. When the call is done, one endpoint says a bye, the other one sends a 200 OK, and we're done. So that's kind of your standard delayed offer SDP setup. With early offer, SDP is actually going to happen a lot earlier, hence the name early offer. Same network. We're going to initiate a call, and in the invite message, we're going to send our capabilities. So that is our SDP media offer. We're going to get the same 100 trying, the ringing. We're going to get ring back to the calling party. The call will be answered, and in the 200 OK, we're going to send our media answer. So that is where our SDP negotiation is taking place. And the rest of the call is the same. You've got the ACK, the RTP stream. One guy hangs up, the other one gives his 200 OK. Now, both delayed offer and early offer support RFC 3960 SIP early media. And early media basically presents a way for the sender to start sending audio before the entire call setup has completed. And you can read more about that on your own. It's not a heavy topic of the exam. But I did want you to understand the fundamental differences between delayed offer and early offer. We're going to get into an example here and go through some basic SIP configuration. I'm going to show you how to provision SIP on a Cisco Voice Gateway and how to do some basic SIP troubleshooting, commands that are useful, what some debug output looks like, etc. So with that, standby 1, I'll get the router set up and we'll go through some basic SIP configuration. Alright, let's go through a basic example of configuring SIP on a Cisco Voice Gateway, and I'll walk you through some of the debugging processes as well. I've created a dial peer on this gateway, and I want to go ahead and show it to you. Show dial peer voice summary. It is dial peer voice 100. So show run pipe begin dial peer voice. So dial peer voice 100. I have a session protocol SIP v2, and a session target IPv4 10.10.2.10.10. So this looks an awful lot like an H.323 dial peer, aside from the obvious, the emitted destination pattern that's there. But what I want to show you is really the only thing I did to make this a SIP dial peer instead of an H.323 dial peer is I changed session protocol to SIP v2. That's a basic, in fact, that's the most basic SIP configuration on a Cisco voice gateway. Now, obviously, I need to have a lot more data in those dial peers and in the dial plan to actually have meaningful call routing, but basics are enough to get us started. Let's create another dial peer. In fact, what I'm going to show you, a lot of the times you're going to use a SIP registrar for your gateway or your endpoints. So we're going to go config T, and I'm going to say SIP UA registrar, and I'm going to put in 10.10.2.10.10. I always forget that IPv4 v4 colon. And I've defined a registrar. I can then define authentication, username, Josh, password, networks, rock, whatever. So I've defined a registrar. I've defined a username and password. These are my digest credentials. And then I can say SIP server 10.10.2.10.10. Does it want what? IPv4 colon? IPv4 colon. No, actually, hang on. What does it want there? SIP server. Ah, okay. I see what it is. SIP server space IPv4 colon 10.10.2.10.10. It still doesn't like me. Hang on. What am I doing wrong here? IPv4 colon. That is exactly. It should be right. Take a look here at another example that I've got and see what I'm screwing up. SIP server IPv4 colon. Oh, I know what I'm doing wrong. Stupid hyphen. SIP dash server. Why couldn't Cisco error logs tell me that? SIP dash server IPv4. Okay, you can tell I don't use this feature very often. But what I want to show you is I've defined a SIP server. In fact, let me do a show run. Let me get down here to all the voice stuff and show you what we've actually done. We've configured SIP UA. We've got our authentication digest credentials in there, so our username and our password. We've defined our registrar, and we've defined our SIP server. Now, if you look at the dial peer I created, you'll remember that I pointed session target IPv4 and the IP of the server. What I can do, in fact, we'll go here, we'll say dial peer voice 101 VoIP, and we'll say session protocol SIP v2, and I'll say session target SIP server. So all I did was redirect SIP server to the IP address I'd previously configured as my SIP server. Both of those are valid dial peer formats. In fact, show, run, pipe begin, dial peer voice. Both of those are legal. Use whichever one you want, but that's really all that's necessary for basic SIP UA configuration. Now let's walk through some debugs. Debug CC SIP messages. I'm going to place a call to this gateway from a call manager that I have configured, and I'm just going to dial extension 7500. Now, it's not hooked up to a phone. It's not going to ring anything. In fact, it's not going to work at all, but I want you to see the debug output. So check this out. We're going to go 7500. And I got all kinds of garbage flying across the screen. We're going to step back and we're going to look at it. I want to show you why I love SIP so much from a debug perspective. We're going to start the call with a SIP invite. And I'm calling SIP colon 7500 at 10.10.2.10.1, which is my gateway. So there's the invite. I can see exactly what's happening here. There's a 100 trying. Now, I actually got back a 403 forbidden, to which I acknowledged. And, that was the end of it. Obviously, it didn't exist, so, we didn't route it anywhere. But isn't that cool? How easy is that to read? You can see exactly what's happening. I would say equally as easy as doing a Q931 debug. It's just dead nuts easy to read. So that's one of the major reasons I love SIP. And I can deal with this on a high call volume gateway because it's real easy for me to look at a message like this 100 trying, for example, and know exactly what call it is. I can see the from, I can see the to, I've got dates and times. It's all right here in front of me. So that's pretty darn cool, if you ask me. So anyway, that's a basic SIP debug. There's all kinds of show commands you can use, and it really depends what you're trying to solve and what kind of problem you're trying to look for. But we can do, like, for example, show SIP UA service and validate that our SIP service is up. Obviously, if you turn SIP UA off, SIP will be disabled. We can say show SIP UA statistics and get all kinds of metric information of messaging, responses, and SDP, etc. We can do a show SIP UA. Which one did I do? I did status. Did I do status? I did service. Let's do status. Show SIP UA status, and I can get all kinds of different information about the user agent configured, and what's set up here on the SDP. So tons of things you can get out of it. Show SIP UA register status. I can get information. If I had a registration to a UA, I would get registration about that. But really, that's going to get you started. Just darn cool. I really can't say much more about it other than it's just darn cool. So with that, you've seen what you need to know for SIP. You're ready to program SIP on a voice gateway, and you'll learn more about programming the actual trunks and call manager when you get into CIPT. So I'm not going to go show you that, but it's relatively straightforward. But anyway, I think with that, we're going to conclude our discussion of SIP. In the next video, we're going to talk about the final protocol I want you to understand, and that is MGCP, the Media Gateway Control Protocol. And then we'll talk briefly about things like fax and modem relay and T.38, etc. And that will kind of cover what you need to know about voice gateway protocols. And at that point, we'll be able to move into the next big topic area, which is Unified Communications Manager Express, or CME. So stay tuned. There's a lot more fun to come. Good luck as you study and practice for your C-Voice exam, and I'll see you in the next video. In this module, we're going to talk about one final gateway protocol, and that is MGCP, or the Media Gateway Control Protocol. We started out by talking about H.323 and then moved into SIP, and we talked about how both of those were peer-to-peer protocols and how the gateways would hold a lot of their own dial plan and kind of be the masters of their own destiny from a call routing perspective, which is all fine and good, but everybody doesn't want that. Every situation isn't right for that. So MGCP provides an alternative where the gateway itself is a thin device and the dial plan is managed by the call manager. As we talk about MGCP architecture, MGCP is a IETF RFC origination. Current RFC number is 3435, which obsoleted a previous version of MGCP in RFC 2705. And MGCP is a centralized device control protocol. And unlike H.323 and unlike SIP, MGCP is a client-server-based protocol, not a peer-to-peer protocol. Now, what does that mean for you within your router? Well, one of the consequences is if you're utilizing survivable remote site telephony, or SRST, you will have extra configuration to do on the voice gateway in the form of dial peers to be able to support that functionality. So keep that in mind. If you're selecting a protocol to use on a gateway that's going to have SRST, MGCP may not be the right choice for that. MGCP has a complete dependency on the call agent, what we call the call agent, from from the perspective of this class, the call agent is going to be Call Manager or Call Manager Express. MGCP does not support ISDN, non-facility associated signaling. So again, if you're using multiple PRIs and trying to share the D channel for signaling, you cannot do that with an MGCP gateway. MGCP uses UDP port 2427 for messaging from the call agent to the gateways, and UDP port 2727 for messages from the gateways to the call agent. There are a couple of advantages of MGCP that I want to make you aware of to keep in mind when you are choosing a gateway protocol. One of the big advantages, in fact the biggest thing really that MGCP has going for it, is that it offers you a simplified configuration within Call Manager, and it's centrally controlled. That's why I call it a centralized configuration. So we do this thing called Q.931 backhaul if we're using a PRI gateway in our environment and we're controlling it with MGCP. And we actually channel or tunnel that D channel, we backhaul that D channel all the way back to Call Manager. So Call Manager is aware of what's happening with that MGCP endpoint. MGCP supports QSIG supplementary services. So if you're doing QSIG trunks between PBXs, MGCP may offer you some advantage in that arena. Now let's talk about MGCP components. We have endpoints, gateways, and a call agent. There are two kinds of endpoints you're going to hear me refer to in this course. One is a trunking gateway, and that's a gateway that's going to connect you to the PSTN. And one is a residential gateway. That's going to connect you to, for example, an FXS port on a router where I've got a POTS phone or similar arrangement like that. So there's the PSTN facing gateways. Those are our trunk gateways or trunking gateways. And there's our residential gateways, which is pointing towards our analog connections. Let's walk through a simple MGCP call flow and explain exactly how the signaling is taking place with this protocol. And I think this will help you understand what's going on. Now, there are different control commands used for MGCP, and I'm not going to lay them all out for you. You can certainly look that up on your own. But I will explain what they do as we use them within this connection. We've got the same topology, or roughly the same topology I've used for other examples, but I want to show you in the middle. Instead of using a PSTN example, I'm going to use a campus example. So I've got my call manager, or my MGCP call agent in the middle. And I've got two voice gateways, and these are configured as residential gateways. So we'll walk you through a call setup between two phones on an MGCP residential gateway. First, we send an RQNT message. That is a notification request, and we're basically telling the gateway to watch for events on the endpoint, so watch the phones. We're going to receive RQNT responses from the gateway to the call agent. When an event occurs, eventually, such as my calling party phone going off hook, the call agent is going to signal the voice gateway with a CRCX message, or is a create connection message. And again, this is issued by the call agent. We're going to receive a CRCX response, and we're going to send a CRCX request, again, that same create connection request, to the destination gateway. And ultimately, the phone will then begin ringing. When the phone is answered, we're going to get a create connection response, and we're going to send an MDCX. This is called a modify connection command. And what we're going to do here is we're going to tell the gateway to update the connection parameters. We're going to receive a response to the MDCX request that we sent, and we're going to nail up the RTP stream. So now end to end we have an RTP stream. Our call has been set up. We're going to use notify messages to inform the call agent of events that occur. So in this case, we're going to initiate a hang-up. the call agent is going to signal both gateways with a DLCX, or a delete connection message, which initiates the session termination. And the gateways will respond with a DLCX response. So a very simplistic example, but gives you a good representation of what kind of communication is happening when using MGCP. We're going to walk through two configuration examples here. One will be for a residential gateway, and one will be for a trunking gateway. So stand by for one moment while I stage the lab, and we'll bring some equipment up here and walk you through the configuration of MGCP on a Cisco gateway. All right, residential gateway configuration with MGCP. I'm actually going to use a different piece of kit here because I happen to have an ideal configuration of modules. So we're going to use my, what is this, a 3725, 3825, I forget what this is. Shover, this is a 3725. And this is actually the gateway that I use here in the lab as my ISDN connection. So we got some FXO ports on it, we've got some FXS ports on it, and some PRI interfaces. I think I got a PRI in it. But anyway, let's get to the MGCP related configuration. Now keep in mind, like I said before, that Call Manager is in control. When you're doing MGCP, it's Call Manager, Call Manager, Call Manager. So this is software configuration. We're going to say CCM Manager MGCP. We're going to say MGCP to turn on MGCP. We're going to define the call agent, MGCP call agent 10.10.210 dot. I'm going to use 80. That's my call manager 9 box. Oh, and I almost forgot. Service type MGCP. There we go. Now, let's create a dial peer. Dial peer voice 77 pots port. Oops, I'm getting a little ahead of myself here. Application MGCP. I'm on old iOS. We're going to go service MGCP because application MGCP is a deprecated command. Thank you, Cisco. Service MGCP. I'm going to say port. What is my port here? 110. That's an FXS port. And now we're going to go dial peer voice 2 pots, not 2, 78 pots, service MGCP, and then I'm going to say port 111. Now, there are different MGCP package capabilities you can turn on, and we'll say exit MGCP package capability. I'm going to say line package, MGCP package capability. We'll say DTMF package. We'll use GM package, and I'm not going to go through what all of these do. You're certainly capable of looking those up on your own. Now, a lot of these are defaults. RTP package, and then we'll say MGCP default package, line package. So, again, most of that's not essential, but we're going to go ahead. Let's see here. What are we going to do next? Let's go Control Z and show MGCP. You'll see that the MGCP administrative state is up. The operational state is active. We've got our call agent defined. And, we're not connected or anything because I haven't programmed this on Call Manager. But really, that gives you, the residential gateway capabilities. So show CCM Manager. This is what you would look at to see if the MGCP device was registered with the call manager. Now my call manager is not programmed, so it's going to say registering. But if I were to add this to my call manager, in fact I will. Let's see. You have to give it config t IP domain name cisco.lab. MGCP uses fully qualified domain names, so gotta put that in there, make sure that it matches my call manager. Let me log into my call manager real quick. I'm not going to show you this, I'm just going to do it so that you can see from a gateway perspective how this would work. So device gateway, add new. This is a 3725, next. Running MGCP, next. Domain name is going to be the device name, so pstn gateway.cisco.lab. And we'll use my default call manager group. So on module and slot 1 is an NM2V, and we'll hit save. And then we're going to tell it what kind of cards are in it. I've got a VIC2 FXO and a VIC2 FXS. Save. Apply. And let's see if this thing comes into service. Show CCM manager. Registering with CM. Let me go ahead and bounce MGCP. No MGCP. MGCP. Show CCM manager. Let's see if we can actually get it to register. I haven't programmed the endpoint. Let me go ahead and program the endpoint here to put a directory number on it here. We'll program that port as a loop start trunk and hit save. Oh, that's right, I gotta put it in a device pool. Tenant DN 5000. Apply. Okay. Registered. So now we registered with Call Manager. So really it's that simple to set up MGCP as a residential gateway. Now, stand by. I'm going to clear this config out. We'll go back and we'll walk through setting up MGCP as a trunk or trunking gateway. And we'll configure it to interface with an ISDN PRI. And I'm actually going to do that on my 2811. So I'm going to hit the pause button and I'll be right back with you momentarily and we'll do the trunking gateway configuration. All right, everybody, we're back and we're on another gateway here at 2811. And we're going to configure trunk side MGCP here. We're going to have this thing controlling a PRI. So config T, whoops, let me click in the right window here. Config T, we're going to say CCM manager MGCP. We're going to go MGCP again. And one of the things I want to show you here is you can actually monkey with the port number here. So if you needed to, you could do that. In fact, the example that I'm following shows that being done. But I'm going to go ahead and take the defaults just because. We're going to say MGCP call agent 10.10.210.80. And then we're going to say controller T1000, which is my PRI module. We're going to say PRI group. And then we're going to say time slots. And I'm only going to configure the first 6 time slots here. Service MGCP. What do I got? Please configure network clock participate WIC 0. I must have been monkeying with timing here. Network clock participate WIC 0. And let's see if it lets me do it now. Yes, there we go. Must have been monkeying with timing earlier. So, really right there is all you need to do on the gateway. You know, we've defined who the call agent is. We've told the physical interface that it's going to use MGCP. So if you do a show run here, we'll jump down to where all of that code went. There's your controller T1, and yeah, I was playing with timing. I've got a clock source done, a little goofy there. But, you know, service MGCP. And then down here, we've turned on MGCP. Whoops, actually, I should show you all of that. We've turned on MGCP, and we've defined the call agent. So what I can do now, config T, IP
domain name cisco.lab. So I'm going to go into my call manager again, just like I did a few minutes ago here. We'll add a new gateway. This will be a 2811. And actually, you know what? I am going to show you this one, just because it's something you may end up doing from time to time. So let's see, 10, 10 to 10, 80. Let me pull this window down here, bring it down there, and we'll log into Call Manager. Proceed anyway. App admin. Cisco systems. All right, here we go. So I'm going to say device gateway, add new. I'm going to pick the model of hardware I'm using. This one's a 2811. I'm going to tell it that it's the MGCP protocol. For the domain name, it's going to be hq-rtr.cisco.lab. We'll pick our default CM group. Now, module in slot 1 was an NMHTV2. NMHTV2? No, I'm not on NMHTV2, am I? No, this is slot 0. Actually, you know, I don't remember how that thing's configured, so I'm going to walk over and look at it. Standby 1, and I'll be right. Alright, so HWIC 0 on slot 0. So we're going to go ahead and tell it we're using the motherboard. We'll hit save here. And it was subunit 0. VIC VWIC 2 MFTT1. That's what I'm using. So save. And then we'll go into the endpoint here and tell it it's a PRI. And give it a device pool. I'm not worried about all these details. But what I want to show you is show CCM. And you're going to see, again, registered to the call manager. Let me show you a couple other commands. Show CCM, not show CCM. So MGCP endpoint. This is going to list the MGCP controlled endpoints. And you can see here, interface T1000. And you can see the 6 DSOs that I provisioned and placed under MGCP control. What you need to be aware of is that MGCP is controlling not the device, but the ports on the device. So that's kind of the beginning to end what you need to know about MGCP. So we're going to stop there. And this concludes our Gateway Protocols conversations. We're going to do a video on voice call quality and QoS and just talking about why it's important and why you need it. Then we're going to briefly change gears and talk about fax. I know everybody's excited about faxing. You know, it's still feels like it's 1970, right? And we'll get into DTMF relay a little bit. But just some spit and polish types of topics that you'll need when dealing with voice gateways. And after that, we're going to dive straight into configuring Call Manager Express. So you thought you were done in iOS. You're not done in iOS yet, but it won't be long. But after all, iOS is the majority of what we're covering in cVoice. So thanks, guys. I appreciate you hanging in there. I know that this isn't the most exciting material in the world, but it is important for you, both from an exam perspective and day-to-day administration of these types of systems. So thanks for watching. Good luck with your studying, and I'll see you in the next video. In this module, we're going to talk about considerations for voice quality
And this is going to be really, really brief. I'm surprised that I'll be surprised anyway if we even spend more than like 5 minutes on this. So we want to talk about some of the conditions of concern dealing with maintaining quality in a voice over IP network. Now, this is not going to be a QoS lecture. We will be covering IP QoS in very granular detail later in this course. And actually, I kind of wish that it was still a separate course. Back when I did my CCVP, we had a whole class on QoS, and I think that I got a much better understanding of QoS technologies than you get today by blending it all into C-Voice. But I'll try to do my best when that time comes to give you a good, solid foundation to build on. So, but again, this is just a real summary conversation we're going to have. Some of the conditions of concern we have when transporting voice over an IP network, one of them is fidelity. What is the degree that we can accurately reproduce the audio from the source to the destination? We care about echo. Echo happens all the time. Most of the time, it is not perceptible to the human ear. But echo has a couple of components. We've got amplitude and we've got delay. And the greater those numbers are, the more perceptible echo becomes. So echo is definitely a consideration. Delay in itself, the amount of time it takes for packets to cross the voice network and arrive at their destination, plays into the quality of experience. As does jitter, which is simply variations in that delay. Packet loss is kind of obvious. If you're missing chunks of the data, you're going to have missing speech components. However, packet loss isn't really that big of a problem in voice networks because most of our networks are healthy enough if we've opted to run voice on them that it's just not happening that much. Side tone, hearing yourself, and this is something even as an instructor creating video content for you, it's important for me to be able to hear myself speak. It's important to hear my own side tone, and that's important on the telephone network too. If you were talking into a phone and weren't hearing your own voice back, you'd think something was wrong. It would just be an uncomfortable situation for you. So having that side tone is definitely a condition of concern for quality on a voice network. Background noise, or what we like to call comfort noise, is a consideration. And there are some techniques we can use to eliminate background noise, but they're not necessarily things you want to do. And we'll get into those more as we go along and talk about things. Latency or delay, there are two types of delay within a network that you're going to be concerned about. There's fixed delays, which are things like coding delays, packetization and serialization delays, and network propagation delays. How long it takes to get in a piece of gear and back out again. These are fixed things. They're always going to take about the same amount of time. You are going to have some variable delays, and those are mostly with regard to queuing and dejitter buffers and things along those lines. If I take a look at an example of a network here, I'm going to walk you through some things. So between a phone and a router, you're going to have, generally speaking, these aren't absolutes, generally speaking, you're going to have a fixed coder delay. When the router has to place the packet on, actually I'm getting ahead of myself. Packetization, or creating the packet inside the router, is going to typically have a fixed delay. Let's see if I can write this small. Packet, I'll just say packet. So packetization. We're going to have a queuing delay, which is variable. Whoops, V for variable. Because it really depends on how full your buffers are and how much queuing you're doing. You're going to have a serialization delay, which is typically fixed. We'll just put an S for serialization, which is how long it takes to put the bit on the wire. Then we're going to have, a variable delay through our WAN, or our wide area network. And, we're going to have a lot of the same kinds of things on the other end, but the one I want to talk about most importantly on the router, which is a fixed delay, is going to be your dejitter buffer. So you can see that in a network, there are a number of delays that are going to exist, and it's okay that they exist. It's the nature of physics. We're not going to change how long it takes for events to happen, but we need to understand what kind of an impact they have on our perceived voice quality. And we're going to talk about how much delay is too much. Between 0 and 150 milliseconds, we generally have an acceptable quality experience. Between 150 and 400 milliseconds, it's often acceptable. In fact, most times it's acceptable given a reasonable performance expectation. So as a systems administrator, when you're communicating to your business users what an experience is going to be, you need to communicate reasonable expectations. You need to set reasonable expectations with the business community so that they understand what is normal and what is not. And granted, different people will have different opinions on what is acceptable and what is not, but it's not your job to change it. It's your job to set the expectations. So as long as expectations are set, generally between 150 and 400 is okay. Above 400 milliseconds of delay, you're approaching darn near half a second there. That's generally unacceptable. So think about this in the context of internet connections and putting, teleworkers at home with IP phones. If you've got somebody with a high-speed cable modem connection and they're using the same internet service provider at home in the same city as you are at the office, generally your latency is going to be pretty low because you're on the same network, and it's going to be a pretty amazing experience. It's going to work really well. However, if they've got, they live rural, somewhere, out in, an hour outside of Cleveland, Ohio, where, there's, a gas station every 30 miles or something, and all they've got's a satellite internet connection, then obviously, latencies are going to impact them in a way that the more urban, lower latency user is going to have. So you have to really manage expectations. You get into this 400 milliseconds plus time with specific exception. This is generally not acceptable for voice performance. Echo cancelers. I mentioned before, echo is always there. It's created by impedance mismatches and audio, leaks and all these other things, and it's always there. But what makes echo a problem is when it becomes highly perceivable. If you don't notice it, it's not a problem. And like I said before, the things that create problems with echo is amplitude and delay. So the more delay there is and the greater the amplitude, the bigger of a problem you're going to have. Echo cancelers will be required when one-way path delay is greater than 25 milliseconds. And you'll find that with exception of the LAN maybe, you're going to have delays greater than 25 milliseconds. Just like when we're dealing with data networks, and I'm going to use fiber optics as an example here to compare. When I'm designing fiber optic networks and I'm looking at how many hops and how many jumpers and loss in patch cables, I'm calculating an optical budget. Well, the same thing is true in a voice network, and you're going to calculate what we call a delay budget. And here's an example of one delay budget. And these numbers are completely fictitious. Please don't hold me to them. If my coding delay is 20 milliseconds, and I said that was fixed, my packetization delay is 30 milliseconds fixed. Queuing and buffering, 10 milliseconds variable. Serialization, 5 milliseconds fixed. My network delay has some fixed and variable components. My dejitter buffer has a fixed delay. These numbers all add up. In this scenario, and this is a completely reasonable scenario for a network with a WAN, I've got 145 milliseconds of fixed delay plus, 30 milliseconds of variable delay. So I may be seeing 160 to 190 millisecond delays on this connection. Is that okay? Sure, it's okay. It's within that range of reasonable expectation of 150 to 400. Is it going to work pretty good? Yeah, I think it work pretty well as long as you set the expectations properly. So consider that you do need to calculate a delay budget. This comes into play more when you're going across wide area networks because on a LAN things are just happening so fast. It's not as big of an issue. And I talked before, echo cancelers, and I just kind of want to hit home on it here. Echo cancelers will be required when the one-way delay is greater than 25 milliseconds. So do you see what I'm showing you here about that? It's always going to be bigger than 25 milliseconds. I mean, it's just so infrequent that it's lower than that, you're going to have echo cancelers, in your network doing things. When we talk about voice and quality of service, there are a number of different factors that come into play and a number of nerd knobs we can tune and things that impact it. And this is just a skim level, so don't try to memorize all this stuff. You're going to consider things like header compression and how can I optimize bandwidth. You're going to think about things like frame relay traffic shaping and FRF12. You're going to think about PSTN fallback options, routing calls around congested links. You're going to think about prioritization and queuing of the IP RTP packets and IP to ATM class of service mappings. And we'll think of QoS at layer 3 and low latency queuing for voice packets to put them at the front of the queue. We'll talk about things like MLP, and we'll talk about things like RSVP, the Resource Reservation Protocol for QoS, which we'll talk about from a textbook perspective, but hardly anybody actually uses because everybody's DSCP based. But I digress. I'm going on a bit of a tangent there. So anyway, just keep in mind these things come into play when planning for and dealing with quality and performance and experience within a voice over IP network. And that's really where we're going to stop it. We're not really getting into any in-depth lectures here. But we wanted to give you a touch of things to come. And like I said before, we're going to go crazy deep into IP QoS, particularly layer 3 QoS and low latency queuing and class-based weighted fair queuing and all of those things later in the course. So hang on, it's a lot of fun and we'll geek out a little bit with it. So with that, I'm going to say thank you for watching. In the next video, we're going to talk about fax services. I know it's your favorite topic in the world. It's certainly one of mine. And I got my fingers crossed as I'm saying that. But anyway, thanks for watching. Good studying, and I'll see you soon. Welcome to Module 16, and we're going to be doing a deep dive of a technology that many engineers kind of run away from. In fact, I would say that most of the voice engineers I've worked with in the past have a bit of an aversion to this topic. And the topic we're talking about is fax. It seems like fax over IP, or just fax in general, is kind of shrouded in mystery. And I want to try to help explain some of the concepts of how fax actually works and make it less of a mystery. There's no reason you should shy away from configuration of fax or leveraging fax on an IP network with some of the traditional PSTN technologies. It works quite well. Sometimes it can be a bit confusing because of so many things going on, but let's try to do a deep dive and give you a good understanding of what's happening behind the scenes with fax so that you don't develop that same aversion that I've seen too many times, and I'm guilty of it myself. So what is this 1970? So fax has been around a long time. In fact, the origins of fax transport date back to the late 1800s. And it seems like, as much as technology has advanced, and we've got email, and we've got document scanners, and we've got optical character recognition and all kinds of other things available to us, we still leverage traditional facsimile technology where we take a picture of a document, turn it into a modulated signal, send it across to PN, and print it out. So traditional T.30 fax. So what is this 1970? Yeah, the answer to that question is, yeah, kind of. We're still leveraging this technology. And as much as you might wish it to go away, it's so widespread that it's not going to. So let's take a look at our voice over IP network shown here on the page. And this will give you an example of how fax might be integrated into your environment. And obviously there are variations on the theme here. But we've got an ATA device connected to a switch that has a fax machine attached. We have an analog gateway. That could be a VG224 or some other variation of an analog voice gateway. And we've got a fax connected to that. Obviously, we're going to have fax machines on the PSTN that are calling us and originating inbound connections. So these devices are going to exist on your network. Let's talk about the different ways we can utilize fax and how to make this an asset, not a challenge for you. We have three methodologies we use to move fax around an IP network. We have what's called fax relay, fax pass-through, and fax store and forward. Now, I'm going to talk about some of my favorite methodologies as we go through here, but we're really going to deep dive into how each of these work and give you an understanding of the fundamental concepts. I'm going to start with fax pass-through. And this isn't really where most people start. Most people start talking about fax relay, but I'm going to start with fax pass-through because it's the most like an audio stream. Basically, what you're dealing with is modulated fax data being passed within the audio codec as though it were voice data. Fax pass-through is going to use, or start anyway, by using the original configured codec, which obviously should be G711 in most cases for calls coming from the PSTN. Fax pass-through will then make changes to the codec and what we call upspeed the connection if necessary to enable G711 if by chance you're not using it. And the communications with fax pass-through is taking place entirely between the transmitting and receiving devices, or the originating and receiving devices, aka the fax machines. The voice gateways and the network are simply treating this as though it is audio. And the data, the modulated fax data tones that we've all heard, are going to be carried in the RTP packets. And you'll hear this referred to as both fax pass-through and modem pass-through. And really the difference, I don't even want to say the difference, modem pass-through encompasses a methodology to allow us to use modulated data for modems and fax machines, where fax pass-through is kind of fax specific. But let's keep going and let's talk about fax pass-through negotiation and how it works. So I mentioned that fax pass-through is sending data, modulated data, in the audio stream. Now, it's not entirely the same as a regular voice call in that we need to be able to manipulate the stream to disable VAD and disable EC, because these things are going to cause problems with transmission of the modulated data. So let's walk through this fast pass-through negotiation process. Again, the call is going to start out as a VoIP call, so a call between a gateway and a gateway. And you'll see this is our internal network here. We've got a fax machine connected to presumably an FXS port on a voice gateway, an IP network in the middle, another voice gateway, and another fax machine. So we start off with a VoIP call. And the faxes, because this is a VoIP call, the faxes are going to initially begin to exchange their T30 data or their T30 signaling from end to end. Now, what's going to happen is we're going to wait as the originating gateway, the gateway there on the left, we're going to wait to hear something called a SED tone. And that's a called terminal identification tone. And what it is it's a 2100 hertz tone that is signaling the beginning of a fax. So we're going to wait to hear the tone, and we're going to send an NSE, a named signaling event, message from the originating gateway to the destination gateway. The destination gateway is going to accept our NSE request, and what's basically going to happen here is we're going to change the codec. So if I originally started as G729 and I need to become G711, that's going to happen here. If I'm already G711 and I simply need to disable VAD and disable EC, that's going to happen here. So once that happens, you're going to have the voice call established, again, end-to-end or gateway to gateway, and that fax is going to just traverse in the RTP stream, so the modulated data. Now, how do we configure fax pass-through? It's actually really, really easy. Let me show you a gateway here in the lab. Let's see if I'm still connected here or if it timed out. Yep, we're still connected. All right, cool. If I go config T, I'm going to show you there's two ways to configure fax or modem pass-through on a Cisco router. You can either do it globally, or you can do it at a dial peer level. So, dial peer by dial peer. I prefer to do it globally, but you're welcome to do this however it makes sense in your environment. Let's talk about global first, and then we'll talk about dial peers. So if I wanted to do this globally, I'm going to go voice service VoIP, and then I'm going to type fax protocol ? You're going to see we've got Cisco, we've got none, we've got pass-through, and we've got T38. So we're going to do pass-through. And then if I hit a question mark, it's going to ask me for a codec. So I can say G711 EULA. Now, right there, we're done. This gateway, globally, will utilize fax pass-through using the G711 EULA codec. Now, remember I mentioned modem pass-through before? It's probably better if you don't do what I showed you. But instead, one small variation on the theme, let me go ahead and issue a no in front of that. And it's going to be modem pass-through NSE codec G711 EULA. It's going to have the same effect as enabling fax pass-through, but it's also going to give you modem pass-through capabilities. So globally, in fact, if I do a show run on this gateway, you're going to see up here in voice service VoIP, modem pass-through NSE codec G711 EULA. And we're done. I mean, that right there, when a fax call occurs, it will do pass-through behavior. So, I told you could also do it on a per dial peer basis. So what you could do, if you wanted to create a dial peer, actually, let's just look at my existing dial peers. Show run, pipe begin, dial peer voice. Let's see what dial peers I've got in here. Let's see, dial peer voice 100 VoIP. I like that one. Let's do it on that one. That's my normal pattern pointing to my call manager. So config T, dial peer voice 100 VoIP. I can go, again, either fax pass-through or modem pass-through NSE codec G711 EULA, and that dial peer will use modem pass-through. So, again, either global or specific to dial peers. You can configure it either as fax pass-through or modem pass-through, and my recommendation would be to go ahead and just do modem pass-through. And that's it. Obviously, this is something that needs to be done on both the sending and receiving gateways. And keep in mind, a receiving gateway might not be an iOS device. This might be a Cisco ATA, and you may have to follow different steps to enable pass-through, or and I'm not going to get into in this video, what devices support what fax types. I just want you to think about it as being a two-sided relationship or a peer-to-peer relationship. There's the PSTN gateway, but then there's also the gateway where your internal fax machine is connected, whatever device type that might be. So we've shown you an example here of PSTN gateway configuration for fax pass-through. I'm going to hit the pause button. We'll come back, do a little bit more lecture talking about the other fax modes, and we'll do some more demonstrations. All right, so I think we've talked about fax pass-through in enough detail that you understand the concepts at play. Now let's jump to the other extreme of what we call T.37 store and forward fax. And then finally, last, we'll cover the different types of fax relay capabilities. T37, or what we call store and forward fax, is pretty cool. And I have to admit that before creating this video, I had never configured it ever. I'd never seen it configured anywhere. And I think a lot of the reason for that is because it's just plain confusing. Looking at Cisco's documentation, I've seen so many iterations of how this can be done, and the examples really aren't that good. So I made it a point to spend a day in the lab setting this up and really getting a feel for how this works. And after doing that, I think it's really pretty cool. So I'm going to walk you through detailed directions on how to configure store and forward fax, or T37. Now we've got two different types of devices with T37. We have a device called an on-ramp gateway and an off-ramp gateway, and they can co-reside on the same hardware if you want them to. You could choose to use one or both types in your network. You've got on-ramp faxing, which takes a fax coming in and converts it to an email to be sent to an email recipient. So let's say you've got a Microsoft Exchange server or some other email server in-house, and you've got just a couple of fax numbers that are all going to come one place. Well, instead of putting a fax machine in your building, you can configure your gateway as what we call an on-ramp T37 gateway. And what's going to happen is when the fax call comes in, presumably on your PRI, it's going to present DNS for that destination, and the destination is the fax machine. Well, we're going to have some configuration logic in the gateway to send that call to what we call a MMOIP dial peer, or a multimedia over IP dial peer. Now what happens is Cisco created a TCL script, or a TCL script, that runs on the router that's actually going to take the fax, receive it, turn it into a TIFF file, and spin up an email and send you an email with this file attachment. So it's a do-it-yourself fax server for inbound fax. Now, if you want to configure off-ramp faxing, where it's the opposite direction, where you've got an email coming from your mail server to the gateway, you want to turn it into a fax and send it outbound, you can do that as well. I'm not going to cover that example here, but you can support both on the same gateway. I mentioned before that it's going to use TIFF file attachments, and that T37's purpose in life is to enable transmissions of fax over email, and we're going to do that using the SMTP protocol. And I said before, it's good for small quantities of users. You are going to end up creating a dial peer per account in most scenarios. There's a couple of ways to wildcard things, but we're going to keep it simple for this example. And this is a validated example. I've built this in my lab. So start here. I know some of the documentation, in fact, like all of the documentation I've seen out there on T37 is very convoluted and difficult to understand. They're talking about lots of different editions and versions of the TCL script, and it just make your brain in knots. So start with this example. So in this device, this is an example of an on-ramp gateway. We're going to configure in fact, give me 1 second, and we're going to switch to pen mode here. Pointer options, pen. Perfect. So what we've got is we're going to configure some information relative to the fax type. So we're going to obviously set our IP domain name on the device. We're going to say fax interface type, fax mail. And this command right here, depending what mode your router's in, may require you to do a reboot. So just be aware of that. And then we're going to say fax receive called subscriber $D $. So what I'm going to do is I'm actually going to capture some information from the call as it's placed and use this, if I choose, later in the process. I'm going to define my mail server. So 10.10.210.44. This happens to be a Linux server that I'm running with Exum on it as a mail transfer agent. And I can customize the subject line of the email that's going to come to me. I happen to make mine say Cisco T37 fax, but you can make it say you've got mail, or anything you want it to say there. And I've got a origin prefix, some postmaster information, some mail from. So what we've got here is we're going to have mail from this device, and then send mail from username, and we're actually going to put the phone number of the calling party in to the message, so you'll see who it's from. And then we set some return receipt commands. So that's all MTA configuration stuff. We're going to have to download and configure this TCL script. You can get this from Cisco.com. It's buried right now within the Call Manager Express downloads, but just search by version number, the 2.0.1.3, and you'll see the TCL script in the zip file. So I'm going to configure an application, service on fax, and I'm just calling my service on fax. That's a name that I can change if I want. And then we point it to the app fax mail on ramp TCL script, and the one I was using was the 2.0.1.3. Now we're going to configure two dial pairs, 1 and 2. We've got a POTS dial pair, and we've got a MMOIP dial pair. The POTS dial pair is doing the same thing as any other POTS dial pair you've ever used. And we're going to say in this example that what I've got happening here is we're going to say PSTN. I've got a fax. I don't even know how to draw a fax machine. There we go. That's a fax machine. We've got a fax machine out on the PSTN making a call. I've got my voice gateway and my network, blah. So there. What I've done is we're going to be sending a DNS of 614.555.1212. So when that DNS comes in from the PSTN to our voice gateway, we're going to match the incoming called number on the dial pair. So we've selected a dial pair. That dial pair is pointing to the on fax service, and we've got an information type of fax defined. And obviously we support direct inward dial so that we can route the next hop without prompting 4 digits. The next hop is going to be that same destination pattern, 614-555-1212. And what's cool here is we've got this service fax on VC on-ramp app outbound. Just type it the way you see it there. And we've defined the information type as fax, and we've created a session target. So josh@howtonetwork.com. And that is going to be the email address that I'm trying to send the email to. And the rest of it, you can look those commands up if you want to know what they have to do. They're tweaks and tunes and nerd knobs. But this is really cool. So what's going to happen is the call is going to come in across the PSTN, hit our gateway, present that DNS, match the inbound dial peer, match the outbound dial peer. The gateway is then going to receive the fax, turn it into a TIFF file, and attach that MIME encoded via SMTP to, see if I can draw, there you go, to my mail server. And it's going to show up in my inbox. I've done it. It works. It's actually really cool. So I would recommend that you consider this as a possibility if you have 1 or 2 numbers that are fax machines or that are fax numbers inbound and you'd like to send it to email. You don't need to go buy, a $10,000 third-party fax over IP server to get some basic fax to email. Now, like I said before, this is an example of an on-ramp gateway. This is going to take a fax coming in and turn it into an email. It is not going to work in reverse. You can make it work in reverse. Go to cisco.com, pull up the docs, and read about off-ramp gateways. But I wanted to really show you a good working model because every doc that I looked at had this kind of sort of working, but not making sense, and it was a pain in the butt to debug, and I just couldn't figure out what was going on. But this sample does work. And I did this on a Cisco 3725, so just as a frame of reference. So that covers store and forward fax, T37. We're going to get into fax relay in the next slides, and we'll talk about both Cisco fax relay and T38 fax relay. So stand by, and we're going to change gears and jump into the fax relay conversation. Fax relay is the final option that you're going to see as a method for moving fax around your IP network. And fax relay is going to be done in one of 2 styles, either Cisco fax relay or T38 fax relay. So Cisco fax relay, and in fact, before I go that far, let's talk about what fax relay is. So when we went through the example of fax pass-through, we talked about how the audio would continue, using G711 to the endpoint, to the endpoint gateway or the destination gateway, and it was an audio stream. And then when we talked about the store and forward T37, we were talking about audio terminating at the gateway and becoming data in the form of an email. Well, fax relay is kind of neither of those, but it's the missing link, the thing that you probably expected in the beginning, and that's data transport of fax over the IP network to the destination gateway. So Cisco fax relay is proprietary, and T38 fax relay is standards-based, and it's an ITU-T-based standard. And they both do the same thing. T38 obviously is what we prefer nowadays, but there are certain pieces of equipment that you may run into that only support one or the other, so you'll need to be fluent on how both are used. Looking at the same network as before, we talk about Cisco fax relay and negotiation. When the initial call is made, the T30 signaling hits the voice gateway. Again, we're going to cut through an RTP path to the destination voice gateway, and we've got the T30 happening end to end. So just like before, we wait for that SED tone to occur, and you remember that was the called terminal identification tone, that 2100 hertz tone. And what's going to happen is when the SED tone is heard, the voice gateway is going to listen for the disk message sent by the fax, and we're going to do what's called a fax relay switchover. Now with Cisco Fax Relay, we're going to do a fax relay switchover, and we're going to tell the destination voice gateway that we're doing this fax relay switchover, and it's going to send us a codec acknowledgement. Both voice gateways are going to do a codec download, and essentially what's happening is that we're going to change parameters like before necessary to support fax. So turning off VAD, playing with jitter buffers, echo cancellation, etc. So what's happening is we're doing the codec download. We are then going to send an indication that the codec download is done and get an acknowledgement, and the fax relay session is established. So the T30 analog fax signals that we're getting from the PSTN are demodulated by the DSP on the gateway. So that's the voice gateway on the left. Packetized and sent across the voice network as data. And then the destination voice gateway is going to remodulate those signals and send them to the destination fax machine as T30. So a little bit different, but you can see certainly an efficient way of doing things. Now this is Cisco Fax Relay. Let me show you T38 for both H.323 and SIP, which again is really strikingly similar to Cisco Fax Relay. This is just a standard. We start with the T38 or the T30 session, our voice call, and T30 at the other end. Again, we wait for our sed tone and our disk message. With H.323, we send a mode request from the first voice gateway to the terminating voice gateway. We get a mode request acknowledgement. We then close the VoIP session and open our T38 channel. So that's our data stream. And then we have the T38 data stream, and we're done. So again, the originating voice gateway and the terminating voice gateway are demodulating and remodulating, respectively, this signal for transport across the network. So guess what codec you need to use on your network? It doesn't freaking matter anymore. So this is the beauty. If you've got sites that are using low bitrate codecs, like G729, you can still send fax across those links. Now with the SIP T38 fax relay, you're going to see the same thing as you did with H.323. You're going to have the T30 signaling, the voice call, your RTP stream between the endpoints. You're going to do the sed tone and the disk message, but this time we're going to send a SIP invite, indicating that we're going to use T38 features within the SDP message to the destination voice gateway or the terminating voice gateway. It's going to send us back a 200 OK. We're going to then send an acknowledgement and nail up the T38 data streams between the two voice gateways. So pretty much the same kind of thing as 323. Now, when we talk about configuring fax relay, I'm actually going to walk you through an interactive tour here. We're not actually going to configure it, but I'm going to show you the flags that you're going to throw. This is so trivially simple to set up that you're going to have no problem with this. So stand by while I bring up my putty session, and we will go into this fax relay configuration. All right, so we've got our putty session here. We'll go ahead and log into my PSTN gateway. And let me do a show run. I believe we've still got some pass-through configuration stuff set. Yeah, so we've still got our modem pass-through configured on this gateway. We'll go ahead and turn that off. We'll say voice service VoIP, no modem pass-through. All right, so for T38 and Cisco Fax Relay, what we're going to do in the same place here, fax protocol, and you've got options for Cisco or T38. If I say Cisco, I hit enter, and now I've told it fax relay Cisco. Pretty easy, huh? Now if I go T38, we have a few more options we need to consider here. If we're doing T38, we're going to say NSE to use Cisco's NSEs to signal the T38 mode switch. And then we've got options for fallback. If we can't negotiate T38, what would we fall back to? And then we've got options for redundancies. So let's go ahead and we'll say fallback, and then we'll say pass-through G711 ULAW, and then enter. Other things I could do is ls redundancy, and I can set a redundancy level. And depending on the redundancy level that I set, we're going to add additional data information so that if a packet is lost, we can recreate the data stream or the fax stream. So basically, this is a kind of error correction. So you can set ls redundancy values of 0 through 5, HS redundancy levels of 0 through 2. Enter. So show run. We'll show you what we've got going on here. So nothing crazy there. Now it appears, and I'm not sure why this is, but it appears that when you're doing the LS and HS redundancy, that you fall back to Cisco fax pass-through. So I'm not sure if that's a limitation or what. I'd kind of like to fall back to G711, but again, whatever. Really, that's all you're doing. And like I showed you before, you can do this either globally or at the dial peer level. I always try to do it globally unless there's a reason that I can't, and I haven't found a reason yet that I can't. So those are my standards. But anyway, we've talked about what you're going to need to know and understand to work with fax within a Cisco voice environment. You're going to see it. It's just the way it is. Please don't have an aversion to fax. Don't run screaming because, oh, I don't want to set up fax because it's weird and I don't know how it works. I hear that too often, and really it doesn't have to be that way. Are there a few mysteries to it? Well, there can be until you get used to dealing with fax on a network, but once you understand the ground rules, it's not so bad. So pass-through, relay, and T37 store and forward, those are your options. Go ahead and spend some time labbing this up for yourself. This is one of those things that I'd recommend. Take it to the next level. Go ahead and play with T37. Set up a mail server in a virtual machine and, actually route some of these things. I actually did that here. One of the notes, actually, that I'm going to share with you for the T37 stuff that tripped me up a little bit, and it may be possible to solve, but I didn't spend the time on it because it's not typical to what we'll be deploying in the field. But I had to use a PRI interface on my router for the incoming DNS. I tried to use an FXS port, and I had problems matching the outbound dial peer leg. And it probably had something to do with DNS and the way that it's detecting the destination I'm calling, but I didn't spend any time trying to figure it out. We just ran it on the PRI. But a lot of fun stuff here. And hopefully this will give you the foundation you need to do fax in a Cisco voice environment. So with that, I want to say thanks for watching. I know this has been a long one. I promise I try to keep the others down. I don't like letting things run 30 minutes. We try to target the 10-minute per video, but this is one that I think was well worth it. And hopefully you feel comfortable with the knowledge of fax now that you didn't have before. So I'll see you guys in the next video. This pretty much wraps up this section, actually. And we're going to get into configuring Call Manager Express and walk through building a basic CME environment, and we'll register some phones and we'll create a dial plan, and it'll kind of be end-to-end, soup to nuts, a working CME environment. So I'll see you in the next video, and we'll start working on Call Manager Express, or Unified CME. In this module, we're going to talk about Cisco Unified Communications Manager Express, or CUCME, or CME as I'm going to call it. CME is something that you're going to find you either like it a lot or you hate it a lot. Personally, I like CME. I think that it fills an interesting niche and it does what it does well. That said, I don't think it is a replacement for Call Manager, but there are certain environments where it fits really well. So let's jump right in and talk about what is Cisco Unified Communications Manager Express, and we'll build some foundations that we're going to use when we begin configuring CME in the next video. And I'm actually going to walk you through a configuration of the basic parameters you need to understand about Call Manager Express. CME is or can be an all-in-one box solution, and it's iOS based, so that means this runs on a router. If you look at the network diagram that I've got here, I've got An IP phone, a switch, what looks like a router, but I'm calling it a PBX/voice gateway, and a PSTN connection. This is our CME, our Call Manager Express. So CME began as something Cisco called ITS, or IP Telephony Services, or what we now refer to as telephony. Let's see if I can spell here. Telephony service, VICE, within the router configuration. So you're going to see a lot of references to telephony services as we go through CME. It supports as a conceptual product or a device, and I'm actually expanding a little bit beyond the role of CME, the software, to talk about the device. The device can be responsible for call processing, which is the CME or the telephony services part of things. It can be your voice gateway. It can be an iOS firewall if the feature pack on the router that you have supports that. Obviously, it's a router, so it can handle communications for WAN connections and LAN connections and routing between subnets and all of the other stuff that a router can do. It can be a DHCP server, etc. With an additional module, what we call a CUE, or a Cisco Unity Express module, it can be a voicemail and an auto attendant platform. In fact, the auto attendant capabilities of CUE are very cool. The same script editor and much of the same script logic that we utilize in a larger product called Unified Contact Center Express is the same as what we use within CME, or within CUE. So it's an all-in-one box solution. This is perfect for a single site solution. If I've got a branch office with 20 or 30 phones that are not frequently changing their configuration, I'm not always adding or deleting phones or changing directory numbers. It's kind of a static environment. CME is fantastic. You can spin up a router. It can be that all-in-one device for the site. And in fact, I show a switch in the diagram here, but you guys know that there are modules that can go in the various models of Cisco routers that are switch modules, ether switches, etc. So we can, basically make this one box on-prem, plug your phones into it, and walk away. So pretty cool, interesting niche product. Now, I said that it fits the role of a single site solution really well. However, you can interconnect multiple sites. And I'm going to show you that here on the next slide. This is one example of a multi-site deployment for CME. So if I look at each location would have IP phones and a CME. And I'm assuming that we've got a switch inside the router here. So we've got 3 sites, and they've each got a CME. They've got connectivity to the PSTN, which could be an ISDN PRI. They could be POTS lines, FXO interfaces. We've got various models of IP phones. Maybe there's 20 phones here, maybe there's 5 phones here, and maybe there's 50 phones here. One or more of these could have a Cisco Unity Express module in it, and they're connected via a common IP WAN. So the CME at one location will be responsible for the registration and call processing of phones at that location, and will play no role in the call processing of phones at other locations. So it's very much site-centric. Now, I can trunk these gateways together using traditional means, because after all, they are just voice gateways. So I could build, for example, an H.323 trunk between the gateways simply by using VoIP dial peers, and allow the phones within one location to call phones within another location. So it's different than Call Manager, where you're going to put a device centrally and manage it, manage remote sites from it, and that we're going to distribute these devices. So that's a really great textbook multi-site deployment example. You can also use a VPIM for some voicemail internetworking as well. And I'm not going to get into VPIM in too great a detail here, but it is something that's possible. When we talk about supported hardware, I want to say this is not an exhaustive list. but it gives you a representative sampling of the types of hardware that you can run Cisco CME on. And CME is versioned, and you'll find that different versions of hardware with different DRAM and flash requirements can support different IOSs, which then produce, version whatever of CME. Looking at a small site, a Cisco 1861, it's a fairly inexpensive router. I can support 15 phones with CME. If I'm using perhaps a 3825, I'm at 175 phones. Or I can really scale this thing crazy huge in a 3945E with 450 phones. Now, if I were designing a 250 or higher endpoint system, personally, I would probably be persuading that customer to use Call Manager. But you can do it with CME. Supported endpoints. A lot of the phones that are supported with Call Manager are also supported by CME, and this is just a brief list. The 7900 series phones, the 9951 71s, a lot of the 6900 phones, they're all supported. Or I shouldn't say they're all supported. Many of them are supported by CME. And check the data sheet for the version of CME you're deploying, as this is not a complete list. Finally, I want to tell you that CME can support both SIP and skinny devices. They are configured differently. Whoops, pushing the arrow the wrong direction there. When you're using skinny devices, we define these as ePhones, and their directory numbers are ePhone DNs. And when we're configuring SIP devices, we're going to use voice register pools. But I'll get into more of that as we actually go through an example of configuring a CME. I'm going to take a 2811, I think, that I've got nearby, and stage it up here. In the next video, we're actually going to do a walkthrough and configure basic CME functions and features within that device. So for now, I'm going to leave this alone and say thanks for watching. This is your intro to CME. And hang on for the next video. It's going to be a lab, and we'll walk you through base platform configuration. So for now, good luck with your studying, and I'll see you soon. In this module, we're going to go through the exercise of configuring a basic Cisco Unified Communications Manager Express or Call Manager Express system. Now, we talked in the previous videos about CME fundamentals and explained to you the role that CME plays as a product and the niches where it fits. And I wanted to walk through at least a reasonably typical installation of CME, just to show you exactly what kind of configuration is necessary and possible with the product. A lot of engineers that I've worked with in the past have considered CME to be a bit of a toy, and I want to respond to that with Ferrari is a bit of a toy as well. So I wouldn't necessarily stereotype the product in a non-serious way, because it can really do some pretty amazing things. We're going to go ahead and spend most of this video inside of a terminal window and do some configuration of CME and walk through, what I would say that a typical config looks like, and actually register some phones and place some calls. So this router that we're in, this is one of my 2911s that we've used before. And we've got it configured with an ISDN PRI. In fact, it's pretty much serving the role right now of just a traditional voice gateway. If I do a show dial peer voice summary, you're going to see that I've got a couple of dial peers built, 101 and 100. Both are POTS dial peers, and they're pointing to a trunk group that's got a PRI in it. And if I do a show ISDN status, you're going to see that the PRI is in service. We've got multiple frame established, etc. So it's a normal voice gateway right now. We're going to layer CME on top of this. I'm going to start out by walking you through some of the basic CME configuration. Now, there are two different methods of configuring phones in CME, and I'm going to approach them separately. I'm going to walk you through an all skinny example, and then I'll come back and teach you what you need to understand about SIP. Since really, if you're going to support skinny endpoints and SIP endpoints on a CME, it's almost like configuring two completely separate systems. I don't think that that was the most fantastic design that Cisco could come up with, but it is what it is, and we'll walk through it. So it all starts with telephony services. In fact, you'll see a reference point from time to time called ITS, and ITS stands for IP Telephony Service. And it was really the service functionality that ultimately turned into the product Call Manager Express. Telephony service is a menu accessed from the config T menu, and there's a lot of things we can do under telephony service relative to building a PBX. CME, like I said, it's a toy. There's a lot of really cool things you can do with it. It can support auto registration of devices or not. I'm not going to show you auto registration in this example. You can look that up on your own, but we will walk through some manual configuration. In fact, the first thing I'm going to do is say no auto reg ephone. So no auto reg ephone under telephony services is going to disable that auto registration. Now, with CME, you're going to define what's called an ephone and an ephone DN. Now, these are concepts relative to the skinny configuration. You can have a given number or a maximum license number as well as a platform maximum of ePhones and ePhone DNs. Now, I said this is a 2911. My max ePhones on this platform are 42, as it's configured. We're going to go ahead and say max ePhones 10 for our configuration. We can do a max DN of up to 144 on this platform. I'm going to go ahead and select 20. Now that I've configured the max ePhones and max DNs, I need to configure the IP address where skinny phones are going to register to. And so this is a combination. This is the IP address and the port. Like I said, this is configured like a typical router or a voice gateway, so we've already got IP addresses on the interfaces. I'm going to say IP source address 10.10.210.1 port 2000. I'm going to configure what we call a system message. System message is a CME feature that lets you, like it says, display a system message at the bottom of the phone. Sometimes this will be like the name of a business or your company name. I'm going to put let's see here, system message how to network.com. Seems like a good example there. Files that configure phones, the XML-based configuration files, just like on Call Manager, exist with CME because obviously the phone doesn't know the difference really from whether it's registered to a CME or whether it's registered to a Call Manager. It's just a skinny device, speaking its language. You can store these config files a couple of different places. In fact, I want to show you CNF. You can store them location, either to the default location, which is called system, and I don't like to do that. You can store them to an external TFTP server, which may make sense in some environments, but for me, I'm going to store them in Flash. So we're going to say CNF location Flash. Now, for each model phone that I want to register to my CME, I need to define a load, a phone load. We do this in Call Manager with device defaults. We're going to do it in CME with a command called load. Now, what we've got here, and I'll paste two of these in, and then I'll walk you through exactly what they're doing. So we've got a 7960 or 7940 image and a 7961 image. The 7940s and 60s use the same firmware. So what we're doing here is we're saying load, we're specifying the model number, and then we're specifying the file name without the file extension of the file as it sits on our TFTP server. Now what I should tell you is, and we'll do it here in a moment, I haven't done it yet, but you need to upload a bunch of different files to the router to enable full CME capabilities. Now CME itself, the feature set is just a part of the router, but there's a web interface you can enable, and I'm not going to go into the web interface at this point. Although we do talk about that a little bit in the CCNA voice videos. There is, phone loads, ringtones, all those kinds of things. You'll have to put them on the router. They're a download from Cisco.com, etc. So we'll show you what some of those look like and how I've set my system up. So we specified the loads. We're going to go ahead and define a time zone, time-zone, and depending where you're at, you can pick your time zone. I am in Eastern Time in the United States. Let me find that. That is 13. So we're going to say time zone 13 for me, lucky number 13. Now, CME, just like Call Manager, can support conference calls. So we're going to define the max number of conferences as between 1 and 16. I'm going to just say 4. Now, if you were doing web administration and had the GUI, there's a command called web admin. I'm not going to finish setting it up, but I want to show you it's there. Whoops, hang on. Web space admin. And you would go in here and define a customer administrator, system administrator, etc. Like I said, I'm not playing with the GUI here, so we're just going to stick to the CLI stuff. But I did want you to understand that, because you'll try to set it up and you'll be like, why can't I authenticate? I've created a user account. And I want you to know that there's a separate account. Call transfers are supported, and you can do a couple of different types of call transfers. Let's go transfer method. We're going to go with a transfer system. And you can either do full blind, full consult, or local consult. I'm going to configure mine as a full consult system. And the descriptions for the different types of conferencing are right there on your screen. Finally, I need to create my XML configuration files. And I'm going to do that pretty much every time I go into telephony services and make a change. So I'm going to say create CNF files and hit enter. And it's going to take a few seconds to do that. I mean, I'm spinning up XML configuration files like crazy. And once this is ready, it'll give me a prompt again. We'll go through. I'm going to show you all the files. I'm going to show you how to do some TFTP bindings. And I'm going to show you how to configure the devices themselves. And at that point, we'll be able to power some switch ports up and register some phones and make some calls. So it really is going to start with, and I can talk about this while the TFTP, or I'm sorry, while the config files are generating. There's a bunch of files that you're going to go on the TFTP server on this device. I am using, like I said before, 7961s and 7940s. In this example, I've actually got a 7985 as well, a video phone that I might register up and show you. And for any phone you put on your CME, just like on Call Manager, you're going to want to define a phone load. Now, I'm going to do it for the 40 and 61. I'm not going to mess with it for the 7985 because it's already running a compatible phone load. But I'm going to show you here that we've got a whole bunch of different commands. And I'm going to paste them in, and then I'm going to walk you through exactly what they're doing so that you have a good understanding of how to use them. So we're going to Control Z, and I'm going to go Config T, and I'm going to paste a bunch of TFTP server lines in here. And once they're pasted, we're going to do a show run pipe include TFTP. And let me show you what we've got going on here. So TFTP server flash /phone /7940 /p 003080102000.bin alias, and then the file name again. What's happening here is I have chosen to organize my flash instead of just dumping everything in the root folder. Hey, if you want to dump everything in the root folder, have at it. I like to be a little more organized than that. So I'm basically defining my path and then creating an alias within the TFTP server so that when the phone requests the file, the TFTP server knows where to find it. So we've got these 4 files are necessary for firmware for the 7940. All of these files are necessary for the 7961. So we've got all those TFTP server bindings in there now. One more thing I'm going to show you before we try to power some phones up and register some endpoints and place some calls, and that is ePhones and ePhone DNs. So in CME, directory numbers have an object of configuration that you need to do. And they're called ePhone DNs. And they're really simple to set up at a basic level. I'm going to drop 4 of them in right now and just show you kind of what's going on. We've got ePhone DN1 dual line. And what dual line means is I've got one button that can be used, but I can have
2 calls on it. Now you can, if you leave off dual line, it's going to be a single, which is 1 call, so you can't have call waiting. Some versions of CME support something called octo line, etc. That gives you 8, but we're going to do dual line on these phones. Now you'll see I pasted them in there. ePhone 1 dual line number 1000, ePhone DN2 dual line number 2000, then 3 and 4 3000 and 4000. Those are my extensions. Lots of other things you can configure on ePhone DNs. They're a little beyond the scope of the CCNP voice, but you should play with them. In fact, let me hit a question mark and show you some of the things you can do. We've got call forwarding parameters, caller ID stuff. We've got ePhone DN templates that you can build and leverage. Intercoms, hunt stops for hunt groups, music on hold settings. It's a full-blown PBX. So if you can think of the feature, it's probably in here, within reason. So lots of things you can do with the DN. For now, I'm just going to keep it at number and keep it simple. Now that I've done ePhone DN, I need to configure, config T, my ePhone. And I'm going to do this one at a time, and I'm going to show you what's going on. We're going to say ePhone 1, and then I'm going to say MAC address, and I'm going to drop in the MAC address of one of my 7961s, and then I'm going to say type 7961. And in fact, if I hit the question mark after type, this will give you an idea of all the different model numbers supported on the CME. Now that I've done type, I'm going to say button 1:1. Now what's happening here is when I say button 1:1, the first digit is the button on the phone, button number 1. The second digit is the ePhone DN. So extension 1000, which was ePhone DN1, is going to appear on the first button of this phone. Now, just like I did that, I'll paste in another 7961. We're going to call him ePhone 2 with exactly the same settings, except he has button 1:2. So he'll have directory number 2000. I'm going to paste 2 more devices in. One of them is a 7940 and the other is a 7985. But again, the exact same configuration process is taking place on all of these. So we've created ePhone DNs. We've created ePhones. In fact, if I do a show telephony service, good show command here, we can see all of the configuration parameters as they're currently set up for telephony services. You can look at how QoS tags are going to happen. We can see the loads I've specified, the max ePhones, max DNs, any locale settings, conferencing, DSPs, SRST, pretty much everything telephony service related. And there's a lot of other things you can look at under show telephony service. You can get into show telephony service, TFTP bindings, or ePhone DN, or dial peer. You can just look at lots of different types of things. So play around in there a little bit and see what's available to you. So we've configured telephony services. We've configured the TFTP server. We've created our ePhone DNs and our ePhones. Let me show you the file system, and we'll go ahead and register some devices. And actually, I'm going to go like that to the top level. Okay, I'm in the root of Flash. dir. I've got a folder called GUI, and that's where my CME GUI files are at. I've got a music on hold file in the root. That's just where I usually put it. I've got a folder called phone, which contains all of my firmwares and in subdirectories. I've got a folder called ringtones. Let me show you ringtones. Tones, dir. Lots of different wave files out there that are available for ringtones, and obviously they're all specified in the ringlist.xml file. In fact, if I want to show you that more, ringlist.xml, you can see the ringtones that are going to be advertised to my phones. And I'm using the default set here. And really, it's set up, it's ready to go. Let's go ahead and get some phones on this here. So we're going to, in fact, let me show you a little bit more about what's going on the router, and we'll register our phones up. We've got a DHCP pool set up for phones. You've done those before, so I'm not going to go over that in detail. Option 150 is pointing to the IP address of our Call Manager Express here. We've got our voice service VoIP configured, just like on a voice gateway, and our T38, which, not part of this exercise here. We've got voice class codec stuff. We've got a T1 with 6 time slots set up. Actually, this is a PRI. You can see the PRI group there. We've got all of our IP configuration. We've got, here's all those TFTP server definitions we put in. You see our voice port for the PRI. You see the 2 dial peers that I've got configured, and then the telephony service stuff. We've just done that, so I think you've got a good handle on that.
our ePhone DNs and our ePhones. And, that's really the router config. So if I want to go ahead, in fact, give me one moment while I connect into a switch here, my 3550, and bring some ports into service, and we'll watch some phones come up and register on the CME. So one moment. Interface FAO2, no shutdown. And FAO3, no shutdown. And FAO7, no shutdown. And FAO9, no shutdown. All right, so I brought some ports into service, and I'm going to show you a command, show ePhone registered, and it's going to show us phones that have registered to our CME. Now, right now, we've got nothing. And you're going to start seeing some messages of devices that register. In fact, the first one there was my 7985. It actually registered so fast because it's not a PoE device, so it was already powered on. So we just had to wait a few seconds for the spanning tree stuff to happen. We've got other phones coming up. It looks like the 7940 is in service. That's the second one you see there. And my 7961s are booting right now. It won't take them very long. I want you to remember the IP phone boot process. Again, we covered this in detail in the CCNA Voice Cert Exam series. But, the phone's coming up. It's requesting config files, or I should say it's requesting ITL files, trustless stuff, and CTL files based on, if it's been in a security by default system before. It's going to then, start asking for config files and, based on the MAC address of the device. And, we're going to give it ultimately either a specific config file or a generic XML default config file. And it's going to tell us what phone load or what firmware load to use. And, if it's not what we have, we're going to reboot. And, the next time we boot, we're going to ask for the files and fetch them and download them and run a patch and boot a couple times and finish that process. And, then we'll be up and in service. These I've already done that too, so you aren't going to have to wait on that process to happen. There's one of the 7961s, and the other one will happen here momentarily. And then we'll go ahead and we'll make some test calls, and we'll make a call to the PSTN, and that'll be it for Skinny on Call Manager Express. Just about there. And it's registering now, and it is registered. So that command I showed you earlier, show ePhone registered. Now you're going to see some pretty nice output there for the 4 phones that have registered. So you can see the MAC addresses, and it's registered in Skinny. You're getting the IP address of the device. You're seeing the model number. You're seeing how the DNs are configured on the buttons and the codecs, and it's pretty straightforward. So 4 phones are up. Let's make a test call. Debug ISDN Q931. I'm going to pick up an IP phone. There's my speakerphone there. I'm going to press 9, and then 555-1212. We've matched a dial peer. We've placed an outbound call. The calling party is extension 1000, and you can hear my test set ringing in the background. I'm going to go ahead and take it off hook and answer the call. And testing 1, 2, 3. It's kind of hard to hear there because that's a piece of test equipment. Let me try this here. Testing 1, 2, 3. 1, 2, 3. So we've got a phone call up. And, if I want to do, show voice call summary, you're going to see that call is connected and in service. Oddly enough, this is my ePhone. So we can see I've got a G711 call up, and, life is good. Everything's working just the way it should. I hung it up. There's our ISDN terminating the call, and we're done. So really straightforward, really easy to use. I can do some phone-to-phone calls right now. We'll go ahead and we'll call extension 3000. There's a 7961 calling a 7940. I can answer it. Hello, hello, hello. I can press the conference button and do a conference call and any of the other typical PBX features that you'd be using. I'm going to stop right here and push the pause button. I'm going to spin up some config and show you the final piece of CME that I want to make sure we go over from a configuration standpoint. And we're going to set up a endpoint as a SIP device using the Voice Register Global. And then we're going to wrap up this video. We're going to circle back, talk about troubleshooting in the next video, and that'll be it for CME. So stand by one while I spin this up in another window, and I'll be right back with you. All right, we're ready to walk through some SIP device configuration on CME. It took me a few more minutes, actually it took me like an hour and a half, longer than I expected to get prepped up and staged for this. I ended up actually uploading some additional firmware. I realized that I didn't have any available phones that already had a SIP image on them. So I went ahead and took one of the 7961s that I was using and converted it from skinny to SIP. So that's been taken care of. It's out of the way, and things have been tested. So let's go ahead and deploy some configuration necessary to run SIP phones on Unified Communications Manager Express. The first thing I want you to understand is you're practically configuring a completely different phone system. So where skinny phones, the core stuff is all about telephony services, and then the phones and DNs are ePhones and ePhone DNs. Well, if you're doing SIP, throw that all away because it's completely different. To set up skinny endpoints, and they can coexist, but to set up skinny endpoints on CME, you're going to start out with voice service VoIP, and we're going to say allow connections SIP to SIP. So obviously, we're going to have SIP endpoints, and perhaps they're going to hit some SIP dial peers, maybe. So we'll go ahead and we'll set that up. We're going to say SIP, and we're going to say registrar server. So we're going to be the registrar server for these endpoints. And I'm going to say bind all source interface fast Ethernet 00.30. So SIP is turned on, and we've set up our registrar server, and we've got it bound to FAOO.30 for median signaling. We're going to type voice register global. This is the equivalent of telephony services. So voice register global, and we're going to say mode CME source address 10.10.210.1 port 5060. So again, this is our SIP port. We're going to say load 7961 term 61.default. We'll go ahead and do max pool. This is the equivalent of the max ePhone entry. So max pool 10, that'll be more than enough. And max DN 10, again, more than enough for the one device. We're going to set some localization settings up, and I'm going to say user locale US and network locale US. We're going to set some time and date stuff here. Everybody seems to want a date format of 12-hour. I'm sorry, a time format of 12-hour. We'll do that in a second. A date format where I'm at in the world of month, day, year. And in fact, you can see all the different options here, day, month, year. And pretty much there's an option for whatever whatever they're doing in your neck of the world. So we've got the date format set. I'm going to say time format 12 hours or 24. I'm going to go 12 hours on mine. And I'm going to say time zone. I'm going to be time zone 12, but we'll show you there are 56 different choices. So time zone 12 for me here in the Eastern time zone. SIP phones, unlike skinny phones, get their time directly from an NTP server. SIP does not provide time sync to them, so we're going to specify an NTP server for them to use. 10.10.210.1. I happen to be running an NTP server on this router. It's an NTP master. The next thing we're going to do is define our TFTP path and some config file stuff. So we'll say TFTP path, and then just like CME, just like skinny, I'm spelling something wrong here. TFTP, I left the mode I was in. Voice register global. That's what I meant to do there. And actually, I made a mistake on the NTP server. I need a dash there. There we go. That's why it exited the mode. I ended up setting it for the router, not for voice register global. So TFTP path, and then I'll show you. You've got flash. You can put it to a card, on a slot, or again TFTP. I'm going to say flash colon. We'll just let it live in the root, and I'm going to say file text. This is going to make my config files ASCII format so that they're readable. And then the equivalent of create CNF files for skinny. For SIP, we're going to say create profile. And again, I'm going to do create profile a whole bunch. So we'll do it now just to show you how, and then we'll do it after we program our phones. To program a directory number, which is the equivalent of an ePhone DN, it's going to be a voice register DN, and I'll pick number 1. And we're going to say number 6000. Seems like a good choice. And exit. Now I'm going to define the equivalent of the ePhone, which we call a voice register pool. Voice register pool. And I'm going to call it 1. I'm going to do an ID, and you can either use the IP address, MAC address, etc. I'm going to go ahead and use my MAC address because it's convenient for me. If you have a static IP on your phone, maybe you'd want to use that. There's my MAC address. I'm going to say type 7961 and DTMF relay, RTP, NTE. And you've got, and I'll show you the options here. You've got SIP notify, SIP KPML, Cisco RTP, but I'm using RFC 2833 on my networks, so RTP NTE it is. Okay, so we've programmed a phone, we've programmed a DN. I like to get in the habit of going voice register global and create profile. And here momentarily, we will be able to boot our phone and forget the error there. We're going to be able to boot our phone and get it registered and make a call from it. So let me do just that. In fact, let me turn a debug off that I had running. And I will tell this phone to reset, and it'll register with CME. And we'll go ahead and make a call. So stand by 1, and once this thing's up, we'll make a test call, and that'll wrap up this video, and we'll move into the troubleshooting stuff. All right, so I'm staring at the phone, and it didn't work. In fact, I'm not going to edit this out. I want to show you. I missed something fairly obvious. I already know what it is, but I'm going to walk you to it here and show you the mistake that I've made. You'll probably do this a bunch if you're like I am. Let's see here. Whoops, I blew right by it here. Voice, service, VoIP. Okay, look at this. I created my phone, and I created my DN, but I forgot to put the DN on the phone. So what I need to do is voice register pool 1, and we're going to say, hang on, question mark here. It is number 1, DN 1. So I'm basically tying the first button to DN 1. And voice register global, create profile. I'm going to tell the phone to reboot again, and that should take care of my issue. What it's telling me is it's actually got a message on the display, and it says unprovisioned. So it was kind of a no-brainer. It's like, duh, you forgot to give it a directory number. So stand by. We're going to let the phone boot, and we'll do that testing I promised you. All right. That phone is finished booting. We now have extension 6000 showing on it, and we're good to go. We're ready to make some test calls. In fact, I'm going to pick up a line here on a skinny phone at 3000. We're going to dial 6000. And we've got a SIP phone ringing. I'll answer it, and you should hear the familiar heterodyne. So we've got calls between phones. I'm going to pick up the SIP endpoint and dial 955511212. And the test set across the room is beeping at us as the PRI is ringing. And we'll go ahead and go off hook and answer the call. Test 1, 2, 3. You can hear my echo there a little bit. So that's working exactly the way we want it to. So we've got a couple of things happening here. Actually, we got a lot of things happening on this router at one time. We've got all of our layer 3 stuff for routing. We've got telephony services for our skinny phones. We've got the voice register services for our SIP phones. We've got a PRI. And I mean, it's all in one box. It's an amazing solution. And that's how you do Call Manager Express. Now, there's a GUI. I'm not going to get into it as part of this. If you want to see it, take a look at the CCNA voice video I did. Knowing the GUI is not really part of what Cisco wants you to know for the C-voice content. But you should have a pretty decent comfort level with configuring Call Manager Express. With that, I'm going to wrap up this video, and we're going to jump right into the last section on CME. And I'm going to talk about a couple of different troubleshooting commands and processes that you need to think about and follow when doing debugs on a CME when something's not working quite right. I've certainly used plenty of them tonight as I was creating this lab. And with that, I'm going to shut up. It's been a half hour. You guys need to take a break, relax, get a cup of coffee, come back, and let's do some troubleshooting on Call Manager Express. Good luck with your studying, and I'll talk to you soon. Module 19, Troubleshooting CUCME. So we've talked about Call Manager Express configuration and how to set up SIP phones and skinny phones, and you saw just a hint of troubleshooting, but there are a few troubleshooting processes I want to make sure you're comfortable with as you both prepare for the C-Voice exam as well as prepare your skills for being a voice engineer and supporting these things. Of the utmost importance, before I talk about anything else, you have got to understand the IP phone boot process. This applies to Call Manager Express, and it is the thing you're going to spend a lot of time doing, over the years as you support things. So let's start from the top here. The first thing you got to do is get power to the device. When you plug in a Cisco phone to a PoE switch, there are a number of different things that happen. One of those is the switch sensing that a PoE device has been connected and applying power to the port. If you want some interesting reading, go read up on Fast Link Pulse. It'll kind of open your eyes a little bit to what's going on behind the scenes. Once the phone powers on, it's going to load the stored firmware that's on it and begin the boot process. It's going to identify via either CDP or LLDP, or maybe you've programmed it into the device, what VLAN we're going to use for voice traffic, because that's the VLAN we're going to send our DHCP request out on. So we're going to send out our DHCP request, we're going to obtain an IP address, and inside that DHCP request, we're going to receive something called an option 150 address. That is our boot server. The boot server is a TFTP server. We're going to request our configuration file from the TFTP server. We're going to retrieve either a specific configuration file for us if the Call Manager Express has one. If it does not, it's going to send us a default configuration file. One of the values in this configuration file, which by the way is an XML formatted document, pull the thing down and read it, it's pretty cool. We're going to update the phone load. It's going to tell us what version of firmware we need to be running. Now, we can upgrade or downgrade. There are lots of rules around where you can get to and from and signed loads and unsigned loads, and we're not going to get into all of that. That's something you can read on your own. But you need to understand we're going to upgrade or downgrade the firmware as necessary to match the system. Ideally, you want every phone in the system, of a model type to be running the same phone load. We're then going to register with the call server. Another parameter within that configuration file is who is my call manager. Actually, it's what are 3 call managers, or up to 3, who is my primary, secondary, and tertiary. So you're typically going to see, a subscriber, number 1, a subscriber number 2, or maybe a publisher, and then an SRST reference. But so you're going to have some capability for redundancy there. Once you register with the call server, final parameters are going to be configured via Skinny, things like what is my directory number, etc. So it's really, really critical you take the time to understand this IP phone boot process because it applies to a lot of different types of troubleshooting that you're going to be doing. I'm going to switch gears here for a moment, and we're going to jump into a console window because most of this video is going to be interactive, and I think you're going to learn a whole lot more from seeing things happen in the router versus just listening to me talk and describe them. So here's my Cisco 2811 that we've been using a lot, and I want to just kind of set the stage here. I've got 2 Cisco 7961 phones on it. I've got a Cisco 7985, which is a video phone, so those are all Skinny devices. I've got a 7940. I should say that. I take that back. One of the 7961s is Skinny, one of them is SIP. And I've got a Skinny 7940. So 4 endpoints on the device here. We're going to go through both SIP and Skinny troubleshooting processes with you just to kind of scratch the surface. So one of the first things when you're troubleshooting a Cisco phone is, if it's not registering, make sure it's in the right VLAN. So we're talking about a switch where we program a voice VLAN. We're going to learn it either via CDP or LLDP. Make sure that's happening. So it's really more of a switching thing, not a router thing. You can go to the settings button on the Cisco IP phone and dig in there and see what voice VLAN it thinks it's using. You want to verify the IP addressing. Make sure you're getting an address from the DHCP server. Verify your TFTP server. Make sure that the DHCP server is sending you a boot server. This router that I'm on, show run pipe section IP DHCP. I'm configuring a DHCP pool of phones, and you'll see in that pool I've got an option 150 IP 10.10.210.1. That is, actually that's this device, but that is my TFTP server. When I tell the device my TFTP server, it has nothing to do with what Call Manager or Call Manager Express I'm going to register to. That is only a TFTP server. You're going to make sure that your TFTP process is working. Debug TFTP events is a great debug, and in fact, if you really need to get granular, you can get into packets, and you're going to see what's happening with the boot process. You'll see the phone as it requests the various configuration files, and things like file not found, those are going to kind of clue you into where your problem lies. If you want to verify endpoint registration for skinny devices, show ePhone is a good place to start. Show ePhone, a phone, and there's actually some options to this. You can go by types, but I like registered. So show ePhone registered. It shows me my 3 skinny devices. I can see the MAC address of each of the devices. I can see the state as registered with skinny. I can see the IP address, the model, and I can see the parameters for the buttons or what directory numbers are assigned. So that is really, really good. We've got an equivalent on SIP phones. Show voice register all. I'm sorry, I gotta spell things right. Show voice register all. And you can see down here we've got voice register DN and voice register pools. So I can see the directory numbers configured, and I can see the phones that are configured, and tells me a whole lot about it here. So that's great, and IP address, etc. If you need to run a debug for skinny registration, because it's not working right, debug ePhone ? And the one I like to use is register. You're going to get a ton of feedback on a phone. In fact, I'm going to show you this one. I like it so much, and I think it's so important that I really want you to see what's going to happen. So we're going to power up a 7940 here, and it's going to go ahead and register. And while I'm waiting for that thing to boot, I'll talk a little bit about what you're going to see. In fact, one more command, debug TFTP events, term mon. You're going to see the phone come up and request some files. It's going to request this configuration file. It's requesting the loads file right now. You can see that. That file tells it, what firmware to use, etc. It's going to, the SEP config tells it what firmware. The phone loads tells it what files make up the firmware. It's happy with everything it sees. It's going ahead and reaching out to different endpoints, and it's going to try to do a registration. So that's kind of the TFTP debug. Next, we're going to see some debugs for the actual registration process itself. I'm just kind of staring at it here as it's going, and you're going to see it go through the registration cycle, and it's really pretty straightforward. Configuring IP, okay. Just waiting on it here. I'm going to actually pause the video. No, I'm not. No, I'm not. Hang on. The phone actually rebooted. I didn't expect that to happen. Let's see what's going on here. Opening 10.10.203. Let's see what we got going on here. And I'm actually going to let this roll because this is the process we go through. Unregister abnormally. Wonder why it unregistered abnormally. Did I delete it? Let me see if I deleted it. That is my 7940. Show run. I like troubleshooting. This is fun. We've got, let's see, we've got all of our TFTP files. Telephony service. Telephony service is shut down. There we go. Telephony service, no shutdown. Make sure telephony service is not shut down. And actually, it came up with a file not found, and then it's just now registered. There's all the registration. So that's the debug ePhone registered. Yeah, it kind of helps if you turn things on. So lots of output here. In fact, let me start at the beginning and show you what we've got. New skinny socket accepted. It tried to connect. Here's the phone. Here's the MAC address, etc. Blah blah blah. capability exchanges, button programming, and it's done. It's up. So, good debug to use to figure out what's happening or not happening with a skinny endpoint. If you need to debug a SIP registration, let me turn those debugs off. Debug voice register events is going to be kind of similar. Let me go ahead and reset a SIP phone and let you see what's happening with that. It's going to be just a little bit slower because this is a 7961. But we're going to let the video keep rolling because if I pause it, I'm probably going to miss it. Keep in mind, your life is going to be a lot easier if you pick one type of phone to use on the system, SIP or skinny. You start programming both, and it's just, that much more complexity that you've got to deal with. When we start looking at best practices for platform configuration, I know this is a troubleshooting video, but I'm going to preach a little while we're waiting on the phone to boot. I like it when you're running your DHCP server on an iOS device. Maybe it's a voice gateway, maybe it's a router. I'm a big fan of it. I don't want to do IP helpers and send stuff, 14 hops down the network on different subnets to some server that is going to be maintenance half the time anyway. I don't want to deal with that. I want core infrastructure providing DHCP services. It's one less thing you have to troubleshoot. It's one less thing you have to worry about, monkeying around with. Use smart configuration processes. Make sure that your phone loads are up to date or standardized across the enterprise. Make sure it's working. Get into CME or Call Manager and actually make sure that the phones you're deploying are taking the new loads. Don't just assume that because you configured it it's working. Actually check the phone. Make sure the phone load that you think is getting applied because you're going to have all kinds of wonky behavior with phones if you've got 13 different or 20 different or whatever firmware versions running on all the devices throughout your network. I'm staring at the SIP phone. It's getting pretty close. I think we're going to see some output here pretty soon. And come on, you can do it. I wish these things were faster. They'll never be, but I wish they were. Like watching water boil sometimes. Here we go. Updating locale. That's the final step. And here is registering. We should see some events pop across the screen. That's what we were waiting for. So we can see a register request for 6000 from 1010-204. Contact matches pool 1, number list 1. You can see it go through and do the device provisioning. So great way to debug a SIP device registration. And I didn't mention it in the provisioning videos, but I'll say it now. You can use... I never have, so I can't tell you how well it's going to work, but you can use third-party SIP devices as long as they're standards-based with Call Manager Express. We can support digest credentials and all those kinds of things. So give it a whirl, try it, play with it, and have fun with it. Other things you want to understand. With CME, everything's in Flash. So show Flash is going to give you some information about all the files in the various folders, what they are, what they are, where they are, do they exist. You see this ITS folder? These are all those XML files, the default ones anyway, that are being created for the various Cisco phones. So that's useful to know. If you want to do some show telephony services, one of the things I like to do is check the TFTP bindings. These are all the TFTP bindings that telephony service is making for the onboard TFTP server on the router, config files, etc. So again, if you're getting file not founds on TFTP, which that happens a lot actually, you can deal with it. We talked about how to verify some of the endpoint registration with like show ePhone, so I think you're good there. Anything else? Use debugs, use your log files, and just kind of step it one thing at a time. Make sure, I'm going to preach it again, make sure you understand that IP phone boot process. It is so crazy important. Most of your troubleshooting is going to happen with the registration cycle, not after the registration cycle. So if you can get that working, you're 90% there. That's really all I needed to show you in this video. I told you it was going to be kind of short, although I'm at about 15 minutes, a little longer than I wanted. But You've got the fundamentals, you've got the foundations for CME. This is what they're going to be expecting you to understand on the exam. So go back through the last 3-4 videos that I've done. Make sure you've got a good grasp on what is CME, where does it fit, how do I use it in my environment, what are its capabilities, what kind of hardware can it run on, how do I program it, and how do I troubleshoot it. And that's going to be the ticket to your success. So with that, I'm going to say thanks for watching. And we'll see you in the next video. We're going to start talking about dial plans and how do I design a dial plan. Ultimately, we're going to get into implementation of some dial plans. And then after that, we're going to talk about the Unified Border Element, or Q, which is a big topic, a hot button topic these days in the world of SIP we're living in. So with that, good studying. Thanks for watching, and I'll see you in the next video. Welcome to Module 20. In this video, we're going to talk about numbering plan concepts. And this is meant to be the first of two pieces of a numbering plan design primer that we're walking through. So I want you to, in this video, focus on understand what makes up a numbering plan. What are the things we have to think about? What are the numbering plans that are popular, in the PSTN today that we're going to have to deal with on a regular basis? How do they work? Where do they come from? And then we'll segue into, in the next video, some numbering plan design considerations when you start planning your own number plans. And then ultimately, we're going to go through an exercise of implementing number plans, and we'll be dealing with gateways and configuration and those types of things. But for this video, we're going to keep it pretty tight from a conceptual perspective. So first off, what exactly is a numbering plan? And you'll hear me refer to a numbering plan as a dial plan from time to time. And really, a numbering plan is a number of things. It's a scheme used to allocate numbers where ranges get assigned to regions or geographies, or services like cellular service in some areas are assigned numbering plan ranges. And numbering plans define the rules for number allocation or assignment. So all of these things are a part of the role of a numbering plan. And you're going to find that the international world is using what we call the E.164 numbering plan standard. And we'll go into a definition and demonstrate how E164 works here, actually towards the tail end of this video. When we talk about the first numbering plan you're most likely to run into, and not just because I live in the United States, but because of its popularity, is the North American numbering plan. It was developed in 1947 and implemented a few years later, and 19 countries in the North American area are sharing the resources and using this North American numbering plan. It's something like 800 area codes. You've got the United States, Canada, Bermuda, Jamaica, the Dominican Republic. There's plenty of others, but very, very predominant in that part of the world. And here is an example of a North American numbering plan formatted number. You've got 3 digits. Well, first off, it's a 10-digit number. The first 3 digits are what we call the NPA. They can be, with the first digit, starting from 2 through 9, so any of those digits, and then 2 additional digits, so that's the NPA. And then you've got the NXX, XXXX, which is the local number portion of things, which it can, again, start with 2 through 9, with remaining numbers being X's. So the first 3 numbers, we call that the area code. And the last 7 numbers, we call the local number. So this is what you're going to run into in the United States and other North American territories. Very popular, widespread use. The North American numbering plan has different reserved numbering codes and really styles of dialing. The first one I want to talk about is called an ERC, or an Easy Recognizable Code. 800 and 888 are great examples of this. And an ERC is any number where the second and third digits of the area code are the same, and they're just allocated for special use purposes. We've got numbers called ANI2 numbers. And ANI, you've heard that term before, Automatic Number Identification Service. It's going to be used ultimately to identify the type of originating station, and they're two-digit numbers. Or I should say it's a pair of two digits. We've got CIC codes, carrier identification codes. They're used for billing and call routing, and they are four-digit numbers. Within the North American numbering plan, if and when you are placing an international call, it's always going to begin with 011. If you're placing a long-distance call, it's always going to begin with a 1. In-state long-distance or local calls, and traditionally this was long-distance, but with the numbering plan, expansion and growth, etc., we're starting to see local calls in some areas require 10-digit dialing, so that's 10-digit codes. And 7-digit numbers are local calls. So that's your traditional NANP numbering scheme, some of the reservations and the function of those. When you talk about special service codes, we've got 8 of them, 211, 311, etc., all the way up through 911. Let's talk about what these are. And some of these are assigned nationally and others within more local geographies. 211 is used for community information. In some areas, 311 is used as a non-emergency number to reach the police or other government entities. 411 is local directory assistance. 511 can be used for local traffic information. 611 to contact repair service. 711 can be used to contact a telecommunications relay service. 811 for the business office, and 911, you're familiar with that one I'm sure, for emergency telephone calls. Another numbering plan or scheme that you're going to run into is the ETNS, the European Telephony Numbering Space. And this exists in parallel to the legacy or the pre-existing geographically related area codes and numbering plan. And we call this the 388 area code. The maximum European subscriber number length is 15 digits, and you're going to find out that that pairs up rather well with E164 standards. And here's an example of what one number might look like. So area code 388 with the access code of 3, and the remaining digits available to you. The ETNS has a couple of reserved service types to define how numbers are assigned. We've got 38831 for public service applications, 38833 for customer service applications, 38835 for corporate networks, and 38837 for personal numbering. When you look at the numbering format here, it's made up of a country code or group ID code plus a European service code, and those two sections together are called the ESI, the European Service Identification, and finally the European subscriber number. E.164 addressing is something you're going to hear referred to a lot, and E164 addressing is kind of the world we live in. It was developed by the ITU, and it can be up to 15 digits in length. So you remember me mentioning in a previous slide about the European numbers, being 15 digits or up to 15 digits. Well, an E164 number, can also be up to 15 digits in length, but it doesn't have to be. Each address in an E164 numbering plan is globally unique, and I mean that literally. I sure hope we don't run out, because that would kind of suck. And I want you to see the format of an E164 number. Like I said, 15 digits in length. The first 3 digits can be the country code, and I should say up to 3 digits long. The next 4 digits are the national destination code. Digits 8 through 15 are the subscriber code. And when you put the national destination code together with the subscriber code, together they can occupy basically 15 digits minus the country code. So if the country code is 1, the NSN can be 14 digits. If the country code is 3 digits long, you're losing another 2. So pretty much that sums up E164. You're going to see a lot of E164 numbers, through the course of this course and this video series and telephony in general. We're going to talk about things like plus dialing and other types of access. So have a good understanding of E164 numbers and how they play. That really sums it up for the the fundamental concepts of numbering plans. In the next video, we're going to get into actual numbering plan design and how to create a scalable numbering plan and deal with numbering overlap or prevent numbering overlap, and ultimately how to route calls based on these numbering plans. So with that, we're going to wrap this one up. I want to say thanks for watching. Good luck with your study, and I'll see you in the next video. In this module, we're going to talk about some numbering plan design considerations. Now, this is only going to take a couple of slides, and a lot of it's going to be obvious as you read it and start to think about the impact on your numbering plan or dial plan design on your environment. These recommendations are a combination of things I've seen published, things I've seen other authors recommend, things that peers have done in the field, and things that I have done in the field, and lessons that I have learned and best practices that I have developed over time. There are no absolutes with numbering plan design, but there are a lot of guidelines that you ought to follow. And the first of those guidelines is that a numbering plan must be scalable. I don't care if you're designing a numbering plan for a single site with 15 phones, or if you're designing a numbering plan for a 150,000 phone deployment. The same planning thoughts need to go through your head. Now, you may not spend as much time on them, but you need to at least think about them. First off, it's critically important that you use a hierarchical design. It is going to make things so much easier if there's a hierarchy to your numbering plan, as far as administrative burden, as well as dealing with things from the user side. So you're going to have an ease of provisioning new numbers, or you need to make sure that you can easily provision new numbers within your numbering plan. So think about how to allocate ranges for what you're going to use now and what you're going to use later. You need to consider an ease of routing. Make sure that your patterns are created in such a way that it's obvious how to get where you're going. One example, when I build a PBX or an IP phone system, my client is going to be asked for a PSTN access digit. More often than not, they use the number 9, but I'm seeing others be popular. 783. There's all kinds of different options that you can use. But use that code or that PSTN access digit to signify a call that is leaving your premise. It's going to make it a lot easier in a voice gateway for it to make routing decisions if it knows that everything that starts with 9 is automatically going out to the PSTN. So think about that. Think about number summarization. I want you to put numbers in contiguous blocks servicing similar geographies. So if I've got an office in Columbus, Ohio, and an office in San Francisco, California, I don't want some 5,000 extensions being in one site and some in the other. I want 5,000s being in one and 1,000s being in the other. Use some contiguous numbering schemes. Consider scalability. Make sure you're leaving space. If I'm designing a network for 5,000 endpoints, I sure better have like 10 or 15 or 20,000 numbering plan entries in my design as possible to accommodate for that future growth. What happens if I make a stupid decision now? Well, it's going to be a pain in my butt later. So think about numbering plan and extensions and how and where you allocate things now, not only for what your immediate needs are, but for 2, 3, 4, 5, 600% growth. It's not that hard to do. You want to make sure that you've got a design that gives you ease of management. If everything's centrally located, obviously managing the numbering plan is going to be a lot simpler. So we've talked about the hierarchy. Now, when planning specific guidelines, minimize the impact on your users. Don't go into a site and change 5,000 extensions on a whim. that's going to really cause chaos for your users and create a lot of frustration, and you're not going to be the popular guy in the IT department that week. So try to minimize the impact on the users. And likewise, minimize the impact on the existing environment. If you've got processes that have been in place for a long time and they continue to meet your business needs, don't just change them on a whim. Use what makes sense and use some common sense within your design. Create your dial plan or your numbering plan to minimize the number of digit manipulations or translations that you need to perform. If there's a way to simplify translations, by all means do it. And make sure you manage and plan for growth. If you don't plan for growth, it's going to just turn around and bite you. So make sure that you're doing that as you work through your numbering plan design. Dealing with overlapping numbers, site codes. So I said try to avoid using overlapping numbers. It's not always possible. If you can't avoid overlapping numbers, let's talk about some strategies you can leverage to deal with them. So site codes are one of those methods. When using site codes, you're going to use an inter-site code similar to a PSTN access digit. So I mentioned before that a lot of times, my users will choose 9 for an outside line. So when I'm programming my dial plan, I'll have patterns that begin with 9. Well, let's say that we're going to implement site codes in our environment. I may have patterns that begin with a 7 or a 6 or a 4 or an 8 or some other digit. And then we're going to have a range of extensions behind that. So here's an example of what a site code based approach might look like. So in this example, I wasn't able to have non-overlapping ranges. In fact, headquarters was the only site that didn't have overlapping numbering ranges. I've got extensions starting with 1000 in headquarters, and I've got extensions that begin with 2000 in branch location A, B, and C. Now, this didn't necessarily happen as a result of a bad design. Perhaps I had some acquisitions and mergers in my company, or maybe we acquired a company and we bought somebody and they had a bunch of phones and PBXs, and it just didn't work out for us. So with this model, we're going to leverage a site code. So for example, I might press 8 as a site code access digit, and then I would dial 2154. And I'm sorry, I skipped one. I would dial 8, I would dial my site code, and then I would dial 2154. So 8202154 would take me to branch location 8, or 8302054 would take me to branch location B. So site codes can definitely help you out. They're more of a traditional design or a legacy design. We're not necessarily, or at least I'm not, encouraging people to use them as much anymore. I think there are better ways of doing things, primarily using longer digit extensions, etc. I mentioned that it's not always possible to design a non-overlapping numbering plan, but if you can, do it. You saw the complexity in the last slide of site codes. I don't love them, but they can solve some problems. But if you're able to design, this is a non-overlapping plan, you're going to have some simplicity by having uniform dialing. Make sure that your users have a consistent experience. If I'm in site A and I need to call site B, make sure that I'm using the same process to call site B as someone in any of my other 400 sites would use. I don't want a completely unique dial plan and dialing behavior from every location. Make it consistent. Your users will thank you. Select a single pattern length that you can use. Either use 4-digit extensions in your system everywhere, or use 5-digit extensions everywhere, or use 10-digit extensions everywhere, or use 3. I don't care. Pick a length and stick with it. Do not get into a variable length dial plan. You will pull your hair out. It doesn't scale well, your users won't like it, and it causes more problems than benefits. So use a single pattern length, 4 digits, 10 digits, etc. Here's an example of a non-overlapping numbering plan. Again, this is the ideal design. Headquarters, we've chosen a 4-digit example here. So we've got a 4-digit range of 1XXX, so that's 1000 through 1999. Branch location A has the 2000 range, and branch location B didn't need quite as many numbers, so we went from 3100 to 3299. And then we've got room for future allocations of 3300 through 8999. Now you'll notice here I didn't allocate numbers starting with 0, and I didn't allocate numbers starting with 9. I like to leave those two patterns out, and leave myself some flexibility for using those for other things. Here's another example of more along the lines of what I'm recommending to my clients these days. This is a 10-digit numbering plan. I'm actually using the full 10 digits of the North American numbering plan to provision an extension on a phone. Now, I'm going to create what I call abbreviated dialing rules, or translations, that will allow a user to have a simplified dialing experience so that they don't have to dial all 10 digits to reach the phones, but the system knows about it, so my routing decisions are a lot easier. So, there's an example of what a 10-digit numbering plan might look like, expanded on that 4-digit example. Consider PSTN to private number extension mapping. Use DIDs where possible. If every phone in your enterprise does not have a DID, but yet you still want to use 10-digit numbering plan, which I would recommend, create yourself some fictitious ranges. 555 is a perfect fictitious range. Your users, unless you've got your users dialing the full 10-digit number, they don't need to know nor care what the whole number is. They just need to know how to dial the people they're trying to call. So if you're using DIDs, try to match that to the extension range, and we'll show you an example of doing that here. My DID range, and actually what I'm programming on the phone, is going to be 614 for headquarters, 555-1XXX. And I'm going to create abbreviated dialing rules so that my users can simply dial 1XXX. Now, the same thing would work if I were using true 4-digit extensions on the phone. And the PSTN has its DID, the 614-555-1000. It's going to hit my system. I'm going to look at the last 4 digits and ring extension 1000. So by having simplicity and by having the private extension mapping match closely my PSTN numbering scheme, it minimizes my dial plan complexity. Is it possible to have, a whole bunch of weird directory numbers and some other sequential DID range and map it to them? Yeah, absolutely. And it's not a good idea. It's going to cause you a lot more trouble than it's worth. So try to avoid that. And finally, tips for optimum dial plan design. First and foremost, avoid ambiguity. We want to make sure that if you're dialing a pattern, that as much as possible, that is the only pattern you could possibly match. If we have to start making decisions on what pattern was the best and which one is the closest match, your dialing plan is going to be less than ideal, and your dialing experience is going to be less than ideal. Avoid overlap whenever possible. It's not always possible to have no overlap in the system. But do as much as you can to get as close to achieving that as you can, and you're going to be a lot happier. My personal recommendation, if possible, use 10-digit or even full E164 extensions, plus dialing included if you want, for directory numbers within your PBX. It's going to make life simpler. If the carrier is sending me 10-digit DNS on an inbound call, and I have 10-digit directory numbers, how many translation patterns do I have to build in the system to route calls to phones? Absolutely none. How many dial plan entries do I have to build? Absolutely none, other than the obvious existence of the directory number in the system. It's going to be like a connected route if I'm talking about routing. It's just there because it exists, and I'm going to match it, and I'm going to go to it, and things were simple. Create translation patterns when you need to use them in such a way as to minimize dial plan entries. If you can have one pattern match a range of numbers, that would be preferential to 100 patterns matching 100 unique numbers. So be smart about your translation patterns. Use contiguous numbering ranges in a geography. So if headquarters can have all extensions beginning with 1, and branch A extensions beginning with 2, and branch B extensions beginning with 3, that is going to perform a lot better for you and scale a lot better than if you put, even numbers in one site and odd numbers in another. I mean, it's goofy. You can do it, but it's not going to make you any friends, and you're certainly not going to like yourself a couple of years down the road administering the system if you do that. Consider your call coverage requirements. Who can dial what? You may find out that patterns and class of restriction come into your dial plan design, and you may want to make decisions based on that. And finally, consider the numbering plan and numbering type. when you're making PSTN calls. When we're going out of PRI, we've got a concept of numbering plan and numbering type. That's something that you've heard me talk about before. And depending on what your provider wants, they may want you to flag all calls as unknown unknown. They may want you to flag long distance calls as national unknown or national ISDN or subscriber national. There's all kinds of different variations on this. Ask your provider how they want calls tagged, because you can influence that a number of places, and your dial plan can come into play as part of how you influence that. So I know this was short and sweet. We ran about 15 minutes, and I think we've hit a lot of the high points here on doing dial plan design and considerations for creating a smart dial plan. In the next video, and actually it's probably going to span a couple of videos, we're going to talk about implementing dial plans. And we're going to actually get into a Cisco router, and we're going to build dial peers. We're going to start with a design and talk about things like digit collection and evaluation, and how do we deal with things like caller ID, and how do we deal with translation profiles, and how do I manipulate digits, and how do I strip digits or append digits, and really it's going to be programming dial plans on gateways. So with that, we're going to put the theory aside. I'm going to say thank you for studying with me. I appreciate you coming along for the ride. Hopefully this has been helpful to you, and I'll see you in the next video. Welcome to Module 22, and over the next couple of videos we're going to be talking about dial plan implementation. And what I mean by dial plan implementation is programming the darn stuff on the CME or on the gateway you're working on. So we've talked about dial plan design and how E164 works, and you've got a background on the North American numbering plan and really, a good primer on numbering in general. Now let's talk about how gateways, or how CME, both deal with digits and understanding how to route calls based on digit collection. So CME and voice gateways are going to make their routing decisions based on dial peer matching. And I've got two dial peers up here that I'm going to use for an example. Dial peer voice 100 POTS, which has a destination pattern of 555, and dial peer voice 101 POTS, which has a destination pattern of 555 1000. How we match a dial peer and which dial peer we select is going to be based on how the digits are collected. So the question I pose to you, using this example as a reference: if a phone dials 555 1000, which dial peer will be matched, and why? You might think that the answer is obvious, but the answer is actually not so obvious. Obviously, we want to get the best match. However, what gateways do, what Call Manager does, depends largely on the device placing the call and where those digits are coming from. So let's go through and analyze how this process works. I want to talk about a concept here of one digit at a time versus en bloc. And we're going to continue to reference these same two dial peer examples. Depending on what the sending device is, a CME or a gateway can receive digits either one at a time or en bloc, which is all digits at once. Skinny phones on CME are always going to send one digit at a time, and that's the nature of the Skinny protocol. Skinny is a client-server protocol, and every time you press a button on that Skinny phone, it's sending a message to the call agent or the call server, whether that's Call Manager, Call Manager Express, and you're getting screen updates and other types of feedback. And once the call agent has collected all of your digits, it's going to make a call, but it's dealing with it one at a time. SIP phones, on the other hand, can send either using NBlock. So for example, a SIP invite message contains the whole destination of a call you're trying to make. Or SIP phones can also send digit by digit if you're using KPML, or the keypad markup language. And whether or not you're using KPML or you're using NBlock is going to be based on the type of SIP phone that you're using. And really it boils down to this: old stuff and newer stuff. And we'll get into that as we go. Again, looking at these two examples, which one will we match? It depends. Looking at digit analysis on CME, let's look at the example that we've continued to reference here and talk about it in the context of SIP phones. So there are two types of SIP phones. There are SIP Type A phones, which are the early Cisco phones, the 7940 and 7960. And really they started off life as skinny phones, and then SIP code was released so they could run that as well. And then there's the SIP Type B phones, which is pretty much everything else since that point in time. If you look at this chart, we show endpoints of IP phones and gateways and the protocols in use. And we show you that skinny is going to be a digit by digit match. That's just the way skinny works. And a SIP phone is going to either be digit by digit if it's a type A phone. I'm sorry, I'm saying that wrong. It can be digit by digit. It can be MBlock, or it can leverage SIP dial rules. So digit by digit would be a type B phone. And my slide's actually wrong here. I'm going to have to correct that. And KPML, that's true. KPML's on type B phones, but you're going to be forced to use NBlock, if you're using a older phone. So here's what I want you to picture. It's kind of like a cell phone. If you are typing the number and then hit dial or hit send, the sending isn't actually happening until you're hitting that dial button. So you can consider that when the digits are being sent, that they're being sent all at once, upon pressing that dial button. If you take the phone off hook first and then dial the digits, you're likely sending things digit by digit. So with Type 1 phones or Type A phones, you're sending it NBlock. With Type B phones, you're using KPML, which can be digit by digit. Or you can leverage SIP dial rules. Now on a gateway, it's always going to be sent NBlock. So think of the protocols you're using. These aren't chatty little, one button at a time kind of things. We're going to evaluate the entire strings. So let's visualize the digit collection process here. And I'm going to use the example number of 555-1000. If I'm a user and I dial 555-1000 and I'm on a skinny phone, you'll see that the phone is sending off-hook messages. And then the first digit, 5. And then the next two digits, 5, and then 5. And then 1, 0, 0, 0. And it's doing it a message at a time. And the gateway is returning, or the CME is returning the dial tone and updating the screen as necessary to reflect what you've done. With a SIP Type A phone, which is going to send things NBlock, we're going to send a message, and really it's a SIP invite message. And that message is going to contain the entire string that we want to dial. So 555-1000, we're sending a SIP invite. And then our call progress messages are going to be returned from the CME to the phone. And finally, SIP KPML, digit by digit, very similar to Skinny in that we're sending it one digit at a time. However, call progress messages, just like in a SIP Type A phone, are going to be sent from the CME back to your dialing device. So I think this chart, or this illustration, really kind of sums it up. The answer really is it depends. So back to our question. Which dial pair is going to be matched when we dial 555-1000? And again, for reference, here are our two dial pairs. Dial pair voice 100 pots with a destination pattern of 555, and dial pair voice 101 pots with the destination pattern of 555-1000? The answer is still, it depends. So, if it's a skinny phone, in this example, because we're doing it a digit at a time, we're going to have determined that we found a match on dial peer 100 once we parse that third digit, because we'll go 5, 5, 5, I got a match. If we're using SIP and block, we're going to have an exact match on dial peer 101 after all of the digits have been received and we analyze based on the string of all digits. So as you'll see, there's some pretty obvious things happening to do digit selection or to do route selection for voice calls, and it's not always cut and dry how it's happening. The lesson to learn here, and what you should take away from this for prepping for your C-Voice exam, is that different endpoints behave differently, and you really need to understand the specifics of your environment to predict the behavior. Now, in the next couple of videos, we're going to talk about actually deploying the dial plane onto the gateways. We're going to get into digit manipulation, so digit stripping and managing the number of digits we forward, and some of the various tests you can leverage, and translation rules that we can do, and really kind of soup to nuts typical voice configuration on an iOS device. So with that, I'm going to say thanks for watching, and good luck with your studying, and I'll see you in the next video. In this module, we're going to talk about digit manipulation on the routers. Now, in the last video, we talked about, or actually the last couple videos, we've talked about dial plan and numbering plan design and the kind of considerations you need to make when designing your dial plan, like avoiding overlapping numbers and using contiguous blocks of numbers for certain geographies. And we've talked about, how to come up with a good design, but we really haven't really showing you where the rubber meets the road, where we're dealing with, performing all these kinds of actions. And that's happening within voice gateways and within your call agents. So let's take a video or two. I'm not exactly sure how far I'm going to dig into this one. I want to kind of keep the time manageable. But let's talk about digit manipulation. And what I want you to understand is in every voice environment, you're going to have a scenario where you're dealing with digit manipulation. So we need to understand the best ways to deal with manipulating digits when you need to do it. So we're talking about things like adding or appending or prepending or stripping or doing all these types of things. I've got a session open here to our 2811 router, our headquarters router, and I'm going to walk you through a number of different types of digit manipulation scenarios that are common when dealing with voice gateways or CME environments. Now, let me give you just a quick primer of the system. This is the CME we were working on previously, and we have, just so that you're familiar with what's going on, we've configured a trunk group for our PSTN facing PRIs. Now, there's only one here, but if we had more than one, we could simply add them to the trunk group. And I'm doing that as a method to minimize my dial pairs. So instead of pointing dial pairs to ports, I'm going to point dial pairs to trunk groups, and trunk groups can contain multiple PRIs. We've got SIP and skinny phones registered on CME. So here's the voice register global and DNs, and you'll see the pools below. That's all of the SIP devices. We've got, as we keep going here, we've got our T1 controller up and in service, and I've got 6 time slots in service for our PRI. We've got, let me keep going here. Here's some dial peers, telephony services for our skinny phones, couple of numbers. And if we do show ePhone registered, registered, you're going to see we've got a couple of devices up and in service. Show ISDN status. is going to show us multiple frame established, and I've got one of my test sets conveniently connected to the gateway, and we're able to make some test calls with it. So if I want to, let me turn it up here so we can actually see what's going on. Setup. Backlight. All right, I can read it now. If I want to dial, for example, in fact, let me turn on a debug. Debug ISDN Q931 term mon. Let's say I just dial it. I'm going to call extension 2000. All right, so we're going to place an inbound call. Let's see, dial 2000 2000 on hook. And you can hear the phone ringing in the background. Now, as I look, I'll go ahead and end the call here. As I look at the ISDN debug here, I can show you that the call coming in is destined to a 4-digit number. And because my phone, this is what we call 4-digit DNS, because my phone has a 4-digit extension, then it matches the dial peer entry for the phone, because remember in CME, show dial peer voice summary, I'm going to have dial peers that relate to the phone. So, I'm looking at the route planner, or looking at the dial plan, and I match it and I ring the phone. Let's say I didn't have 4-digit extensions. Maybe I had 5-digit extensions, and my phone was 2000. I would need to be able to prefix or to append a number to make the 2000 that's coming in look like 2000. Or maybe I have, let's see here, maybe I have 4-digit DNS and 3-digit extensions. Maybe my extension is 500, but calls are coming in to 2500. Then I would need to do some digit stripping. Or perhaps, a call coming in to 2000 really needs to ring to 5000. So I'm going to have some more advanced modifications to do. So let's walk through some of the simple stuff here that we can deal with. And keep in mind the same thing's true in the outbound direction. In fact, let's look at outbound first. Show run pipe again dial peer. If we look at the dial peers, you're going to see the POTS dial peer that I have here, dial peer voice 100 POTS, is using a destination pattern of 9 and 7 digits, and I say forward digits 7. What I'm doing here is I'm actually telling the dial peer to only forward the last 7 digits. So don't forward my PSTN access code of 9. So I'm effectively stripping the 9. I could also use a command called digit strip on a dial peer, and it's going to strip the matched digits in the destination string. So, that comes in handy for like wildcard kind of stuff. So you can do digit manipulation that way. We can do numbering expansion, where we take a small number and turn it into something else, and inflate or deflate things, or we can use voice translation profiles and rules, etc. So, pretty straightforward here. But lots of things you can do. Lots and lots and lots of things you can do. So let's see here. We were already showing you an example of forward digits. Let's actually go through that one. Forward digits 7. So what I'm going to do, dial up your voice 100 POTS. I'm going to change it. In fact, let me make a call from it, and then I'll show you what happens when I change it. So I'm going to dial 9-555-1212. I'm ringing outbound with a called party number of 555-1212. Because I did just what I said I was going to do. I stripped that 9. Let's change the behavior so that I don't. So let's look at the dial peer again. 100. So config T, dial peer voice 100 POTS. And we'll say forward digits all. So now I'm not stripping. Now watch what happens on my debug. I'm going to dial 9-555-1212. And now the outbound call is ringing with that 9 still attached. Maybe I needed to only send 4 digits out to the PSTN. That's kind of unusual, but let's say I wanted to do 4 digits 4. Again, on that same dial pair, I'll place the same call, 955511212, and you're going to see that now I'm simply calling the called party of 1212. So it's very easy to deal with stripping digits. Now let's talk about appending digits. We'll go back to that dial pair, and we'll say forward digits. Let's see. I'm going to say forward digits 7. So it's a normal 7-digit call. Now let's say that for whatever reason I needed to dial a prefix code. Maybe it's because this is a tie line to another PBX and I need to leverage its dial plan or whatever. But let's say I needed to append a 5. Or no, I'm going to pick something a little easier to see, a 2 to the beginning of all these numbers. I could say, again, on that same dial pair, that I could do, let's see here, thinking about the best way to do that. I could do prefix. Let's see here. Yeah, I think prefix is what I'm going to do here. Prefix, question mark, and I'm just going to say 2. So again, show run, pipe, begin, dial, peer, voice. You'll see that 100 that I've got here. So our destination pattern starts with a 9 and is 7 digits long. We're going to forward 7 digits, so we're going to drop the 9, and we're going to prefix a 2. So we should see a 255511212 coming out to the PSTN. So we're going to say 955511212, and we should send down the ISDN a 255511212, which we're doing. So right there, we're showing you the basics. How do I strip digits? And how do I manipulate or prefix? Now, if I had a dial peer that was perhaps variable length and wildcard based, let's see here. Let's do dial peer voice. We'll just call it 150 pots. And let's see how the other one's configured here. We're using trunk group PRI. All right, we'll point it to the same trunk group. And then we'll say destination pattern 9011T. That's the perfect example for an outbound international call. Now, what's going to happen here is I'm by default going to strip the 9011 because that was the exact portion of the match. I'm not doing any kind of forward digits thing here. So let me show you what's going to happen. So I'm going to go off hook and I'm going to say 9011 and I'm going to dial a variable length number 5, 6, 7, 8, 9. Yeah, I think I hit the buttons there. And what you're going to see happening is, okay, so I skipped a 7. So 5, 6, 8, 9 is what I dialed. So because 9011 was the specific entry in my dial pair, it matched it and stripped it automatically. So what I'm going to have to do to make that call successful is prefix 011. So now when I call 9011 5, 6, 7, 8, 9, you're going to see 011 5, 6, 7, 8, 9. So I think we've kind of covered prefixing and stripping adequately. The next thing you need to understand how to do is number expansion. And what you can do with number expansion is you can turn one type of digits into another type of digits. So, for example, let's say num expansion, and we'll say 555. What's a good extension? I've got a 2000 number here. We'll use that. 2 ... 2614 555 2 ... Now check this out. When I make a call, and it might look goofy in the debug, and I might even not match dial pair here as I haven't looked, but I'm just going to dial the digits and roll with it, fix what breaks. But I'm going to go ahead and go off hook, and we're going to say 9 555 2000. So I've dialed 555-2000. Oh, actually, I matched the wrong pattern there. That's not going to be terribly useful for me. Let me change some things up here. Show run, pipe again, dial peer voice. Whoops, I scrolled right by it. 101, 150. Let's go back to that 100. Dial peer voice 100 pots. We'll say no prefix 2. Alright, so 4 digits 7, so that's back to looking normal. Number expansion. Actually, you know, I'm going to use it as an inbound test instead of an outbound test. I think it's going to work better. So what I'm going to dial, in fact, let me do show run, pipe include num. We're going to see the number expansion. So 5552 ... is going to try to ring 614-5552 ... So let's go ahead to that ePhone. Let's see here, show run, and I'm going to modify the number so the phone actually has a 10-digit number on it. So we're going to present 4-digit DNS from the PSTN, expand it into the 10 digits, and ring the phone. So where's it at? There's ePhone DN. I'm going to use the phone with extension 2000, so ePhone DN 2. Okay, so we're going to go config T. We're going to say ePhone DN 2 dual line, and I'm going to say number 614-555-2000. So now it's got a full 10-digit number on it. We're going to go ahead and reset that phone. So we'll say config T. We'll say ePhone to restart. And that will cause it to re-register. And I'm staring at it now. And now it has a 10-digit number on it. Perfect. So if I do show ePhone reg, you're going to see ePhone 2 has a 10-digit DN on it. So call's going to come in from the PSTN to 2000. Should hit number expansion. And again, let me show you. Show run, pipe include num expansion. We're going to take that 5552 ... and expand it to 614-5552 ... So I'm going to call, let's see here, off hook. Whoops, hang on. Getting ahead of myself here. Say 555-2000 dial. So what happened is I called into 555-2000. We matched number expansion, and we expanded 555-2000 into 614-555-2000. And hello, hello, hello. We can ring the phone, answer it, and hang it up, and we're good to go. So that shows you the first couple of strategies relative to manipulating the dialed number. We've talked about digit stripping, we've talked about prefixing, and we've talked about number expansion. I'm going to stop this video here and just to kind of keep things short, and we're going to go into some caller ID manipulation or calling party manipulation, and then we're going to get into the big boy, the voice translation profile, or how do I make the real magic happen when I want to change something crazy weird into something else crazy weird. So for this video, we're going to say thanks for watching. I'll see you in the next video where we talk about additional digit manipulation techniques. And thanks for viewing. I'll see you soon. Welcome to part 2 of our digit manipulation video series, and it seems like it anyway. And we talked in the last video about some of the fundamental digit manipulation concepts that you're going to deal with on a CME or a voice gateway, and prefixing digits and messing with the forward digits, so that you can effectively strip digits when placing calls. And really, we were focusing on basic manipulation of called party information. We were worried about the destination. Now, there's one more bit of information you need to worry about, and that's the calling party. So we're going to go ahead and jump into a router here. This is a different gateway. This is actually my PSTN gateway that I use for the lab here. And I want to bring your attention to some configuration relative to, for example, an FXS port. So I'm showing you here voice port 111. So 111, that should be my FXS port. Let's see if that's right. Show voice port. Is it voice dash port or just voice port? That's the one I want. Show voice port summary. And we are FXS. So 111 is a loop start FXS, plain old analog phone. So nothing crazy there. If I want to go ahead and take it off hook here, and we'll do it again, you can see that it is, and actually 110 is the one I'm on. FXS, showed it go off hook. So 110 is the one we'll focus on. Now, right now, if I call something, and let's see here, I'm going to check and see if I've got anything dialable on this. Let's do a show dial peer voice summary. I had some PSTN patterns. Oh, where do I want to send it? 10, 11. Give me a second. I'm going to go ahead and hook up that FXO line, and we'll actually send some calls to the PSTN. I want to show you some caller ID features. So stand by one while I connect the FXO port. All right, we've got the FXO port in service and a PSTN connection available here. Since it's a POTS line, we're going to have to run a slightly different debug. But what I want to show you is debug voice CC API in out. Term on. I'm going to make a call to a toll-free number here. So we're going to go off hook, and you'll see some debugs here. And I'm going to say 9-1-800-444-4444. Now, as I place the call, I've got obviously a called party number, but I don't have any calling party information. And I'm going to hang this up, and then we'll scroll through the debugs, and I'll find where to show you that at. Let's see here. Where is it? Takes me a minute. I don't do these debugs all that often. And usually I'm searching. Here we go. So I've got a called number, but I don't have a calling number. It's blank. I don't have any caller ID on that voice port. If I want to set up caller ID on that voice port so that this actually presents some caller ID to people, what I'll do is I'll actually go to that voice port. What did I say that was? 100? Show voice port summary. 110. We'll say voice port 110. And we're going to say station ID. And you can do name or number. I'm going to go ahead and say number. And I'm going to say 614-555-1000. And we're going to use that as the station ID number. And I'm going to go ahead and make a call. And now I should send that caller ID 9-1-800-444-4444. And there we route. And I will go ahead and hang it up. And I actually saw it fly across the screen. We'll scroll back and look at it, and it's right here. Calling number equals 614-555-1000. And obviously we're doing that same 800 number destination. So manipulating caller ID on things like FXO ports is relatively straightforward, as is on a PRI. You can send whatever type of called number, or calling number you really want. Sometimes the carrier will not allow calls originating from incorrect numbers. Other times they will. And I'm really not going to get too deep into the calling party manipulation. but I did want you to understand that those are configurable parameters, and there are things you can do with them. But the real topic for this video, the thing that I'm going to dive crazy deep into, in fact, let me open a different terminal window to do it, because we're going to hop in a different gateway, is regular expressions and understanding what you can do with voice translation profiles. So let me log in to the other device here and bring it down into the window. This is the same router we were using earlier, our HQ router. And voice translation rules and translation profiles work together. You can attach a voice translation profile to lots of different things. You can attach it to VoIP dial peers, voice ports, trunk groups, lots of different ways you can deal with them. But I want you to think of voice translation profiles and voice translation rules as ways to turn anything you want into just about anything else you want. I use them a lot on inbound calls. I'll have a DID that was dialed that I want to redirect to another destination. And, so I can do that. Now, I want to show you how to configure voice translation rules and how to map them. I'm going to use a voice interface or a voice port as my example, but keep in mind these can be applied lots of different places, lots of different ways. But once you've seen the basics, it's pretty straightforward. So the first thing I'm going to do is, let me think about the scenario I want to map out. I'm going to accept an incoming call to a 10-digit number, 614-555-1212. And I'm going to redirect it to extension 3000. Okay? So we're going to go config T. And I'm going to create a voice translation rule. So voice translation rule 1, enter. And I'm going to define rule 1. And you're going to define a matching pattern. And the matching pattern is going to be contained within these forward slashes. And then we're going to define a substitution pattern, what to put in it. And it's going to be in a pair of forward slashes. So I said I'm going to, and this is regular expression stuff, so you'll want to see how Cisco uses regex. I'm going to use a caret, which means if the number begins with 614-555-1212, then turn it into 3000. I could technically do this and do an exact match, but I like using begins with in my rules most of the time. There are lots of different regular expression characters you can use. There's a $sign, which is used for matching expressions at the end of a line. You can have, it's just gobs and gobs of different kinds of regular expression variables and wildcards and things. So I'll leave that as an exercise for you to research. But this is the basic structure of a translation rule. Now that I've created the translation rule, I'm going to create a voice translation profile. And the profile is going to contain the rule. And then I'm going to apply the profile somewhere. So we're going to say exit, and I'm going to say voice translation profile, and we'll just call it inbound. Because remember, I'm going to manipulate inbound digits. And I'm going to say translate called 1. So the 1 is going to revert back to this voice translation rule 1 that we had. Now, so I've got a profile, and I've tied it to a rule. Now, I'm going to put that on a voice port for inbound calls. So let's take a look and see what we've got here. Show ISDN status 0000. So we're going to go voice port 000:23. And I'm going to say, now that I've got it on the voice port, let's see here. Let me go translation profile. And then we're going to say incoming or outgoing. So I'm going to say incoming. And then I'm going to give it the profile name, which was inbound, I think is what I called it. Yeah, I called it inbound. And I'm going to hit enter. So now, what should happen And if it doesn't, I'm going to not cut it out and we'll troubleshoot it together here in real time. But what should happen is I'll make a call across the PRI coming in from the PSTN. I'm going to present 614.555.1212. And what should happen is I should match it. I'm going to rewrite the destination to 3000, and I should ring a phone. So let's see if that's what happens. In fact, let's see if I've got any debugs on. I do. I like Q931. We'll go ahead and leave those the way they are. So I'm going to say 614.555.1212, and I'm going to hit the hook and dial, and whoops, term 1 would be helpful. So you actually missed the debug. You can probably hear the phone ringing behind me in the background. I'm going to end the call, and we'll place it again with a slightly better debug output. So here we go again, 614.555.1212, send. So extension 3000 is now ringing, and you'll see I dialed, the called party was 614.555.1212. But extension 3000 is ringing because we leveraged that voice translation profile. So this is a good example of how you might match a DID number that is not a pattern match to, or not an obvious pattern match anyway, to the destination device you want to ring. You can also manipulate the calling party or the caller ID information like I showed you before. But for me, primarily, I'm messing with called party information. So we've applied it to the port. Now there's, I really made a simple rule. That was kind of a get your feet wet kind of rule. There's so many things you can do with input and output strings. Let's talk about what some of them might look like. So we'll go again to voice translation rule 1, and then we'll say rule 2. We'll create another rule under it, and we'll say match anything that begins with a 9 and turn it into nothing. So basically, we're going to do a digit strip. So that's a pretty straightforward way to do things. In fact, let's make a call from the PSTN. I'm going to dial 9. Whoops, that's not what I wanted to hit. I'm going to dial 93000. We're going to strip the 9, and it's going to ring 3000. So we're going to say 93000 dial. Whoops, I didn't have quite enough digits there. That was 9300. So 93000 dial. So we're stripping the 9 that I've got coming in, and we're ringing 3000. So again, another very simple example. Well, let me give you a show run, just so you can see what this translation structure is taking on. So here it is, voice translation rule 1. So I've got 2 rules that we've put in there so far, and we're dealing with these at the inbound voice port. So let's create some more complex rules. Voice translation rule 1, and we'll say rule 3, begin, and we're going to match anything that starts with, let's see here, a 3, 4, or a 5, ... and we're going to convert it to 3000. All right, so if I dial 3000, 3001, 3099, 4000, 5000, any of those numbers, we're going to turn into a 3000. So let's see if it works. So I'm going to dial a 5. Whoops, hang on, ignore that. I hit send too fast. I'm going to dial 5000. And it's going to, come on. I'm missing digits here. Got some sticky keys on my test set. 5000 send. 5000 is ringing in. I'm matching that translation rule and ringing extension 3000. If I want to dial 4206, again, I'm matching that same rule and continuing to ring extension 3000. So lots of really, really cool things you can do with these voice translation rules. Let me show you a couple more examples. Voice translation rule 1, rule 4. Let's say that we want to, I don't know. Let's rewrite it. Let's do a complex pattern. So rule 4, if it starts, actually not starts, we're going to say special character, okay, 9, backslash, and I'm reading this out of an example in a textbook, so keep in mind, you have to spend some time and create your own scratchpad of a regex to use. So it starts with a 9, or has a 9 special character, parentheses, and then you'll see that I'm putting these escape characters between the parentheses. And then we're going to say, boom, begins with 1, 0. And forget me saying begins with, I'm just kind of talking to myself as I think through this. Dot, star, backslash parenthesis. All right. So there's our match pattern. And then we're going to turn it into / backslash 1 614 2 / I screwed it up. There was no way I was going to get that perfect the first try. So we got parentheses around the 9s. We've got brackets here, and we're going to need a parenthesis before the bracket. There we go. Much better. Now, what's going to happen is if I call 9 555 1000, it should convert it to 9 1 614 555 1000 if I wrote the rule right. Like I said, I was referencing another example here. But what I'm going to actually do is we'll put that number on a phone. So config t ephone dn2 number. And it should be 9 1 614 555. Where did I say 1000? All right, now let's see if it actually works. So show run. And here are the rules we have. And actually, I've got to reset my ephone. ephone 2, restart. And the rule I'm going to try to match is this last one here, this rule 4. So I'm staring at the phone, and it looks like it's back up. So I'm going to call 9 555 1000, send. Unassigned number. It did not like me. 9 555 1000. Let's look at that rule and see what I'm doing wrong. We'll pick it apart a little bit here. Some of the fun of trying to do these things on the fly. So there we go. We've got it on our clipboard. We'll go ahead and throw it into a notepad here. And let's work the logic out. So if it begins with so first digit would be a 9. And then begins with 1 or 0, so 1, then a dot star, dot star. So a dot is going to mean match any single character, and then star is going to repeat the previous regex 0 or more times. So that's like a 4-digit pattern so far, or more. So 9 1 something, and then whatever else as a length. So that's our match. So for example, if it was 9 1 6, and then now we're to star. Actually 9 1 and then 5 5 5 1 0 0 0. So 9 1 5 and then 5 1 0 0 0. So that's where we are so far. And we're going to take that and we're going to say turn it into, let's see here. The rule we have is a backslash 1614. A backslash is a special meaning of the next character. So /1. So that has to do with variable pulling from the beginning. Okay, and then 614 /2. Okay, so 9 pulls over 1614, and then that should be 555-1000. But clearly something's not working there. So let's do this. You know what? I think it makes sense on paper. Let's see what's actually being translated, and we'll pick it apart from there. There's a way to do a test on a pattern and on a voice translation profile, and it'll make it a little bit easier to diagnose what's going on. So let's do a test on that. Let's say test voice translation rule. The number is going to be 1. We're going to type the input number, which is going to be, what did I say I was going to dial? I was going to dial 9-555-1000. Enter. Matched with rule 2, and it translated it to 555-1000. Well, wait a minute. Rule 2, aha, I have some overlapping rules. Let's get rid of rule 2. Voice translation, rule 1, no rule 2. And this is exactly the kind of stuff that I run into, all the time when dealing with dial plan on gateways. You have things that overlap, and it's not apparent and obvious why they don't work, so you've got to pick them apart like this. This is actually a really good example. So let's run that test again. 9-555-1000. So we're turning it into 9-3-0-0-0-0. Okay, that's interesting. We matched rule 3. Again, an overlap problem. So let's get rid of rule 3. No rule 3. Once we finally hit that correct rule, I think we're going to like our results. Much better liking the results. So our original number is 9-555-1000. And our translated number is 9-614-555-1000. I forget if I put a 1 on that phone. I may want to add one more digit in there. Let's show run, and let's take a look at what I put on that ePhone DN. ePhone DN2. Yeah, I put a 1 in there. So actually, I'm going to change the digits here. And we're actually going to put the 1 in there. So show run. We're going to pull that translation rule stuff up here. So there's rule 4. We're going to modify that here, and we're going to put an additional 1 here. That should do it. Voice translation rule 1, and then rule 4. I wonder if it'll let me update it. Whoops. Too many. Let me do this. Paste. There we go. It did let me update it. Let's run that test again. There we go. Now we're getting the 9-614-555-1000. So I'm going to make the test call on my PRI here. So 9-555-1000. 9-555-1000. And make the call. And there we go. We've expanded it to the ePhone DN2. And we're ringing the phone with 9-1-614-555-1000. So very, very cool. I think we've shown you the power of these voice translation profiles and translation rules. And I want you to experiment with them on your own and create some translation scenarios that you would use to do some goofy things. You're going to run into these kinds of problems more often than not in a production environment. And it's important to understand exactly what's going on. So I think with that, we've covered the critical components of implementation of dialing. And, we talked before about how dial pairs match in other videos. So I think you've got a good understanding of how that's functioning. We've talked about, outbound preferencing and how to do those kinds of things. I think all of our inbound matching we've covered. We've talked about examples for prefixing and stripping and doing regex. Really, the only thing I think we haven't covered yet, and I'm going to save it for the last video in this sequence because it's a topic of its own. And in fact, I've got some really good coverage of this in my CCNA voice class, and that is class of restriction. And really, you're more often going to use class of restriction, or COR, in a CME type environment. Not so much in the role of a voice gateway, but I'm not going to go any deeper than that. We're going to save that for the last video. So for now, play with regex, play with voice translation rules and profiles, and inbound digit stripping, and outbound stripping, and prefixing, and forward digits, and you'll have a really good understanding of the core concepts necessary to successfully program gateways, manipulate digits, and take you through the CCNA voice, as well as this course, the C-Voice exam. So thanks for watching, and I'll see you in the next video. In this module, we're going to follow up with the last piece of dial plan implementation logic that I want you to understand, and that is implementing class of restriction on a gateway or CME. So what I want you to focus on in this video is the CME portion of things. And in fact, what I'm going to show you is a snippet of video that I did as part of my CCNA voice video series. I think it was a really good example and fits this lecture well. So there's no sense reinventing the wheel. We're going to just go ahead and launch into that content and talk about dial plan implementation and class of restriction on CME. All right, so what I want you to keep in mind when understanding core lists is the concept of an incoming and an outgoing core list. Now, there's more than one way to configure this, and I'm going to show you one common example. Keep in mind that there are you can do it backwards of what I'm doing. You could use core lists if you wanted to restrict inbound calls to certain destinations. But the example I'm going to show you, pretty straightforward. I'm going to control who a directory number can call. All right, so check this out. The first thing we're going to do is go to config T. And we're going to say dial peer core custom. We're going to create a tag called 911. So name 911. We're going to create a tag, name local, and we're going to create a tag, name LD. Incoming core lists, or core lists applied, in my example, keep this in mind, in my example, are going to be applied one or more tags. The tags applied are going to be matched against the tags required by an outbound core list. So let's go ahead and create the core list and apply some tags. So exit. We'll say dial peer core list, and we'll create the incoming ones first. And actually, no, let's create the outgoing ones first. Keep it simple. We're going to call it outgoing 911. This is going to be applied to the 911 dial peer. So we're going to say member 911. Exit. We'll say dial peer core list outgoing local, and we'll say member local. And we'll say dial peer, let's type it right here, core list outgoing LD. No space. There we go. Member LD. So we've created 3 core lists, and we'll show them to you here. Outgoing 911, outgoing local, and outgoing LD. These outgoing core lists are going to be applied to the dial peers. So for my dial peers, config T, dial peer voice 911 pots, which is my 911 pattern, we'll say core list outgoing 911. And we'll do the same one for 912 here. So those are our 911 core lists. For dial peer voice 101 pots, which is our local calls, our 7-digit calls, we'll say core list outgoing local. For 102 and 103, which I'm considering long distance, we're going to assign the outgoing LD. All right, perfect. show again, show run, pipe again, dial, peer, can't see what I'm typing here. Dial, peer, core. There we go. So we've got our dial pails programmed, and we've got our outgoing core lists programmed. Now remember, the outgoing core lists in this example are being applied to the dial pairs. We're going to go and create our incoming core lists. Config T, and we're going to say dial peer core list incoming local. And we're going to say member. Actually, you know what? Let's do 911 first, just to keep it in order. Incoming 911, and we're going to say member 911. Then we're going to say dial peer core list incoming local, and then we're going to say member 911 member local. So you can see that this is additive. So I'm on the directory number, which is where we're going to assign these, going to tag as 911 or local or LD for, depending which core list I'm in. And we're going to say dial peer core list incoming LD. We're going to say member 911, member local, and member LD. So let's go to our ephone DNs, exit. We'll say ephone DN1. We're going to allow this guy to dial 911. So we're going to say core list incoming 911. ephone DN2, we're going to allow him to make local calls. ephone DN3, we're going to allow to make long distance calls. And that pretty well sums up what you're going to need to understand from a core list configuration perspective for the CVoice exam. I stopped shy of walking through any kind of interactive testing and such because, like I made notes on the screen, those dial peers weren't optimal. We would have had some overlaps and problems with call routing there. But, this was more about core lists, not so much the dial peers. So if you can walk away from this and understand that core lists are used by CME to create some call routing restrictions and enforce those on an ephone DN level, you should be good to go for the CVoice exam. So with that, I'm going to say thanks for watching. Hopefully this information was informative to you. We're going to move into the next video, really into the next section even, and start talking about gatekeepers and then Cisco Unified Border Element, or Cube, which is a session border controller. So lots of fun stuff to come. Thanks for continuing to stay tuned. I know some of this is exciting and awesome. Other, is a little theory dry. But we'll do the best we can to keep things upbeat here. So thanks for watching. Good luck with your studying, and I'll see you in the next video. In this module, we're going to be discussing a feature set we call Cube, Cisco Unified Border Element. Cube is one of those things that's, to many people anyway, seems fairly new. However, the base functionality of a cube and what a cube does has actually been around for quite some time. We're going to jump right into things, and I'm going to give you a basic cube primer in this video. And following this up, we'll get into some configuration exercises and show you exactly how to implement and leverage Cube in your environment. Like I mentioned before, Cisco Unified Border Element is the name of the product. And you may know Cube by its feature set description and what it does, or maybe even what Cisco used to call it, which was the IP to IP gateway. In fact, if you go back to like iOS 12 and, 5, 6, 7 years ago, I'm guessing off the top of my head here, the first time I heard this technology mentioned, we were calling it IP to IP gateway. But these days we call it Cube, Cisco Unified Border Element. And what Cube is it's a session border controller. And Cube is a gateway. I don't want you to think Cube is a separate product you go buy, although, everybody knows that Cisco is a license-happy company, and these features are things you have to purchase licenses and entitlements for. But Cube itself runs on a traditional voice gateway and differs primarily in the way that, and in fact I'm going to show it to you, that both dial pairs are VoIP. So think of Cube as a feature set and not a product. That doesn't mean it's free, but Cube is feature enablement of a iOS gateway that you already have. What are Cube's main responsibilities? Well, first and foremost, Cube, as a session border controller, terminates RTP and RTCP. So it's terminating SIP and H.323 IP data streams. It provides border interconnection services, and it's a session border controller. So what's this mean to me? Well, one very popular scenario for where you would deploy a cube is at your perimeter. If you're doing business-to-business internetworking between your IP network, your IP-enabled voice network, and someone else's IP-enabled voice network, you'll typically interconnect these systems via a cube at your perimeter, or perhaps one at both perimeters. When we look at cube functionality, there are a number of different core features and pieces of functionality that Cube are providing. And this is just a short list. There are other features that Cube can provide you. But first and foremost, like I mentioned, H.323 and SIP signaling internetworking. So this lets me have my call manager signal my cube, and your call manager, or perhaps even your cube, signal my cube. And it's a demarcation barrier, so it's almost like a voice firewall. It provides for DTMF internetworking. Because we're looking at different kinds of VoIP dial peers, one dial peer may perhaps be RTP-NTE or RFC based, and the other may be H.245 alphanumeric. And we need the ability to convert between the two. So DTMF internetworking. Codec transcoding, just like another gateway is providing codec translation and transcoding services, Cube can continue to do that. Address and port translations for privacy and address hiding. This is a security feature, but also an internetworking feature. Maybe we've both got 10 networks and they overlap, but we need to be able to internetwork with each other. So long as our cube or cubes have public-facing IP addresses, we can signal to Cube, and it can signal to us, and it can handle dealing with those network discrepancies. And Cube can also provide call detail reporting normalization for billing features on a VoIP-enabled network. So when we really start looking at Cube versus a traditional voice gateway, what you'll see with a traditional voice gateway is that it interconnects an IP network with a non-IP network, such as in this example, a PSTN. Our gateway would typically have a VoIP dial peer, commonly H.323 or SIP, but perhaps it's an MGCP controlled device as well. And it would have POTS dial peers connecting to analog or digital telephony services. So that's your traditional voice gateway. Cube doesn't look a whole lot different, except that it's an IP network on both sides. So we've got either an H.323 or SIP connection to one network, and an H.323 or SIP connection to another network. And a cube is going to have voice over IP dial peers on both sides, or for both call legs. Cube capabilities, can coexist with normal gateway functions. This is just enabling a gateway to do something it wouldn't normally do, and that is terminate an IP call leg to another IP call leg. When we look at the role of Cube in the enterprise, it can be used to service internal connections, and the reason we would do this, perhaps I have two call manager clusters, and I'm going to interconnect them with a SIP trunk. But I'm actually going to run the SIP trunk to a cube. So call manager A has a SIP trunk to cube, and call manager B has a SIP trunk to cube. I can now leverage the cube as a point of demarcation. I can do things like digit manipulation, etc. Externally, we can use cube as a point of service demarcation, and it gives us capabilities of address hiding and ease of integration with external business-to-business connections. More about Cube in the enterprise. There are a number of different features, and I'm going to show you over the next 2 slides many of those features, but there are some that I have omitted from the list to keep it a little bit on the brief side. 2 pages was enough. But protocol support, like I mentioned previously, both H.323 and SIP are supported protocols for a cube. The cube is capable of doing network and address hiding, which is both an interoperability convenience as well as a security feature. So it can handle hiding IP networks and performing these address translation functions. Cube does support call admission control, leveraging RSVP, which, let's be real, hardly anybody uses. This is pretty much a non-RSVP world. But it is there, and it is supported if you're in an environment that requires it. And you can use this type of call admission control to manage the maximum number of calls per chunk. Among other RSVP stuff that, is just normal RSVP. We've got protocol and signal internetworking capabilities for IP protocols to IP protocols. So H.323 to H.323, H.323 to SIP, or SIP to SIP. We've got media support for RTP and RTCP. And we have 2 media modes we can leverage with Cube. And I'll show you a drawing of this in another slide coming up here. But we call them media flow around and media flow through. Cube can support video with H.261, H.263, and H.264. And it supports transport modes of TCP or UDP, as well as TCP to UDP internetworking. Additional features and functionality provided by a cube, DTMF internetworking. So maybe, like I mentioned before, one of my VoIP dial peers is using H.245 alphanumeric, and one of them is using RFC 2833. We can support that. So DTMF internetworking. We've got support for fax and modem, relay and pass-through in various combinations. We've got supplementary services for hold and transfer and forward using H.450. We've got hold and transfer sub-services for SIP. And then we've got the H.323 to SIP supplementary service support for things like media termination points. Cube can provide for NAT traversal and do stateful NAT traversal. It can do QoS marking and remarking for IP precedence and DSCP. It has multiple codec support and can transcode between codecs. It gives you security capabilities with IPsec and secure RTP and TLS, and there's other features that I haven't got into, but this kind of hits the high point of talking about some of the capabilities of a cube. So it's more than just a gateway. It's kind of like a gateway on steroids. When we talk about cube protocol internetworking, we've got support for a couple of different modes, and there are different features that are supported depending on which mode you're using. So for H.323 to H.323 internetworking, so I've got 2 networks that are both H.323 interconnecting with cube. I can support all combinations of H.323 fast start and slow start. If we're doing H.323 to SIP, I can support H.323 fast start to someone doing SIP early offer, and I can support H.323 slow start and SIP delayed offer in combinations. For SIP to H.323, I can do SIP early offer to H.323 fast start, SIP early offer to H.323 slow start, and SIP delayed offer to H.323 slow start. And we talked about these techniques at length in a previous video in this course, so these should be still something in the front of your head. And with SIP to SIP, we support all combinations of early and delayed offer. So lots of capabilities here for protocol internetworking. This is pretty cool. Cube can do this thing called media flow around or media flow through. And really what you're going to choose to use is kind of depending on why you're using a cube. With media flow around, let's take a look at an example network here. I've got a cube with 2 call manager clusters interconnected. And let's presume that these are both on my network, or they're on a common infrastructure that can communicate end to end. Well, with media flow around, the cube is not involved in the RTP portion of the call. So the call manager will signal to cube for call setup, and cube will signal to the other call manager. But in the end, the IP phones will exchange media directly. That's what we call media flow around. It flows around the cube. And it's pretty lightweight on the cube. It doesn't tax a lot of resources. Media flow through in a similar network topology. Again, signaling between the call managers and cubes, but the audio stream from the IP phone is also going to flow through the cube, hence media flow through. This does present a higher CPU load on cube than just doing signaling. But again, if you're doing address hiding, and this is sitting at the perimeter of your network, this can be a very useful feature to have, because there's a good chance that the endpoints at either end can't talk to each other except through the cube, so hence RTP streams flowing through the cube. So very, very cool. Cube can either support codec transparency or codec filtering, and it really depends on what you're trying to achieve. But basically, keep in mind, Cube is just a router with the capability of interconnecting, multiple VoIP networks, via the dial peer. So the same kind of codec selection choices that you have available traditionally continue to be available with Cube. If you use transparency, the endpoints are going to directly negotiate their codecs. But if you use filtering, you're capable of negotiating a preferred codec. So if I look at IP network A and B, they both support G711 ULAW and G729B, but the cube is configured in such a way that it is only going to internetwork with G711 ULAW. So we're going to force the calls to use that particular codec. Now this can come in handy when you're dealing with an internal network with lots of codec support, and you're using Cube as a demarcation point for a carrier-provided SIP trunk, perhaps to the PSTN. And maybe this carrier only supports one codec. So we can enable, some negotiation of these codecs. And finally, Cube supports RSVP-based call admission control. Again, not a lot of people use an RSVP out there. I wouldn't call it dead, but I am saying that it's not as popular as some of the other methods. But Cube can support both audio and video calls and leverage RSVP capabilities for CAC. If you're doing RSVP-based CAC, it does require at least 2 RSVP peers. Now that should be pretty obvious to anyone who is supporting RSVP in your network, because obviously resource reservation is kind of a collaborative, interactive process. If you don't have multiple endpoints to talk it, it's not going to do you any good. So it does require at least 2 RSVP peers. And when you're doing RSVP-based CAC, media flow through is required. So this hits the high points on what Cube is and what it can do for you. In the next video, we're going to get into describing some of the Cube call flows and exactly how things work. And then we're going to jump into some setup and actually do some basic Cube provisioning. So I'm going to leave it at that, and I'll see you in the next video, and we'll play around with the Cisco Unified Border element in the CLI. So good study. Thanks for watching, and I'll talk to you soon. You'll have to forgive me this evening. It seems like whenever I'm super excited about an episode or a video to record, something pops up. Either I get sick, I get the flu, I get the hiccups, or whatever. Tonight is one of those nights. I've got the hiccups, so I'll apologize in advance. And I'll try to keep from being annoying and skipping a beat there during the video presentation. But tonight I want to talk about Cube, and I really don't want to wait. I want to kind of go through this. We've gone through Cube fundamentals, and we have covered the what is Cisco Unified Border element, and we've covered what are the features and what kind of things can you do with Cube. I want to walk you through a basic Cube configuration, and that's really what this video is all about. I want you to think about Cube call flows, and I want you to consider that we have options for media flow through and media flow around, and you'll want to select the configuration most appropriate to your environment, based on what your goals are for Cube. I also want you to consider the H323 to 323, the 323 to SIP, or the SIP to SIP feature support necessary for your environment. If you'll recall, relative to support for things like early offer and early media, etc., there are different rules that apply and different things that are supported and that are not supported. So, keep those in mind, and you should be good to go. Keep in mind 323 to 323. Any combination of fast and slow start on both call legs is supported. SIP to SIP, any and all combinations of early and delayed offer are supported on both call legs. 323 to SIP, fast start to SIP early offer, and H323 slow start to SIP delayed offer is supported. And SIP to 323, SIP early offer to 323 fast start, SIP early offer to 323 slow start, and SIP delayed offer to 323 slow start are supported. When configuring Cube, you want to keep in mind this is just like any other voice gateway. We've got an inbound dial peer, we've got an outbound dial peer. The same rules we leverage to match a dial peer applies, and really the only thing that's unique is that both call legs are IP based. In the example we're going to show, here's the architecture of the lab environment, or the nodes that we're using in the lab environment anyway. We've got the Cube here in the middle, the big blue box. It's a iOS router. In this case, it's a 2811. It's that HQ router we've been using. And we've got two IP networks. And really, I'm showing you a capability of Cube that you may use it for. This is an enterprise kind of model, but this same model could apply equally to an external interface of Cube. So I've got two call manager clusters, and I want to build a SIP trunk between them. But I want to run it through Cube to give me an additional point of demarcation. Perhaps they live on the same network and then they're in the same data center, but they're managed by two different business entities or two different arms of a business that are under separate management domain. So we've got 10.10.2.10.10, which is a call manager cluster, and 10.10.2.10.80. I'm going to go ahead and pull down a terminal window here. And we'll make this a little bit bigger. And we're going to walk through basic Cube configuration. Now this is that same 2811 we've been doing a lot of testing on. And I've ripped out pretty much all of the voice configuration. CME is gone. The dial peers are gone. It's pretty much a router at this point. The first thing you're going to do when configuring Cube is configure protocol internetworking. To configure protocol internetworking, you can turn on whatever features you're trying to use. And it all starts with voice service VoIP. Now, I want to show you all of the different options available to you under voice service VoIP. And I want to draw your attention to the second one, allow connections. Allow call connection types. This is really where we're turning on Cube features. I'm going to say allow connections, and I've got a source or a from type protocol selection. So I'm going to say allow connections SIP to SIP, and I'm going to say allow connections SIP to H323, and allow connections SIP, H323 to SIP, and allow connections H323 to H323. So I've turned on kind of the whole matrix of protocol support. And you'll see it here under voice service VoIP that we've turned on those protocol internetworking components. And the next thing we're going to configure is DTMF relay. And DTMF relay is one of those things that's going to happen on the dial pair. And really, we're going to configure more than DTMF relay. We're going to create the dial pairs. I could assume they're already there, but we're going to go ahead and create them from scratch here. Let's go config T. We'll say dial peer voice 100 VoIP, and we'll say destination pattern, 5 ... It's an example. And we'll say session protocol, hang on, what am I doing wrong here? I gotta spell it right. Session protocol SIP v2, session target IPv4 :10 10 to 10 10. So that's the first call manager. Whoops, what have I done wrong here? Session target IPv4 :10 10 to 10 10. It doesn't like something here. What have I done that it doesn't like?
Session. Session. I keep missing the I key on the keyboard there. Target. IPv4 should be fine. 10, 10, 210, 10. Well, that time it worked. Maybe I had an extra space or something in there. Anyway, we've set our session target. And we'll do a show run here, and I'll get to the bottom, and I'll show you the dial peer we've created. This is one of 2 VoIP dial peers that we're going to be using to point to our call manager clusters. And you'll see there it is, dial peer voice 100 VoIP, destination pattern 5 ... session protocol SIP-v2, and session target IPv4 1010 21010. Now let me go ahead and create another one. Config T, dial peer voice 200 VoIP, destination pattern, and we'll say 6 ... session protocol SIP-v2 session target IPv4 :1010 So that's the other one. So we've got 2 dial peers, and this is pretty much a vanilla kind of configuration on the gateway. Now, if I want to configure DTMF methods, and let's say that one of my connections, well, they're SIP to SIP, so I'm gonna back up for a second. Because they're both SIP in this example, I'm probably going to be using the same DTMF relay method. With SIP, you've got 2 choices. You've got RTP-NTE, which is RFC 2833 based DTMF relay, and that's an in-band DTMF relay method. And with SIP, you've also got SIP notify, which is an out-of-band method. Let's go ahead and say on this one that we want DTMF relay RTP NTE, and then we'll go back to that other dial peer 100, and we'll say DTMF relay, and we'll say SIP notify. So there you go. We've got a cube. We've got our dial peers configured. Voice service VoIP will allow SIP to SIP, which is the example that we're doing here. I'll get down here and show you our dial peers. There's our dial peers. One dial peer, or one call manager cluster, is using SIP notify. The other one's using RTP NTE. Enjoy your cube. It's really that simple. I mean, cube is a gateway. There's nothing all that crazy different in building a cube to building a gateway. Now, there's other things we haven't configured here. We haven't configured our media type. So let's go ahead and let's tell this one, for whatever reason, that it's going to be a media flow through. So let's go to, let me get in here real quick. It's going to be on the dial peer. So config T, and say dial peer voice 100 VoIP. We'll say media flow through. And then we'll go to the other dial peer and media flow through. Well, there you go. Now you got a cube that supports media flow through. I mean, are you getting the picture how easy this is? If we wanted to configure H323, it really wouldn't be all that different. In fact, let me do show run pipe again, dial peer voice. We'll show you the existing dial pairs. Here's 100 and 200. We'll go ahead and convert 200. Let's say that for whatever reason 200 is now a 323 gateway. So we'll say dial peer voice 200 VoIP VoIP, and we'll say session protocol. Actually, I'm just going to say no session protocol SIP-v2, and that'll peel up back to standard H323. We can leave the SIP session target the same. Since we're H323, we're going to need a DTMF relay type that is supported under H323. And you'll notice I've got different options here. Because I'm 323, and because I understand what cube supports, I'm going to say H245 alphanumeric. So now you've got a cube, show run, that's supporting H323 or 323 to H323 or 323 to SIP. Either way, depends who's originating the call. One of them is using SIP notify, and the other is using H245 alphanumeric. And cube will take care of the rest. So, what are commands you can use to troubleshoot cube? Well, one of the commands, show, and there's no calls active, but we'll show you what it would be. Show call active voice. Same kind of command we're going to use on any other kind of gateway. Show call history voice.
another good one. There's not a whole lot going on this gateway. Show dial peer voice, and I like throwing summary on there at the tail end to see what dial peers are in there. But let's say I didn't put summary on there. We've got a lot of detailed information relative to the individual dial peer configuration, probably more than you thought you'd ever need to know. If we have calls in progress, a show VoIP RTP connections is useful, and there's no active connections on this server right now. You've also got some debugs you can run. Debug VoIP IP gateway, can give you some good cube debugs. Debug CCH323 all is useful. Debug CC-SIP messages, that's kind of my new favorite debug of all type, good for debugging SIP. If you need to get into the H225 and H245, there are various debugs for that. So debug H225, 225, question mark. You've got events, Q931, ANSI, etc. Or H245, you've got ASN1 events or SRTP. So we're covered there. And then really the other big one, debug voice, the one I hate more than any other debug in the world, CC API, in out. Will tell you everything you never wanted to know about what's happening in your cube or in your gateway in general. So that kind of covers the high level of basic cube configuration. I told you it wasn't difficult, and it's not all that different from a normal gateway. You've just got to think about it a little bit differently. Certainly there's lots of features you can leverage that we haven't touched on. They're well outside of the scope of the C-Voice exam, but they are things you should spend some time getting your arms around. So I would encourage you to spin up a couple of call manager clusters, build an H323 gateway and a SIP trunk, and set up a cube and try to route some calls between these things and play with the different DTMF relay options and the media flow through versus flow around. And if you really want to get into some interesting stuff, when you're integrating with the cube to, for example, an ITSP or an IP telephony solutions provider or service provider, think of it as a telco over a SIP trunk. You're going to find that they have all kinds of different rules of what they'll let you do on the SIP trunk relative to cube. And you'll get into things like modifying SIP diversion headers and, for call transfers to work and all kinds of lovely stuff. So a lot of fun to be had with cube, lots of features, but yet not really that complicated to set up. So hopefully this video has been informative to you and has given you a good summary of Cisco Unified Border Element and what you need to understand relative to the C-Voice exam. In the next set of videos, we're going to talk about gatekeepers, the technology that seems like it's been around for a long, long time, but yet hardly anybody is still using because there are better and smarter ways of doing things. But I digress. I'm not going to pass too much judgment on Cisco. I can't be a hater for having options with technology. So anyway, thanks for watching. Good studying, and I'll see you in the next video. In this module, we're going to give you an introduction to gatekeepers. Now, I've got to admit, I hate gatekeepers. I really do. Gatekeepers come from a time when H323 ruled the land, and we used gatekeepers as a way to globally distribute H.323 dial plans and endpoint information. Think of it as kind of like a dynamic routing protocol where we're routing by rumor and saying, I've got these guys, and another router says, well, I've got these guys. It worked. It's still used somewhat, but from a design perspective, we tend to do things a little bit differently. So you're not going to see as many gatekeepers in modern networks that you would have, say, 15 years ago or 10 years ago even. So times have changed a little bit. But that said, understanding gatekeepers is still part of the C-Voice exam, and it's something you're going to need to understand, particularly in larger enterprise networks. So let's jump right in and talk about gatekeeper technology, how it's used, and a little bit of the fundamental concepts. And then in the next video, we'll go through some basic gatekeeper configuration. First off, Understanding the role of a gatekeeper. What a gatekeeper does is it allows us to globally distribute an H.323 based dial plan. So, for example, we're going to be able to advertise what endpoints we have registered to us. And it allows for local dial plan control. And what I mean by local dial plan control is that a given gateway can have its resources, or not even a gateway, a given call manager, for example, can register with a gatekeeper. A given endpoint or group of endpoints can be shared with from a gatekeeper to another gatekeeper. So I'm kind of rambling here, but here's a good drawing. It demonstrates it way better than I can explain it. So let's say I've got two gateways here, and a gateway's let's say these are CMEs or whatever, and we've got endpoints on them. The left one has 5001, 5002, and 5003 extensions, and the one on the right has 1001, 1002, 1003. And up here in the middle, we've got a gatekeeper. So each gateway can tell the gatekeeper what endpoints it's in control of, and make the gatekeeper aware of where endpoints are on the network. What are the responsibilities of a gatekeeper? Well, there are both mandatory and optional responsibilities of a gatekeeper. The mandatory responsibilities on the left are going to include things like address resolution. So if I'm an H.323 gateway, and I've got a call coming in from the outside, and it may have an E164 address or an alias assigned to it that we're going to use to route that call. So address resolution, of those addresses to an endpoint would be one role of a gatekeeper. Admission control, bandwidth control, zone management, those are all mandatory responsibilities of a gatekeeper, and those are the core things that they're going to do. Optionally, a gatekeeper can do call authorization based on policy, maybe some time of day policies. It handles call management, so if an endpoint is busy, it can redirect a call perhaps. And it can reject calls, do bandwidth management if insufficient bandwidth exists. So lots and lots of things can happen within the realm of a gatekeeper. And like I mentioned here, a call manager cluster can register with a gatekeeper. Endpoints, non-call manager can register with a gatekeeper. We saw a lot of video endpoints doing this back in the day. And each endpoint can be registered in one zone. And we'll talk about zones when we get into actual configuration of gatekeepers, but I'm going to kind of keep that out of this video for now. When we talk about the gatekeeper call process, endpoints are going to register with the gatekeeper at startup. So you're either going to go through an auto discovery process, or you're going to be programmed with the IP address of your gatekeeper. And we'll talk about that, those options here in another couple of slides. But you're going to register with the gatekeeper at startup. And when you want to place a call, you're going to request admission. You're going to send a message to the gatekeeper and says, I want to place a call. And it's going to look and see, can you place a call to the endpoint you're requesting to place a call to? Is it busy? Is it available? Do I have any idea where it is? And it's going to send you a message back and either accept that request and confirm it, or reject it. And more about that as we go. If the gatekeeper accepts the request, it's going to return to you, or return to the originating endpoint, a destination IP address. So you're going to know where to go next. Gatekeeper signaling. I can tell you right now, this is something you're going to have to memorize. This is, at least the tests I've taken, your knowledge of this is something that they expect to be very thorough. So hint, hint, good test material here. Gatekeepers use H.225 RAS for signaling, or for the initial setup. That's going to be over UDP. Next, H.225 over TCP is going to be used to set up the connections between the endpoints. And if there's no gatekeeper present, that H.225 signaling is going to just happen between the endpoints directly. Once we've established the connection, we're going to use H.245 with TCP to establish the media flow, and then throughout the duration of the call, H.245 signaling is going to continue to manage that call. And here are those messages you're going to need to understand. Boom. I'm going to walk you through these and give you a basic overview of what these are used for. So it all starts off with gateway discovery messages. Endpoints are going to either use unicast or multicast to try to discover their gatekeeper. And we've got three different messages at play here: gatekeeper requests, gatekeeper confirmations, and gatekeeper rejects. A gatekeeper request message is plain and simple. It's a message that's going to be sent to the gatekeeper from the endpoint asking, it's a discovery message, are you there? A confirmation, a GCF, the gatekeeper confirmation, is going to be a reply from the gatekeeper indicating the transport address of the gatekeeper RAS channel. The gatekeeper reject is going to be a reply, again, from the gatekeeper, rejecting the request for registration. So there could be a number of different reasons I'm not getting into for that now. But I want you to see a pattern. We've got requests, confirmations, and rejects. And that pattern is going to apply to many of these different message types. So as we move on, gateway and terminal registration, we've got registration requests, registration confirmations, and registration rejects. We've got gateway and terminal unregistration, request, confirm, reject. We've got resource availability indicators, RAIs, and then confirmations. We've got bandwidth requests, confirms, and rejects. Location requests, confirms, and rejects. And the list keeps going. Yes, there's more. We've got, and these are really important ones right here, the first three. The admission requests, confirmation, and rejects. Those are what we're going to use when we try to request admission to place a call. We've got disengage requests, confirmations, and rejections. And we've got a request in progress message. And we've got some information request messages for status. So information request and response and acknowledge. We've got a negative acknowledgement or a NAC. And then we've got an information request confirmation. So lots of H.225 RAS messages out there. Again, it's just stuff you're going to have to commit to memory. And you'll want to read about all of these different RAS message types. There's way too much information here for me to get into in a video. This is something that merits cracking open a textbook and going through. So I will not try to explain them all in granular detail, but I do want you to understand the call admission requests, the ARQs, ACFs, ARJs, because we're going to use the heck out of those things. Talking more about the gatekeeper discovery process, I told you before that endpoints are going to attempt to register with a gatekeeper when they power up. And what they're trying to do is, discover a gatekeeper so they can register with it, and ultimately discover what zone they're a member of. And I told you I'll talk about zones when we go through the configuration video. So we're going to leave it at that level of detail for now. This discovery process can be either unicast or multicast. And this is one of those message types, the gatekeeper request message, the GRQ that we're going to send. If it's unicast, or if we're doing a unicast discovery, we're going to use UDP port 1718, and it's going to require static configuration of the gatekeeper on the endpoint. So I mentioned using this on video endpoints years ago. We would, literally we'd program an IP address, a subnet mask, a default gateway, and another one of those parameters we would set up is gatekeeper IP address. So that was a unicast-based discovery. You can also do a multicast-based discovery, which is going to use multicast address 224.0.1.41. And if you're doing multicasting for gatekeeper discovery, it is not necessary to have static configuration in your endpoint. It's just going to use multicast. And when you send this gatekeeper request message, you're either going to get a GCF, which is obviously what you hope for, a confirmation of gatekeeper registration, or a GRJ for a gatekeeper rejection. And again, that can be a number of different reasons. Usually these are configuration-related errors, but other things can happen there. Gatekeeper re-registration. Back early on with H.323 prior to version 2, so we're talking H.323 version 1, a gatekeeper and an endpoint, there would be a registration event take place every 30 seconds, in full effect. It would basically be a gatekeeper request, gatekeeper confirm, gatekeeper request, gatekeeper confirm, every 30 seconds. Well, that was kind of overhead on a network that really wasn't necessary. So in H.323 version 2, we came out with lightweight registration. And what's going to happen with a lightweight registration is you're going to send a registration request just like you normally would. And it's going to contain a TTL value. If it doesn't, the RCF coming back to you is going to have one added into it, and it's going to return you a TTL value. Shortly before the expiration of this TTL value, the endpoint is going to send an updated RRQ message with a keep alive field in that message set to true. So we're shortening the process here, and obviously if you expire those TTLs, you do it, eventually the thing's going to fall off the map. But more about that later. Let's talk about a couple of these messages in detail. The more critical messages, the things that are going to make or break base Gatekeeper functionality. The first one is the call admission stuff, the ARQ, which is an admission request, an admission confirmation ACF, and an admission rejection ARJ. So to place a call, the endpoint is going to send an admission request message to the gatekeeper. The gatekeeper is going to look at the endpoint, check its status, see if it's busy or available, or able to have a call routed to it. And the gatekeeper is going to return a confirmation or a reject message. So you're going to send an ARQ, and you're going to get back an ACF or an ARJ. That's simple. That's your call setup process. Information request messages. This is the last one I want you to have an understanding of. They're sent periodically to all registered endpoints. This is basically, endpoint death detection. It's sent to verify that the endpoint still exists. If we don't receive a response, an information request response, the IRR, the endpoint will be considered dead and aged out of the system. With that, we've covered basic gatekeeper concepts, or at least the high-level stuff anyway. We're going to get into a little bit more. We'll talk about zones and configuration in the next video, and that'll pretty much wrap up this section of the course. Once we get through that, there's not a whole lot left. We're going to talk about quality of service, and you should be in pretty good shape for final preparation towards your CVoice exam. So I'm going to wrap this one up. I'll see you in the next video. We're going to do some configuration to gatekeepers, and then we'll move on to QoS. Thanks for watching. Have good studying, and I'll see you in the next video. In this module, we're going to go through some basic gatekeeper configuration. Did I mention that I hate gatekeepers? I want to be clear. It's not because they're difficult or challenging. I just think that we've reached a point where there are better ways to do things. But if you ever have the need to configure a gatekeeper to distribute some H.323 dial plan among your enterprise network, you'll have the skills and knowledge necessary to do so. Now let me start off by saying that configuring gatekeepers is really, really easy. I mean, this is not a crazy process that is some big magical mystery. It's really pretty straightforward. I'm going to walk you through the most basic configuration examples and talk a little bit about how this works. And that should be adequate to cover what you're going to need to understand to successfully pass the CVoice exam, and really to deal with gatekeepers if you ever do cross paths with one. Let me go ahead and start by bringing up a connection to our router here. This is the same 2811 we've been playing with all course. I love this hardware. It works really well for me. And I want to tell you that I took a little time to install a new iOS on this router. The reason for that is the code that I was running did not support the gatekeeper feature set. And I was a bit surprised that the IP voice, which is what I typically run on a voice gateway, that didn't support the gatekeeper feature set. So I went ahead and went out to Feature Navigator and looked it up and found an iOS that did support it. And I've gone ahead and I've updated the router, so we're running a little different code than we were before. But just a hint that when you try to type these commands in, you may get an error that the gatekeeper command does not exist. So you'll need to visit your friend Feature Navigator and find out what iOS and feature set is necessary to support this on your lab platform. So same old router, nothing crazy going on here. We're going to walk through some basic gatekeeper configuration. First thing you're going to do, config D, just like anything else, and we're going to say gatekeeper. When you do this the first time, as you go through the configuration, it may actually prompt you. In fact, it may very well prompt me to accept a EULA for a license agreement, because this is a feature that you have to turn on. So, if that pops up, you'll understand why. So, gatekeeper. Gatekeepers have zones, and we've kind of talked about zones before. A zone is a group of devices under a management domain. You may have one or more local zones, and you will likely have one or more remote zones. I'm going to configure one local zone and one remote zone in this example, and that should give you what you need to use as a building block to configure more. So what I'm going to do is I'm going to go ahead and I'm going to say zone local, and I'm going to say Columbus, because that's where I'm at. I'm located in Columbus, Ohio. So zone local Columbus, and I'm going to define a domain, howtonetwork.com. And then I'm going to say 10.10.210.1. That's the IP address of this gateway that we're going to use for our zone, or for our gatekeeper. I can create multiple local zones if I have multiple local zones. I don't, but if you do, certainly feel free to create those. I'm going to go ahead and create 2 remote zones. I'm going to say zone, gotta get my fingers on the keyboard here, remote, and we'll create one called New York, howtonetwork.com, and it'll be 10.50.210.1. And we'll create zone remote Chicago, howtonetwork.com, and it'll be 10.100.210.1. So we've configured one local zone and 2 remote zones. Now I'm going to issue a no shutdown command, and it actually would have asked you for the EULA here, but I've already accepted it, so we're good to go. And it tells me that the feature gatekeeper is activated. There's no error. So we've now configured the most basic settings related to a gatekeeper. Now, the whole purpose of gatekeepers is dial plan distribution. So we're going to need some kind of routing intelligence to build a dial plan that understands how to reach other gatekeepers, not necessarily gateways, but other gatekeepers to look for endpoints. We're going to do that using zone prefix. And what zone prefix is going to do is it's an association between a dialed number and a gateway, really. I mean, when you really get down to it at the end of the day. We're going to do that by going, again, we're still in the gatekeeper configuration mode. We're going to say zone, and let me show you what else is available to you here. A few different commands. I'm going to go ahead and say prefix, and it's going to allow us to define the E164 address space, so zone prefix. And I'm going to say Columbus, and I'm going to say 5, ... So I'm telling this gatekeeper that any endpoints or any E164 numbers matching that pattern are in the zone of Columbus. I'm going to say zone prefix New York 6, ... And I'm going to say zone prefix Chicago 2, ... And, there's other kinds of wildcard patterns and things you can use, but I think that gives you the basics here. Let's talk about technology prefixes. That's the other thing you're going to want to understand when dealing with basic gatekeeper configuration. A technology prefix is an optional H323 feature, and the short and skinny of it is it gives you additional flexibility in making call routing decisions. It's used to group gateways together by type or class. So think of it as, if I have some gateways that are used for voice, and I have some gateways that are used for video, and I have some gateways that perhaps point to H320 endpoints, or there's all kinds of ways to do this, but it's a class or a grouping of devices. I can use technology prefixes to pool these gateways into a group. For example, that we could use, and in fact, we'll go ahead and we'll build it here. 1 pound. Let's say that that's the technology prefix used for voice. If I try to route a call based on a technology prefix of 1 pound, I'm going to randomly select a gateway in that pool, and there you go. If the majority of your calls are going to use one class or one type of service, like voice, what I just talked about with the 1 pound, you can also define a default technology prefix. So let's go ahead and configure that. I'm going to say GW type prefix 1 pound star. And what 1 pound star means is tech prefix of 1 pound, and any number that's at least no digits or longer is going to match that pattern. And then I'm going to say default technology.
So we've configured the gateway prefix of £1 and we've actually made it the default technology prefix. Now, if you wanted to configure an H323 gateway to register with your gatekeeper, you would go into the gateway, and it's actually a very simple process. It's just part of the H323 configuration. And what you do, I'll go ahead and I'll do it on the same box here. Typically you'd be doing this on a different router, but for the purposes of this demo, that'll suffice. I'm going to go ahead and create a loopback interface. Int loop the 10. I don't know if I have it 10. I might have a 0, so we'll just skip it and go to 10. We'll say IP address 172.16.20.20. And we'll bring that into service. So loopback 10, goodest place of any to use it. We're going to say H323 gateway VoIP interface to turn H323. Oh, I can't do that. I've already got it turned on FAST00. Okay, you know what? I'm going to go to FAST00 and temporarily turn that off. And FAOO, no H323, 323 gateway. VoIP interface. We'll go back to my loopback and do it here. I don't really want to mess around too much. Oops. Put it here. There we go. I don't want to mess around too much with that Ethernet port. The next thing we're going to do is an H323 gateway VoIP bind source address. And I'm going to use the address of that loopback interface. So 172.16.20.20. And I'll hit enter. Now, this is where the rubber meets the road here. I'm going to say H323 gateway VoIP ID, and it's going to be the ASCII ID string of this gateway. So I'm going to call it Columbus1. And I'm going to say IP address, and I'm going to type in the address of my gatekeeper. So let's say it's 10.50 to 10.1. And we'll go ahead and hit enter. And I'll again define my H323 ID. We'll go ahead and call that Columbus. So H323 gateway, VoIP, H323 ID, Columbus, enter. And if we wanted to define a tech prefix, we would then go VoIP tech prefix, wait, maybe I can't do that on this iOS. I should be able to do that. Oh, no, I'm missing the command. H323 VoIP tech prefix £1. So that's pretty much it. I mean, that's how you tell a gateway to register with a gatekeeper. If you were configuring dial peers, in fact, I'll show you what a dial peer would look like just because I'm in here. Very simple to set up. Dial peer voice. We'll call it 500 VoIP destination pattern, and we'll say something like 5 ... And then I'll say tech prefix £1 session target RAS. Session target RAS. Enter. So now we're going to use the gatekeeper to route the call. So that's pretty much it. You've got a couple of commands you can use to verify that your gatekeeper is working. I don't have any endpoints registered to this one, so the output will be a little bit on the blank side. But some commands that are useful for you is show gatekeeper. In fact, let me stop there. Let me show you all the commands that are down here. You've got calls, circuits, clusters, endpoints. We've got the type prefix stuff, performance, data, server status zone, all kinds of stuff. So if I go show gatekeeper, GW type prefix, we'll see the prefix that's been configured and that it's the default gateway technology. We can do a show gatekeeper status, and it's going to show us that the gatekeeper is up. It's going to give us other information about the gatekeeper. If you've done any kind of bandwidth stuff with it, you'll see those values here. A show gatekeeper zone prefix is going to show us zone prefix table information that includes the gatekeeper name and the E164 prefix in use. If there are calls that a gatekeeper is aware of, you could do, and we won't have any, but you could do a show gatekeeper calls, and it would give you information. Obviously, we have no active calls. If you want to know about the endpoints registered with you as a gatekeeper, show gatekeeper. I'm going to let you guess here. What do you think it is? Yes, endpoints. I don't have any active registrations right now.
But that's it. If you get into debugs, remember we talked about two protocols that were being used. We've got H.225 and H.245. The normal debug H.225 or H.245, you'll see them both listed there, are useful to you. And then you've got options here for ASN1 events or Q931. You can also debug the RAS messages, which is debug RAS. So there's not going to be a whole lot useful here because we don't have anything going on. But that's pretty much it. If you wanted to get into call admission control and deal with bandwidth-based CAC, you can do that. It's as simple as defining the bandwidth under the Gatekeeper. So I can go config T and we'll say Gatekeeper, and then I've got these commands here for bandwidth, and then I could just set bandwidth, interzone, defaults, and put a value of bandwidth in there. So like 256K. And then I could go bandwidth total default. I could say something like 10 meg. See if I got enough zeros in there. Bandwidth session default. 512, etc. So you can do a lot of things here as far as CAC goes. But I don't want to dig too deep. I want to just give you the basics and get you started on gatekeepers and provisioning things. So remember to get an iOS that supports it in the feature pack. Remember, there's nothing too scary about gatekeepers. And remember, don't put these things in production on new networks. There are better, smarter design methods to do this than gateways. I've got a colleague who has 200,000 Cisco IP phones in his enterprise. And how many gatekeepers do you think he has? One. So with that, I'm going to say thanks for watching. We've wrapped up this section. In the next set of modules, we're going to get into IP QoS and talk about QoS design strategies and give you some basics of what you need to understand for IP quality of service on a unified communications network. So thanks for watching. Have a good evening, and I'll see you in the next video. In this module, we're going to start diving into QoS and IP quality of service. And we really need to start by talking about what are the quality issues that exist in the network today that we need to be considering when designing, implementing, and supporting these unified communications environments. So let's start at the beginning, and let's talk about where we came from and the networks of yesterday. And the reason I call them networks of yesterday is because they were truly separate, unique environments. So we look here at a typical data network where we would have our LAN and a router or a switch and a WAN connection, and then we'd have the same thing at the other side, and these were point-to-point links, and this was the data network, and it worked really well. And then we had the phone system, and we had our PBXs, and they would connect via the PSTN. And then we had our video conferencing endpoints. Maybe they were on an H320 network. And there were just separate environments. Voice and video and data, were all using their own equipment and following their own pathways and had their own addressing schemes. And they were separate. And it worked. But we had all these multiple infrastructures to manage. We had, to some extent, redundant types of services. They weren't necessarily redundant services because a PSTN at this point in time was not something that was a substitution for a frame relay connection, and it didn't handle the video links and all the stuff. It was all separate, so you couldn't just swap one out for another. And as technology evolved, we began to get this ability. So when you look at the network of now, it's really not all that different from the network of yesterday, except for the fact that we've consolidated technologies. We've collapsed things together. Instead of having to run video over H.320 and ISDN lines, we're packetizing the content and sending it over our packet switched network instead of our circuit switched network. The same thing is happening with voice traffic and telephone service. We're packetizing this content and using RTP over UDP and sending it across the WAN and through the networks at the individual sites. Our LAN is, our PCs, we're still using the data network. And, these phones and these video endpoints, etc., they're all just more endpoints on the LAN. So, you get an idea here of what's going on. We're really collapsing things together, and the WAN becomes a facilitator for all types of traffic to any destination, regardless of mode of communication. So that's the network of today. When we think about voice quality and delivering a consistent voice experience over the data network, there are a number of different factors that we have to account for. When we look at what voice and video are, there are a number of different problems that you can anticipate occurring, and a couple of these, for voice. What can you expect your help desk to hear as a phone call? I'm placing a call and my audio is unintelligible or it breaks up, it's choppy. I can't have a good conversation because I keep losing pieces from the other end. That's one of the conversations you might hear for someone experiencing voice quality issues. The video stream is jerky and I keep getting pixels on the screen, things are freezing, and those are the kind of calls that you can expect to hear when video is not being transported properly across the IP network. So what do we do about these things? First we got to start by understanding the fundamental needs of these types of transport, of these technologies. So voice and video, they're time sensitive. The traffic is only meaningful, or the content is only meaningful if delivered on time. When you look at packetized voice and video, we have packets of a constant size that are competing with bursty data traffic. And from a user perspective, obviously downtime is not acceptable. You pick up the phone, they expect dial tone to be there, and they expect it to just work. So these are all things we've got to consider when thinking about quality on an IP network. So not only what are the technical requirements, but what are the user requirements? What's going to be acceptable to the end user and what's not? Some of the technical issues that we have to resolve. One is bandwidth. You must have adequate bandwidth, and you must use the bandwidth that you have effectively. So this doesn't mean throwing bandwidth at the problem is a solution, but it does mean that you can only optimize something that you have enough of to begin with. So if you don't have enough to begin with, optimizing it's not going to do you a whole lot of good, because at the end of the exercise, you're still not going to have enough. So you must be able to use the bandwidth you have effectively, and you must have enough. We need to be able to manage delay or latency of data arriving. If data arrives too late, it's not useful anymore. And we need to manage jitter, those variations in the delay. We must be able to prioritize the traffic that is not tolerant and cannot handle the delay, and voice is a great example of that. And we need to prevent packet loss. On our data networks, packet loss was not such a big deal because the protocols like TCP that we use have mechanisms built into them to acknowledge that data sent was received and retransmit data as necessary. Well, that's not terribly useful with a voice or video type of network because, like I said before, the information is delay sensitive. If it doesn't get there on time, it might as well not have gotten there at all. So as we go into planning for bandwidth, and this is just a summary, we're going to dive into how do we address each of these issues specifically in the next slide deck. But as we plan for bandwidth, keep in mind that you only have as much available bandwidth as the weakest link in the chain. So if I've got a network here with a 10 meg hop and a 100 meg hop and a T1 link and then another 10 meg, keep in mind that for traffic crossing this network, you've only got as much available bandwidth for voice conversations or video conversations or whatever you're talking about as the weakest link in the chain. So if I've got a T1 line in this otherwise high-speed WAN, then consider that T1 line, that 1.5 megabits per second connection, is going to be the weakest link in the chain, and it's going to determine the amount of voice or video or whatever traffic I can successfully deliver end-to-end on my network. So if we're talking voice, you take that 1.5 meg link, you divide it by 80K per stream, and you're going to come up with the number of supported streams that you can support end-to-end on your network based on this weakest link. Traffic classification is going to be one of the techniques that we use as part of a overall QoS strategy. And again, we're going to get into these strategies and QoS policies in depth in the next video or several videos. But by classifying traffic and putting it into buckets, and then prioritizing the delivery of the traffic appropriately, we can effectively increase this usable link bandwidth. Once we classify traffic properly and put it into these buckets, we can give it the appropriate treatment from a queuing perspective. And there's various queuing mechanisms available to us. We have strict priority queuing, custom queuing, weighted fair queuing, class-based weighted fair queuing, and low latency queuing. And we'll get into these techniques as we continue to go. But I just want to show you, some of the technologies that are available to us in consideration of how we might resolve these quality issues on our environment. When we talk about delay and jitter, which I mentioned before, there are a number of different factors that contribute to total path delay and jitter on a network. If I look at a network here, we're going to have things like serialization delays. How long does it take to put the bits on the wire? We're going to have propagation delays that are, just laws of physics stuff. How fast can a T1 move bits of data from Los Angeles to New York? It takes time because I'm crossing physical distances. So there's a number of factors that are going to come into play here. And finally, packet loss. We look at networks where we're typically experiencing packet loss. It's going to be at points of congestion. So if I look at this sample network here on the screen, I've got a high-speed network on one side of a device, 10 mega bandwidth, and a significantly lower speed network for a connection to the next device, 1.5 megabits. Obviously, at that interface where I'm trying to shove 10 mega traffic onto a 1.5 meg interface, we're going to have packet loss. We're going to have to drop some packets because we can't sustain that 10 meg throughput anymore. So we'll have to think about packet loss within our network. So these topics or these bullet points have been very high-level summaries of the types of things you're going to need to consider from a user perspective and from a technical perspective when managing quality on a voice network, or a converged network, I should say. In the next video, we're going to talk about QoS strategies for unified communications networks, and we're going to get into a little more detail on this traffic classification and then what we can do from a policy perspective, and talk about how and when and where we should do these things. And as we move forward, we will go through some examples of configuring QoS. In fact, we're going to have a pretty good section on actually implementing a QoS policy on a network. So with that, I'm going to say thanks for watching. It's been fun, and I'll see you in the next video. Good luck with your studying. In this module, we're going to talk about QoS policies. So previously, we talked about many of the QoS fundamentals and how do I look at my network and understand the quality issues that face me. And we talked just a very little bit about some of the things you're going to consider when addressing those issues. In this module, we're going to dig deeper into that topic, talk specifically about things you need to target when resolving those quality issues, and talk about QoS policy design as a whole. Now, I'm going to go through an example policy in this video, but it's not the one that I use in production networks. In fact, later we're going to cover a video specifically on the Cisco baseline QoS model, which gives you an 11 class policy that I've learned to adopt over the years. Now, I don't necessarily implement all 11 classes, but I use the structure so that I have the flexibility as the network grows and expands. But I digress. Let's get back on the topic for this module, QoS policies. Now, when we talked about addressing quality issues in your network, we brought up delay as a problem and talked about the need to reduce the delay. So that's one of the things that you're going to need to consider when addressing quality issues. So how do I go about doing this? Well, first of all, make sure you have adequate link capacity or bandwidth. I talked about using QoS as a means to utilize the bandwidth available to you most efficiently, but you have to have the bandwidth in the beginning to optimize it. Plain and simple, you're not going to send 2 meg of data down a 1 meg pipe. I don't care what kind of QoS you have, it's not going to happen. So make sure you've got adequate link capacity and bandwidth. Let's make sure that you're prioritizing those types of packets that are latency sensitive. So an FTP session is not latency sensitive. A telnet session can be. Voice and video most certainly will be. So make sure you're utilizing a method to prioritize your latency sensitive packets, and we'll talk about how to do that within this module. I want you to consider the use of payload and header compression, particularly on low speed links when you're dealing with fractional T's and things below 768K. And I know a lot of you international guys are going to tell me, hey, in my neck of the world, we don't have bandwidth like crazy. We're using frac T1s all over the place. And if so, that's okay. Consider these other alternatives for you with compression of data. We've talked about the need to reduce packet loss, and we have to think about really where packet loss comes from. Packet loss comes from congestion most of the time. So again, back to the same link capacity thing. Either you have enough bandwidth to meet your business needs, or you don't. If you don't, pony up and increase your bandwidth. So reduce the congestion points. If you have traffic that has a requirement, obviously your network needs to be sized appropriately. Consider increasing your buffering space, and there's lots of buffer tuning you can do on Cisco routers, and this will help you deal with bursting of traffic. And drop the low priority packets. Try to reduce the congestion. If you can't necessarily increase the link capacity, use QoS methods to drop lower priority packets. Back to my FTP example. If I'm doing a data transfer with TCP data and a little bit gets lost now and again, sure, I may slow down the transfer, but I'm not going to kill the transfer. TCP has built-in mechanisms for retransmission of lost packets, whereas UDP, such as voice, does not. So if I don't have enough elbow room, selectively drop the data that can deal with being dropped, not the data that can't. So now that we're going to get through the basics and the high-level topic of what do I do, it's kind of leading you back to the conversation of you need to design an enterprise QoS policy. And the first thing I want to get in your head is that when dealing with quality of service, you need to think global. QoS is a strategy that you leverage. It is not a feature you turn on. I mean, granted, it is a feature you turn on, but features don't solve problems, and features don't implement QoS. I don't care how big or how small you are, you need to think about your traffic and develop a global enterprise QoS strategy. You need to write your QoS policies considering both the business requirements as well as the technical requirements. And kind of the point I want to lecture here about a little bit, and I may be on a soapbox a little bit here, but you cannot, as a network architect, as a network engineer, you cannot simply let the business decide what is more important and what is not. You cannot let the business group things into these QoS buckets that we're going to talk about. Now, that doesn't mean that their business priorities don't come into play. They absolutely come into play, but you as an engineer need to translate those business priorities along with the technical priorities into a comprehensive QoS strategy. So you might as well start now getting the support of your management team. That the business doesn't get to just gold, silver, bronze things. There's more to it than that, and you as a technical resource are going to help liaise between the technology needs and the business priorities. So you need to be part of influencing these decisions. And I like to say, show the business what they need, but listen to what they think they need. So I know I'll stir up a lot of discussion, based on that recommendation, but I've been in that role. I worked for major industries where the business had certain priorities, and they knew what those priorities were, and they were important to us getting paid and servicing our customers. However, if I would have simply asked the business to create a QoS strategy and prioritize data, it would have been completely broken, and we probably wouldn't have been doing business because the right types of traffic wouldn't have been getting through. So act as that liaison. When we talk about steps for implementing QoS, there's really 3 steps in the planning process that you're going to need to do. First off, step 1, identify the traffic. You need to know what traffic is on your network, and this is not something you can simply guess at. It's not something that you really should just say, oh, I'm the network guy, I've been here for 15 years, I know what's on my network. You know what, you probably don't know what's on your network. It changes. Applications are doing things behind the scenes that you don't necessarily become intimately familiar with for all applications. So take an audit, look at your network, figure out what's really going on your network, and consider both the business and technical implications of what this traffic is. Step 2, group traffic into classes. When you have traffic that has similar treatment requirements, you can group it together. And that's going to make managing your QoS policy a lot simpler. You simply can't define 500 kinds of traffic and 500 treatments. That's insane. That's not scalable, and it's not going to perform well. So you need to create traffic classes. Once you've classified traffic into buckets, you're going to define specific QoS policies and definitions of how you're going to treat that traffic. For example, I may allocate and guarantee certain amounts of bandwidth for a specific type of class. I may do strict priority queuing and for a type of class. I may decide that a particular class of traffic is less important than default. It's a scavenger type of traffic that I only want to cross the network when nothing else needs the bandwidth. So you'll come up with these rules, and we're going to give you an example in this slide of a very basic and typical model, and then we'll actually have a slide later on about the Cisco QoS baseline template. And I remember first seeing that template back in one of the Cisco Press books. I want to say Tim Seghetti was the author, and it was something like Enterprise QoS Design, or something along those lines was the title. Fantastic title. Tim's a great guy. Knows everything in the world there is to know about QoS. Puts me to shame by a long shot. But a lot of those resources, have developed these methods. We're simply sharing with you at this point in the game what works, and what best practices you should follow. So these are the steps you're going to follow to implementing QoS on your Cisco network. Step 1 is identifying the traffic. You need to understand the traffic on your network, and I kind of dove a little deep into this, in the summary, but we'll hit it again. It's important that you understand exactly what's happening on your network. Do an audit and don't assume. I've found when doing network audits in the past that there was not only IP traffic we didn't know about, but there were other protocols in use. We had print servers speaking IPX and AppleTalk, and we didn't have an Apple in the building. We didn't have anything running IPX. These were just defaults. This was garbage traffic that was on my network that we went around and we disabled, and we cleaned up and reduced some some Ethernet latency that we had. Obviously, could I measure it? Yeah, maybe not. But was it there? Yeah, absolutely. There were benefits there. So do it on it. Don't assume. Know what's happening on your network. Document the technical and business requirements for the traffic and applications on your network. If you're running a latency-sensitive telnet, transactional-based system like a terminal emulation to a mainframe environment, obviously that has certain performance metrics that are going to need to be met for it to be a usable application. You can't just, even though this telnet data is data traffic, doesn't mean you can slow it down and kill it to the point that it interrupts these interactive sessions. However, that FTP data transfer or that backup that is running, perhaps you can. So understand both the technical and business requirements for the traffic and applications that are running on your network. And you need to also define the necessary service levels for each traffic class. And I talk about that a little bit with prioritizing, telnet. For example, if you've got these interactive sessions, they need to be treated with a certain service level that back-end data doesn't necessarily need to be treated with. So consider both the business and the technical requirements. Step 2, we're going to group traffic into classes. And I'm going to say, from my experience, somewhere between 5 and 10 classes of traffic is common. I mentioned before the Cisco baseline QoS model with 11 classes. I love it. You should use it. But we're going to give you a little simpler example as we walk through this. I've seen in the past a lot of enterprises use this whole gold, silver, bronze model for defining traffic types. And in my opinion, and in the opinion of a lot of my peers in the industry, 3 traffic classes is simply not enough. You're not going to have the flexibility or the resolution to deal with the unique traffic on your network if you're restricting yourself to only 3 classes. So it can work, but I'm going to recommend that you use more. Here is what I would consider the most lightweight or the simplest class model you should consider in a modern network. Voice media would be a class for handling real-time audio flows, perhaps real-time video flows as well if you have video on your network. Voice signaling, obviously the signaling, the call setup and teardown, those things are important, almost as important as the media itself for voice. We have our mission critical data, our transactional data, our best effort data, and our scavenger data. So this is where you and the business may have some disagreements. They may say, this mainframe application is absolutely the most important thing in the business. And, there may be this thing like, I don't know, a routing protocol. You're going to have to consider in your environment what takes priority and where. But we're giving you classes and giving you flexibility in the grouping of these things to let you do that. So mission critical, transactional, best effort, and scavenger seem to work pretty well. Again, we'll show you a much detailed or a much more detailed or a lot bigger model in future slides. Step 3, develop QoS policies for traffic classes. Here is an example of the QoS policy, or potentially one QoS policy anyway, that we might apply to those classes I defined. So voice media, we're going to mark the packets with a DSCP value of EF, or expedited forwarding. And we're going to talk about DSCP in the next video, so don't try to commit this all to memory. And I don't know what DSCP, EF, and the CS3 and all this is. Don't worry about that. We'll cover that. So voice media, we're going to mark it with a DSCP value of expedited forwarding, and we're going to use low latency queuing to always prioritize the voice media. Why? Is it the most important business application? Maybe not. Is it the business application that'll, fall to bits first and be noticed first and generate the most number of phone calls? Yeah, probably. So it's got its own traffic class. Voice signaling, we're going to mark packets with the DSCP value of CS3, and this actually changed. We used to mark the stuff as AF31 if memory serves, but that has changed in what Cisco's doing over the years. So we're going to current recommendations mark it as a CS3. Mission critical data, we're going to define some kind of minimum bandwidth guarantee. In this example, we're showing 1 megabit. Maybe it's 10 meg, maybe it's 5 meg. Use a number appropriate to you. We're going to mark the packets with the DSCP value of AF31 for assured forwarding. And we're going to use class-based weighted fair queuing. I love class-based weighted fair queuing. You're going to see me use this a lot. For transactional data, AF21. It's more important than best effort. It's less important than mission critical. Best effort data. We still may be guaranteeing some bandwidth, but we might be creating some caps. We might say best effort data gets a cap of 500 KB. We're going to mark it with a DSCP value of default and use class-based weighted fair queuing. Scavenger data. Maybe this is the stuff I don't really want on my network. Maybe it's that eDonkey peer-to-peer traffic. Maybe it's I don't know. It could be anything. Whatever's not important to you, or kind of the opposite of not important, but I don't want it on my network at all. Maybe you put that into the scavenger class and you use this to police it down. You mark the packets with a DSCP value of CS1, and we're going to use red. WRED is how I should pronounce that, which is weighted random early detection to tag these packets as drop me first. In the event that we're having congestion and need to start dropping packets, we're going to use this as a flag to drop me first. And more about all this low latency queuing and DSCP and class-based weighted fair queuing and red and all that more coming up in future slides. Additional considerations for voice. You need to understand the characteristic of voice traffic. Its demand for bandwidth is what we would call smooth. It's not bursty in nature. Packets are small. The sizes are predictable. You're not going to have these big, giant, flows of voice all of a sudden and then drop off. It's going to be fairly smooth and predictable. Voice cannot tolerate delay. It cannot tolerate excessive jitter. So you've really got to make sure voice is moving and moving efficiently around your network. There are standards out there, and I can't recite it by name, which standard this is defines this, but no greater than 150, it's hard to say, millisecond one-way delay in the audio path. You start getting greater than 150 milliseconds, and the user is going to start perceiving delay with voice. And this isn't a call manager, a Unity connection kind of number. Those applications actually have much smaller numbers for delay. But this is is my brain and my ears and my mouth and everything gonna deal with voice kind of number. You start trying to get half second each way delay, and it's more like two-way radio where it's talk over Roger. It sound like I'm talking on a CB radio or something. But you got to keep this delay small, or you're going to start getting that asynchronous type of behavior and experience, and that's not what you want. So keep your delays low. And we want to have less than 1% packet loss with voice. If I'm talking and you start missing every other syllable or every third word or even every 10th word, you're going to lose your mind because you're not going to know what I'm saying. We're not going to be able to have an effective conversation, and you're going to freak out. So less than 1% packet loss for voice. When we deal with video, consider that it's bursty. Video is sending differential information, and I'm not going to get into all of the I frames and P frames and B frames and all of that. But if you're interested in how video transports, certainly look that up. But video sends data, sends information as it changes. It sends the difference of information. So even though you think video, that's got to be a lot heavier than audio. Well, yeah, it uses more bandwidth, but it's different than voice. Video also cannot tolerate delay, so that's something you need to consider when designing for video support on your enterprise network. And finally, data. TCP, which is what by far the vast majority of enterprise data is. I'm not saying that all data is TCP, that wouldn't be fair, but we got a lot of TCP out there these days with HTTP and FTP, and the list goes on and on. TCP can deal with loss of data. We've got handshaking that goes on, and we've got methods to retransmit lost data when we've detected that what we've sent hasn't reached the destination because the destination didn't acknowledge it, and blah blah blah. All that stuff's there. We're using it. That doesn't help us in a voice and video world, but data can deal. So let's leverage and lean on the fact that data can deal when creating QoS policies in our infrastructure. I'll be the last person to tell you to never drop a packet. I'm going to say if it makes sense to drop a packet and it protects the traffic that needs protected the most and doesn't create perceivable user impact, then drop that stupid packet and let it through the next time around. So these are things to think about. So we've covered the QoS policy approach. We've talked about strategies. We've talked a little bit about QoS policy classes and how to treat traffic based on class. We're going to get a lot deeper into that. This was just scratching the surface, but that should give you a good start. So in the next video, we're going to talk about some of these technologies that I've called out by name. What is DiffServ and DSCP? We'll talk about differentiated services versus integrated services and explain a little bit about RSVP and talk a little bit more about how these actual mechanisms work. So with that, I'm going to say thanks for watching. Good luck with your studying, and I'll see you in the next video. In this module, we're going to talk about two of the QoS methodologies that Cisco is going to want you to understand as part of the CCNP Voice C-Voice exam curriculum. And as I talk about the differences between integrated services and differentiated services, I want to kind of level set your expectation of what you're going to see in the field. Never in the last decade that I've been doing unified communications have I personally worked on a network that was leveraging integrated services. Now, I do know that they exist. I do know of some clients and people that I've worked with in the past having these environments. They're typically government in nature and are things that most of you will never touch because, by and large, DiffServ is kind of ruling the world. So I don't want to say that integrated services doesn't exist or that nobody's using it, but its use cases are very specific, and it is by far in the minority. So let's get right into it and talk about integrated and differentiated services. When we talk about the QoS models, there are really three different approaches you can take when developing an enterprise QoS strategy. There's the best effort delivery model. This is what the internet uses, or what we need to presume the internet is using anyway. And that is that no QoS is applied to network transport. We're not treating any traffic in a specific way. We're not queuing or prioritizing. All traffic has best effort treatment, and we do with it what we can. So that's one QoS approach. It's kind of the lack of quality of service treatment, if you want to consider it that. We have the integrated services model, or IntServ, which is designed to provide absolute guarantees of bandwidth. And that's what I want to zoom in on. Absolute guarantees. And it does that by using a process of resource reservations and call admission control. So RSVP is a protocol and call admission control mechanisms. Now, integrated services is not very scalable. It's highly complex, and there's a lot of configuration involved. And like I said before, it is not the predominant method in use in most of the networks I've ever touched. Differentiated services, or DiffServ, is kind of what rules the world, at least in my neck of the woods. And it provides what I'll call almost guaranteed bandwidth, but it's much more scalable and flexible than integrated services. And QoS treatment within a DiffServ environment is handled on a per hop basis. In fact, we call these things per hop behaviors, but we'll get more into that as we get through the slide deck. So DiffServ is what Cisco wants you to understand in depth because it's what's popular, but you may have some questions on the exam relating to the integrated services model because it's fair game within the curriculum. So let's go ahead and start there, and let's talk about integrated services. So integrated services has the benefit of offering guaranteed bandwidth for a flow
if the bandwidth is available, because we reserve it before we make a call. So it gives us explicit end-to-end control of resources. Now, the disadvantage to that is that this flow-based approach doesn't scale well, and it's very labor intensive, and it doesn't support large networks well. Integrated Services uses the RSVP protocol along with call to mission control mechanisms to provision or to reserve bandwidth from end to end across a network before flow is ever created. So you're getting a true guarantee. And I'm saying here that Integrated Services is not often used in modern environments. DiffServ is much more widely adopted as a technique. So I'm not bashing RSVP. I'm not bashing integrated services. I'm simply saying that it is a niche solution deployed, within silos of its own. So you may run into it. It works. It works pretty well, but it's not the popular method in the industry. And that's most of what I'm going to tell you about integrated services. Now, when we get into DiffServ, which is kind of the world we're living in here, DiffServ, or differentiated services, is highly scalable, and it supports many different classes of traffic. And we're going to get into this whole classes of traffic thing in great detail. Now, some of the disadvantages to DiffServ, if you want to call them that, if we're going to kind of get down to the letter of the law here, there is no quote-unquote absolute quality guarantee because we're not provisioning bandwidth across the network. We don't know what's available when we're setting a call up. We're simply setting a call up, hoping the network's healthy, and allowing per-hop behaviors to treat our traffic appropriately from end to end. Multiple mechanisms are going to come into play in order to seamlessly deploy DiffServ throughout an enterprise environment. I think that kind of speaks for itself. You've got a lot of places to configure things. I've mentioned it before. I'll mention it again. It's the most widely deployed QoS mechanism in enterprise networks today. And it is handled, or treatment of traffic is handled hop by hop. And we call these per hop behaviors. But more about that in slides to come here. So how DiffServ works. Let's get some terms out of the way. They're things that I'm going to reference throughout this module. DiffServ treats traffic with a common QoS tag called a BA, a behavior aggregate. Similar traffic has a similar behavior aggregate. DSCP, or DiffServ code points, are values contained in the IP packet header that is used to assign a treatment to a packet. So we're going to group things together, and we're going to detect them. We're going to classify the traffic based on its DiffServ code point value. More on that as we go. And PHB, the per hop behavior, is the behavior that takes place on a network hop by hop. So queuing decisions, packet scheduling, policing, shaping, etc. are all happening. These decisions are happening as the flow is created, hop by hop, or one hop at a time. So DiffServ behavior. If we take a look at the example network, we've got an IP phone. This could just as easily be a PC. Couple of routers and an IP phone. So we've got multiple hops along the way. The flow of data is going to be end to end, obviously. And what's going to happen is as the packet travels from the originating device to the first router, the first layer 3 device, obviously when this hops on the network, we're going to classify traffic, we're going to identify it, and mark it appropriately at the network edge with a DSCP value. As we egress the first router to the second, we're going to apply a per hop behavior. So we're going to decide on our queuing mechanisms, our packet scheduling, our, etc. as we egress. The next router is going to do the same. And the next router is going to do the same. So it's very unique. It's very independent of the end-to-end infrastructure. Now, you still need an enterprise QoS strategy to deal with this, but it is a hop-by-hop decision that's taking place. Understanding DSCP, when we talk about DiffServ code points, basically these are numeric values, and we use them to identify a class of traffic. Now I'm going to get into a really nice chart and show you the DiffServ code points, but I want you to understand what's actually happening here. We're going to get into understanding the IP packet header and the type of service field, which is an 8-bit field, and we're going to talk about what the individual bits in the field are used for and how this all really works. So here is an IPv4 packet header, and I've simplified it to just focus on the type of service byte.
today we're calling it the DS field. And I'll explain what I mean by today we're calling it as we get a little farther down here. As with all standards, they evolve over time. So early on, we used something called IP precedence. Actually, early in the beginning, we used something called type of service in an IPv4 packet header. Later, we moved into IP precedence, and finally today we're using DiffServ code points. So the DS field in the IP header, right here, is used by DiffServ. Formerly, we called it the toss byte, but today it's called the DS field. As things evolved, or I should say in the beginning, RFC 791 introduced the specification for the type of service field. The first 3 bits were used for IP precedence, so that's these bits right here. The next 3 for delay, throughput, and reliability. So that was IP precedence. Along came RFC 1812, and it modified the definition of the toss field by removing the meaning of the last 5 bits or marking them 0. And this is what we call RFC 1812 IP precedence. So an evolution was happening. So now, these bits don't mean anything anymore, and they're all 0. So what's that leave us? It leaves us these 3 bits, and those are going to create what we call IP precedence values. As evolution continued, RFC 2474 replaced the TOS field with the DS field, and we stopped looking at IP precedence and we started looking at DSCP and ECN. Now, we'll get more into each of the bits in this field in another slide, but I want to show you, just at a high level, the IPv4 packet header and the TOS or the DS field. So DSCP values, here's where we're really going to break it down for you. This chart is a lot of fun. I've written different variants of this chart over the years. I'll never memorize it, although I wish I would. But I really want to show you exactly what's happening. So when we were using IP precedence, I told you, in fact, I'll circle it here, we were using the first 3 bits, bits 0, 1, and 2. So we had, values of 0 through, I have to do my math there. How high can that go? Let's see, 1, 2, 3, 4, that's like 7? I think we can go up to 7. My binary counting is a little rusty. We've got 3 bits to play with. An IP precedence value of 1, actually let's start with 0, is going to have a value of 0, 0, 0 in those 3 fields. So we're doing normal binary counting. An IP precedence value of 1 is going to be 0, 0, 1. So we've put a 1, or a flag, if you will, in the first bit column. An IP precedence value of 2 was 0, 1, 0. An IP precedence value of 3 was 0, 1, 1. An IP precedence value of 4 was 1, 0, 0. An IP precedence value of 5 was 1, 0, 1. A value of 6 was 1, 1, 0. And a value of 7 was 1, 1, 1. So you can see how we're using just these 3 bits is all we're using. So that is our IP precedence value. So that covers, the first half of the chart. Let me go ahead and clear the ink here. And we'll keep going. As time went on, and as we began to adopt DSCP, we created DSCP classes. And there's the default DSCP per hop behavior, or default class, which has a DSCP binary value of 0, 0, 0, 0, 0, 0. And I want you to notice that the first 3 bits of the DSCP binary value equal the IP precedence binary value, because They're the same bits. It's these bits right here, these first 3 bits. So that's right there. The second 3 bits, or the 4th, 5th, and 6th bit, or if you're counting from 0, 3, 4, and 5 here, that's the next 3. So together, those make the DSCP value. And what's happening here is we've made DSCP backwards compatible to some extent with IP precedence, so that devices using the network that honored the previous means of IP precedence could still somewhat deal with modern QoS mechanisms. So we've talked about the default class. Now we're going to talk about expedited forwarding. EF, down here at the bottom. Whoops. EF. EF is used for typically priority queued traffic. This is going to be our voice traffic. You don't use a lot of EF traffic on a network. In fact, most of the time the vendors will recommend, or sometimes mandate, that you use less than 30% of link bandwidth for EF-based traffic. EF is going to be a DSCP value of 46 in decimal, or a 101.110, which is going to equal an IP precedence value of 5. So that's EF. Assured forwarding has multiple classes. In fact, we have 4 classes of assured forwarding. And in fact, let me fix something in my notes here, because 4 classes with 4 drop priorities is supposed to be talking about assured forwarding. This is something separate. So, assured forwarding, we have 4 classes with drop priorities. And the way that this works is we've got AF 11, 12, 13. We've got AF 21, 22, 23. And we've got AF 31, 32, 33, and 41, 42, 43. So here's a class, here's a class, here's a class, and here's a class. So in the AF1 class, we have a low drop priority. So AF11, this last one, is the drop priority. So it is a low drop priority. The higher the number, the higher the drop priority. AF1, drop priority 2. AF1, drop priority 3. And so on and so forth. The AF1 class, I just want to back up here, contains a low drop priority, which is here, a medium drop priority, and a high drop priority. And the same thing recycles here. We've got low, medium, high, low, medium, high, low, medium, high. Oops, H for drop priority. So that's our AF, or our assured forwarding classes. And assured forwarding classes are what we do for most, most data. And what's good about assured forwarding is that it's going to allow us to allocate or guarantee a certain amount of bandwidth to the class. However, if extra bandwidth is available, we'll allow it to access it. We'll go ahead and we'll clear the screen again here. And let's talk about class selector. We have CS1, CS2, CS3, CS4, 5, 6, and 7. The CS classes, or class selector, is giving you bit for bit backwards compatibility, I should say, for DSCP with IP precedence. So you're getting a way to map to a precedence of 1. You're getting a way to map to a precedence of 2. You're getting a way to map to a precedence of 3. So slightly different, and you'll find that voice RTP on a Cisco phone is going to be EF, so we'll say voice RTP, and the signaling for the call is going to be CS3. Now, back in the earlier days, Cisco used AF31, so we're just going to do this, and we'll say voice signaling. But today, it's up here at CS3. The biggest thing I want you to understand when looking at this drawing or looking at this chart is that there is a method to the madness. We're not doing anything all that crazy here. We're simply looking at the bit positions, these 3 for IP precedence, and then we're going to assume these are all 0. These 6 for DSCP, and you're good to go. So network endpoints, routers, etc., that were compatible with IP precedence to some extent can still function and deal with packets that are tagged using DSCP. So what I'm showing you here is just a chart. Don't freak it out, about it. Don't try to memorize it. Is it important? Absolutely. But I want you to understand what's happening more than I want you to remember these exact numbers. Know that there are 4 assured forwarding classes. Know that you've got a low, medium, and high drop priority. Know that there are 7 CS classes. Know that there's EF. If you've got that, and as long as you understand that the first 3 columns, there's no way I'm going to get this line straight, but the first 3 columns in the DSCP binary value are going to equal the IP precedence binary value, then you should be good to go. So we'll move on to the next slide. I know that was a lot to cover. And let's talk about the DiffServ QoS mechanisms. We have got classification and marking, congestion management, congestion avoidance, policing and shaping, and link efficiency mechanisms. So all these different mechanisms available to us within the DiffServ QoS model. Classification and marking, we're going to classify traffic at the input or the ingress interface on our device. We can look at its DSCP value, its IP precedence value, its source or destination address, and we can do this classification either via the MQC, the Modular QoS CLI, which is what you're going to see me do in the next, the next section, and we'll actually do some QoS configuration. It can use NBAR or policy-based routing and classify based on an ACL. Congestion management, and I'm not talking about Sudafed there. Congestion management gives us queuing algorithms, and this lets us deal with congestion as it's happening. So FIFO, first in, first out, priority queuing, custom queuing, class-based weighted fair queuing, and low latency queuing are all available to us. I want you to know that low latency queuing is the preferred method by Cisco and is a hybrid. It's a combination of priority queuing and class-based weighted fair queuing. So basically, we're going to strict priority queue voice RTP, and then we're going to weighted fair queue everything else based on class. So it's very flexible, and it works really, really well. Congestion avoidance. We've got congestion avoidance techniques that we can implement on egress or output interfaces. Things like weighted random early detection. WRED is Cisco proprietary, and it's useful for dealing with TCP-based flows. And what WRED is going to do is it's going to drop lower priority packets instead of dropping higher priority packets. So it's got some evaluation and decision making going on here that can help us deal with, or stop from happening, I should say, because this is all about congestion avoidance, link congestion. Policing is good for controlling burst, and it helps to make sure that the types of applications that need bandwidth can get their bandwidth. Policing is going to drop or mark packets once predefined limits have been reached. And you're going to see policing used, in service provider environments a lot. I've done it in the enterprise, but I don't do it often in the enterprise. So the vast majority of what's happening in the enterprise is classification, marking, and then that's pretty much it. I'm not doing a whole lot of policing. I'm also not doing a lot of shaping, but from time to time I do. So shaping is used on egress interfaces, and it's allowing us to structure what and how gets placed on an egress link. It's going to keep low-speed links, or help keep low-speed links, from being saturated by flood of traffic. We've got available to us both generic traffic shaping and frame relay traffic shaping, so you'll want to know those for the exam. Compression, again, something I'm not doing a lot in modern enterprise networks, at least not here in the United States because our links are relatively fast. Two types of compression are available. You've got header compression and payload compression. Header compression, or compressed RTP, is going to reduce the size of the RTP, UDP, and IP headers. However, it's going to come at a cost of CPU overhead. And payload compression is going to give us layer 2 frame compression using either the stacker or predictor methods. Again, these are things that you want to use on low speed links only because they do make your router work quite a bit harder. And the number that I like to throw out there, and I don't remember where I read it, was don't even consider using this stuff unless you're on links slower than 768K. So you're half a T1. LFI, link fragmentation and interleaving, is also a technology that's available to you. And you can use it on slow WAN links to fragment larger data packets and interleave smaller voice packets within where the areas those larger data packets would have been sitting. So this is a lot. I know we've been kind of drinking by the fire hose in this module, but this should give you the fundamentals of integrated services and more importantly, differentiated services. And when we get into the next set of videos, or the next section where we're actually doing QoS configuration, you'll understand what I'm referring to when I talk about classifying traffic and marking traffic and queuing traffic and weighted fair queuing versus LLQ versus priority queuing. You'll probably want to go back and watch this video a second time. Like I said, drinking from the fire hose, that chart alone on DSCP values and how they map to some of the other type of service byte fields and IP precedence fields can be a bit daunting, especially if you're trying to memorize it. So spend the time, get a good understanding of what's happening. Don't sweat the details right now. Those are things you can go back to prior to your exam and try to cram into your brain. But right now, I want you to understand it. I want you to get a good feel for what's happening behind the scenes. So that's it for this video. I know it's been a little bit of a long one. I really try not to make them this long, but I feel that for DSCP and integrated services, or DiffServ and integrated services, it's best to just kind of get it out there on the table and talk about it all at once. Rewind this one, do it 2 or 3 more times. It should hurt a lot less the second and third time through. And I'll see you in the next video where we're going to be talking about a benchmark or a baseline QoS model that is being pushed these days. And I'm not sure exactly where it originated. I've seen, like I mentioned before, I've seen Tim Seghetti use it in his Enterprise QoS book. I know Cisco Press is using it in some other books. I've seen other engineers in the field using it. So we're not going to spend tons and tons of time on it. It's only a couple of slides. But I do want to show you that baseline that I like to use in my own environments. And it'll give you something to build on. So with that, thanks for watching. Good studying. And I'll see you in the next video. I know after that last video, your head's probably spinning just a little bit. Hopefully you've taken my recommendations and rewound and watched it a couple more times. If you haven't, stop now, go back and watch that again. It really is not terribly complex, but it's so much information to take in at once that you just kind of need to spread it out a little bit. This video here is wrapping up the fundamental knowledge you'll need of QoS for the C-Voice exam from a theory perspective. And it's only one slide, and it's not going to take a lot of time, so this is a good wind down exercise to kind of decompress a little bit and think about QoS. So let's get right into it, and this is the 11 class Cisco baseline QoS model. I've seen variations on this theme for years, and I really like it. I worked at a large, multi-billion-dollar-a-year healthcare organization for a number of years. I was their network architect, and we implemented a very close approximation to this 11 class baseline QoS model, and for like 8 years used it, and it grew and changed and adapted with us very, very well. And the beauty of an 11 class model, or of this 11 class model, or really the class models in general, is you can add to them and subtract from them at any time. If you design it flexible enough in the beginning that you leave yourself some elbow room, you can modify and tweak things as necessary. What I want to show you here is one concept. This is a very detailed methodology that allows us to, in my opinion, clearly other people's as well, maximize our use of different DSCP values to kind of get the most capability and flexibility out of how we tag our traffic. So let's just kind of start at the top, which is going to be, in fact, the order you see this in is going to be, kind of the highest priority to the lowest priority. And you're going to see that, things like mission critical data, are kind of a little lower than you might think that they need to be. And, web traffic, general data, normal stuff's almost clear at the bottom. And your business, your management, if they were to look at this chart, would not understand why. They would not get that, sometimes technology needs for things to operate properly come before the warm and fuzzy, but I'll let you manage that on your own. That's another challenge. But anyway, starting at the top, the most important traffic on your network, and what needs to be prioritized as a CS6 is routing protocols and network control. So the stuff that keeps your network up is more important than the applications that the network is servicing. Obviously, the network, the apps can't override these things that keep the network running. So it really needs to be number one above any and all applications from a QoS perspective. Cisco recommends CS3, layer 3 per hop behavior with rate-based queuing and random early detection. Voice RTP, a close second. That's our bearer traffic or the audio content. We want to do that as an expedited forwarding, which is going to be call admission control plus strict priority queuing. So we're going to guarantee bandwidth for voice. Dial tone just has to work, so that's why it fits in the way that it does. Video RTP, the bearer traffic for video, is going to be next with an AF41, which is CAC plus rate-based queuing plus weighted random early detection. Streaming video, very similar. That's our streaming media content, but not video conferencing. When I see video, I'm thinking video conferencing two-way. Streaming video would be a one-way thing, and that's going to be a CS4. Again, CAC plus rate-based queuing plus weighted random early detection. Mission critical data comes next. That's the critical enterprise data apps. So your business's number one, most important, we got to have this to do the business app. I don't care what they say, fits here, at number 5, AF31, rate-based queuing plus weighted random early detection. Call signaling, that's your call setup, teardown, and any other kind of necessary communications to keep calls running for voice and video is going to be a CS3 and rate-based queuing plus random early detection. The reason we're using red instead of WRED here, and in fact you'll see the same thing happen now with network management, is that weighted random early detection is for TCP. And these are typically UDP signaling flows, so that's why you'll see red down here. It's not an absolute statement, but that's kind of a generalization. Transactional data, things like database apps, mainframe apps, your telnet sessions, I want to put them in here. AF21, rate-based queuing plus weighted random early detection. Network management, things like SNMP, we're going to give a CS2, rate-based queuing plus red. Most of the rest of the data on our network that we're not going to classify, and really, like 70% of the stuff really ought to fit here, guys. So try not to go crazy on what you classify up above. Bulk data, that's web traffic and generally everything else. AF11, rate-based queuing plus weighted random early detection. Scavenger traffic class. This is our nuisance traffic. This is our
what I want to say, eDonkey, peer-to-peer traffic, and things along along those lines. Stuff that we really don't want on our network, and we definitely don't want to give special treatment. That is scavenger class traffic. And then finally, best effort. That's the default class. That's everything else. We're going to give a bandwidth guarantee with rate-based queuing plus red. So the 11 class model is going to give you a lot of capabilities and a lot of flexibility. Now keep in mind, you don't absolutely have to do this. If this just makes your head spin and you say, dang it, Josh, I don't want a baseline model. I don't want 11 classes. You're on drugs. Then I'll say, how about an 8 class model? And, if you agree to that, then we're just going to combine the voice and video RTP. Whoops, I'm clicking ahead of myself. The voice and video RTP into one. We will combine the routing and network management into one. And we'll combine the mission critical and transactional data into one. And we'll reduce the number of classes you have to deal with. I got to tell you, there's not really that much complexity that you're losing. This stuff isn't that hard to set up, but if you can't handle 11 classes, take it down to 8. If you can't handle 8, take it down to 5. And really, this is the smallest that I would ever recommend you do. There are ways to take it down to a 3-class model, but I don't really subscribe to that. So if you wanted a 5-class model, you could have a real-time class. That's your voice and video. You'd have call signaling in a separate class. You'd have critical data, which would be your network control, your critical data, your bulk data. And then you'd have a best effort, and then you'd have a scavenger. So that would get you down to 5 classes. So ways to reduce it, yes. But let me twist your arm a little bit. Go for the 11 class model. There's no real reason not to. It's a couple more lines of code. It's not like it's going to, confuse your, to the point of not being able to deal with it. Give yourself the flexibility. Design it in now so that it scales and works well for you for years to come. So that's probably more time than I really should have even spent on the baseline QoS model, but I find that it's helpful to give you a reference. And just like every book I've ever seen on QoS tends to give you a baseline reference model, so I figure we should probably follow suit and do it here as well, and really give you an idea how these things stack up. So with that, I'm going to say thanks for watching. This wraps up our video section on the theory behind QoS. In the next section, we're going to be covering configuration of QoS on Cisco routers and setting up our network, and really a little bit of switching for that matter, and setting up our enterprise to handle all these QoS methods that we've talked about and actually doing the implementation. And that is going to be the end of the C-Voice course. So you're really close. We're almost there. Thanks for hanging in there with me. I know it's been a lot to deal with, but I'm hoping you're having as much fun as I'm having. And with that, I'm going to say thanks for watching, good studying, and I'll see you in the next video. Welcome to Module 34. We're going to go through some demonstrations of creating QoS configuration on a Cisco router. And specifically, we're going to focus on classification and marking of traffic. Now, there's a lot of different things that play into enterprise QoS. There's LAN-based QoS and considerations for the switched environment. And we're not going to dig crazy deep into that. There's WAN-based QoS, where we're trying to prioritize traffic going from a high-speed network to a low-speed network. We're going to focus on that in great detail. And kind of everything in between, literally. So let's kind of start at the beginning. I'm going to give you a quick little sketch of what's going on in the network. And then we're going to jump into our 2811 router here and actually do some QoS configuration. Now, I'm going to sketch a little network for you. I'm going to show you Josh's IP phone is connected to a switch, a layer 2 switch. And Josh's layer 2 switch is connected to a Cisco router. And that router has a T1 line as part of an IP WAN. That T1 line happens to go to another router. On that router is another layer 2 switch with another Cisco IP phone. When the phone creates an RTP packet, that RTP packet that is sent to the switch is going to have a layer 2 and a layer 3 QoS marking. The layer 2 marking is what we call a class of service marking. And we're not going to get heavy into layer 2 QoS within the C-Voice exam. It's something you'll do now and again. I would recommend you deploy it, but by and large, most of your QoS exercises are going to be from a routing perspective. So, layer 3 markings are going to be intact on this packet as well, and that is going to be a DSCP value within the TOS byte of the IP packet header. So, layer 2 markings, layer 3 markings. And keep in mind, back from your CCNA days, that a layer 2 frame contains a layer 3 packet. So, this switch is not going to monkey with this DSCP marking at all. It's a layer 2 switch. It doesn't look at, doesn't see, doesn't care that layer 3 marking. The switch is going to pass the packet to the router. So the router is going to see an incoming packet that it doesn't know what this thing is. It doesn't know its voice. It just knows that it has a layer 3 DSCP marking of EF, expedited forwarding. So we're going to say marking of EF. So that packet comes in with a marking of EF. We are going to create classes inside of class maps on the router that identify the traffic and allow us to group things together. So we're going to have like VoIP RTP, VoIP control. We'll have a class called class default, for everything else. And you'll continue to build on this as you deploy your QoS model, hopefully that 11 class baseline model that we showed you. As traffic hits this egress interface, and the same would be true for packets coming in the other direction, as they hit that interface, this is where we need QoS to do its magic. That's our congestion point. I've got this, 10, 100, 1000 base T network out here running at potentially gigabit or faster speeds, and this little 1.544 megabit T1 interface. So where do you think dropping packets is going to happen? You got that right. It's at the low speed egress interface. So we're going to talk about how to configure the class maps, how to configure the policy maps on the router, and how to deal with the classification and marking of traffic. So let me go ahead and clear this screen here. And we will jump over to our handy dandy 2811 router. And this router has absolutely no QoS configuration on it whatsoever. So let's walk through some basic class map configuration. I'm going to say class map, and then I've got two options here. I can either go match all or match any. It's as obvious as it sounds. If I match any, if any parameter in here matches my packet, then I am in this class. If I use match all, then I'm going to have to match, every condition within this. So I'm going to, almost all the time, I'm going to say match any. And we're going to create a name for the class. And like I said before, VoIP RTP. Now that I've created a class map, I'm going to configure the matching rules. So we're going to say match, let's say DSCP, and then here's our options. I want to show you what's available to you. EF. I could also use the decimal value if I wanted to. I could also say match IP precedence 5. That would be the same as the DSCP EF, but perhaps my legacy application
didn't tag DSCP, it tagged IP precedence. Perhaps I've got traffic coming from a VLAN, and I've actually got an access list I've created. We'll say match access group 101. That's a simple IP access list with a source network of 10, I think 10.100/16 going anywhere. So any traffic from that subnet, it's going to be VoIP RTP. It just is because we said so. So we've configured our match rules. And let's go ahead and create another class, exit. We'll say class map VoIP control, and actually match any VoIP control. And we'll say match, I don't remember off the top of my head what the IP precedence value was, so we'll just go DSCP CS3 and AF31. We'll assume for a moment that those are how my packets are being tagged. So I've created two class maps, and in fact, if I do a show class map, you're going to see the class default, which is there by default, which says match any. You'll see the VoIP RTP that I created with a match DSCP EF, and you'll see that it, for convenience, shows you the decimal value. It has a match IP precedence 5 and then a match for that ACL. And then we've got our VoIP control that we've configured. So we've got some class maps going on. Now that I've configured and classified my traffic, I need to decide what to do on how to treat it on my egress interfaces. Now, there's lots of things I can do with with QoS on these egress interfaces. I'm going to start off simple just by showing you how to remark the traffic. Let's say that I matched this ACL and it didn't have a DSCP value, but every other router downstream from me is going to look at that DSCP field, so I really need to make sure something's in there. So I'm going to put something in there. So we're going to create a policy map. It's going to be policy map, and I'm just going to call it QoS. And then we're going to say class VoIP RTP. And we're going to say set, and you can see all the things I can set, DSCP EF. So now, everything that matched the class of VoIP RTP, it's going to be retagged with EF, and I'm going to use EF through the rest of my network. So I've put some other detection mechanisms in there. In fact, I'm even going to go back and do one more, just because I want to show it to you because it's cool. Show run pipe section class map, and the one I'm going to do is I'm going to say class map match any VoIP RTP. I'm going to say match protocol RTP. That's what we call NBAR, Network-Based Application Recognition. It is a little more CPU intensive, but it's a really cool way to deal with QoS and how to detect packets. So we've got that. So let me just sum it up again here. Show run pipe section class map. So we've got our class maps for VoIP control and VoIP RTP and a bunch of different match rules. Show run pipe section policy map. And you'll see we've got a policy map QoS, a class VoIP RTP, and I'm doing a set DSCP EF. That's classification and marking right there. Now, to attach this policy to an interface, I don't think I actually have a T1 in here that's configured for data. Let's see what I've got on here. Show IP int brief. Doesn't really matter. I don't have one for data. But Fast Ethernet 01 is not in use, so we'll use that. Let's pretend that that's my egress interface. I'm going to say interface. This would be exactly the same on a T1. In FA01, and we will say service policy output QoS. So I've applied the policy map using service policy. And if you think about it this way, classes get configured in a class map. Class maps get configured in a policy map. Policy maps get assigned to egress interfaces as a service policy. So right there, we've actually configured basic QoS. And that's going to handle the basic layer 3 functionality for classification and marking. Now, we haven't actually configured any queuing behaviors or any kind of policing and shaping or anything like that. We will be doing that. I'm going to go back to these service policies and we'll perform that configuration in a later slide. So for now, let's keep it simple. Classification of traffic and marking of traffic. Now, there's one more thing I want to talk about, and I hinted to it lightly within the the PowerPoint as we were getting started, and that was about Layer 2 QoS. Layer 2 QoS is a little different than Layer 3. So, first off, IP headers are preserved end-to-end across the network because they're inside Layer 2 frames. However, Layer 2 frames are not preserved. They're recreated from switch to switch to switch as packets work their way through your network. To provide for true end-to-end continuity of your QoS tags, at some point, you really need to map Layer 2 tags to Layer 3 mappings. And like I said, the biggest point in your network where you need to deal with QoS is definitely the WAN and the congestion points. But you will get into some basic Layer 2 QoS. I want you to understand, in fact, we're going to jump back to PowerPoint for a second. I want you to understand the concept of a trust boundary. So in a network, we'll go ahead and show you, it's real similar to what I drew before. Phone, switch, router, T1 line to a WAN, T1 line to a router. And let's make this network a little more complicated. To a switch, to a switch, to a switch, to a phone. Now, when the phone tags the traffic, I said it's going to do it at Layer 2 and Layer 3. So you've got class of service and DSCP. If the switch has QoS enabled, we have to understand its behavior with the Layer 2 mappings. So let's talk for a second about trust boundaries. You want to define a trust boundary on your network for QoS mapping as early as you can when a packet or frame begins to travel across your network. So we want to define this trust boundary out here at the port where the IP phone connects. So that's our trust boundary. If we trust the markings at Layer 2, then if QoS is configured, we will not strip the markings. If we do not trust the port, then we will strip the markings and mark it as a preference of 0. Now, it's only going to matter as it propagates through the switched portion of the network. As soon as it hits the router, this router is not looking at that Layer 2 frame. It's looking at the Layer 3 packet inside of it, which still has that DSCP EF in it. So, everything across the WAN is going to work. But this poses a concern out here at the other site. So when this phone is originating traffic, let's say that this is the trust boundary here. Actually, that's not it. This port's the trust boundary. That QoS is enabled, and we are getting a class of service mapping. We want to make sure that from here to here, and from here to here,
and ultimately from here to here, there's no reason not to, that marking remains intact, particularly between the switches, because if I experience congestion on the switched LAN, I want to be able to leverage my QoS protection. Now, I'm not going to get into all the layer 2 configuration right now, but I want you to understand this trust boundary. So assume, as we continue through this example, that we have defined that trust boundary. And in fact, I'm going to show you how to define that trust boundary on a switch. So stand by 1 second, and we'll bring the 3550 up. So here's our 3550 switch, and I'm going to show you real basic how to define that trust boundary. We're going to go, whoops, let me click in the right window here, config T, and globally, I want to enable MLS QoS. So we've done that. We've enabled MLS QoS. I'm then going to go to an interface, or perhaps all of them, int range FA01 through 23. I'm going to say MLS QoS trust, and I can tell it what to trust. I can say trust the packet class of service, or the frame class of service, which I'm going to do. And I could also say MLS QoS trust device Cisco phone. So if this switch port detects that a Cisco phone is connected, it's automatically going to trust the layer 2 QoS tags. Pretty cool, huh? Now, when you get into layer 3 switching, you're going to be a little more concerned about this. And it's still something you have to think about in the layer 2 world, but by and large, I'm doing this on layer 3 switches. But we want to make sure that we have class of service to DSCP mappings, because I want to make sure packets leaving the switch, or frames leaving the switch, are tagged properly. Now, I want to clarify something I said earlier, because it applies conditionally, and I think I may have said it in such a way that it sounded like it applied globally. When a phone marks layer 3 DSCP values on a packet, I said that those markings are preserved end to end. Now, that's true in a network when we don't have switches running QoS and trying to manipulate values. If you choose not to implement LAN-based QoS on your switched environment, QoS is off on your switches, those layer 3 markings will be intact as they reach your router. If you do turn on LAN-based QoS, the switch contains a DSCP to QoS mapping table. And what's going to happen is it's going to rewrite, based on the trust, it's going to rewrite the class of service value and the DSCP value based on the map. Now, there are default maps, or you can configure the maps. And you need to understand the QoS to DSCP mapping. So, because a phone is mapping a DSCP value of 46, the EF, and a QoS value of 5, that QoS value of 5 by default is going to get remapped to some DSCP value. Your switch may not be mapping that DSCP5 to a that QoS 5 to a DSCP of 40. If it's not, to 46. If it's not, that's not ideal, because when it comes out, well, that's not EF anymore. That's DSCP of 40. So you can actually manipulate these DSCP to QoS mapping within the switch. And let's take a look at the switch here and
zoom in a little bit more into how this works. There's a command we can run, show MLS QoS maps QoS DSCP. And this is going to show us the default mapping for our switch. So in this example, this switch is going to take packets with a QoS of 0 and map them to a DSCP of 0. QoS of 1 and 8. And let's jump straight up to 5 because that's how our packet's going to be tagged. And sure enough, it's trying to rewrite a QoS value of 5 to a DSCP value of 40. Well, that's not what we want. We want these things to be 46. So we actually need to manipulate the map a little bit. We can do that really easy with a command called MLS QoS map. Hang on a second. MLS QoS map QoS DSCP. Whoops, got to spell things right. QoS DSCP. And it'll let us define the values. So let's say 0 for a QoS of 0, 10 for a QoS of 1. We'll say 18 for a QoS of 2, 26 for a QoS of 3, 34 for a QoS of 4. Now here's where we're customizing it a little bit. 46 for a QoS of 5, 48 for a QoS of 6, and 56 for a QoS of 7. So now we've redone that map. So check this out. So now when I look at the map, a QoS of 5 is now going to map to a 46, which is DSCP-EF. So you want to make sure you're doing this QoS to DSCP mapping on your switch closest to the trust boundary so that the packets are being remarked appropriately. In fact, it's not a bad idea to go ahead and do this, on all the switches in your environment from a consistency perspective. Because after all, traffic can originate lots of places and be manipulated lots of places. So you want to make sure that this is intact end to end. So we're good there. So that's really all that I care about showing you on a switch. So back to our router. We've done the classification. We've shown you how to do the marking. We've shown you how to apply the service policies. And really, that's about all we need to do on this video. We're going to go through some other examples, we're going to continue to build on this example in some other videos, and we'll talk about things like the interleaving and fragmentation. We'll talk about the queuing and what we can do with that. Go through some examples on configuring, shaping, and policing, low latency queuing, and those kinds of things. But for now, classification and marking, you've kind of got it covered. So again, on the router, show run, pipe section, class map. Whoops, back up here. This is kind of where we're starting. We've got VoIP control and VoIP RTP. Show run, pipe section, policy map. We'll show you the policy map QoS where we've gone ahead and set a DSCP value for a particular class. And in another video, we'll go through the queuing and other associated configurations. So I'm babbling. It's been a long video. I know we're, again, drinking from the fire hose a little bit, but having a lot of fun doing it. So thanks for watching. Good studying. Rewind this one if it doesn't make sense. There's a lot of good stuff in here, and we're feeding it fast and furious. So I'll see you in the next video, and talk to you soon. In this module, we're going to talk about link efficiency mechanisms, and this is going to be most applicable to those of you in a part of the world where low speed, sub T1 or fractional T1 services are still in, a lot of use. So, those of you in the U.S. who are using, multi-meg and gigabit interfaces and MPLS with gobs of bandwidth and Metro Ethernet, you're not going to use these kind of things. But slow links, we need to squeeze as much out of them as we can. So let's talk about link fragmentation and interleaving. So what in the heck is link fragmentation and interleaving? Well, this is simple. Picture you get a slow circuit, a 56K line, and you're throwing a 1,000 byte packet on the wire. You're going to be waiting a few milliseconds, or more than a few milliseconds, for that packet to be put on the wire. And what's happening with your voice? It's waiting. that's a problem. So what link fragmentation and interleaving is going to do, or LFI, is it's going to allow us to chop up those big data packets into smaller ones. It's going to allow us to then stuff some voice in between. So if I wanted to give you a quick little sketch example here, let's go ahead and pull the pen up here, and I'll show you kind of what's going on. And that'll work. If I had, a big data packet, and I had a little bitty voice packet behind it, and I'm sending traffic, and this is my interface on the router, I got to wait for that whole data packet to cross the link before that itty bitty voice packet can go. And then I might have another huge data packet after it. So, voice is not doing necessarily the most optimum thing. What link fragmentation and interleaving is going to let me do is it's going to let me take this data packet and chop it up. So data voice, data voice, data voice, and send it like that. So I'm able to throw those voice packets in there, help get them out the wire faster, and the data is just being sent in multiple chunks. So that's kind of it right there. Go ahead and clear the screen here and walk through a little bit more. So I talked about it already. We're breaking up the big data packets and interleaving small voice packets with them. The net result of this is going to be a gain of performance for you. It's going to help you reduce the packet delay and jitter. There are two LFI types we can use. If you're doing multi-link PPP, you can use MLP, interleaving, and if you're doing frame relay, you can use FRF12. MLP is, by far the most widely used. Frame relay is all but gone in this part of the world. I know, again, it still exists other places that I'm not, but we're mostly beyond the frame relay days here. We're going to show you in this chart that link speed really comes into play here. If you're greater than 2 megabit, Cisco recommends you don't even think about link fragmentation, interleaving, or compressed RTP. Just leave it alone. If you're on a really small circuit, less than 768K, use LFI. Cisco recommends that you're going to use compressed RTP, and you should avoid using video on these links because you just really don't have the bandwidth anyway. And from 768K to 2 megabit, it's kind of up to you. LFI is not necessary. Use it if you want. And compressed RTP also, it's not necessary. Use it if you want. This chart is really going to show you, the benefit, not the benefit, but how bad these serialization delays can be for a given packet size and a given link speed. A 56K line with a 64-byte packet, it's going to take roughly 9 milliseconds to serialize that packet, to do everything necessary to put that bit on the wire. You increase that packet size to 1024, and now I'm waiting 144 milliseconds. Holy cow, that's a long time. Voice is almost not even possible anymore on those kind of links when you get into those metrics. We got to stable at this 150 milliseconds. You up that link speed to 512K, and then the difference is 1 to 16 milliseconds. You get into 1 meg circuits, T1s, and bigger. The problem just disappears. It's not a problem anymore. But these really slow links, low speed links, definitely can see some gains from this. Now, I've got a router here, and I've got a really basic FRF12 configuration set up on it, and I wanted to show you exactly what it takes to do this. This isn't a live frame relay link, so I'm not going to give you, any real-time statistics or anything like that, but I do want to show you the commands. The first thing you're going to do when configuring FRF12, obviously you're going to need to have a working frame relay configuration. And what I've got on this router is I've got a serial interface, and we'll show it to you right here. We've got a serial interface configured for frame relay, and we've got a point-to-point sub-interface with the interface delc 101. Now, I've created a map class called frame right here. Map class, frame relay, frame. And I've defined my frame relay traffic shaping parameters, my committed information rate, and my burst class, and my fragment size, and it's set up for fair queuing. All I really have to do is I go to this serial interface, and I reference that frame relay map class from within the sub interface, and we're going to be then able to leverage the frame relay, or the FRF12 link fragmentation and interleaving. And we're defining our fragment size down in these map classes. Now you won't be able to see any output because I'm not actually have this thing running, but a show frame relay fragment is a command that you could use to get some statistical information on the performance of this. And that's really all I'm going to talk about with FRF12. We don't need to get into full-blown examples because it's not that big of a topic and it's not something you're likely going to run into. I do want to talk quite a bit about multi-link PPP. In fact, give me just a second and we're going to back some of this frame relay configuration out and program this for MLPPP. So interface serial 000:0 encap PPP. Let's see here. That should have got rid of my frame relay subinterface. If it didn't, then I'll get rid of it by hand. Let's see if it did. Yeah, it did. Okay, so 000:0 encapsulation PPP. I'm going to first create a multi-link interface. PPP multi-link. Can use this to aggregate circuits. So interface multi-link 1, and then we're going to say PPP multi-link enter. Now I'm going to say PPP multi-link interleave and hit enter, and that has enabled interleaving of fragments. Now I'm going to go to the actually let me do a show run on that real quick and make sure it's all good before I continue. So there's our hang on, where's my multi-link? There it is. PPP multi-link group 1, PPP multi-link, and multi-link interleaving. Okay, cool. I'm going to go to my serial interface, config T, int serial 000:0. And whoops, what did I do wrong? Oh, spelled it wrong. Int. Having a great day here with the keyboard. Perfect. I'm going to say PPP multi-link and then group 1. So, this is basic multi-link configuration. If I want to, I can specify the maximum desired fragment delay for the interleave multi-link connection, and I'll do that under the multi-link interface itself. So int multi-link 1, and I'll say PPP multi-link fragment delay, and then I've got between 0 and 1,000 milliseconds. So I can say 5 milliseconds or 10 or 15 or whatever I want. And if you want to get statistical information and some stats on how this is working, show interfaces multi-link. Let's see. Oh, I need an interface number 1. It's down, so you're not going to get a whole lot, but you can get information about the performance of the multi-link interface. So really, those are the two LFI methods that Cisco is going to expect you to use and understand for the C-Voice exam. If you want to get into header compression and do things like that, it's basically class map stuff. So not a whole lot, a challenge there. You've done class maps before. So if I wanted to go in here, we'll do an example here. Config T, class map, and we'll just call it VoIP. And then we'll say match protocol RTP. So we're using nbar here. And then we want to create a policy map, and we'll just call it my VoIP policy. And then we'll go ahead and do compression. No, why is it not letting me do that? Oh, duh. Class VoIP. Now we'll be able to do compression. Compression, header, IP, and then you can go RTP or TCP depending what you're wanting to do. So, RTP. And then you'll use this just like you would a QoS policy. So if I wanted to go like int serial 000:0, service policy output, and then VoIP. What did I call it? Did I call it VoIP? Let's see. My VoIP policy. And yeah, I didn't
set up IP on the interface, but you get the point. It's just complaining because there's no IP address. But really, that's it. I mean, LFI is pretty straightforward. Header compression is pretty straightforward. Again, low speed links only. You're not going to be doing these things on, DS3s or 10 meg Metro Ethernets or MPLS connections. Keep this, for those sub T1, less than 768K kind of connections. But I know I've kind of babbled a little bit on this. I've honestly shown you more than you really need to understand for the C-Voice exam as far as FRF 12 and MLP goes. But hopefully this gives you a little practical baseline understanding of what's going on behind the scenes and how LFI can work, and when you should use it. But again, rare occurrences, low bandwidth links only. So I'm starting to repeat myself. I'm sure it's getting boring. We're really close to wrapping this up. We've got a really, really interesting section coming up next. In fact, this is a lot of the meat and potatoes on QoS, and this is all about queuing and traffic conditioning. So I'll see you in the next video where the rubber's going to meet the road on building these QoS policies, and we'll talk about queuing, the real magic of QoS. So see you in the next video. Good luck with your studying. In this module, we're going to be getting into configuration of queuing, and really this is where QoS kind of has the rubber meets the road, if you want to think of it that way. And we're going to talk basics first about queuing methods and how queuing really works, and then we're going to get into the specifics of class-based weighted fair queuing and low latency queuing. So first, let's talk about queuing methods. We have strict priority queuing, where we reserve bandwidth for an application, and the app can use it, and nothing else can touch it. It's not the most efficient use of bandwidth, so we don't do a lot of strict priority queuing these days. We have class-based weighted fair queuing, where we're going to create user-defined traffic classes, and then we're going to apply queuing policies to those individual traffic classes. Basically, we're going to have a queue for each class and different treatment rules. And then we're going to have low latency queuing, which is a way of using class-based weighted fair queuing, but still assigning a strict priority queue type of behavior to traffic that can benefit from it. So it's an interesting combination of different QoS technologies. So together, leveraging class-based weighted fair queuing as part of an LLQ implementation, and really you can just call it LLQ, is the most popular and widely deployed QoS method used in Cisco networks today. Queuing is going to need to be performed at the points of congestion on a network, and we'll talk about a little bit about how that works as we go on. So let's talk about queuing basics. First off, there are two types of queues. We've got hardware queues, what we call the TX queue, and hardware queues are first in, first out, period. Packets in a hardware queue cannot be reordered, and typically a hardware queue is only a few packets in size. And then we have software queues. Software queues, this is where the real magic of QoS happens. They're used for scheduling the packets into the hardware queues, so they're in front of the hardware queues. This is an important piece of information that sometimes gets lost when talking about IP quality of service. Software queues are only implemented when the interface is congested. And what I mean by that is if the hardware queue doesn't have anything in it. If a packet arrives on the router is going to place the bits on the wire and the data is going to be sent. Only when the hardware queue is full, when the hardware queue has data in it, is software queuing going to be used. Within a software queue, we can reorder packets. That's kind of the concept of what we're doing here with the modular QoS CLI and the whole QoS architecture that we're going to talk about. And that's going to be manipulating the software queue to schedule packets into the hardware queue how we want them to be scheduled into the hardware queue. Let's get into configuring basic LLQ. And what I'm going to do here is use this same 2811 router. We've been putting through a fair amount of exercise here lately. And we're going to go through basic LLQ configuration. So we're going to be doing class-based weighted fair queuing along with some priority queuing. So when you're configuring LLQ, the first thing you're going to do, in fact, let me show you, show run pipe section class map. We defined class maps early on, whoops, and we defined our match rules. Let me grab it in the right place here. And we were looking for packets based on their DSCP tags, etc. Or, we were doing NBAR, or, whatever. So we've got a couple of different, methods. In fact, let me get rid of that class map match all VoIP. That's something that's not related to this discussion. So let's just simplify this a little bit. No class map match all VoIP. So we've got our VoIP control and VoIP RTP. Let's focus on that. So now that I've got these classes, we are going to configure within our policy maps how to treat the traffic. And if I do a show run section policy map, you'll see the policy map that we already created. And this is where we were setting some DSCP values if we needed to do that. I'm going to go ahead and go into that policy map QoS. And I want to talk about, on a per class basis, what do I want to do? So let's go into class VoIP RTP. So VoIP RTP is our media. Now, we said before that the media, the audio, needs to be treated in a priority queue. We're going to do that using a command called priority. In fact, there are two commands you're going to use when configuring the classes for queuing. It's either priority or bandwidth. Priority is the command you use when you're doing priority queuing. Bandwidth is used to allocate bandwidth to classes that are not priority classes. This is our class-based weighted fair queuing. So this is going to be a priority queue. So I'm going to say priority, question mark. Now I can either specify a % of total bandwidth or a value in kilobits per second. Cisco is going to tell you that you should not have, in most cases, more than 30% of your bandwidth allocated to priority queues. So we're going to keep this number low. I'm going to say 10. Priority 10. That's not what I wanted. Priority % 10. I would have been doing 10 kilobits per second, which is not what I want. So priority % 10. Guess what? That's it. We've already applied this service policy to, in theory, our egress interface. We've now said priority % 10. There you go. If I want to look at the LLQ configuration, we can do a show policy map interface. In fact, let me look here to see which interface I applied it to. I want to say it was one of the Ethernet ports. It was, let's see, 0001. Okay, it was 01. So if I do a show policy map interface, FA01, you're going to see what we've configured. Now, if you look at the class map of VoIP RTP, match any, we can show the matches that are being made. We see metrics on the matches being made, how many packets have matched, and we see that we are doing priority 10%. Pretty cool, huh? And it's based on the interface speed, obviously. So right there, we've configured the priority queuing part of LLQ. Now, for other classes, I want to configure class-based weighted fair queuing. So let me do a show run on the section policy map again. So we've done the class VoIP RTP. And the other class, let's look at the class map as well, because we'll need to reference that. So we'll go config T. We'll go to policy map QoS, and we'll say class VoIP dash control. So this is our signaling traffic. We can then use the command bandwidth question mark, and we can either say the amount of bandwidth in kilobits per second. We can use % of total bandwidth, or we can use the remaining bandwidth. I'm not going to tell you exactly what values to use here, because this is going to vary from network to network. In fact, you need to do some calculations relative to the specifics of your network to figure out how much bandwidth you want to allocate. So we're going to just kind of keep that simple here. I'm going to, in this example, allocate that as %5. So if we do a show run pipe section policy map, you'll see for each class what we're doing. So for the class VoIP RTP, we're setting the DSCP tag as EF. Perhaps it already wasn't. Perhaps it was, and that's unnecessary. But priority %10, so that's priority queued. Class VoIP control, bandwidth %5, so that's going to be class-based weighted fair queued. Pretty simple, right? Now, if I wanted to define other classes, I would simply create those classes and use the bandwidth commands, or the priority commands up to 30% of the interface bandwidth, but use the bandwidth commands to allocate bandwidth amounts to my individual classes that I've defined. So potentially there's 8 classes in my model. Probably 1 or 2 of them are priority queues. Everything else is class-based weighted fair queuing. Divvy up the bandwidth however you'd like to divvy up the bandwidth. Now, when you use the bandwidth command, it's going to, let's see, what's the best way to describe this? If congestion occurs, because remember, this stuff's only happening when congestion is occurring. If congestion occurs, traffic exceeding the specified bandwidth is going to be dropped. Yeah, that's probably the best way to put it. If it's not congested, then you can continue to use bandwidth. But if it's congested, traffic in excess of the configured bandwidth value will be dropped. It's going to be tail dropped by default, but if you're using something like weighted random early detection, then obviously you can specify drop characteristics. Pretty straightforward there. So if you want to, I already actually showed you the show command from Honor, and let me run it again and show you the policy map is applied and let you see, at first we had this VoIP RTP, priority 10%, and now we've got the VoIP control, and we've got bandwidth 5%, so 5,000 KB. And then we've got the class default. That's going to be everything else. So pretty straightforward. You just continue to build on this to make a larger model. In fact, we'll show you an example of what one configuration could be for that QoS baseline reference we talked about, that 11 class model. Again, your network is going to dictate the exact values, but this should be a nice, high-level overview of what's going on with basic LLQ and class-based weighted fair queuing that's participating in there. Now that we've covered the queuing concepts, we're going to talk about traffic shaping and policing as we go on. So thanks for watching. I'll see you in the next video, and good luck with your studying. I originally intended to cover traffic shaping and policing as part of the same video where I discussed queuing, but things just got a little bit long and I didn't want to drag it out into a big 30-minute clip, so I've decided to cut that first video short, and we're going to pick it up here with the shaping and policing part of the theory and configuration on the router. So with that, into traffic shaping and policing. Let's talk about traffic shaping and policing. And the first question that I'm going to present to you, and the first thing I'm going to try to explain, is, first off, what's the difference? Queuing only gives us so much. It gives us the ability to order or schedule how packets are placed into a queue and placed on an interface. But it doesn't really allow us to deal with traffic in excess of what we're trying to transmit or manage. Traffic shaping and policing give us the ability to manipulate the data flows in a way that queuing alone cannot. So first off, when we talk about policing, a policer is typically going to be involved in discarding or dropping traffic, whereas a shaper is typically going to be buffering excess traffic to transmit at a later point in time. So as we talk about policers and shapers, you need to understand how this evaluation takes place and the exercise we go through. Shaping and policing can work together as part of your enterprise QoS policy to manage traffic in the way is most appropriate for your business and for your infrastructure. You need to understand some basic concepts about traffic rate measurements and the methods used to measure traffic rate, which is going to be at the forefront of any policing or shaping activities. First off, the concept of a token. A token gives permission to send X number of bits. A token bucket can hold a specific number of tokens. And really, the relationship here is that a token bucket can hold so much data. So let's start with that. Tokens arriving after the bucket is full are discarded and are not available to future packets. So once you fill the bucket's full. Any more data you throw at it is gone. If there are not enough tokens in the token bucket to send the traffic, i.e. if the bucket is full and the traffic you're trying to send exceeds the amount of tokens available in the token bucket, you can either discard the packet, and we call that policing, or you can continue to wait for enough tokens to accumulate to give you the ability to send the packet, and we call that shaping. There are some reference indicators we need to talk about relative to traffic rate. There is the BC, or what we call the committed burst rate, and that's the amount of data guaranteed to be delivered within a given interval. There is a BE, which is an exceed burst or an excess burst, and that's an additional amount of data that you'll permit to be attempted for transmission if there's no congestion. The TC is the time interval, and you've heard the term committed information rate, and that's really what shaping and policing about is matching up to a committed information rate. And a committed information rate can be calculated as the committed burst rate divided by the time interval. A bucket size, the token bucket in total, can be conceptualized as the committed burst rate plus the exceed burst rate. And we're going to get into this whole token bucket model, and I'm going to sketch it up and explain it to you. But let's make sure we understand these basic concepts. Typically, under normal use, at a normal rate, the committed burst rate, so much data, whatever that rate is sent every time interval. On exception, or some of the times, or I should say when permitted, the committed burst rate plus the exceed burst rate can be transmitted if enough tokens have been previously accumulated in the token bucket. To understand how policing and shaping work, you need to understand the token bucket model. And token buckets really play into how decisions are made. We need to figure out, am I meeting the committed information rate or am I not meeting the committed information rate? And if I'm not meeting it or if I'm exceeding it, what do I do? So let's start by talking token buckets. So a token bucket, quite simply, we'll see if we can draw a, that's supposed to be a bucket. So that's my token bucket. And it has a certain capacity of tokens. Let's say it is 1,000 tokens. And say that it's actually 1,000 bytes worth of tokens. If a packet comes in that is 1,000 bytes, and I have 1,000 tokens, then I'm good. I conform to the token bucket rate, or I'm conform to the committed information rate, and the packet is forwarded. So if I don't, then I don't have enough tokens, and the packet will not be forwarded. The way we scale this into policing and shaping is by concerning ourselves with the rate at which packets, or tokens I should say, are placed into the bucket and passed through the bucket. So in a single token bucket model, the token arrival rate, or the CIR, the committed information rate, is going to flow into the bucket. So I showed you here that was 1,000 bytes in this example, right there, 1,000 bytes. And this value, the depth, is our burst commit, or our committed burst rate. So the fact that we have a input rate that conforms to our committed burst rate means our traffic will conform. Now, let's say it doesn't conform. Let's say I have more than 1,000 bytes. Let's say I have, 9,000 bytes. What do I do? Well, if I conform, great. If I don't conform, well, say no. If I don't conform to the rate, then I can throw that packet into a second bucket. And I can configure the burst rate, or the exceed rate, we'll just say exceed, of that bucket. If I am small enough to be underneath this maximum exceed rate, then I exceed. Now that's not a bad thing. That's kind of like a success. If I am not, and I'm still too big, then I violate. And that's bad. Violating is bad. So, not the prettiest sketch. Hopefully this makes sense. What's going to happen with these methods, conform, exceed, and violate, is we're going to be able to configure our QoS behavior, or our shaping and our policing behavior, based on whether or not we conform, we exceed, or we violate. So conforming, just to sum it up, means there are enough tokens to, in the first token bucket that we've sent it to conform with the maximum size of the BC. Exceed means there are not enough in the first bucket. However, there are enough in the second bucket I'm a little slow writing tonight, that we are under, I should write it in here, the BE, the burst exceed. If we are violating, it means there are not enough in 1 or 2. Okay? So, token buckets, very important. As we jump into the next section here, or the next slide, we're going to go into the router and talk about configuring policing and shaping, and go through some examples and show you how to leverage these conform, exceed, and violate actions. All right, so we're back in the router, and we're going to configure some shaping and some policing. Now let's do policing first. When you think about policing, we're going to limit the input or output transmission rate relative to a particular class of traffic that we have defined. We can use either a single or double token bucket method, and so that we can specify violate actions. If you use a dual token bucket method, you're going to be able to conform to the rate limit when the traffic is within the average bit rate. You're going to be able to exceed the rate limit when it exceeds the average bit rate but doesn't exceed the excess burst rate. And we're going to violate the rate limit when the traffic exceeds both the average and the excess rates. So just like the sketch that I showed you. And basically we're marking things. We're making decisions based on what happens. Could I choose to transmit traffic all the time that exceeds my CIR? From a router perspective, yeah, I could do that. My service provider might have a problem with it, or my billing department might have a problem with it when they see the bill of that when the bill comes in because I've been bursting above my CIR that I'm paying for. So let's get into a really quick policy map here. So let's define a class map. Config D. We're going to say class map, and we'll just call it my traffic, and we'll just say match protocol HTTP. That's good enough. Now we're going to go policy map, and we'll just call it QoS. We'll be in that same policy map, and we'll say class my traffic. Now I'm going to say let's do policing first. Police, and I'm going to say either bits per second, the CIR, or the rate. I'm going to go ahead and do this one in bits per second, 256,000. So there's my bits per second. Now, check this out. I've got conform action, so I can specify what to do when I conform. So I can say transmit. I can manipulate DSCP values and then transmit. So maybe I could, if I conform, I'm probably not going to mess with DSCP values. But if I exceeded, maybe I'll lower the QoS level down. So, but for now, we'll just say transmit. If I exceed action, maybe I transmit anyway. Okay, fine. Maybe I drop. Maybe I remark the packet or remark the DSCP value so that downstream, this is treated differently. If I'm going single token bucket, we've got the conform and exceed, we will say drop. So there's single token bucket. So show run, we'll just go full-blown show run, and I'll show you what's important here. So we've got our normal class map. We defined a new class here. We called it my traffic, and we said match protocol HTTP. We're using the same QoS policy map that we've been using, but for the new class we've defined, we set up police at a rate. We said conform action transmit, exceed action drop. That's single token bucket policing. If I wanted to use a dual token bucket model, we'll go back into that policy map, and this time, whoops, hang on, class my traffic, and then we will say exceed action transmit, violate action drop. So now, show run, get down to it here. We will have a conform, an exceed, and a violate. Now, you've got the ability to, really, it's kind of up to you, as far as how you want to do this and what you want to do. But very, very cool. I wish I could give you some best practices on policing and shaping, but it's really so unique to each environment. I had one time, an example that comes to mind is I had a WAN link and I had a really, really chatty database connection. And it was just hammering the snot out of my WAN link, and I needed to cap it. I did some shaping and policing to keep that traffic under control, and I actually did some, a lot of dropping, and it solved my immediate problem, but certainly started some other conversations. But that's basic policing. If I wanted to get into shaping,
and try to manipulate things a little bit more, I'll go ahead and do it for that same class of my traffic. We'll go config T, and we'll say policy map QoS, class my traffic, and then we'll say no actually, no, let's get rid of all this. Boom. Gone. Okay. We will this time say shape, and I can do shape to average or shape to peak. I'm going to go ahead and shape to average. I, again, define a target bit rate or a percent of the interface bandwidth for the configured committed information rate. So we'll go ahead and we'll be explicit here. And let's see, what's a good rate to use? Let's say 32000. Enter. And now we're going to shape it. See how easy that is? If I wanted to do a shape peak, again, 32000, then I can do a shape peak. And what's interesting about shaping versus policing is the goal, in fact, let me kick back over to the screen here. The goal of shaping, if you look at a graph here, you've got your traffic, and you've got, policing behavior. So this is our traffic rate. And I'm going to show you shaping. The goal of shaping is when the traffic levels are increasing is to try to level them off. If I'm doing policing, again, the same chart, what's going to happen is as traffic ramps up, it's going to drop like this. So that's policing. So I'm going to cut it off when it hits a high enough level. Whereas with shaping, I'm going to try to massage it and smooth it out. Policing, when you're dropping these packets, obviously you're going to be causing, it's data not getting where it needs to get. So you're going to have TCP retransmissions happening. Because you're shaping, in the other example, you're going to minimize the number of TCP retransmits. So, there's places for both. And, again, I wish I could give you some more, best practice use, but it really is business case dependent. So those are the foundation concepts that Cisco is going to want you to understand relative to traffic shaping and policing. Don't make it harder than it has to be. It's really a lot more work to explain it than it is to configure it. Like I showed you, a couple lines of code here is really all we had to do. In fact, let me do, just for another zoom in on things here, a show run, and let's get down to our policy stuff. And, right there's our class of traffic, and there's our shaping configuration. So that's pretty much it. I think that's going to wrap up this section of the video. We've got one more to do, and that's going to be talking about Cisco Auto QoS. And it sounds exciting. It sounds like, gee, Josh, if we have this thing called Auto QoS and I can just turn it on, why do I need to know all this other stuff? And we'll talk about that. We'll answer that very question. And should be a good, good way to wrap up and round out your Cisco QoS toolbox knowledge and prep for this C-Voice exam. And then finally, we'll have a video and we'll talk about an example of how to do all this stuff we've done combined relative to that large 11 class baseline QoS model that we demonstrated earlier. So with that, I'm going to say thanks for watching. I know we've covered a lot of information here. This is definitely one of those videos you're going to want to rewind and go back through. I've tried to purposefully slow down my description. I know I tend to go a little fast, and this is one of those that you kind of need to creep into, so I've tried to talk a little slower and not rush myself. But feel free, you're not going to hurt my feelings if you press that rewind button and play it over. So I'll see you in the next video, and good luck with your studying. Welcome to Module 38. In this module, we're going to be talking about Cisco Auto QoS. And I want to tell you that we've reached, or you have reached, pretty much the last instructional model within the course. Sure, we're going to have one more video following this where we talk about, the 10 class, or I'm sorry, the 11 class Cisco baseline QoS model, and we go through a complete review of the configuration of the model. But really, that's a bonus. You've seen how that works already, so that's not building new skill. You've got that skill already. Auto QoS is kind of wrapping things up for you. Now, let's talk about Auto QoS. We went through the modular QLS, CLI, and MQC, and took the time to understand how we can implement queuing methods using class-based weighted fair queuing and low latency queuing. We took the time to understand how layer 2 and layer 3 QoS mappings worked, and we went through examples of shaping and policing, and we really covered how class maps and policy maps work together to provision an enterprise QoS deployment. So what is Auto QoS, and why are you telling me about it, or why am I telling you about it now at the end of that? Well, the answer is simple, because if I showed you Auto QoS, you'd never take the time to learn what's really happening behind the scenes. And you need to. Understanding QoS and designing enterprise QoS strategies is important. It is something you're going to do quite a bit of, and you really need to understand it well. So what is Auto QoS, and why am I going to use it instead of taking the time to design those enterprise QoS strategies that I just talked about? Well, the reality is, in the industry, you're going to run into a lot of different networks, and they're all going to have different characteristics, and you or the client may not have adequate time, staffing, resources, whatever, to fully understand their network. But yet, they still need to have a quality QoS deployment done. So what do? Auto QoS is kind of the next best thing to, and dare I say it this way, but to doing it right. That's probably a bit unfair for Auto QoS. It's Auto QoS is doing it right. It's just not doing it manually. So let's talk about what is Auto QoS. So we've got two components to Cisco Auto QoS. There's Auto QoS VoIP and Auto QoS Enterprise. And Auto QoS VoIP is a technique. In fact, it's the earliest thing that we called Auto QoS, and it lets you quickly and concisely deploy QoS policies to your routers and switches with configuration applicable to voice transport. It really doesn't take into effect the rest of the enterprise. It's really just a kind of a voice thing. Auto QoS Enterprise takes that concept to another level and helps you automate the deployment of QoS policies using a 10 class model. So instead of being just kind of watered down for voice, Auto QoS Enterprise helps you step it up a little bit. And Auto QoS Voice or VoIP is a couple of commands to deploy, and it's going to create class maps and policy maps and apply those service policies to your interface and do those things for you. Auto QoS Enterprise is a little bit different in that it's going to actually go through two phases. You're going to take it through an auto discovery phase where it watches the traffic on your network and figures out what you have going on. And then there's a provisioning phase where it actually creates these policies and structures things out. So we'll take a look at the Auto QoS configuration. Auto QoS VoIP is where you need to focus most of your effort or most of your time on this. But know about Auto QoS Enterprise and that it exists. Now, I'm going to walk you through some configuration of Auto QoS. And let me pull our good old HQ router here, the 2811, and let's walk through some basic Auto QoS configuration. If I do a show run, if I can type it right here, show run, there we go. I'm going to show you that there are no class maps and no policy maps created on this router. It's blank from a QoS standpoint. For me to enable Auto QoS VoIP on a router, what I'll do is I'll go to an interface of interest. Let's act as though this is my WAN interface, that interface of congestion. So we'll go to config interface serial 000:0. And I'm going to say Auto QoS VoIP. And then I have a choice to make. I can either trust the DSCP markings
as they come in on the interface. Or I can not trust it, and I'll use NBAR to detect the application and kind of do my own thing. I'm going to not trust. I'm just going to go ahead and let NBAR do its thing. NBAR support is required for Auto QoS. And for NBAR to work, you must have Ceph enabled, Cisco Express Forwarding. So keep that in mind. This is supported on most of the gear you're going to run into. And actually, following command was not properly applied. Service policy output Auto QoS policy untrust. I have no idea why it couldn't apply that. Let's take a look and see if we can find out why. Let's see. Let me show you what it built. Serial 0000. I actually don't see any real reason why that would have failed. Let me get rid of some garbage here. This has nothing to do with the failure, but let me get rid of this no map. Class frame, relay frame, just to get the garbage config out of our way. Let me go ahead and put an IP address on that interface. Interface 0000:0 IP address 172.16.5.1 255.255.255.252. No shut. Let's see if it lets us do it now. It's possible that because I didn't have an IP address on the interface that it didn't want to run. Auto QoS VoIP. Let's cross our fingers and see if this works. I'm hoping that it does. It's grinding along here. No, it still doesn't. Service policy output, Auto QoS policy untrust. That's weird. You know, let me do this. Let me go ahead and try this on an Ethernet interface just to see what happens. Int FA01 Auto QoS VoIP. And really, the command I'm showing you, that's how you enable it. You just turn it on. And it's going to generate the class maps and policy maps and things like that for you. Now that worked. Let's take a look at the show run. I'm going to show you exactly what it generated and what it built, and then we'll continue to dig into what that error is coming from and why it's causing it. So if we look at our configuration, Auto QoS has generated 3 class maps. A class map match any Auto QoS VoIP remark, and you'll see that it's matching traffic with VoIP related DSCP tags, so EF, CS3, and AF31. We have a class map match any for Auto QoS VoIP control untrust, which we're going to be matching in ACL, and we'll take a look at that ACL here in a second. And that's called Auto QoS VoIP control. And then we've got a class map match any Auto QoS VoIP RTP untrust. And then we're going to do a match protocol, RTP audio, using NBAR, and then match an ACL. So, okay, so we're looking for stuff that hasn't yet been trusted, and trying to classify it with NBAR down there. And we're trying to classify with an ACL, presumably based on port numbers and stuff here. So, pretty straightforward. So, we've created some class maps. We've created a policy map called Auto QoS Policy Untrust. And we've got class, Auto QoS VoIP RTP untrust, priority %70, set DSCP EF. So, ooh boy, we're doing a lot of priority queuing, allocating a lot of bandwidth on this interface for RTP audio. So that's definitely a voice-centric thing. VoIP control, bandwidth %5. So we're doing some class-based weighted fair queuing, and we're setting a DSCP tag. In fact, we're doing that up here in the RTP as well. And then we've got the VoIP remark, set DSCP default. So we're basically, in this one, if we see these tags, we're going to go ahead and clear them and set the DSCP marking back to default. So interesting. Class maps and policy maps. Let's keep going down. And let's look at our interfaces. Oh, I bet I know why it wasn't working. It's because it's a PPV multilink, and I would actually want to do it on the multilink interface, not on the individual serial. So let me do this real quick. Let me back out what I did. I'm going to go to interface FA01, and we're going to turn off Auto QoS VoIP, just simply by saying no Auto QoS VoIP. It's going to rip out those policy maps and class maps that it created. And we're going to go to this interface serial 000:0, and we're going to say no PPP multilink. So that should be out of there now. Let's see if it is. Yes, it is. So that's a normal link now. Enter serial 000:0, Auto QoS VoIP. Enter. Let's cross our fingers. That should apply successfully now.
That has to have been why it was erroring out. I can't think of any other good reasons. Let's see here. Fantastic. Okay, so it was just a problem with the fact that I had PPP multi-link turned on. So good troubleshooting exercise there. So show run. Again, nothing's changed as far as what class maps are going to be created. So we've got the same class maps that I described to you. And we've got the policy map created. So again, some priority queuing for LLQ. We've got some class-based weighted fair queuing. And if you look at the interface, that serial 0, 0, you'll see Auto QoS VoIP is there, and it's attached the service policy output, Auto QoS policy untrust. So it did a traditional modular QoS CLI style configuration, leveraging the parameters that we configured. So we weren't trusting the DSCP data that the router had. We were configuring marking based on our own protocol detection using NBAR. So definitely pretty cool. There's nothing else that it really built. There's these ACLs I was talking about right here. It built those, and like I said before, the VoIP control, we're doing some permits of TCP and UDP. So you can see we've got some key ports in there, 5060. We've got some, for SIP, we've got some skinny. I don't know what all these ports are without looking them up. But VoIP control related ports, and then we've got some RTCP stuff here as well. So really, Auto QoS VoIP on a router is nothing more than automating the deployment for you. It's not any real magic. It's not doing things drastically different than we do if we did them by hand. It's just not giving the level of granular attention that we would give to a manual configuration. So is there anything wrong with using Auto QoS? Absolutely not. If you're not going to turn on QoS, then at least turn on Auto QoS. Auto QoS is great for the guy who has 200 sites and one IT guy. And that one IT guy is never going to become a QoS expert, but he knows he needs it. And he needs it to be consistent across all 200 sites. So he turns on Auto QoS. The router takes care of the rest, and life is good. So that's Auto QoS VoIP, and that's really all you need to understand about it. To configure it on a switch, in fact, standby one, we will open another PuTTY window here into the 3550 switch that we've been using. And we'll drag it down here to about the same size. A little bit bigger. And to configure Auto QoS on a 3550 switch, I'm just going to say Auto QoS. Am I even supported on this version of iOS? I may not be. Let's see. I actually have to turn on QoS globally first. So MLS QoS. Can I just do that? And then go to the interface. We'll say interface FA01 Auto QoS VoIP. Yes, I can. And then we'll say Cisco phone. So what I've done here is on that interface FA01, show run at FA01, I have created all of this configuration relative to Auto QoS. So you can see I'm doing some weighted round robin queuing, class of service maps. We're doing some bandwidth allocations for weighted round robin queuing. We're actually trusting the DHCP tags if we detect using CDP that the connected device is a Cisco IP phone. So, pretty straightforward stuff. Obviously, I could do this to, all the access ports, and, I'd want to, do some things a little different to the uplink ports relative to trust or not, depending what is called for in my environment. But Auto QoS is there. It's that easy to configure. There's not a whole lot else going on in this switch. Let's take a look. You see that we've got the basic MLS QoS configuration. We've got our cost to DSCP mappings set up. We've got that one port we've configured, but other than that, things are pretty much vanilla relative to the configuration of this device. So, very, very cool stuff. And really, that's all I want to show you about Auto QoS VoIP. Let's go over real quick to the... actually, one more thing I want to show you. Before I leave the switch, show Auto QoS, enter. You can see FA01, Auto QoS VoIP Cisco phone. So it's showing you the interface that I've got turned on for Auto QoS. So cool stuff. Now, if I want to do Auto QoS Enterprise, let me get out of the switch. I'm done in there. And back to the router. For Auto QoS Enterprise, things are a little bit different. In fact, let me back out
interface 0000:0, no auto QoS VoIP. We'll get rid of auto QoS VoIP, and we'll walk through. Remember I said auto QoS Enterprise has two phases. You've got auto discovery and you've got provisioning. To get into auto discovery mode, we're going to go to the interface. Actually, I'll go ahead and use that same serial interface, and we'll say auto discovery QoS. And then again, either trust or don't trust the markings. So we're going to not trust the markings, and we'll use nbar to decide what's going on. And typically, you're going to want to run this discovery on the ports of interest for a couple of days, 2 days, 3 days, a week, through the course of your normal business cycle. And things are going on here. All right, cool. So auto discovery QoS has been turned on. Once we're done, then we're going to need to accept the configuration after we've done the discovery. So we're going to do that by saying auto QoS. Enter. Now, I haven't had any data, so it didn't discover anything. Let me try another interface just to make this a little more interesting. F interface. Let me do the show IPN brief. How about we do it on F800.30? We will say auto discovery. Is it gonna let me run it on the sub interface? It may not. I may have to do it just on the FA00. Auto discovery. Yeah, I'll have to do it there. So interesting. Can't do it on a sub interface. I did not realize that. So we've got auto discovery QoS running, and we'll just let that run here for a few minutes. And let me see if it lets me go auto QoS. Yeah, no auto QoS data discovered. I'm not letting it run long enough. If you were going to use this in the enterprise, like I said before, you're going to let it run for 2, 5, 7 days, whatever. And what's going to happen is once I generate the policy based on what I discover, that auto QoS command that I'm typing is going to commit it to the device, and it's going to actually have built multiple classes for us in the policy. And there's some commands. It's probably not going to give me a lot of output at this point since we haven't discovered anything. But if we do show auto discovery QoS, it actually does let us see a little bit here. So you can see for FAST-00 and the serial, the discovery uptime. In fact, if I refresh that, you'll see it's continuing to clock. I just don't have enough traffic running through this router to generate anything. But what it's going to show you is what classes have been discovered and what it's creating. It's going to show you recommendations for minimum bandwidth detected applications. Really just kind of break it down for you. And it's going to build you, like I said before, a 10-class QoS model. Not all that different from the baseline QoS model that we've talked about Cisco using. But you don't need to get a whole lot deeper into this for the C-Voice exam. They want you to know it exists. They want you to know how to kick off a discovery and commit the changes. Beyond that, you should be good to go. So as we wrap up this final video, and again, I told you there'll be one more. I'm going to talk about that 11-class model and show you a working example. But as we wrap up this video, we've wrapped up the heart and soul, if you will, of what you're going to need to be able to prepare for the C-Voice exam. Like I always say, one resource, whether it be a class that you've taken, a book that you've read, or a video series that you've gone through, no one source is going to adequately prepare you for this, any certification exam. Use as many sources of material as you can. Use on-the-job experience. Use your own lab or rack rental, or take a class and read a book and watch a video course. All of these things are going to help, well round you off as an engineer and prepare you to leverage these technologies in the real world and ultimately pass the certification exam. So I really appreciate you hanging in there with me. I know that we've covered a lot of material. Sometimes it's hard to demonstrate these things outside of a real world environment, but we've tried to do that. And that's pretty much it for the C-Voice exam course. So hang in there, take a look at my enterprise baseline QoS video next,
And after that, review, rewind, watch the videos as necessary, and good luck on your exams. As you go into the test, I want you to think about it as an opportunity to prove to yourself what you know. I am not the best exam taker, and it takes me, sometimes, several attempts to pass tests. And there's nothing wrong with that. Create a study plan that works for you. If you don't pass right away, the best advice I can give you is to go back, study immediately, fill in the gaps, and go take it again. Do not wait 2, 3, 4 weeks. Do not wait a month. Don't do that. Take it right away, and you're going to have the best preparation to pass on your next attempt. So thanks for watching, guys, and I'll see you in the next video and in the next course. You've made it. You have reached the final video. We're going to talk about the Cisco Baseline QoS reference one more time, and I'm going to give you a configuration example. I know we've gone through a lot of different QoS stuff, and we've shown you examples of shaping and policing and queuing and building class maps and policy maps, and we've shown you Auto QoS, VoIP, and Enterprise, and I want to round it out by showing you how I do things. This 11 class model I certainly did not invent, but I've adapted to my own purposes throughout the years, and I've had really, really good luck with it. I have to credit Tim Seghetti, one of the CCIEs that I know, for including this design in a book he wrote several years ago, End-to-End QoS Network Design. In fact, I think he's got a new edition out. I need to pick it up. But that book really went a long way at explaining QoS models to me, and he thought enough of the model, the Cisco reference model, to include it in his book, and I have adapted it slightly and included it here in the video. So if we look at the 11 class model, I've got a breakdown of the types of traffic we're going to be including. We're accounting for voice, video conferencing, streaming video, call signaling, routing, network management traffic, mission critical data, transactional data, bulk data, scavenger traffic, and then best effort. We are going to allocate bandwidth based on the percentages shown in this graph, and keep in mind these values are not set in stone. These values can vary from enterprise to enterprise, and they should be set up to match your unique environment. That said, this model can give you a solid starting point for doing your own design. Looking here, the things I want to point out is we're using voice, video conferencing, and streaming video are all going to be priority queued. So 18% plus 10% is 28%. And 5% for streaming video is 33%. And I mentioned earlier that you want to stay not to exceed about 30%. The actual number is 33%. But as far as what you're going to strict priority queue or LOQ. But so we've done that here. And really, I'm going to walk straight into it. We're going to show you the class maps and the policy maps that you can use to implement this 11 class model. So we've created class maps for each of our classes. We have class map match any network management, match IP DSCP CS2. Class map match any bulk data, match IP DSCP AF11 and AF12. Class map match any voice, match IP DSCP EF. Class map match any mission critical data, match IP DSCP 25. Class map match any routing, match IP DSCP CS6. Class map match any scavenger, match IP DSCP CS1. Class map match any video conferencing, match IP DSCP AF41 and 42. Class map match any streaming video, match IP DSCP CS4. Class map match any call signaling, match IP DSCP CS3 and AF31. And we've got a class map match any transactional data, match IP DSCP AF21 and AF22. Again, this is not an absolute. You can adapt this model as needed for your environment. I'm not using, in this example, anyway, I'm not using NBAR. I'm assuming that my packets coming in are appropriately marked. Now, that may or may not be the case in your environment, so keep that in mind as you go through your configuration examples. We've got a policy map that matches up to these class maps. We're going to call it policy map QoS, and we've defined for each of the classes an entry. So class voice, priority %18. Remember, I'm using the priority command. That means LLQ, or low latency queuing. Class video conferencing, priority %10. Class streaming video, priority %5. Now we get into the class-based weighted fair queuing, where we've got the streaming video class with 5%, the call signaling class with 5%, routing with 3%, network management with 2%, mission critical data 15%. And keep in mind, think about that. If this were up to your business without technical input, how many percent do you think they'd allocate to mission critical data? I guarantee you it's going to be way up there. It's not going to be 15%. They look at that and they'll say, what? Are you nuts? But really, this is appropriate. You need to play that liaison and help guide them towards a good solution. So we're showing you here 15%, and we're doing random detect. Class transactional data, bandwidth %12 with random detect DSCP based. Bulk data has 4%, again, random detect DSCP based. And our scavenger class, bandwidth %1. So we're really dropping that down. And then class default, that's the everything else. Bandwidth %25, random detect. So I think this is going to give you a good solid model to build on. This is a fantastic model for a branch router or a core router doing WAN services. And I think you can build on this for your own QoS policy as applicable to your network. And when I mentioned partially deploying the 11 class model, you may not build every one of these classes, but you should, consider the possibility of leveraging the same values anyway. Just because you've got 100%, if you only choose to implement class voice and class call signaling, you've accounted for 18% plus 5%. You got a lot of percents left. I wouldn't recommend changing the numbers. Leave yourself that elbow room so that later you can come back and add additional classes as you choose to leverage them in your environment. So this is a good example to start with. It's not, it's not something I would say copy, paste, and run within your router. In fact, I'm not even going to do that here in the lab. It's a reference. Use it as one, and hopefully it'll help you have a good gut feeling of where to begin. So this is it. This was kind of a little bonus thing. Thanks for tuning into this video series. I think we've had a lot of fun demonstrating how things work. Sometimes we've had a lot of fun demonstrating how things may not always work and troubleshooting techniques. And gee, why isn't that working? And I'm sitting here and I'm recording and I'm screen capturing and it didn't work perfect the first time. So what do? We're not going to stop the video. We're going to let it play. We're going to go through the troubleshooting thought process and the exercises, and we'll figure it out. In fact, we had a pretty good one about a video or two ago. Where we were working on a serial link. So that stuff all adds value to the instruction process. It's the kind of stuff you're going to run into in the real world, and you need to understand how to deal with it. So I like to leave it in there when possible, when I'm not looking like a complete and total moron. And even if I am, that's okay. But good luck with your studying process. I hope that this video series has been helpful to you. We will be creating video series for the rest of the Cisco CCNP voice track. In fact, next up is CIPT1, which is primarily a call manager class. So hopefully by the time you have passed your CVoice content, or your CVoice test, we'll have the CIPT1 content ready to go, and you'll be able to jump right on in and keep moving with your certification process. My name's Josh Kittle. It's been a pleasure being your instructor for this video series, and I hope to see you in the next video series. Good studying, and thanks, guys.